Good morning everyone, good morning. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. So people, just let me know in the chat box first of all if I'm audible and visible to everyone. Just let me know in the chat box. Good morning everyone, good morning. Welcome back my dear elites, welcome back. Welcome back. Just let me know fast in the chat box. My God, chat is running fast, so I cannot read all the names. So good morning, welcome back people, welcome back. So as you all must be knowing, today we are going to do the complete revision of the chemistry in the form of questions, right? And I have selected some 1,000 questions. By solving these, I'm sure your entire chemistry will get revised properly, okay? Yeah? So people, are you super excited for it? Yeah? Are you super duper excited for it? Just let me know in the chat box. That's great. Taslim Sheikh, that's great. That's wonderful. Perfect, guys. So before starting the session, the ones who are new to the channel, let me introduce myself. Well, my name is Wassim Sir and I'm your chemistry master teacher writer on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with your friends, and do subscribe to the channel. And do not forget to hit the bell icon so that you get the notification of every single session which we take live on this NEET Elite channel, yeah? So do like the video, share the video with your friends, and do subscribe to the channel as well, yeah? So people, this is the sequence which we are going to follow in the today's session. We'll be starting with the solid state, then comes electrochemistry, chemical kinetics, surface solutions, D&F, coordination, GOC, haloalkanes, arenes, amines, and so on. This is the sequence which I'm going to follow in the today's session, yeah? So you can let me know in the chat box if you people are super duper excited about this session. Yeah, let me know in the chat box, people. Let me know in the chat box. Welcome back everyone. Welcome back. Good morning. Welcome back. Perfect, guys. Perfect. Huh. So let's get started. Let's try to kill the chapter solid state first, yeah? Right? The first question which I'm going to start with, that's going to be a complete basic question, right? And I'm sure you all must be knowing its answer. Which of the following is not a characteristic of a crystalline solid? As you all must be knowing, on the basis of the arrangement of constituent particles in three-dimensional space, we classify solids into two types. One is called as crystalline, one is called as amorphous. In crystalline solids, there is a regular arrangement of constituent particles. In case of amorphous solids, there is the irregular arrangement of constituent particles, right? What I'm supposed to check, which of the following is not the characteristic of crystalline solid? People, have you ever heard crystalline solids are isotropic in nature? No way, right? Crystalline solids, they are not isotropic, they are anisotropic in nature, right? So this is the incorrect option among all, right? The first one, crystalline solids, they have got definite and characteristic heat of fusion, which is absolutely correct. Regular periodicity, absolutely correct. It's also called as a true solid, absolutely correct. Only this part is left. Crystalline solids, they are not isotropic, they are anisotropic in nature, right? Question number 1 is done and dusted. Which of the following statements about amorphous solids is incorrect? What about the amorphous solids? Which of the following among the all is incorrect? Well people, the first statement says amorphous solids, they melt over a wide range of temperatures, which is absolutely correct. Amorphous solids, they do melt over the wide range of temperatures. They do not have the sharp melting points, right? They are anisotropic. So option B is the one which is going to be our correct answer. We know amorphous solids, they are isotropic in nature. Okay, so statement number 2, this is incorrect. There is no orderly arrangement of particles, absolutely correct. They are rigid and incompressible, absolutely correct. So option B is the one which is going to be our answer of this question, right? So remember in short, crystalline, isotropic, amorphous, anisotropic, right? Sorry, I told the reverse, right? Crystalline solids are anisotropic, amorphous solids are isotropic. Okay, this is something which I want you guys to remember in short. Yeah? Moving on to one more. In graphite, electrons are localized on each carbon atom. Electrons are spread out between the sheets, localized on every third carbon atom, present in anti-bonding orbital. What do you think should be the correct answer of this question? Well, I can see majority of the people are coming up with the correct answer. Absolutely, guys. In graphite, the electrons are spread out between the sheets. In the graphite, you have got that sheet kind of a structure. Okay, if you remember, that layered structure is there in the graphite, in which the electrons are spread out between the sheets. So option B is the one which is absolutely the correct answer of this question, right? Okay. Which of the following is a network solid? Network solid means covalent solid. Which of the following is the covalent solid among all? Which of the following forms the huge network, right? Let me know fast. Okay, let me know fast, people. It's absolutely going to be a diamond, which forms the covalent solid, which forms the network solid, right? Because diamond absolutely is formed of carbons, and carbon atoms, due to its property of catenation, it forms huge chains, right? So it forms, if we talk about diamond, if we talk about the structure of diamond, it forms the network structure, it forms the covalent structure. Yeah? Right? Okay. Crystals can be classified into basic structural units equal. Basically, how many crystal systems are there? You can let me know in the chat box. How many? These are all easy kill questions, guys. These are all easy kill questions. How many crystal systems are there? I'm not talking about the Bravais lattices. I'm talking about the crystal systems. How many crystal systems are there? There are actually 7 crystal systems, and these are the crystal systems starting with cubic, tetragonal, orthorhombic, hexagonal, right? Rhombohedral, monoclinic, triclinic, okay? These are the 7 crystal systems which we have, right? Okay. All right, this sort of a question, guys, I told you in the last session as well, there's a chart given on your NCRT. Do remember that chart in which this part is given, right? In which this part is given. Which of the following represents the monoclinic crystal system? You can let me know its answer. Just let me know its answer fast. Yes, these are going to be back-to-back questions. Which of the following represents the monoclinic crystal system? Well, I can see majority of the students are coming up with option C, and absolutely option C is the correct answer of this question. In case of monoclinic crystal systems, A is not equal to B, which is not equal to C, but alpha and gamma, they are equal to 90, beta is not equal to 90 degree, right? Very simple question, memory-based one. Do remember this, people. Do remember this from your NCRT, okay? Do go through it once again, right? I mean this chart, which is given on your NCRT, right? And at the same time, do remember these examples as well, right? Any example can come in the form of the memory-based question in your NEET 2021 examination, right? Okay. How many three-dimensional crystal lattices are possible? And right now I'm talking about the Bravais lattices. So how many Bravais lattices are possible over here? You can let me know fast its answer. There are basically 7 crystal systems and 14 Bravais lattices, right? That's something which you all must be knowing. Option C is the correct answer of this question. How many three-dimensional crystal lattices are possible? It's going to be option C. So 14 three-dimensional crystal lattices are possible, and we call those crystal lattices as the Bravais lattices, okay? Perfect. And these are the 14 Bravais lattices which we have, right? You can remember them as well. Perfect. In face-centered cubic lattice, a unit cell is equally shared by how many unit cells? Okay, this is one question. I want you guys to let me know its answer now in the chat box. Give it a try, people. In face-centered cubic lattice, a unit cell is equally shared by how many other unit cells? See, guys, if you talk about the face-centered cubic unit cell, let's say this is the face-centered cubic unit cell. Let me change the color of the pen first. Yeah. Let's say this is the face-centered cubic unit cell, right, which is going to be cubic in shape. Can I say on one side of it, just like this, on one side of it, there'll be one more unit cell like this, okay? Just downwards, there'll be one more unit cell like this. On the side of it, there'll be one more unit cell like this. On the top of it, there'll be one more unit cell like this, right? And behind this unit cell, there'll be one more, and just just in the front of the unit cell, there'll be one more. So I'll say this unit cell is equally shared between how many other unit cells? It is equally shared between 6 other unit cells at the same time, right? So what is going to be correct answer of this question? Correct answer of this question is going to be C. So this unit cell, this face-centered cubic unit cell, this cubic unit cell, it is shared between 6 other unit cells, right? Perfect. Moving on to one more. The number of atoms per unit cell in case of BCC structure. As you all must be knowing, in case of BCC, the constituent particles are present at the corners. The constituent particles are present at the corners and at the body center. The contribution of the corner particle towards the cubic unit cell, that you all must be knowing, that's 1/8, and total there are 8 corner particles, right? The particle which is present at the center, its contribution is 1, and there is only one particle, so the value comes out to be 2. So basically there are 2 atoms actually present in case of the body-centered cubic unit cell. Again, it is the easy question. Option B is the one. Yeah? Perfect. A compound formed by the element X and Y crystallizes in a cubic structure. Okay, we have got a cubic structure which is made up of 2 atoms. One is X and one is Y. This is X and this is Y, correct? In which X atoms are present at the corners, X atoms are present at the corners, and Y atoms are present at face centers. It's a very simple, easy question, right? Face centers. What is going to be the formula of the compound? It's simple. It's simple, right? X particles are present at the corners. Contribution of corner is 1/8. Total there are 8 corner particles, right? Face center contribution is 1/2. Total there are 6 face centers. So the value comes out to be 1. This value comes out to be 3. So the formula is going to be X1, Y3. Simple. X, Y3. Easy question again. I'm sure you can kill these sort of questions, right? One more, people. In a face-centered cubic lattice, atoms A are present at the corner points, B at the face-centered points. If B is missing from one of the face-centered positions, the formula of the compound will be. What is going to be the answer of this question? Have a look. Simple. See guys, we have got a compound in which we have got 2 types of atoms, A and B. Okay? A particles are present at the corners. A particles are present at the corners. And B particles, as per the question, B particles are present at the face centers, right? If atom B is missing from one of the face-centered positions, so one of the atom B is missing from the face-centered position, what is going to be the formula then? See, A particles are present at the corners, contribution of corner is 1/8, total there are 8 corner particles, correct? Contribution of face-centered particle is 1/2. Total there were 6 face-centered particles. Out of those 6 face-centered particles, 1 face-centered particle is missing, so I'll be only left with 5 face-centered particles, correct? So this value comes out to be 1, this value comes out to be 5/2. If I multiply this term by 2, this term by 2, what I'll be getting? This is something which I get as 2, this is something which I get as 5. So A2, B5 is going to be the formula of the compound. So option D is the one which is the correct answer of this question, right? Perfect, absolutely. Okay, let's move on to one more question. This is one more question on a screen. You can kill this one as well. Simpler one. See guys, a body-centered cubic lattice is made up of 2 different types of atoms, A and B, right? A and B. A body-centered cubic lattice is made up of 2 types of atoms, A and B. Atom A occupies the body center. Atom A occupies the body center, right? And atom B occupies the corner positions. Atom B occupies the corner positions. Yeah? One of the corner is left unoccupied. One of the corner is left unoccupied. Correct? What is the empirical formula of the unit cell? Simple again. Have a look. A particles are present at the body centers. The contribution of the body centered particle towards the unit cell is 1, and there is only 1 body centered particle in the unit cell. Correct? Corners, contribution 1/8. Total there are 8 corner particles, but one of the corner particle is left unoccupied, so there will be only 7 corner particles. So multiplying this with 7. So this value will come out to be 1. This value will come out to be 7/8. If I multiply this by 8, this by 8, I'll be getting the value as 8. This will be 7. So A8, B7 is going to be the formula of the compound, right? A8B7 is going to be the formula of the compound. It's again the easy equation. I'm sure it's clear to everyone, right? Yes? Perfect. Exactly, guys. Moving on to one more question from the chapter solids. If A stands for the edge length of the cubic system, simple body centered and face centered. See, guys, have a look. In general, we talk about these three types of unit cells. One is going to be simple cubic unit cell, one is going to be body centered cubic unit cell, one is going to be face centered cubic unit cell. Do remember the relation between edge length and the radius of the constituent particle forming the unit cell. Do remember it, okay? In case of simple cubic unit cell, remember R is equal to A divided by 2. In case of body centered cubic unit cell, R is equal to root 3A divided by 4. In case of face centered cubic unit cell, R is equal to A divided by 2 root 2. Correct? You simply are supposed to take the ratio of these. So A by 2 is to root 3A by 4 is to A by 2 root 2 is going to be the answer of the question. So option A is the one which satisfies it. Absolutely, it's going to be option A. Yeah? Right? Perfect. Let's move on to one more. This is one more question. You can kill this one as well. Trust me on that. It's again the easy kill question, guys. First of all, you all must be knowing how to calculate the density of the unit cell. Density of the unit cell is calculated by the formula Z multiplied by M divided by Na multiplied by A cube, right? This is the formula by means of which we can calculate density of any unit cell, correct? So people, can I say density of the unit cell is directly proportional to Z inversely proportional to A cube, right? Where Z represents the effective number of particles. Yeah? A metal crystallizes in two cubic phases. A metal first is forming FCC, then it's forming BCC. First it's forming FCC, then it's forming BCC. So I'll be writing density of, calculate the ratio of the density of FCC and BCC. Okay, density of FCC divided by density of BCC is simply going to be equal Z for FCC divided by Z for BCC multiplied by A cube for BCC divided by A cube for FCC, right? This formula I used. That's it. I need to calculate this ratio. The equation is almost done. What is the value of Z for FCC? There are 4 particles forming the face-centered cubic unit cell. There are 2 particles forming the body-centered cubic unit cell. What is the A cube for BCC? What is the edge length of BCC? Okay, whose unit cell lengths are 3.5 and 3 angstroms respectively. Okay, so a metal crystallizes in 2 cubic phases, FCC. When it's forming FCC, its edge length is 3.5, right? And when it's forming BCC, its edge length is 3. So it's going to be 3 divided by 3.5 whole cube like this. You just need to solve this value, get the value of the ratio. That's something which I was supposed to check, right? Isn't it very, very simple, people? Yeah? Isn't it very, very simple? So finally, you'll be getting the answer as 1.26 exactly. The way we have done it, right? Okay, just after this, you are supposed to do a bit of calculation. That's all. Yeah? Perfect. Moving on to one more. A metal crystallizes in a face-centered cubic structure. If the edge length of the unit cell is A, the closest approach between the 2 atoms in the metallic crystal will be. See what the question says exactly. First of all, if I make the face-centered cubic unit cell, let's assume this is the face-centered cubic unit cell. And we know, in case of face-centered cubic unit cell, the constituent particles are present at the corners and at the face centers. That's something which we all know, correct? The constituent particles are present at the corners and at the face centers. I'm only taking the top face. I'm only considering the top face, right? Remember, in case of face-centered cubic unit cell, the face diagonal particles touch each other. The face diagonal particles touch. In case of what? In case of FCC, face diagonal particles touch each other, right? So people, have a look properly. Can I say, if I join this particle with this particle, it's going to be the face diagonal of the top face, right? What all particles come along this line? What all particles come along this diagonal? They'll be touching each other. That means this particle will be touching this particle, and this particle at the same time will be touching this one, right? Okay, I need to get the distance of 2 closest neighbors. First of all, if these two particles are touching each other, I'll say these two are the closest neighbors. These two are the closest neighbors, absolutely, right? I need to get the distance from this point to this point. How will I be getting this? See, it's simple. Have a look properly, guys. Have a look properly. This side, this edge length is, for example, A. This will be also A because it's a cube. So this is going to be root 2A. So phase diagonal, let's call this as A, let's call this as B, let's call this as C, right? So I'll say AC, which is the phase diagonal, it's simply going to be equal to root 2A, correct? But am I supposed to get the whole distance AC? No, I just want the distance from here to here, right? It's going to be the distance between the two closest neighbors is going to be root 2A divided by 2. So root 2A divided by 2 will come out to be simply A divided by root 2. So this is basically the distance between the two closest neighbors, as simple as that. So which option satisfies it? A by root 2. Yeah? Right, people? Yes? Perfect. Absolutely perfect. Let's move on to one more question. A metal crystallizes with a face-centered cubic lattice. The edge length of the unit cell is 408 picometers. The diameter of the metal atom will be. We have got a metal, it is crystallizing in a face-centered cubic unit cell, right? And in case of face-centered cubic unit cell, we know R is equal to A divided by 2 root 2. This is something which is valid for the face-centered cubic unit cell. You all must be knowing this, correct? So if I write it like this, 2R is equal to A divided by root 2. It does not make any difference, right? 2R is something which we call as diameter. Diameter of the particle which comes out to be A divided by root 2. A value must be given to us. A is the edge length of the unit cell, that is 408 picometers. Divided by root 2. Root 2 value, all of you must be knowing, that's 1.41. Just solve it, get the value in picometers. That's all, right? That's all. Perfect. Absolutely. Finally, you get the answer as 288 picometers. Simple? Yeah? Absolutely, guys. Let's move on directly to one more question. See, one more similar type of question, and I'm sure you can kill this again. It's again the easy kill question, guys. Yeah? Sodium metal crystallizes in a body-centered cubic lattice. Okay, with the edge length of 4.29 angstroms. The radius of sodium atom approximately is. So sodium metal is crystallizing in the body-centered cubic lattice. And for the body-centered unit cell, R is equal to root 3A divided by 4. This is something which I've told you already. Correct? What do I need to calculate? I need to calculate the radius of the sodium atom. I need to get the value of R. So the question is almost done. Root 3 value, remember it's going to be 1.71. A value, edge length is going to be 4.29 angstroms. Okay, divided by 4. Just solve it, get the final answer. That's going to be your job afterwards. Correct? Simple. So what you'll be getting at the end? You'll be getting 1.86 angstroms as the answer of this question at the end, right? Absolutely. Let's move on to one more then. Okay, the cubic unit cell of the metal has the edge length of this much, its density is this much, the type of the unit cell is. See guys, I'm just going to give you the approach of solving the equation. You know the density formula, right? You know the density formula. D is equal to Z multiplied by M divided by Na multiplied by A cube, right? This is the formula to calculate density. Density is given to me as per the equation, right? Okay, molar mass of the metal which is forming the unit cell, that's also given to me, correct? Na is the Avogadro's number, that's something which you all must be knowing, 6.022 10 raised by 23, right? A cube, edge length must be given to me, right? Edge length is given to me, but do convert this edge length into centimeters because you're given with the density as grams per centimeter cube. So do convert this picometer into centimeters, right? Then put it here. After putting all the values, can I get the Z value from here, right? After putting all the values in this equation, I'll be getting the Z value. Now, if the Z value comes out to be 1, if the Z value comes out to be 1, then the unit cell is going to be SCC. If it is coming out to be 2, the unit cell is going to be BCC. If it is coming out to be 4, the unit cell is going to be FCC. If it is coming out to be 6, it's going to be hexagonal unit cell, right? Do remember these parameters, correct? Just get the Z value. After getting the Z value, right, you can easily see which kind of unit cell it is. And as far as I remember, I think Z value comes out to be 4. So it's going to be FCC, face-centered cubic unit cell, right? Yes? Perfect. Okay. One more simple question. AB crystallizes in a body-centered cubic lattice with the edge length equal to 387 picometers. The distance between two oppositely charged ions in the lattice is. How do I calculate this sort of equation? Understand. We have got a crystal which is basically BCC. It is a body-centered crystal, right? That means the constituent particles are present at the corners and one at the body center. Okay? Let's assume A particles are present at the corners. Let's assume these are the A particles. Correct? And let's assume B particle is present at the body center. Let's assume B particle is present at the body center. Correct? What do I need to calculate? I need to calculate the distance between the two oppositely charged ions in the lattice. I need to calculate the distance between the two oppositely charged ions in the lattice. First of all, remember, in case of BCC, remember, body diagonal particles touch each other. Body diagonal particles, they touch each other, right? See, if I join this corner with this corner, that's going to be one of the body diagonals, right? So along this body diagonal, which all particles are coming? This particle, and this particle. They will be touching each other because they are lying along the body diagonal, okay? Remember, what is the body diagonal length? Body diagonal length, remember from now onwards, is going to be root of 3a. This is the body diagonal length. This is the body diagonal length. And do remember at the same time phase diagonal length. As I told you earlier, phase diagonal length is always equal to root of 2a. Correct? See guys, we have A particles present at the corners, we have got B particle present at the body center. So this particle and this particle, they are going to be of oppositely charged manner, right? They'll be having charges opposite to each other. I mean this particle and this particle, because this is A particle, this is B particle. Both are having opposite charges and they'll be touching each other. So basically I need to get the distance from this point to this point, that's all. I need to get this distance from here to here. The whole body diagonal length is root of 3a. So I'll do its half. It's going to be root of 3a divided by 2. This is the exact distance between these two oppositely charged ions, right? A value must be given to us. That is 387 picometers divided by 2. Root 3 value that you all must be knowing. I told you 1.71 multiplied by 387 divided by 2. Solve this. This is going to give you the distance between the two oppositely charged ions. I'm sure it's clear to everyone, right? Yes, people? Yeah? So finally, you get the answer as 335. My exam center is near Kilpauk. Kilpauk used to be a medical college, right? Kilpauk Medical College. Something as far as I remember. Yeah? Is it a dream college? Well, during my college days, I have done a show there, one modeling kind of a show in Kilpauk Medical College. There used to be a fest. Okay, let's move on. What is going to be the answer of this question? If Z is the number of atoms in the unit cell that represents the closest packing sequence ABC, the number of tetrahedral whites in the unit cell is equaled. What is going to be the answer of this question? Let me know fast. It's a very simple and ordinary question. People, whenever you see ABC packing, whenever you see ABC packing in 3D, remember the unit cell which gets generated in this packing is going to be FCC, right? And in case of FCC, the value of Z, as you all must be knowing, that's equal to 4. And whatever is the value of Z, same is the number of octahedral whites, right? And twice of it will be the number of tetrahedral whites. So in a face-centered cubic lattice, remember there are 4 octahedral whites, 8 tetrahedral whites. So what is going to be the answer of this question? The number of tetrahedral whites is going to be 2 times Z. Total, there will be 8 tetrahedral whites in case of face-centered cubic unit cell, right? And sometimes in the question, you might get confused. Instead of FCC, they'll mention CCP, cubic closed packing. But remember, CCP means FCC. Remember, CCP means FCC, right? Okay. Perfect. Which of the following is the correct increasing order of packing efficiency in case of HCP, BCC and CCP? Okay. If I talk about simple cubic unit cell, what is the packing efficiency? Remember from now onwards, it is 52%. Just a second. It is 52.4%. In case of FCC, the packing efficiency is 74%. In case of BCC, the packing efficiency is 68%, right? In case of hexagonal unit cell, In case of the hexagonal unit cell, the packing efficiency is again 74%. Now you can arrange them on the basis of increasing or decreasing order, whatever. Yeah? Right, people? Now you can arrange them on the basis of increasing or decreasing order, whatever you're supposed to calculate. Packing efficiency, which of the following? Increasing order of the packing. Increasing order of the packing. So smallest first. SCC comes first. SCC simple comes first, right? Then comes BCC, then comes HCP. So option C is the one which is correct among all. Right, people? Yeah? Absolutely, option C is the one which is going to be correct among all. Okay. A metallic element crystallizes in the lattice containing a sequence of layers, AB. Any packing of the layers leaves out the voids in the lattice. What percentage of the lattice is empty? Okay. Which kind of packing do we have right now? This is AB packing in 3D. And which kind of unit cell is generated there in AB packing in 3D? It's going to be hexagonal unit cell. It's going to be hexagonal unit cell, right? And in case of hexagonal unit cell, I told you a few minutes back, what is the packing efficiency? That is 74%. So what is going to be the percentage of voids? Percentage of voids is going to be 100 minus 74, which comes out to be 26. So this much is the percentage of voids in case of this packing, right? As simple as that. Yes? So 26% is going to be the answer of this question. Okay. One more question on your screen, guys. A compound is formed by the cation C, and the anion A. Right? A compound is formed by the cation C and anion A. Correct? The anions form hexagonal close packing. Anions, they form hexagonal close packing. The cations occupy 75% of octahedral voids. The formula of the compound will be, again it's simple. First of all, in case of hexagonal unit cell, I'm sorry, in case of hexagonal unit cell, the value of Z is 6. So directly there will be some 6 A particles, because A particles, they form hexagonal unit cell. So Z value for hexagonal unit cell is 6. So A particles directly will be 6. If Z is 6, so total there will be 6 octahedral voids, and total there will be 12 tetrahedral voids, right? Okay. C cations, they occupy 75% of octahedral voids. 75% means 3/4. 3/4 of what? Octahedral voids. Total there are 6. So 3/4 of 6 voids are getting occupied, right? Now solve it. It's going to be 6 ones are, it's going to be 6 ones are. So the value comes out to be 3/4. This value comes out to be 1. Multiply throughout by 4. So I get the answer as 3. This is 4. So it's going to be C3A4. C3A4 is going to be the formula of the compound. C3A4, option C. Right, people? Yeah? Absolutely, it's going to be option C. Perfect. Moving on to one more. We have got one more question on the screen. I want you guys to solve it. Gautam, on the actual Vedantu platform, we take class through the wave platform, not through this screen. There is a different platform called as wave platform, through which we take classes in the actual Vedantu. See, guys. Yes, Yuvan, I can read your comments. Okay. See, guys, how this sort of a question is solved. It's again a simpler one. Say, in a solid, atom M occupied CCP. M atoms are forming CCP. As I told you, CCP is nothing, that's FCC. Correct? And 1/3 of tetrahedral voids are occupied by atom N. N occupies 1/3 of tetrahedral voids. Correct? Find the formula of the solid. Simple. Have a look. M forms FCC. For FCC, as you all must be knowing, the value of Z is 4. If the value of Z is 4, that means there will be 4 M atoms first of all. How many total octahedral voids will be there? Total octahedral voids will be 4 and total tetrahedral voids will be 8. As simple as that, right? N particles occupy 1/3 of tetrahedral voids. So it's going to be 1/3. Total tetrahedral voids are 8, right? So it's going to be 4/1. This is going to be 4/2. The value comes out to be 1 is to 2/3 multiplied throughout by 3, so that this 3 and this 3 gets cancelled out, right? So the formula is going to be 3, this is going to be 2. So it's going to be M3N2. M3N2 is going to be the formula of the compound. Option A is the one which is correct. I'm sure it's clear to everyone, right? Yes? Perfect. Moving on to one more. Element B forms CCP and A occupies half of octahedral whites, while oxygen atoms occupying all tetrahedral whites. The structure of the bimetallic oxide will be. See guys, we have got element B. It forms CCP. CCP means FCC, right? Forms CCP structure. A occupies half of octahedral whites. A occupies half of octahedral whites. Correct? While oxygen atoms occupy all tetrahedral whites. Oxygen atoms occupy all tetrahedral whites. What is going to be the formula of the compound? It's again a simpler one. Have a look. See guys. Tilak, it is going to be Hg2 dye positive plus 2 times Cl negative. Okay. B forms FCC, right? In case of FCC, the value of Z is 4, as you all must be knowing, right? If the value of Z is 4, there'll be total 4 octahedral whites and there'll be total 8 tetrahedral whites. Total I'm saying, right? Total I'm saying. B particles are forming FCC, so directly 4, right? Half of octahedral whites. Half of octahedral whites are total 4. All tetrahedral whites, that means 8 directly, right? So the value is going to be 1, this is going to be 2. So 4 is to 2 is to 8. Just make it in the simplest form, divide it throughout by 2. It's going to be 2, it's going to be 1, it's going to be 4. So formula is going to be B2, A1 and O4. B2, A1, O4. Or you can say A1, B2, O4. A1, B2, O4, that means option B is the one which is coming out to be correct. Right, people? Yeah? Absolutely, option B is the one. I'm sure it's clear. Okay, one more question, people. One more question on your screen. It's a nice question, I must say. A compound MPXQ has cubic closed packing arrangement of X. Its unit cell structure is shown below. The empirical formula of the compound will be. See guys, this is the unit cell which is given to me, right? This is the unit cell which is given to me. I need to get the formula of the unit cell. See guys. First of all, this square represents M. Square represents M. And X represents, these circles, they represent X. Okay. Just look at the occupancy of this X. X particles are present at the corners everywhere. And at the same time, X particles are present at the face centers as well. You can see it, right? Face center, face center, face center, face center, face center, face center. Correct? So if I talk about X first of all, X particles, they are simply present at the corners and at the face centers. Corner contribution is 1/8. Total there are 8 corners. Apart from that, they are present at the face centers. 1/2 multiplied by 6. 1/2 is the contribution of one face center. There are 6 face centers. Whereas if I talk about M particles, where are the M particles present? See guys, this is M particle, this is M particle, this is M particle here, this is M particle here, and this is M particle here. Is there any other M? No. So basically, M particles are present at the 4 edge centers and 1 body center. The contribution of the edge center is 1/4. And how many edge centers are being occupied by M? There are 4 edge centers being occupied by M. Apart from the edge centers, 1 is exactly present at the body center. So 1 multiplied by 1. So this 4 and this 4 gets cancelled out. It becomes M, 1 plus 1, 2. It becomes X. This is 8, 8 gone. This is going to be X4. So just divide throughout by 2. It becomes MX2. MX2 is the formula of the compound, which is option B. Right, people? Yeah? Right? As simple as that. Option B is the one which is correct. Yes? So first of all, you might be given with the unit cell directly, right? You need to see the exact location of the particles. After seeing the exact location of the particles, you can check it out, right? Perfect? Wonderful. Surely, Santosh, I'll pay a visit. Surely. Okay, one more question. One more question over here. Shortcut effect. Okay, before solving this question, one question I have missed over here. People, you might have seen one question given in your NCRT. The question might be something like this. Fe 0.93O, something like this. Have you ever seen this sort of equation? Have you ever seen this sort of equation? Yeah? Say yes or no. Right, you must have seen. See, you might get this sort of equation as well. This is something which I forgot to add in the slides. So let me show it to you separately right here. See guys, you need to see, in case of this compound, this is the non-stoichiometry compound, okay? In case of this compound, how many iron atoms will be there in the form of Fe di positive and how many iron atoms will be there in the form of Fe tri positive, right? Okay. For example, we know, first of all, iron exists as Fe di positive as well as Fe tri positive. Okay? Okay, before solving the equation, this compound, there is no charge, there is no net charge present on the crystal. I mean, there is no net charge present on this compound, right? Otherwise, the charge would have been mentioned over here. There is no net charge. That means whatever is the charge present on cation, same is the charge present on anion, but of opposite sign. The charge present on oxygen is going to be -2, so the charge present on this Fe 0.93 is going to be +2, right? Okay. Let's assume there are some X particles present in the form of Fe di positive. That means Fe tri positive will be simply 0.93 minus X. Just use the charge conservation principle. See guys, Fe di positive. How many Fe di positives do we have? X. So what is the total charge present with Fe di positive? It's going to be X multiplied by +2. This is the charge present with Fe di positives. What is the charge present with Fe tri positives? It's going to be 0.93 minus X multiplied by 3, right? This total charge should be equal to +2, right? You simply are supposed to solve this. After solving this, you'll be getting the value of X, and X was Fe di positives in this compound, and once you get the X, you can calculate 0.93 minus X as well, which gives you the Fe tri positive ions in the crystal, right? Simple? Simple guys, right? I'm sure it's clear? Yeah? Perfect. See guys. Okay, now what about this question? Schottky defect. In Schottky defect, what happens? Equal number of cations and anions will be missing from the lattice points, right? Schottky defect in the crystal is observed when an ion leaves its normal sites, occupies the interstitial. Okay, when equal number of cations and anions are missing from their sites, from their lattices. Option D is the one which is correct. Okay, this is something which we call a stoichiometric defect. Due to Schottky defect, okay, if I'll ask you, due to Schottky defect, will the density of the crystal increase or decrease? Due to Schottky defect, density of the crystal decreases. That's something which you all must be knowing, right? What happens with stability of the crystal? Stability of the crystal also decreases, right? That's something which you all must be knowing. Yeah? Do remember the examples of the compounds which show Schottky defect as well. And do remember one more thing. This question has been asked many a times in JEE examination. Which of the compound shows both Schottky and Frankel? It's going to be AgBr, right? Many a times the question has been asked. Which of the compound shows both Frankel as well as Schottky? It's going to be AgBr, right? Do remember this thing as well. Okay. Each of the following solids show the Frankel defect except each of the following solids show Frankel defect except, it cannot be B guys, B AgBr, it shows both Schottky as well as Frankel. It's going to be option D, KCl. KCl is the one which does not show the Frankel defect. What are the conditions for the crystal to show the Frankel defect? Remember, Schottky defect is common in the compounds having high coordination number. Let me write the criteria. For the crystal to show the Schottky defect, there should be high coordination number, and small difference in the size of cation and anion. In the size of cation and anion, right? This is the criteria for the compound to show the Schottky defect. And what is the criteria for the compound to show Frankel defect? It's going to show low coordination number, and large difference in the size of cation and anion. Do take a note of this thing, right? Do take a note of this thing. Yeah? Okay? This statement is directly given to you in NCERT. Perfect. So with this, your solid state is done and dusted. And people, one more thing. There will be some structures given in your NCERT, right? NaCl structure, rock salt structure, there will be zinc sulfide structure, right? There will be cesium chloride structure, correct? There will be fluoride structure, and there will be anti-fluoride structure. do go through these structures once and do remember the occupancy of ions in these, right? Do remember the occupancy of ions in these crystals, right? In case of, for example, NaCl, where are the cations present? See, if I talk about NaCl, okay, in case of NaCl, Cl negatives, they form FCC, Na positives, they are present at octahedral wides, correct? They occupy all the octahedral wides, right? What is the coordination number of Na positive and Cl negative? It is 6:6, right? It's 6:6. Similarly, how many formula units of NaCl will be there? There will be 4 formula units. All this data is given in your NCERT, so do take a note of this data as well. For NaCl, zinc sulfide, cesium chloride, fluoride, and Nd fluoride. That's all. That's all. Okay? Right? People, is everything clear till here? Should I be moving on to electro? Yeah? KP, no need to go for the magnetic properties and all, no way. You can remember those examples, right? Which one shows paramagnetism, which one shows ferromagnetism, right? Just remember those examples, that's it. Perfect. All right, so let's move on then. Let's move on, and let's get going with something called as electrochemistry. This is the first question from the chapter Electrochemistry. See guys, as per this question is concerned, have a look. The reducing power of the metals, increases in the order. See how I'll be solving this sort of equation, understand properly, okay? Reducing power of the metals. Basically, you're supposed to check which of the following is the strong reducing agent. Whenever a term comes like reducing power, that means you are supposed to check which of the following is the better reducing agent. And reducing agent is the one which reduces others and itself undergoes oxidation. Okay. So remember that substance among all which undergoes oxidation easily will be the better reducing agent, will have the more reducing power, right? Now, which of the following will undergo oxidation easily? The one which has got maximum standard oxidation potential. The one which has got maximum standard oxidation potential will undergo oxidation easily, will be the better reducing agent, will have the more reducing power, right? Okay, now how do I check it? Understand properly, guys, understand properly. First of all these reactions which are given to me, are these reduction reactions or oxidation reactions? Everywhere gain of electrons is happening. Gain of electrons means reduction. Every reaction is the reduction reaction, okay? So basically, Zn dye positive is getting reduced, Mg dye positive is getting reduced, calcium dye positive getting reduced, Ni dye positive getting reduced. So this is basically the standard reduction potential of Zn dye positive. This is the standard reduction potential of Mg dye positive. This is the standard reduction potential of Ca dye positive. This is the standard reduction potential of Ni dye positive, right? But do I need the standard reduction potentials or I need the standard oxidation potentials? I need the standard oxidation potentials. So first of all, if this is the standard reduction potential of Zn dye positive, if I reverse its sign, it becomes plus 0.76, and plus 0.76 becomes the standard oxidation potential of zinc. It becomes the standard oxidation potential of zinc. See guys, minus 0.76 was the standard reduction potential of Zn dye positive, but plus 0.76 will be the standard oxidation potential of zinc. Similarly, plus 2.87 volts, it is going to be the standard oxidation potential of calcium, right? Plus 0.25, it is going to be the standard oxidation potential of nickel. Similarly, plus 2.36, it becomes the standard oxidation potential of what? Of magnesium, right? Now say, which one has got the maximum standard oxidation potential? I must see. This one has got, calcium has got the maximum standard oxidation potential. If calcium has got the maximum standard oxidation potential, it will undergo oxidation easily. It will be a better reducing agent. It will have the more reducing power. So calcium will have the maximum reducing power. Okay, calcium will have the maximum reducing power, followed by magnesium, then after magnesium, I'll be giving preference to zinc, then after zinc, at the end, I'll be giving preference to nickel, right? So this should be the increasing order of the reducing property, right? This is the increasing order of the reducing power. So which option correctly satisfies it? It's absolutely going to be option B, which is going to be the correct answer of this question. I'm sure this is clear to everyone, right? It's again the easy question, right, people? Right? So option B is the one which is the correct answer. Wonderful. Let's move on to one more. Okay, this is one more question, the similar type of question, but in this question, people, what you are supposed to do is, you are supposed to check the oxidizing power of the species. Oxidizing power. Basically, you need to see which one of the following is the better oxidizing agent. Oxidizing agent is the one which oxidizes others, but itself undergoes reduction. Itself undergoes reduction. Okay. Now, which among the following will undergo reduction easily? That will undergo reduction easily, which will be having maximum value of SRP. More the value of standard reduction potential, easily reduction takes place, better will be the oxidizing agent, more will be the oxidizing power, right? Yes. See guys, how I'll be approaching to this topic question. See, every reaction which is given to us, in every reaction, gain of electrons is happening. Gain of electrons means reduction. So this is the standard reduction potential of CO tripositive. This is the standard reduction potential of Ce plus 4. This is the standard reduction potential of Pb plus 4. This is the standard reduction potential of Bi tripositive. The species which are encircled, basically these species are undergoing reduction, right? So these are the reduction potentials of these respective encircled species, right? Yes? Right, people? Now have a look. Now have a look. Now have a look. Now, where is the standard reduction potential maximum? Say plus 1.81, 1.61, 1.67 and 0.20. So Pb plus 4, sorry, not Pb plus 4, just a second. CO tripositive is showing maximum standard reduction potential. If CO plus 4 is showing maximum standard reduction potential, it will undergo reduction easily. Better oxidizing agent, more oxidizing power. So CO tripositive will have the maximum oxidizing power, right? Followed by what? After 1.81, I'll be giving preference to 1.67, which is Pb plus 4, right? After Pb plus 4, I'll be giving preference to 1.61, which is Ce plus 4, and after Ce plus 4, I'll be giving preference to Bi plus 3, right? This is the increasing order of the oxidizing powers. I'm sure this is clear to everyone, right? Okay? I'm sure this is clear to everyone. Perfect? Yes, Kishore, exactly. Yeah? Okay, let's move on to one more then. Let's move on to one more question. This is one more question, guys. Which of the following is the strongest oxidizing agent? Simple. Have a look. Oxidation state, charge present on A is 0, charge present on A is plus 1. 0 to plus 1 means increase in oxidation state. Increase in oxidation state means oxidation. So this is the standard oxidation potential given. This is the standard oxidation potential of A given, right? See, from 0 to minus 1, 0 to minus 1, decrease in oxygen state. So this is the standard reduction potential given, right? And again, this is the standard plus 1 to 0, decrease in oxygen state. This is again the standard reduction potential. Okay, so first of all, I'll be converting this SOP into SRP. So standard reduction potential of the first one is going to be minus 1.1 volts, correct? Minus 1.1 volts. Which of the following is the strongest oxidizing agent? As I told you, oxidizing agent is the one which oxidizes others, itself undergoes reduction. And which of the following will undergo reduction easily? The one which will be having maximum SRP will undergo reduction easily. If it undergoes reduction easily, it will be the better oxidizing agent. So which one of the following has the maximum SRP? Maximum SRP is for this one. So C is undergoing reduction easily, right? It will be the better oxidizing agent. Sorry. Perfect? Absolutely, guys. Moving on. Let's move on to one more. Calculate the oxidation potential of the following half cell, right? Okay, before solving this question, let me tell you a few important points. Remember, more the standard oxidation potential of the element, more is its tendency to undergo oxidation, and it's going to be a better reducing agent. better reducing agent, and more will be its reducing power. More will be its reducing power. Do remember this statement, that's it. Yeah? Similarly, more the standard reduction potential of the element, more is its tendency to undergo reduction. It is going to be the better oxidizing agent. More is going to be its oxidizing power. In short, remember this thing. In short, remember this thing, right? Okay. One more thing which I would like to share with you. What is that? On increasing the concentration of electrolyte in the container, reduction potential increases, right? And similarly, on decreasing the concentration of electrolyte in the container, reduction potential of the electrode, it decreases, right? If the reduction potential increases, that means oxidation potential decreases. If the reduction potential decreases, that means the oxidation potential increases. Do remember these things as well, right? Anything can be asked out of these things, right? Where I'll be using these things, just you need to wait for that. You need to wait for that in order to see where I'll be using these things, right? Okay, I'm sure you'd have taken a note of it, correct? So see guys, how this sort of a question is to be solved. Understand properly. See, I'm given with the half cell. It is the electrode which is given to me. It is the electrode which is given to me. Have a look. What is the charge present on iron right here? The charge present on iron is 0. Charge present on iron is +2, right? Okay. Calculate the oxidation potential of the half cell. In order to calculate the oxidation potential of this half cell, in order to calculate the oxidation potential of this electrode, I'll make sure this electrode behaves like the anode, because we know at anode only oxidation takes place, right? Oxidation means loss of electrons, and iron is getting converted into Fe di positive. So let me write the reaction first. Fe solid, it gets converted into Fe di positive aqueous, and with this Fe di positive aqueous, you write 2 electrons, right? This is the reaction which will be taking place when this electrode will be behaving like the anode, oxidation, right? So how many moles of electrons are being exchanged? I'll say 2 moles of electrons are being exchanged first of all, right? Now, let's write the expression for QC. QC is simply going to be concentration of Fe di positive raised to the power, it's stoichiometric quotient 1. This is in solid form, I've got nothing to do with this. What is the concentration of Fe di positive that's given to me? That's 10 raised power minus 1 molar. Sorry, 10 raised power minus 1 is the value of QC which I got, correct? Am I given with the standard oxidation potential or standard reduction potential? Since I'm supposed to calculate the oxidation potential, so I need the standard oxidation potential. See, +2 to 0, decrease in oxygen state, right? So this is the standard reduction potential. Let me convert it into standard oxidation potential. It's going to be plus 0.44 volts, plus 0.44 volts, right? Okay, now we will have a look. Have a look properly. Have a look properly. I'll be using the Nernst equation. I'll write oxidation potential of the electrode is equal to standard oxidation potential of the electrode minus 0.0591 divided by N. It's going to be log of QC. Right, people? See, I'm supposed to calculate the oxidation potential of the electrode, which will be equal to standard oxidation potential of the same electrode, which is plus 0.44 volts minus 0.0591. What is the value of N? N value is nothing, that's 2 log of QC. QC value I got from 10 raised power minus 1. So you just need to do a bit of calculation. It is 0.44 minus 0.0591 divided by 2 log of m to the power n, which is n log m. Log 10 is 1, right? You need to solve this equation, get the answer in volts, and people are saying in the chat box the answer comes out to be 0.47. Is that? Is that? Okay, people are saying the answer comes out to be 0.47 after solving this, so 0.47 volts is going to be the answer of this question, right, people? Clear to everyone? Yeah? Perfect? Wonderful. Yes, Fawaz, you can do that as well. You can do that as well, no issues. You can do that as well. Perfect. Moving on to one more question, guys. This is one more question on your screen. This is one more question on your screen. Yeah? See. Calculate the oxidation potential of the following half cell. Again, I'm given with one electrode. Again, I'm given with one half cell. Half cell and electrode, both are same, right? Either you call it as half cell or you call it as the electrode, right? See, what I'm supposed to calculate? I'm supposed to calculate the oxidation potential of the following half cell. This is the half cell that's given to me, right? See, the charge present on chlorine right here is 0, right here it's -1, 0 to -1. Decrease in oxygen state means reduction. means reduction, right? Means reduction. What am I supposed to calculate? I need to calculate the oxidation potential. I need to calculate the oxidation potential, okay? In order to calculate the oxidation potential, I'll make sure this electrode behaves like the anode because I need to calculate the oxidation potential. I'll make sure this electrode behaves like the anode, and at anode oxidation takes place. Oxidation means increase in the oxidation state, but see what is happening. If I move from Cl2 to Cl negative, oxidation state is decreasing. So this means reduction. What do I need to write? I need to write oxidation. So I need to write the reaction in the reverse way. I'll be writing 2 times Cl negative. 2 times Cl negative gives Cl2 plus 2 electrons because I need to write the oxidation reaction. I'm not supposed to write the reduction reaction. Okay? Now we will have a look. How many moles of electrons got exchanged? 2 moles of electrons got exchanged in this net cell reaction. Yeah? Now QC value is going to be equal. This Cl2 is in gaseous form, so I'll be using its partial pressure. Partial pressure of Cl2 raised power 1 divided by concentration of Cl negative raised power 2. What is the partial pressure of Cl2 gas? That is 10 atm. What is the concentration of Cl negative? That is 10 raised power minus 1 molar raised power 2. The value will be 10 divided by 10 raised power minus 2. The value will be simply 10 raised power 3, right? You got the QC value. What do I need to calculate? Oxidation potential. But I need to calculate the standard oxidation potential first. See, minus 1 to 0, increase in oxygen state. So this is standard oxidation potential. I'll simply use an Nernst equation. Oxidation potential is equal to standard oxidation potential, which is minus 1.36 volts minus 0.0591 divided by n value is 2 log of QC. QC value is 10 raised power 3. You need to solve this part of the equation, get the answer in volts. That's all which you have to do. Log of m to the power n, n log m, right? Yes? Right, people? Simple? Yeah? Exactly. Perfect. So finally, you get the answer as minus 1.45 volts over here. Yes, you are Shri here. Exactly right. Exactly, Farooq. Okay? Moving on to one more question. Calculate the oxidation potential of this half cell. Okay, I'm given with one more half cell over here. Basically, you can see this is the hydrogen electrode which is given to me. I'm given with the hydrogen electrode. What do I need to calculate? I need to calculate oxidation potential of this hydrogen electrode. And how am I going to do it? How am I going to do it? Understand. In order to calculate oxidation potential of this electrode, I'll make sure this electrode behaves like the anode, because at anode only oxidation takes place, and oxidation means simply loss of electrons. So reaction should be H2 gas gives 2 times H positive aqueous plus 2 electrons. This is the reaction which happens right here. Yeah? This is the reaction. Correct? Now we will have a look. How many moles of electrons got exchanged? 2 moles of electrons got exchanged. This is something which I got. Let's try to write the expression for QC. It's going to be concentration of H positive raised by its stoichiometric coefficient, that's 2, divided by partial pressure of H2 gas. Right, people? Concentration of H positive is given to me as 10 raised by minus 1 raised by 2, divided by partial pressure of H2 gas is given to me as 10. The value will be simply 10 raised by minus 2 divided by 10, and it comes out to be 10 raised by minus 3. Well, you got the QC value. Remember, standard oxidation potential as well as standard reduction potential of the hydrogen electrode, both are taken as 0 as per the reference. Okay, that's something which you all must be knowing, right? Now we will see. QC value you got. QC value you got. What am I supposed to calculate? I need to calculate the oxidation potential. So I'll be simply using the Nernst equation. Oxidation potential of the hydrogen electrode is equal to standard oxidation potential minus 0.0591 divided by n value is 2, it's going to be log of QC. QC value is 10 raised by minus 3. That's all, right? So it's going to be minus 0.0591 divided by 2 log of m to the power m comes out to be n log m, so minus 3. So finally solve this, get the value in volts. That's basically the oxidation potential of the hydrogen electrode. I'm sure it's clear to everyone, right, people? Yes? Perfect? Exactly, guys. You all are perfectly right. All right, one more nice question. This is, people. Calculate the reduction potential at the pH equal to 14. Okay? See. First of all, I need to calculate the reduction potential of copper electrode. In order to calculate the reduction potential of copper electrode, I'll make sure this copper electrode behaves like the cathode, and at cathode reduction takes place. So reduction means gain of electrons. So my reaction will be Cu di positive aqueous plus 2 electrons. It changed to Cu solid. This is my reaction. This is my reaction, right? This is my reaction. I need to calculate the reduction potential, right? In order to calculate the reduction potential, I'll make sure reduction happens at the copper electrode, and reduction will only happen at copper electrode if copper electrode behaves like the cathode, right? So this is the reaction, first of all. So what is the value of N? How many moles of electrons got exchanged? 2 moles of electrons got exchanged, as you can see right here, okay? What is the value of QC? QC value is nothing. This is in solid form. Its active mass is 1 divided by concentration of Cu dye positive. But people, I'm not given the concentration of Cu dye positive. I'm not given the concentration of Cu dye positive. How do I do it? How do I calculate the concentration of Cu dye positive? Okay, perfect. Now, one more thing. Since I'm supposed to calculate this reduction potential, is this the standard reduction potential? Check it out. Plus 2 to 0, decrease in oxygen state, reduction. That means this is the standard reduction potential, absolutely. This is the standard reduction potential, absolutely, right? What do I need to calculate now? Before using the Nernst equation, I need to get the concentration of Cu dye positive. Now the point is how. See guys, pH of the solution is given to me. pH of the solution is given to me as 14, right? You all must have heard about one relation, pH plus pOH is equal to 14, right? If pH is equal to 14, that means pOH is equal to 0. If pOH is equal to 0, pOH means minus log of OH negative concentration. Minus log of OH negative concentration is 0, right? Power is 10 over here. So I'll say OH negative concentration from here will be 10 raised power 0, that comes out to be 1, right? Or if you do not want to do it, just remember one thing. If pOH is given to us, you can directly calculate OH negative concentration, which is going to be equal to 10 raised power minus pOH, right? So this value comes out to be 1. I got the OH negative concentration. But I do not need OH negative concentration. I need Cu dye positive concentration. Why did I calculate OH negative concentration, right? Why did I do it? See guys, have it. Understand. I'm given the Ksp of CuOH whole twice. I'm going to use this parameter. Ksp of CuOH whole twice. First of all, CuOH will undergo dissociation as Cu dye positive aqueous plus 2 times OH negative aqueous, right? If I write the expression for Ksp, it's going to be concentration of Cu dye positive raised power stoichiometric coefficient multiplied by concentration of OH negative raised power 2, right? Ksp value is given to me as 10 raised power minus 19 is equal. I'll write Cu dye positive concentration. OH negative concentration is given to me as 1. So I got the concentration of Cu dye positive. So it's going to be 10 raised power minus 19. The value finally comes out to be 10 raised power 19. I got the QC value. Now put all these parameters into the Nernst equation, kill the equation. I was supposed to calculate the reduction potential, which is equal to standard reduction potential of copper electrode, which is 0.34 volts, minus 0.0591 divided by N value is 2, log of QC value is nothing, that's 10 raised power 19, right? So finally you'll be getting something like this, 0.34 minus 0.0591 divided by 2, log of m to the power n, which is going to be n log m, right? You need to solve this equation, get the value of reduction potential of copper electrode in volts. That's all. Yeah. It's simple, guys. Isn't it simple? Right? And if you have not liked the video, please do like the video, share the video with your friends, and do subscribe to the channel as well. Perfect? I'm sure that's clear. Moving on to one more. This is one more question. Guys. This is one more question. Have a look properly. Calculate the EMF of the cell, right? I need to calculate the EMF of the cell. How do we calculate EMF of the cell? In order to calculate EMF of the cell, I will definitely need Nernst equation, because Nernst equation gives us the EMF of the cell. E cell is equal to E naught cell minus 0.0591 divided by N log of QC, right? All of you must be knowing that, correct? Now people, let's have a look and see how this sort of equation is to be solved. First of all, there are 2 lines which you can see in the middle. These 2 lines represent the salt bridge, remember. On the left hand side of the salt bridge, we always write the anode. So this is my anode and this is going to be my cathode. This is cathode and this is anode, right? So first of all, I'll write the reaction which will be taking place at anode. We know at anode oxidation takes place. Oxidation means loss of electrons. Your tin is getting converted to Sn dye positive. So the reaction will be tin solid gets converted into Sn dye positive aqueous, and with this you write 2 electrons. This is a little lengthy equation, right? Okay. Now people, the reaction which will be taking place at cathode. At cathode, we know reduction takes place. Reduction means gain of electrons. Your Pb dye positive is getting converted into Pb solid. So the reaction is going to be Pb dye positive aqueous it will be gaining some 2 electrons and it will be getting converted into Pb solid, right? This is the reaction taking place at cathode. Now simply I'll be adding the 2 reactions. On adding the 2 reactions, this and this got cancelled. So my net reaction becomes tin solid plus Pb di positive aqueous. It gives Sn di positive aqueous plus what? Plus Pb solid. Plus Pb solid. This is the net reaction which is taking place, and how many moles of electrons got exchanged in this net cell reaction? 2 moles of electrons got exchanged in this net cell reaction. Yeah? Now people understand. Let's try to write the QC value. QC. Starting with Sn di positive. So concentration of Sn di positive raised by its stoichiometric coefficient, that's 1. This is in solid form, its active mass is 1, divided by concentration of Pb di positive raised by its stoichiometric coefficient. Well people, concentration of Sn di positive must be given to me, that's 1 molar, divided by concentration of Pb di positive must be given to me, that's 10 raised power minus 3, the value comes out to be 10 raised power 3. So QC value I got, QC value I got. Now after getting the QC value, I need to get the value of E naught cell. E naught cell is nothing that is equal to E naught of cathode minus E naught of anode, right? And this is the standard reduction potential of cathode. This is the standard reduction potential of anode. What is the standard reduction potential of lead? This is the standard reduction potential of lead. Lead electrode is my cathode. So this is the standard reduction potential of cathode, which is minus 0.13, minus standard reduction potential of anode. This is the standard reduction potential of anode, which is minus 0.14. The value comes out to be 0.01 volts. This is the E naught cell. Well, after getting the E naught cell, use the Nernst equation now. You can say E cell is equal to E naught cell, I got 0.01, minus 0.0591, divided by N value is 2, log of QC. QC value I got to know as 10 raised power 3, right? The equation is done and dusted. It will be 0.01 minus 0.0591 divided by 2. It's going to be 3 log 10, that means 3, right? You need to solve this part and get the answer in volts, right? That's going to be the EMF of this cell. Yes, people? Simple? Simple? Yeah? I'm sure it's clear. So finally people are saying the answer comes out to be minus something, right? Let me exactly check. Finally the answer will be minus 0.07 volts, correct? Absolutely. No, there is no shortcut to solve this question. You need to follow all these steps, then only you can reach to the final conclusion, right? There is no shortcut for this. Perfect? Okay, moving on to one more, guys. For the cell, I'm given the cell, right? Choose the correct option. Choose the correct option. Okay. Before doing this question, let me tell you one important concept. For the cell to be working, for the cell reactions in the cell to be spontaneous, for the cell reactions in the cell to be spontaneous, delta G for the cell must be negative. Delta G for the cell must be negative. Then only cell reactions in the cell will be spontaneous. Then only the cell will be working like the normal galvanic cell. Then only the direction of electrons will be from anode to cathode and the direction of current will be from cathode to anode, right? Yes? Yes? Now we will see. Delta G is negative. For the cell to be spontaneous, for the cell reactions to be spontaneous, delta G must be negative. Delta G is nothing, that is minus NFE cell. Okay, so minus NFE cell should be negative. This term can be only negative if E cell will be positive. If E cell will be positive. So let's make a criteria. Let's make a criteria. See guys, for the cell to be spontaneous, for the cell reactions to be spontaneous, for the cell to be working, E cell must be positive. E cell must be positive, right? Right, people? This is the concept which I'll be using in order to solve this question. Have a look. See, remember, for the cell to be working, E cell must be positive. E cell must be positive, right? Yeah? Now people, see how will I be solving this one. Understand. For the cell, I'm given the cell, right? I'm given the cell. Have a look properly. On both the sides, I'm using the same electrodes, zinc, right? So it is first of all the concentration cell, right? In the concentration cell, we use the same electrodes, right? If I've used the same electrodes, what about the E naught cell? For the concentration cells, we know E naught cell value is taken to be 0. Because we have used the same electrodes. So E naught cell is absolutely going to be 0. Point number 1. Point number 2. Let's try to solve it. How do I solve it? Have a look. Have a look properly, guys. This is the salt bridge in the middle. On the left hand side of the salt bridge, we always write the anode, and we know at anode oxidation takes place. Oxidation means loss of electrons. Zinc is getting converted into Zn di positive. So I'll be writing zinc solid gets converted into Zn di positive aqueous. With this you write 2 electrons, right? This is the reaction which will be taking place at anode, right people? And what is the concentration of this Zn di positive? It is C2. It is C2. Similarly, I'll be writing the reaction which will be taking place at cathode. At cathode, reduction takes place. Reduction means gain of electrons. So Zn di positive getting converted into zinc. So the reaction must be Zn di positive with the concentration of C1. With the concentration of C1, will be gaining some 2 electrons and will be getting converted into zinc solid, right? You wrote the reaction at anode, you wrote the reaction at cathode, right? Let's add these 2 reactions. Let's add these 2 reactions. This zinc solid got cancelled out. I got the net cell reaction as Zn di positive with the concentration C1 gets converted into Zn di positive with the concentration C2. This is my net cell reaction. Okay. So people, if I'll ask you what is the value of N for this net cell reaction, see 2 moles of electrons got exchanged in the net cell reaction. So N value is 2. N value is 2, right? E naught cell already we know. QC value is simply going to be equal to C2 divided by C1. C2 divided by C1. This is QC. Now we use the Nernst equation. If I'll use the Nernst equation, I'll say E cell is equal to E naught cell, that is already 0, minus 0.0591 divided by N is 2 log of QC. QC is nothing, that is C2 by C1. Okay, I'll be writing it like this as well. 0.0591 divided by 2, it's going to be log of C1 divided by C2, right? I told you a few minutes back, for the cell to be working, for the cell reactions to be spontaneous, for the cell reactions to be spontaneous. For the cell reactions to be spontaneous, E cell value must be positive. When can E cell be positive? E cell can be only positive if this term is positive. When can this term be positive? This term can be only positive if this term is greater than 1. Right? So C1 divided by C2 must be greater than 1. Then only E cell value will be positive. Right? Which clearly says C1 is greater than C2. So people, I got the condition. For this cell to be working, for its cell reactions to be spontaneous, C1 should be greater than C2. C1 should be greater than C2, right? The cell reaction will be spontaneous if C1 is greater than C2. Is it right? Just a second, guys. Did I do any sort of mistake somewhere? Just a second. This was C2, this was C1. So this is going to be C2 divided by C1, right? It's correct. E cell is equal to minus 0.0591 divided by 2 log of QC, C2 by C1, right? So I multiplied with minus sign, C1 comes up, so C1 divided by C2 should be. This is correct, right? This one is correct. So for the cell reactions to be spontaneous, C1 must be greater than C2. If C2 is greater than C1, okay, one more thing. If C1 is greater than C2, E cell will be positive. E cell will be positive means this cell will be working like a normal galvanic cell in which the direction of current is from cathode to anode. Now, if C2 is greater than C1, current will flow from cathode to anode. No. If C1 is greater than C2, then current will flow from cathode to anode. So this one is wrong. If C1 is greater than C2, current will flow from cathode to anode. Absolutely right. If C1 is equal to C2. If C1 is equal to C2, log of 1 comes out to be 0. This whole term will be 0. E cell will be 0. And when EMF of the cell becomes 0, we say the cell does not work at that time, right? So A, C, and D are the correct answers of this question. I'm sure it's clear to everyone. Yeah? Right, people? Clear to everyone? Someone is saying about this minus. I multiplied this minus with this log. That's why the reciprocal came over here. Yeah? Perfect? Okay, let's move on then. This is one more question, guys. This is one more question. See, understand. First of all, we have got similar electrodes, 2 similar electrodes, hydrogen electrodes, 2 same electrodes we have used. So it is first of all the concentration cell. If it is a concentration cell, so first thing E naught cell is 0. That's something which we already know, right? That's something which we already know. Yeah? Now we will have a look properly. It is the concentration cell. But in this concentration cell, the concentration of H positive in both the containers, anodic container as well as cathodic container is different. The concentration of H positive in anodic container as well as cathodic container, that's different. But the partial pressure of H2 gas is same. partial pressure of H2 gas on the electrodes is same, right? So which type of concentration cell it's going to be? It is going to be electrolytic concentration cell involving hydrogen electrodes. Whenever you'll be having two hydrogen electrodes connected with the help of a salt bridge, right, in which the partial pressure of hydrogen is kept same but the concentration of H positive is kept different, we call that cell as the electrolytic concentration cell involving hydrogen electrodes. And how do we calculate its EMF? There's a formula for it. This is the formula. This formula is particularly valid for the electrolytic concentration cell involving hydrogen electrode. So it's going to be 0.0591 multiplied by pH of anode minus pH of cathode. Bus, the question is done. pH of anode contained, that's X. pH of cathode, since concentration of H positive is 1 molar, so pH of cathodic contained is going to be minus log of H positive concentration, so minus log of 1, that comes out to be 0. Finally, you get the value of X as 4. That's all. Yes, that's all. X will be 4, absolutely. Yeah? Perfect? Now, moving on to one more. This is one more question. Guys. Calculate the EMF of the cell. We are supposed to calculate the EMF of the cell, right? Okay. Again, if you can see, hydrogen electrode. This is the salt bridge. So it is again the concentration cell, and in case of concentration cells, we know E naught cell value is 0. First thing which I got, right? Now we will have a look properly. First of all, let me write the reaction which will be taking place at anode. At anode, oxidation takes place and H2 is getting converted into H positive. So the reaction will be H2 with the pressure of P1. It gets converted into 2 times H positive aqueous, and with this you'll be writing 2 electrons. Okay. Similarly, what is the reaction which will be taking place at cathode? At cathode, reduction will be taking place. Reduction means gain of electrons. H positive is getting converted into H2, right? So the reaction will be 2 times H positive aqueous plus 2 electrons. It gets converted into H2 gas, right? Yes? Okay. Now people, what is the partial pressure of this H2 gas over here? Partial pressure of this H2 gas is P2. What is the concentration of this first H positive? Concentration of first H positive is C1. What is the concentration of the second H positive? That is C2 over here, right? Let me write the net cell reaction. Net cell reaction is going to be H2 with the pressure of P1 plus 2 times H positive with the concentration of C2, right? It gives 2 times H positive with the concentration of C1 plus H2 with the pressure of P2, right? This is the net cell reaction which I got, okay? If I'll ask you what is the value of N, how many moles of electrons got exchanged, you will clearly say 2 moles of electrons got exchanged, right? Yes? Right, people? Now, have a look. Let's write the QC expression. QC expression is going to be concentration of H positive, which is C1, raised by stoichiometric coefficient, that's 2, multiplied by partial pressure of H2, which is P2, divided by concentration of H positive over here, that is C2, raised by stoichiometric coefficient, that's 2, multiplied by partial pressure, that's P1. This is QC. E naught cell is already 0. Now use the Nernst equation and calculate the E cell. So E cell is going to be equal minus 0.0591 divided by N value is 2. It's going to be log of QC. QC is nothing. QC is C1 square multiplied by P2 divided by C2 square multiplied by P1, right? If you knew all the parameters of C1, C2, P1, P2, you would have easily calculated the E cell over here, right? If I'll ask you to check the criteria, what are the conditions which the cell must follow such that its cell reactions will be spontaneous? What are the conditions for this cell to be spontaneous? For the cell to have its cell reaction spontaneous, its E cell must be greater than 0. Then only the cell reaction will be spontaneous, right? Yes, people? Then only the cell reaction will be spontaneous. Now, cell reactions will be only spontaneous if E cell will be greater than 0. E cell will be only greater than 0 if this log term is greater than 0. And this log term will be greater than 0 if this term is greater than 1. Right? What is this term? It is C1 square multiplied by P2 divided by C2 square multiplied by P1. This term should be greater than 1. Right? So, I got the criteria over here. Criteria is something like this. C1 square divided by C2 square must be greater than P1 divided by P2, then only the cell reactions will be spontaneous, right? I'm sure it's clear to everyone. Perfect, guys? Yeah? Okay, I think I did a mistake. Is there a mistake? Yeah, this is the minus sign, guys. So first of all, you are supposed to multiply with this minus sign. I forgot to multiply with minus sign. Yeah. So you can say it like this. E cell is equal to 0.0591 divided by 2. It's going to be log of. Just take the reciprocal, right? It's going to be C2 square multiplied by P1 divided by C1 square multiplied by P2. Now, E cell will be only greater than 0 if this term is greater than 1. So finally, C2 square divided by C1 square should be greater than P2 divided by P1. This is the actual answer. This is the criteria which the cell must follow. Then only the cell reactions will be spontaneous. Absolutely. Yeah. Perfect. Okay, let's move on to one more, guys. For the cell involving one electron, right? So n value is equal to 1 first of all. Okay. E naught cell value is given to us. What are we supposed to calculate? We are supposed to calculate equilibrium constant of the cell reaction. Right? Right, people? We are supposed to calculate equilibrium constant of the cell reaction. In order to calculate equilibrium constant of the cell reaction, the cell must be at equilibrium. And when the cell is at equilibrium, remember, at that time, E cell value is taken to be 0. Right? N value is 1. E cell is equal to 0 because the cell is at equilibrium. So I'll be directly using the Nernst equation. As per your Nernst equation, E cell, we know, is equal to E naught cell minus 0.0591 divided by N log of QC. But when the cell will be at equilibrium, this term will be 0, is equal to E naught cell minus 0.0591 divided by N. Instead of QC, you'll be writing KEQ, equilibrium constant, right? The equation is almost done and dusted. So what you'll be getting right here, you'll be getting E naught cell is equal to 0.0591 divided by N log of KEQ. Now put all the parameters into this equation. Those are given to you. E naught cell is given to me as per the equation 0.59, right? Divided by what? Divided by 0.0591 multiplied by N value. N value is given to me as 1. So N value, it does not make a difference, is equal to log of KEQ to the base 10, right? This value will come out to be 10. So 10 is equal to log of KEQ to the base 10. So finally from here, you'll be getting KEQ as 10 raised power 10. So this is the equilibrium constant which I was supposed to calculate. Right? Naresh, if you have studied this chapter, then only you can understand these questions. If you have not studied these chapters, so you won't be able to solve these questions. Clear, guys? Perfect? Okay, let's move on then. Okay, now comes one more question, guys. Calculate how much current is required to produce Cl2 gas at the rate 1 liter per second under standard conditions. So first of all, Cl2 gas has to get liberated. When will Cl2 gas get liberated? First of all, Cl2 gas will only get liberated when this reaction takes place at any of the electrodes, right? When this reaction takes place at anode, then only Cl2 gas will get liberated. If you remember, electrolysis of molten NaCl, what happens at anode? At anode, this reaction takes place due to which Cl2 gas gets liberated, right? We know it, yeah? Now guys, see, have a look. At anode, this reaction has to take place, correct? So first of all, what do I need to calculate? See, calculate how much current is required to produce Cl2 gas at the rate 1 liter per second. So first of all, 1 liter of Cl2 gas has to get liberated in how much time? In 1 second. 1 liter of Cl2 gas has to get liberated in 1 second. So for that purpose, how much current is required? That's something which I need to calculate. I'll be simply using the Faraday's first law, right? But before talking about the Faraday's first law, let me calculate the n factor of this Cl2. You'll clearly see n factor of this Cl2 will be equal to total moles of electrons exchanged, that's 2. Stoichiometric coefficient is 1, so divide by 1 comes out to be 2. So n factor of Cl2 you got to know as 2. So I'll write something like this. Mass of Cl2 liberated is equal to As per Faraday's first law, equivalent mass of Cl2 multiplied by I multiplied by T divided by what? Divided by 96500. This is one of the relation which you can use. Or instead of this, what you can do is, just in order to simplify it, have a look. This much volume of Cl2 has to get liberated in 1 second. So if I'll ask you how many moles of Cl2 are supposed to get liberated, you will say 1 divided by 22.4 liters, right? So these many moles of Cl2 has to get liberated. Now there's a formula. Number of moles of gas liberated will be equaled. It is equal to I multiplied by T divided by what? Divided by n factor of Cl2 multiplied by 96500. This is one more relation which we have as per Faraday's first law, right? Okay, let me give the relation first. See, mass of substance deposited or liberated is equal to EIT divided by 96500. This is one of the relation. Number of moles of the substance deposited or liberated is equal to I multiplied by T divided by n factor of the substance which is getting liberated or deposited multiplied by 96500. Just to remember these relations, yeah? Now the question is almost done. Number of moles of Cl2 which are getting liberated, that we already know, 1 upon 22.4. 1 upon 22.4, right, is equal to I multiplied by T. I value I'm supposed to calculate, right? T value is 1 second. N factor of Cl2, that is 2, multiplied by 96500. If you solve this equation, you'll be getting the value of I, which is something I was supposed to calculate. I was supposed to calculate the amount of current which is required to produce 1 liter of Cl2 gas in 1 second. So 8616 amperes, this much amount of current is required to liberate 1 liter of Cl2 gas in 1 second. Yeah? Done? Right, people? Let's move on to one more question then. Okay, this is one more question. Have a look. 1 farad of electricity is passed through 10 liter of an aqueous solution of NaCl. Calculate the pH of the solution. When we do the electrolysis of aqueous NaCl, this is the reaction which takes place at cathode and this is the reaction which takes place at anode, right? pH of the solution, you all must be knowing, is due to the presence of either H positive or OH negatives, right? This reaction does not produce either H positive or OH negative, but this reaction, it produces OH negative. So this reaction which is happening at anode, it is basically producing OH negatives, due to which there will be pH in this. This reaction is responsible for the pH of the solution. This reaction is responsible for the pH of the solution, right? Yes? This reaction. Yes, Rahul, A is the equivalent mass. This reaction is responsible for the pH of the solution because this reaction leads to the production of OH negatives. Yeah? Now see guys, how do I calculate pH? Understand. First of all, if I'll calculate the n factor of OH negative, n factor of OH negative is going to be equal to number of moles of electrons exchanged divided by stoichiometric coefficient, that's 2. So 2 divided by 2 comes out to be 1. This is the n factor of OH negative. Now I'll use the formula. Number of moles of OH negative liberated is equal to I multiplied by T divided by n factor of OH negative multiplied by 96500. Right, people? Now have a look. Number of moles of OH negative I'll be calculating from here is equal to I multiplied by T. Current multiplied by time. That's Q, charge. How much charge is given to me? 1 farad. 1 farad, all of you must be knowing, that's 96500 coulombs. So in case of I multiplied by T, I'll be using 96500 coulombs divided by n factor of OH negative. N factor of OH negative is 1. Correct? Multiplied by 96500. So people, can I say I got the number of moles of OH negative which are getting liberated in the solution? Yeah? So these many moles of OH negative are getting liberated in the solution. Okay? If I got the moles of OH negative liberated in the solution, can I calculate OH negative concentration, which is equal to number of moles of OH negative liberated divided by volume of solution in liters, right? I think I'll fall ill soon, yeah? Number of moles of OH negative which are getting liberated, that's 1. Volume of solution in liters, that's 10 liters, right? So the value comes out to be 10 raised power minus 1. This is OH negative concentration. Well, if you got the OH negative concentration, you can calculate POH. POH is nothing, that is minus log of OH negative concentration. It's going to be minus log of 10 raised power minus 1. The value comes out to be 1. So this is POH. If you got the POH, you can calculate pH. pH is going to be 14 minus POH. The value comes out to be 13. So 13 is going to be pH of the solution which I was supposed to calculate, right? Yes? Simple? Right, people? So first of all, I got the moles of I got the moles of OH negative which got liberated. Yeah. After calculating the moles, I got to know the concentration of OH negative. After calculating the concentration of OH negative, I calculated the pOH. After getting the pOH, I got the pH. That's all, right? Yes? I'm sure it's clear to everyone. Let's move on to one more then. Okay. When 0.1 mole MnO4 dinegative is oxidized, the quantity of electricity required to completely oxidize MnO4 dinegative to MnO4. Okay. So first of all, as per the question, MnO4 dinegative is getting converted into MnO4 negative. Okay. What is the oxygen state right here? Oxygen state of Mn is +6. Over here is +7. +6 to +7, increase in oxygen state. Increase in oxygen state means oxidation. Oxygen means loss of electrons. So from +6 to +7, it is basically losing 1 electron. This MnO4 dinegative, it's losing 1 electron, then only it's getting converted to MnO4 negative. Yeah? Correct? Right? We will +6 to +7, increase in oxygen state means oxidation, loss of electrons. So you can say when 1 mole of MnO4 dinegative undergoes oxidation, 1 mole of electron is lost. 1 mole of electron is lost, right? So 1 mole during the oxidation of 1 mole of MnO4 dinegative, how many moles of electrons are exchanged? 1 mole of electron is exchanged, right? So I'll say during the oxidation of 1 mole of MnO4 dinegative, how many moles of electrons are being exchanged? 1 mole of electron is being exchanged. But during the oxidation of 0.1 moles of MnO4 dinegative, I'll say 0.1 moles of electrons will be getting exchanged, right? So these many moles of electrons are being exchanged when 0.1 mole of MnO4 dinegative undergoes oxidation, right? We know the charge present on 1 mole of electrons. The charge present on 1 mole of electrons is 96500 coulombs, right? That's something which you all must be knowing. 1 farad, 96500. If the charge present on 1 mole of electrons is this much, what is the charge present on 0.1 mole of electrons? So 0.1 mole of electron will carry the charge of 9650 coulombs. So this much amount of charge is exchanged when 0.1 moles of MnO4 dinegative undergoes oxidation. So the answer of this question is going to be option C. I'm sure it's clear to everyone. You can let me know in the chat box fast. Right, people? Absolutely. It must be clear to you. Okay, one more. What is the volume of oxygen liberated at anode at STP in the electrolysis of aqueous CuSO4 when the current of 2 amperes is passed for 8 minutes? See guys, when we do the electrolysis of aqueous CuSO4 at anode, this reaction takes place and O2 gas gets liberated. O2 gas gets liberated. Why I wrote this reaction? Why I did not write the reaction for cathode? Because I need to calculate the volume of oxygen liberated, and oxygen gets liberated only at anode, right? Oxygen gets liberated only at anode, yeah? Okay, now we will have a look how I'll be solving this question. First of all, let me calculate the N factor of O2. N factor of O2 is going to be equal number of moles of electrons exchanged, that's 2, divided by stoichiometric coefficient, that's 1/2. The value comes out to be 4. So I got the N factor of O2 first of all, yeah? Now, number of moles of O2 liberated will be equal to I multiplied by T divided by N factor of the substance which gets liberated multiplied by 96500, right? Is the value of I and T given to me? Absolutely. Current 2 amperes passed for 8 minutes. So 8 multiplied by 60 seconds divided by N factor of O2, that's 4 multiplied by 96500. So from here you can calculate number of moles of O2 liberated. But am I supposed to calculate moles of O2 liberated? No way. I'm supposed to calculate the volume of oxygen liberated at STP. So you can say volume of oxygen liberated at STP is equal to moles of oxygen liberated multiplied by 22.4 liters, right? Okay, so moles of oxygen liberated you have calculated from here, multiply this term by 22.4, you'll be getting the volume as 0.05 liters. So 0.05 liters of O2 got liberated as per the equation. I'm sure it's clear to everyone, right? Right, people? Okay, one more question we have, and this is something which you can solve on your own, right? No, Rahul, the equation won't be given to you. You're supposed to remember the products of electrolysis. You're supposed to remember what are the reactions which will take, what are the reactions taking place at anode and cathode during the electrolysis of aqueous NaCl, aqueous CuSO4, molten NaCl, molten CuSO4, and so on. Those reactions are given in your NCERT. Do remember those reactions, okay? These reactions won't be given to you as per the equation. Yeah? You need to remember on which electrode which gas gets released, on which electrode which metal gets deposited, and so on. Yeah? Okay. One more question we have. During electrolysis of aqueous CuSO4, the mass of metal deposited is equal to this much. Calculate the mass of gas released and volume of gas released at STP. See guys, when we are doing the electrolysis of aqueous CuSO4, this is the reaction which takes place at cathode, and at cathode copper is getting deposited. At anode, O2 is getting released. I'll be using the Faraday's second law. I'll simply say gram equivalence of metal deposited should be equal to gram equivalence of gas released. Faraday's second law, right? I'll be using gram equivalence of copper deposited, right? Gram equivalence of copper deposited should be equal to gram equivalence of oxygen liberated. Okay, gram equivalence of copper deposited will be equal to mass of copper deposited divided by equivalent mass of copper is equal to gram equivalence of oxygen liberated is going to be equal to mass of oxygen liberated divided by equivalent mass of oxygen. Okay, now people, what is the mass of copper which is getting deposited? 63.5 grams divided by equivalent mass of copper is going to be equal to molar mass of copper divided by n factor of copper. N factor of copper, moles of electrons exchanged divided by stoichiometric coefficient. So 2 divided by 1 comes out to be 2, right? Is equal to mass of oxygen liberated. I'll be calculating from here equivalent mass of oxygen, molar mass of oxygen divided by n factor of oxygen. N factor of oxygen is 4. Few minutes back I showed you how to calculate it, right? So from here you'll be getting the mass of oxygen which is getting liberated. People, can you let me know how much mass is getting liberated? I'll say simply 16 grams of oxygen is getting liberated as per the equation, right? 16 grams. Now first of all I got the mass of gas released. Now let's calculate the volume of gas released. Mass of oxygen released I got as 16 grams. So can I calculate number of moles of oxygen released? It's going to be mass of oxygen released divided by molar mass of oxygen. So these many moles of oxygen are being liberated. So volume of oxygen which gets liberated, it's going to be equal to moles of oxygen liberated multiplied by 22.4 liters. The value comes out to be 11.2 liters. So this much volume of O2 gets liberated at the end. Yes? Simple? Right people? I'm sure it's clear to everyone. Faraday's second law this is. Yeah? So these many liters of O2 are getting liberated. That's something which I was supposed to calculate. Correct? Okay. One more question. This is something which you can do on your own. This is again based on the Faraday's second law. Okay. This is a similar type of question. First I'll be using the Faraday's first law and get the, what do I need to calculate? I need to calculate the time. Okay, get the time, and after that you'll be using the Faraday's second law. This is the similar type of question, so I'm not going to solve this one. Okay. Similar type of question. Okay, the specific conductance, that means conductivity, kappa, it is given to me as 0.009 Simon centimeter inverse, 0.009 Simon centimeter inverse, right? Molarity of the solution is given to me as 0.1. Cell electrodes of 1.5 centimeter square, okay, area of cross section of electrodes is given to me as 1.5 centimeter square. And distance between the electrodes is given to me as 0.5 centimeters, right? How much current should flow if potential difference between the electrodes is 5 volts, right? How much current should flow if potential difference between the electrodes is 5 volts? So potential difference between the electrodes is given to me as 5 volts, correct? What do I need to calculate? I need to get the current. I need to get. I is nothing that is equal to V divided by R. V value is given to me. I need to get the value of R first. Then only I can calculate I. Now, how do I calculate R? R is involved in one relation, if you remember. Kappa is equal to 1 divided by R multiplied by L by A. I hope you know this relation, right? Conductivity is equal to conductance multiplied by cell constant. This is something which every one of you would have heard, right? Right, people? Now have a look. Kappa is given to me. Conductivity is given to me as 0.009 is equal to 1 divided by R multiplied by L by A. L value is given to me as 0.5. A value is given to me as 1.5. So from here I'll be getting the resistance in ohms. Once you get the resistance in ohms, put that value into this equation, get the value of current which you were supposed to calculate, right? Yes, people? So Javed is saying I value comes out to be 0.135. So finally I value comes out to be 0.135 amperes, which I was supposed to calculate. Simple, right? Right, guys? Okay, moving on to one more then. This is one more question. This again a similar question, right? I need to calculate the conductivity. First of all, kappa I need to calculate, which is going to be 1 divided by R multiplied by L by A. See, are all these parameters given? Resistance is given to me as 210. This value is given to me. L by A is something which we call a cell constant. This is also given, right? So this term is given, this term is given. You can calculate kappa. Equivalent conductivity, people, lambda EQ is equal to kappa multiplied by 1000 divided by normality. If you are supposed to calculate lambda EQ in Simon centimeter inverse per equivalent, right? Okay. So lambda EQ is equal to kappa value you would have calculated from here. 1000 is a constant. Normality of the solution is given to us. So you need to put all these parameters in this equation. You can calculate lambda EQ, right? Simple. Simple, guys, right? Yes. See. Simple, I got the value of kappa. First of all, I have the R, I have the L by A. I can calculate conductivity. After getting conductivity, I'll be putting that conductivity into this equation. Kappa value I'll be putting here. Normality I know I'll be getting lambda EQ, which is equivalent conductivity. Simple, right? Okay. So lambda EQ finally you're getting is 419 something. Okay, one more question we have, guys. You can solve this one as well. It's a simpler one again. See, the equivalent conductivity. Lambda EQ is given to us. Equivalent conductivity, lambda EQ. It's given to me as 100. It's given to me as 100, right? Okay. The equivalent conductivity, normality of the solution is given to me as well. That is 0.1. Okay. Cell constant, L by A is given to me as 0.25. Centimeter inverse. How much current will flow when the potential difference between the electrodes is 5 volts? Potential difference is given to me as 5 volts, right? I'll be again doing the same thing. Right? I'm again going to do the same thing, correct? I'll be simply getting I is equal to V divided by R. This is the Ohm's law. V value is given to me as 5. I need to calculate R. Correct? How do I get the R value? I'll be using the equation kappa is equal to 1 divided by R multiplied by L by A. Yes. But people, at the same time, am I given with the conductivity? Am I given with the conductivity? No. I'm not given with the conductivity. If I'm not given with the conductivity, I cannot calculate resistance. So I need to calculate conductivity first. How do I calculate conductivity? For that, I'll be using the equation lambda EQ is equal to kappa multiplied by 1000 divided by normality, right? Lambda EQ is given to me as per the equation. Normality of the solution is given to me. From here, I'll be calculating K. If you get the value of K, put it over here. Cell constant L by A is given to me. I will be calculating R. Once you get the value of R, put that value of R into this equation, get the value of current, right? Right, people? Clear to everyone? Clear to everyone? So people are saying 0.2 amperes is going to be the answer of the question. So I believe 0.2 amperes is going to be the answer of this question. Simple, right? Right, people? Yeah? Okay, let's move on to the new one. One more question we have. You can simply solve it. It's a very basic and ordinary question. The number of farads required to produce 20 grams of calcium from the molten CaCl2, okay? From the molten CaCl2. How do we get calcium, first of all? How do we get calcium from molten CaCl2? So for that, in order to produce calcium, a reduction has to take place like this. Ca dipositive should gain 2 electrons, then only calcium solid will be getting deposited at cathode, right? This is the reaction which will be happening by means of which calcium will be getting deposited, right? Yes? Right, people? Now, first of all, if I'll ask you what is the N factor of calcium? N factor of calcium, you can say moles of electrons exchanged, that's 2. Stoichiometric coefficient is 1. The value comes out to be 2, right? This is the N factor of calcium, first of all. Now, people, I can say something like this. Mass of calcium deposited is equal to equivalent mass of calcium multiplied by I multiplied by T. Instead of IT, I'll be writing Q divided by 96500, right? Okay, so Q from here will be equal to mass of calcium deposited, that's equal to 20 grams, multiplied by 96500, divided by equivalent mass of calcium, which is molten mass of calcium, divided by N factor is 2. Right? The value comes out to be 96550 coulombs. Yeah? Sorry, 965. Did I miss anything, people? Did I miss anything? Just a second. I think I missed something. the number of farads required to produce 20 grams of calcium, right? 20 grams of calcium. Okay, this is not 2, this is 20, right? Okay, this is 20. So the value comes out to be 96500 coulombs, and 96500 coulombs means 1 farad. So 1 farad is going to be the answer of this question, right? Yes, Sabrina, you can use the mole method as well and solve the equation, right? You can do that. Perfect. Okay, one more question. I need to calculate the value of delta G naught. Well, people, delta G naught is nothing. It is equal to minus NF E naught cell, right? Minus NF E naught cell. So in order to calculate delta G naught, you should know all these parameters. Well, what is the value of N? How many moles of electrons have been exchanged in this net cell reaction? You can clearly see 2 moles of electrons have been exchanged in this net cell reaction. So N value is 2. F, Faraday's constant, 96500 coulombs. E naught cell is given to me as 2 volts, right? Okay, E naught cell is given to me as 2 volts. Now the value of this whole term will be right now in joules, but if I divide it with 1000, it will come in kilojoules, because I need to get the answer in kilojoules, I believe, right? I need to get the answer in kilojoules. Yeah, the question is done and dusted. You can solve it on your own, right? So the answer of this question is going to be option C over here, which is minus 384 kilojoules per mole. Yeah, I'm sure it's clear to everyone. Well, this is something which you can do on your own. Let me know its answer, people, first. Give it a try. Let me know its answer. Limiting molar conductivity of NH4OH. Limiting molar conductivity of NH4OH. NEET 2013. What is going to be the answer of this question? Simple, guys. Kohlrausch's law, you are going to use, that's it, right? Yeah? NH4OH, limiting molar conductivity of NH4OH. See, people are saying option D, is that? So NH4Cl plus NaOH minus NaCl. So Na gets cancelled, Cl gets cancelled, so I'll be left with NH4 positive and OH negative, so absolutely option D is the one which is correct, right? Yes? Simple. Okay, one more question. The most durable metal plating on iron to protect against corrosion is galvanization zinc plating, right? Every one of you must be doing this, right? It's going to be zinc plating, option D. Yeah? Absolutely, guys. Okay, so with this, electrochemistry is completely revised. I missed one topic over here. What is that going to be? That is your cells, those batteries. Please and please do study that topic, that storage cells, everything batteries. Do study from your NCERT. Those are small 2-3 paragraphs given. Do have a look on that as well, because the memory based questions can be asked from that. Okay? Yes? So you want a break? You guys want a break? Yeah? Okay. So the time right now is 11:08, yeah? So I'll meet you guys exactly at it is 10:08 right now. What time you want me to start again? 11:20. Let's take a break for 15 minutes. I'll see you at 11:25 sharp. Is it AM or PM? I do not know, by the way. I'll simply write 11:25 sharp, yeah? Okay? Yeah? Okay, till then, you guys can have some snacks, some tea or something, get refreshed, but do get back, because chemical kinetics is one of the important chapters, right? Okay? So let's wait for some time. Let's take a break. I'll catch you guys exactly at 11:25 and be there on time, please. Okay? Everyone got back, yeah? I think you guys can hear me again, right? You guys can hear me? Right, people? Okay. Just give me a second. Perfect. Perfect, guys. So, should we start with chemical kinetics now? Should we start with chemical kinetics now? Just give me some thumbs ups in the chat box. Yeah? Perfect, guys. Perfect. Yes, Asif will complete fully. Okay, no issues. We'll complete fully. You need to stay with me till the end, but yeah? Okay, so let's get going with the chapter called as chemical kinetics. The first question which is on your screen. Okay. See guys, a very simple question based on a very simple concept. Okay, and frequently these sort of questions are asked nowadays in your NEET examination. Yeah. See guys, how this sort of equation is to be solved. First of all, I'm given with a balanced chemical equation. This is a balanced chemical equation, right? Stoichiometric coefficients involved are 1, this is 1, and this is 1 by 2. First of all, what I'll be doing is I'll be writing the differential form of rate equation for this equation, right? I can say rate of reaction with respect to H2O2. H2O2 is the reactant. I'll start with the minus sign. Change in the concentration of H2O2 divided by time interval dt, which is also equal. With respect to H2O, H2O is the product. I'll be starting with plus 1 divided by stoichiometric coefficient, that's 1. Change in the concentration of H2O divided by dt, which can be also written in terms of O2. O2 is the product. I'll start with the positive sign. 1 divided by stoichiometric coefficient. 1 divided by 1 by 2, that means 2. Change in the concentration of O2 divided by dt, right? This is a differential equation which I formed over here first of all, correct? Now, what are the things which are given to me as per the question? As per the question, the concentration of H2O2 changes from 0.5 molar to 0.05 molar, right? So basically, as per the question itself, this is the initial concentration of H2O2 and this is the final concentration of H2O2, and this is the time interval, 15 seconds. What do I need to calculate? I need to calculate rate of reaction. I can calculate rate of reaction by solving any of these terms, right? Let me take this term out from here. Let me calculate rate of reaction from this term. I'll say rate of reaction is equal to minus times change in the concentration of H2O2, which will be final concentration of H2O2, that is 0.05, minus initial concentration of H2O2, which is 0.5, divided by time interval is given to me as 15 seconds, right? You need to solve this. You'll be getting the value in moles, liter inverse, second inverse. This will give us the rate of reaction. Well, people are saying it is coming out to be as 0.03. Okay, so finally, rate of reaction you guys are going to get as 0.03 moles, liter inverse, second inverse, right? First part of the question is done. Second part of the question, calculate the rate of appearance of O2. First of all, how do we write the rate of appearance of O2? I'll say rate of appearance of O2. Rate of appearance of O2. How do we represent it mathematically? Since we are talking about appearance, I'll start with the positive sign. Change in the concentration of O2 divided by dt without dividing with the stoichiometric coefficient. Right? So it's going to be equal. So, this term we are supposed to calculate. D of O2 divided by dt we are supposed to calculate. So what am I going to do now? Have a look properly, guys, what I'm going to do. Understand. First of all, let me take this term out from here and let me take this term out from here. Let me equate these two terms directly. If I'll equate these two terms, what I'll be getting? I'll be getting 2 times d of O2 divided by dt is equal to minus times d of H2O2 divided by dt. Correct? Right? I took these two terms out from here. Okay, what am I supposed to calculate? I'm supposed to calculate this value, d of O2 divided by dt. I'll say d of O2 divided by dt, which is basically rate of appearance of O2. It is minus 1 by 2 d of H2O2 divided by dt. Correct? Now people, The question is almost done. It's minus 1 by 2. D of H2O2, change in the concentration of H2O2, which is final concentration of H2O2, that is 0.05, minus initial concentration of H2O2, that is 0.5, divided by time interval, that's 15 seconds. Solve this term, you're going to get the value as 0.015. Okay, you're getting the value as 0.015 moles liter inverse second inverse. This is basically the rate of appearance of O2 which I was supposed to calculate, right? As simple as that. Yes, absolutely, people. Absolutely. So you got to know how do we approach to these sort of questions. What you're supposed to do is you're supposed to write this equation. That's it. When you write this equation, you can calculate anything, whatever you're supposed to calculate as per the equation. Yeah? Perfect. Let's move on to one more question which is going to make your one more concept clear. See guys, this is one more question that's given to me. I'm given with a reaction 2 times NH3 gives N2 plus 3 times H2, and I'm given with a curve, concentration versus time curve, right? Can you first of all let me know, is this curve valid for reactants or products? Can you just let me know fast in the chat box? Is this curve valid for reactant or product? We know concentration of reactant decreases with time, right? This curve is valid for the reactant. Yes, people? Because for the reactant only the concentration decreases with time. So this curve is basically valid for NH3. This curve is valid for NH3. What do I need to calculate? I need to calculate the rate of reaction in the interval 5 to 15 seconds. I need to calculate rate of reaction in this interval 5 to 15 seconds. What is the time interval? Time interval is 10 seconds. From 5 to 15, the interval is 10 seconds. I need to get the rate of reaction in this time interval 10 seconds, right? So how I'll be solving it? I'll be writing rate of reaction. Stoichiometric coefficient is 2. I'll start with minus sign because NH3 is a reactant. 1 divided by stoichiometric coefficient. Change in the concentration of NH3 divided by time interval dt, right? Okay. Now we will have a look. It's going to be equal to minus 1 divided by 2. Change in the concentration of NH3. What is the final concentration of NH3? See, I need to get the rate of reaction in this time interval, 5 to 15 seconds. So this is the final concentration. At time 15 seconds, this is the final concentration of NH3. And at time 5 seconds, this is the initial concentration of NH3. So final concentration minus initial concentration of NH3. Final minus initial divided by time interval is 10 seconds. Just solve it. Get the value in moles, liter inverse, second inverse, right? This is the rate of reaction, which I was supposed to calculate. Well, Farooq is coming up with 0.02. Well, after solving this, people are saying it is 0.02 moles liter inverse, second inverse, right? This is the rate of reaction which I calculated with respect to NH3, right, people? Simple. Yeah? I'm sure it's clear to everyone. Perfect. Let's move on to one more question then. This is one more question. How do we approach to this sort of a question? Understand. I'm given with some data. Minus d of N2O5 by dt is something, this is something, this is something. Find the relation between K1, K2 and K3. Find the relation between K1, K2 and K3, right? And I'm given with the reaction as well. And the reaction is given in the balanced form. This is a balanced chemical equation which I'm given with, right? Okay. Now people, understand. I'll be writing the rate of reaction as per the differential form. With respect to N2O5, which is the reactant, I'll start with minus sign. Change in the concentration of N2O5 divided by dt, which is also equal to, this NO2 is the product starting with the positive sign, 1 divided by stoichiometric coefficient is 2, change in the concentration of NO2 divided by dt, which is also equal to plus 1 by stoichiometric coefficient is 1 by 2, 1 by 2 comes out to be 2, d of O2 divided by dt. This is the differential form of rate which I wrote. Yeah? Now we will have a look. Minus d of N2O5 divided by dt. Minus d of N2O5 divided by dt. This value is given to me as K1 N2O5. K1 multiplied by concentration of N2O5 is equal to plus 1 divided by 2. D of NO2 divided by dt. D of NO2 divided by dt is given to me as K2 multiplied by concentration of N2O5 is equal to plus 2 times d of O2 divided by dt. D of O2 divided by dt is given to me as K3 multiplied by concentration of N2O5, right? So what all parameters will get cancelled in this equation? N2O5, N2O5, N2O5 got cancelled. So I got something as K1 is equal to K2 divided by 2, which is equal to 2 times K3. If I multiply throughout by 2, it becomes 2 times K1 is equal, K2 is equal to 4 times K3. So this is something which I was supposed to calculate, and this gives me the relation between K1, K2 and K3. I'm sure it's clear to everyone, right? Yes, people? Perfecto. Wonderful. Let's move on to one more question then. This is, see guys, what kind of question was asked in NEET 2019, right? This is your level of NEET examination, by the way. Yeah? Okay. See guys, I'm given with a reaction. I'm supposed to write its differential form. I'll write rate of reaction with respect to N2. It's going to be minus times change in the concentration of N2 divided by dt, which is equal to H2 is also reactant, minus 1 divided by stoichiometric coefficient 3, change in the concentration of H2 divided by dt, which can be written as, in terms of NH3, it's going to be plus 1 divided by 2, change in the concentration of NH3 divided by dt, right? Okay, which option satisfies it? I think it's done, right? Which option is the answer? In terms of H2 and NH3, H2 is minus, so this cannot be because there's a minus sign mentioned over here. In terms of N2 and NH3, this cannot be the answer because this is 2 over here, but this 2 should be in the denominator. What about the third one? D of N2 divided by dt is equal to 1 by 2 D of NH3 divided by dt. So option C is the one which is correct among all. I'm sure this is clear to everyone, right? Yes, absolutely. It's option C. Okay. Let's move on to one more then. This is one more question. For a chemical reaction A gives B, it is found that rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. See, for example, the reaction that's given to me is A gives B, right? Its rate constant is K. Let's assume the order of this reaction is equal to N. This is the nth order reaction, for example, right? Yes, simple. Now we will understand. If I'll be writing the rate law for this reaction is going to be R is equal to rate of reaction is equal to rate constant multiplied by concentration of A raised to the power order is N, correct? Let's keep this as equation number 1. Now what we are doing is, we are increasing the concentration of A 4 times. Initially, the concentration of A was this much. Now I'm making the concentration of A as 4 times A, right? And when we increase the concentration of A as 4 times A, what happens to rate? What happens to rate? Rate doubles. Initially it was 2R, now it becomes 2. Initially it was R, now it becomes 2R, right? Let's keep this as equation number 2. Just the equation is done. Divide equation 2 by 2. Divide equation 2 by first one. R get cancelled. So we get 2 over here. KK got cancelled. A raised power N, A raised power gets cancelled. This is 4 raised power N. When is this equation possible? When is 2 is equal to 4 raised power N? 2 is equal to 4 raised power N only if N will be equal to 1 by 2. And what was N? N was the order of the reaction which I was supposed to calculate, right? So order of reaction is going to be 1 by 2. I'm sure it's clear to everyone. Yes? Absolutely, people. Absolutely. Moving on to one more question. This is one more question on your screen. Calculate the order of the following reaction. We are given with a reaction whose rate constant is given to us, right? And I'm given with some experimental data. When the concentration of NO was kept this much, H2 concentration was kept this much, at that time rate of reaction is this much. When the concentration of NO is changed, when the concentration of H2 is changed, rate is changed and this much, right? We are given with 3 experiments basically. We are given with 3 experiments. We are supposed to calculate order of the reaction. How do I do it? See guys, see how to approach to these sort of questions. First of all, let me write the rate law for this reaction which is given to me. I'll be writing R is equal to K multiplied by concentration of NO raised power X multiplied by concentration of H2 raised power Y, correct? This X is called as the order of reaction with respect to NO. Y is called as order of reaction with respect to H2. And X plus Y gives us the overall order of the reaction, as you all must be knowing, right? Now we will understand. Now we will understand. Look at the experiments carefully. Look at the experiments carefully. If I look at the experiment number 1 and experiment number 2, in the first 2 experiments, concentration of H2 is kept same. In the first 2 experiments, concentration of H2 is kept same, right? In the first 2 experiments, concentration of H2 is kept same. So I've got nothing to do with this term, concentration of H2. Just remove it. Just remove it. Now, in the first 2 experiments, am I increasing the concentration of NO? Absolutely. I'm increasing the concentration of NO 3 times. On increasing the concentration of NO 3 times, rate is also increasing 3 times. On increasing the concentration of NO 3 times, rate is also increasing 3 times. That means the power over here must be 1, right? The power over here must be 1. See, concentration of H2 is kept fixed in the first two experiments. I'm increasing the concentration of NO 3 times. Rate is increasing 3 times, which is only possible if the value of X is 1. So I got the value of X. That's 1, right? Now what about value of Y? What about value of Y? Look here, people. Look here properly. If you look at experiment number 2nd and 3rd, in the experiment number 2nd and 3rd, I'm keeping the concentration of NO fixed. I'm not changing the concentration of NO. Now I have got nothing to do with this NO. What I'm doing is, I'm increasing the concentration of H2 4 times, as you can see. Concentration of H2 is increased 4 times. On increasing the concentration of H2 4 times, rate also increased 4 times, right? Okay, so in the experiment number 2nd and 3rd, I'm keeping the concentration of NO fixed. I'm increasing the H2 concentration 4 times, rate is increasing 4 times, which is only possible if the value of Y is 1. So we got the order of reaction with respect to NO, we got the order of reaction with respect to H2. So in order to calculate overall order of the reaction, we need to directly sum them up. So X plus Y comes out to be 2. So overall order of the reaction is 2. Simple? Yeah? Right, people? Got it? If rates will be different or if concentrations will be different, then you are going to make the equations. You will write this rate law for experiment number 1, rate law for experiment number 2, rate law for experiment number 3, then manipulate, divide the two equations, get the value of X, then divide other two equations, get the value of Y. Yeah? But you don't get those sort of questions in your NEET examination. In NEET, if question comes from experimental study, the question will be simple, so that calculations will be simple, right? Yeah? Perfect. Moving on to one more. See, this is the actual method of solving this, right? See, I wrote the rate law for experiment number 1, rate law for experiment number 2, rate law for experiment number 3. If I divide equation 1 by 2, I'll be getting X as 1. If I divide equation 2 by 3, I'll be getting Y as 1. So X plus Y is equal to 2. This is the actual procedure of solving this question. Yeah, I'm sure it's clear. Right, people? Okay. Perfect. Let's move on then. Let's move on. A zero order reaction is 20% completed. So before entering into the zero order reaction, let me give you some basic facts about zero order reaction. For example, I've got a reaction as A gives B. Let's assume its rate constant is K. Let's assume its rate constant is K. Let's assume order of this reaction is equal to 0. Order of this reaction is 0. Let's assume at time t is equal to 0, initially the concentration of reactant is A0, the concentration of product is 0. What is going to happen when the reaction will start? When the reaction starts, the concentration of reactant will keep on decreasing and the concentration of product will keep on increasing. We know it, yeah? Now people, at some time t, the concentration of reactant which is left is represented by AT. AT is the concentration of reactant left at time t, A0 is the initial concentration of reactant. Remember the integrated rate equation for the zero order kinetics? AT is equal to A0 minus KT. This is the integrated rate equation for the zero order reactions. Point number 1. Point number 2. Remember the half-life of the zero order reactions as well, which is equal to A0 divided by 2K. Right? A0 divided by 2K. This is the half-life of the zero order reaction. Remember the completion time, the time taken to complete 100% of the zero order reaction. Remember, it is equal to A0 divided by K. Okay? If you look at these two expressions, time taken to complete half of the reaction is A0 by 2K. Time taken to complete 100% of the reaction is equal to A0 by K. Can I say a zero order reaction gets completed in 2 half-lives? Absolutely, do remember this as well. A zero order reaction gets completed in 2 half-lives. Correct? Yes, absolutely. Now, one more thing people. If I need to calculate degree of dissociation for a zero order reaction, how do we calculate degree of dissociation? Number of moles dissociated, number of moles of reactants dissociated, divided by initial moles of reactants taken. So for example, these are the initial moles of reactants. These are the moles of reactant left at time t. So how many moles of reactant got converted into products? I'll say initial moles were A0. Finally, I'm left with AT. So A0 minus AT, it is going to give me the number of moles of reactant that dissociated in the product divided by initial moles of reactant is A0. Initial moles of reactant is A0, right? So I'll be writing it as A0 minus, instead of this A0, instead of this AT, I'll be writing A0 minus KT. Divided by what? Divided by A0. And finally, what do you get the answer? You get the answer as KT divided by A0. So degree of dissociation of a zero order reaction, it is inversely proportional to the initial concentration of reactant. Do remember this thing as well. Do remember this thing as well. These are some important points about the zero order reactions, right? Now let's try to solve this question. It's a very simple one. Let's try to solve it. I'm sure you would have taken the note of everything. See guys, I'm given a zero order reaction A gives B, for example, right? Let's assume its rate constant is K. A zero order reaction is 20% completed in 10 minutes. At what time it will be 80% completed? Simple. See the actual procedure I'm showing. At time t is equal to 0, let's say the initial concentration is A naught. The initial concentration of product will be 0. Okay, after 10 minutes, 20% reaction is completed. That means after 10 minutes, 20% of the reactant got converted into product. If 20% of the reactant got converted into product, I'll say 80% of the reactant will be still left in the container as such, and the concentration of reactant left at any time t is represented by 80, right? So 80 value after 10 minutes is simply 0.8 A naught. Yeah, right? This is my first condition. I'll be using this condition in a while, right? Now what am I supposed to calculate? At what time the reaction will be 80% completed? When 80% of the reaction gets completed, that means when 80% of the reactant gets converted into products, I'll be left with 20% of reactant at that time. So 80 value is basically 0.2 A naught at this time t, which I'm supposed to calculate, right? So I got two conditions. I'll be using these two conditions and I'll be solving the equation. Use the integrated rate equation for the first condition. See, my integrated rate equation is AT is equal to A naught minus KT. For the first condition, AT value is 0.8 A naught is equal to A naught minus K multiplied by T value is 10 minutes. So from here you can calculate a K value, right? So 10K is going to be equal to A naught minus 0.8, which comes out to be 0.2 A naught, right? Or K value you'll be getting as 0.2 divided by 10 multiplied by A naught. This is the K value I got by using the condition number first. Now use the condition number second, right? For the condition number second, what is the value of AT, which is 0.2 A naught, right? Is equal to A naught minus K. K is nothing, that is 0.2 divided by 10 multiplied by A naught multiplied by T. This T we are supposed to calculate, right? A naught gets cancelled everywhere. When you solve this, T will come out to be 40 minutes. So after 40 minutes, basically, you'll find out 80% of the reactant would have got converted into the product, or you can say 20% of the reactant will be still left in the container, right people? Okay. Or you can do it like this. See, it's a zero order reaction, right? It's a zero order reaction. See, 20% of the reaction, the procedure which I'm showing you now, it's only valid for zero order. Don't use it for first order, okay? 20% reaction is completed in 10 minutes. Okay, that means 40% reaction will be completed in 20 minutes, 60% reaction will be completed in 30 minutes, 80% reaction will be completed in 40 minutes. But this procedure is only valid for the zero order reactions, right? Okay, I'm sure it's clear. Yes, Rahul, this is the method, right, for zero order. Perfecto. Wonderful. So I'll be moving on to one more then. Let me move on to one more question. This is one more question, guys. Okay. A first order reaction. Okay. So before solving this question, let me tell you a few important things about the first order reactions. Let's say I've got a reaction as A gives B. Its rate constant is K. Let's assume order of this reaction is 1. It's a first order reaction. Let's assume at time t is equal to 0, the initial concentration of reactant is A naught. So this will be 0 automatically. Let's assume at any time t, concentration of reactant left is AT. AT is the concentration of reactant left after time t, correct? Now, if the reaction is first order, then you should remember the first order integrated rate equations as well. There are a lot of forms for the first order integrated rate equations. The first form is ln of AT is equal to ln of A naught minus KT. This is the first form of integrated rate equation for the first order kinetics. Okay. Then we have one more in terms of log. Log of AT is equal to log of A naught minus K upon 2.303 multiplied by T. This is one more form. One more form is K is equal to 1 divided by T ln of A naught divided by AT. This is one more form. One more form is K is equal to 2.303 divided by T. It's going to be log of A naught divided by AT. This is one more form, correct? One more form for the integrated equation is AT is equal to A naught e raised power minus KT. Right? This is one more form. So all these are basically the different forms of integrated rate equations for the first order reactions, point number one. Point number two, if you want to calculate the half-life of the first order reaction, T half for the first order reaction is equal to ln 2 divided by K. Ln 2 is nothing, that is 0.693 divided by K. This is valid for first order kinetics, 0.693 divided by K, right? Now people at the same time, one more thing. This is the time taken to complete 50% of the reaction. This is the time taken to complete 50% of the first order reaction. Before going into the next thing, let me calculate alpha. Degree of dissociation of the first order reaction is going to be 1 minus e raised power minus KT. Do remember this as well, right? Okay, do remember this thing as well. And do remember few more things about first order reactions. Remember, time taken to complete 75% of the first order reaction is 2 times its half-life. Time taken to complete 87.5% of the first order reaction is equal to 3 times the half-life of it. And at the same time taken to complete 99.9% of the first order reaction is equal to 10 times its half-life. These are few things which you need to remember before solving the equation, right? Now you can easily solve this question. See guys, it's mentioned in the equation, the first order reaction is 75% completed in 100 minutes. Time taken to complete 75% of the first order reaction is given to me as 100 minutes. What do I need to calculate? I need to calculate time taken to complete 87.5% of the first order reaction. See, time taken to complete 75% of the reaction will be equal to 2 times the half-life is equal to 100. So from here, can I calculate the half-life of the reaction, which is going to be simply 50 minutes? I calculated the half-life of the reaction. Now, can I calculate the time taken to complete 87.5% of the first order reaction, which is going to be 3 times the half-life, right? Which is 3 multiplied by half-life is 50. The value comes out to be 150 minutes. So 150 minutes is going to be the answer of this question. Simple, right? Yes? I'm sure it's clear to everyone. Perfecto. Please explain the dissociation part. All right. This dissociation part you want me to explain? Surely I'll be doing that. See, in order to calculate degree of dissociation for this reaction, alpha is equal. Degree of dissociation of the reaction is number of moles of reactant dissociated divided by initial moles of reactant taken, right? Divided by initial moles of reactant taken. Now people, how many moles of reactant got dissociated? I started with A naught moles. I'm left with 80 moles. So A naught minus 80. This is going to give me the number of moles of reactant that got converted into product divided by initial moles of reactant. That's A naught. So it's going to be A naught minus. What is the value of 80 for the first order reaction? It is A naught e raised power minus KT divided by what? Divided by A naught. A naught, A naught, A naught everywhere got cancelled. It is 1 minus e raised power minus KT. This is alpha for the first order reaction. Yes, I'm sure it's clear. Right, people? Perfecto. So let's move on then to a few more questions. Okay. For an elementary reaction, I'm given an elementary reaction. Elementary reaction is the one which gets completed in one step, right? Single step reaction. For an elementary reaction, X gives Y plus Z. Half-life is given to me. In what period of time concentration of X be reduced to 10% of its original value? Okay. Let's see how this question is to be solved. First of all, I do not know whether the reaction is of first order or zero order. I have no idea about it. But remember, for the elementary reactions, always order is equal to molecularity. For the elementary reactions, order is equal to molecularity, right? What is the molecularity of this reaction? See, you have got only one reactant species over here, okay? So its molecularity is 1, right? If the molecularity of this reaction is 1, and at the same time, it's elementary. For elementary reactions, order is equal to molecularity. So I'll say order of this reaction is also 1. The reaction was X gives Y plus Z, and I got to know it is a first order reaction. I got to know it's a first order reaction. Okay? I got to know it's a first order reaction. Now, I'm given with the half-life as well. I'm given with the half-life of the first order reaction is 10 minutes. Can I calculate rate constant? Absolutely. Half-life of a first order reaction is nothing, that is 0.693 divided by K is equal to 10. So from here, you get the value of K as 0.0693 minute inverse. You got the value of K, correct? You got the value of K. In what period of time would the concentration of X be reduced to 10% of the original value. See guys, at time t is equal to 0, initially the concentration of reactant is A0, for example, right? Now what will happen to the concentration of reactant? It will keep on decreasing, right? It will keep on decreasing. At what point of time the concentration of A will be reduced to 10% of its initial value? So finally 10% of reactant is left. Finally 10% of reactant is left. I basically need to check at what point of time 10% of the reactant will be left in the container. So 80 is the concentration of reactant left in the container, which is 10% of A0. 10% of A0 means 0.1 A0, right? So just use this condition in the integrated rate equation and kill the equation. I'll say T is equal to 2.303 divided by K. It's going to be log of A0 divided by 80, right? A0 divided by 80. It's going to become as 2.303 divided by K. K value already I got to know, 0.0693. It's going to be log of A0 divided by 80 value. 80 value is nothing, that is A0 by 10. That's A0 divided by 10. A0 divided by 10. 10 goes up, right? This and this got cancelled. Log 10 is 1. This whole term comes out to be 1, right? Just solve this term, get the value of T. So people are coming up with the answer 33 minutes. So finally, what you're observing after 33 minutes, 10% of the reactant will be left in the container, right? Yes, I'm sure it's clear to everyone. Right, people? Moving on to one more then. Okay, this is one more question. We can solve this as well, right? How do we do it? But how do we do it? See. An organic compound undergoes first order decomposition. An organic compound undergoes first order decomposition. It's a first order decomposition. That means order of this reaction is, for example, 1. Okay. The time taken for its decomposition to 1/8 and 1/10 of its initial concentration are T1 by 8 and T1 by 10 respectively. What is the value of this term? T1 by 8 divided by T1 by 10 multiplied by 10. This is the question which I need to solve, right? How do I approach this sort of equation? Have a look, guys. See. Let's assume at time t is equal to 0, the initial concentration of reactant is A0. It is going to be 0, right? It's mentioned in the equation. This at time t is equal to T1/8. What is the concentration of reactant left in the container? It is going to be equal to 1/8 of its initial concentration. 1/8 of its initial concentration, right? The concentration of reactant left at time t is equal to T1/8 is going to be A0 by 8, 1/8 of initial concentration. Similarly, at time t is equal to T1/10, the concentration of reactant left in the container is 1/10 of its initial value. So it's going to be A0 divided by 10. This is the value of concentration of reactant left after T1 by 10. This is the value of concentration of reactant left at time t is equal to 1 by 8. So just I got the two conditions. I'll be using these two conditions in the integrated rate equation and kill the equation. See guys how I'll be doing it. First thing, I'll be writing T1 by 8. T1 by 8 is equal to 2.303 divided by K log of A0 divided by 80. What is the value of 80 at T1 by 8? It is A0 by 8. It is A0 divided by 8. So it becomes log of 8. Log of 8 means log of 2 raised power 3. 2 to the 4 to the 8, right? Log of 2 raised power 3 is 3 log of 2. 3 log of 2. And log 2 value must be given in the equation, which is 0.3. So log 2 is 0.3. So 3 multiplied by 0.3 comes out to be 0.9, right? So I got T1/8. Similarly, calculate T1/10 as well. T1/10 is going to be 2.303 divided by K. It's going to be log of A0 divided by 80. 80 at T1 by 10 is going to be A0 by 10. So this is A0 divided by 10. That 10 goes up, right? A0 cancel. Log 10 is equal to 1. So this whole term becomes 1, correct? What do I need to calculate? I need to get the ratio of T1 by 8 to T1/10 multiplied by 10. So divide the two over here. So I'll be getting T1/8 divided by T1/10. This will come out to be 2.303. This and this got cancelled. It comes out to be 0.9. But am I supposed to calculate only this part? No. I'm supposed to multiply it with 10 as well. So multiply 10 from here, 10 from here. The value comes out to be 9. So the value of this term, which I was supposed to calculate, came out to be 9, right? I'm sure this is clear to everyone again. Yeah, people? Perfect. Okay, moving on to one more then. This is one more question, guys. Okay, one thing I forgot to tell you about the first order reactions. There is one more thing by means of which you can calculate the concentration of reactant left at any time t. Whenever in the first order reaction, you are supposed to calculate the concentration of reactant left at time t. There are many ways to do that. One of the ways, by this, AT is the concentration of reactant left at time t is equal to initial concentration of reactant divided by 2 raised per n. What is n? N is not the order of reaction. N stands for number of half-lives. Number of half-lives. And how do we get it? Given time divided by t half. Given time divided by t half, right? Okay, now see how do I solve this question. What do I need to calculate basically? Okay, I need to calculate half-life of this reaction. I'm given with the curve log of AT versus T. I'm given with the curve log of AT versus T. First of all, I told you one of the integrated rate equation forms, log of AT is equal to log of A naught minus K upon 2.303 multiplied by T. This is one of the equation which I gave you a few minutes back, right? Now log of AT I'm plotting along y-axis. Log of AT I'm plotting along y-axis. Yes. And time I'm plotting along x-axis, right? So this automatically becomes my m. The sign over here is minus, and this automatically becomes my slope, intercept. Y is equal to minus mx plus c. It's going to be a straight line. It's going to be a straight line, right? With a negative slope. What is slope of this curve? Slope of log AT versus T. Slope of log AT versus T curve came out to be minus k upon 2.303, right? So slope of log AT versus T curve came out to be minus k upon 2.303. Now people have a look. See, slope of log AT versus T curve. How do we calculate it? Tan of theta. Tan of theta gives me the slope of the curve. What is theta basically? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. Theta is the curve. Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. So this is theta 135. So tan of 135 comes out to be minus 1 simply, right? So slope is basically tan of 135 which comes to be minus 1. Minus 1 is equal to minus k upon 2.303. So from here you can calculate the value of k which came out to be 2.303, and options are in minutes, so it's going to be minute inverse. I got the k, right? Why did I calculate k? Why did I calculate k? Because I need to calculate the half-life, right? And half-life of the zero for the first order reaction, I told you a few minutes back, it's going to be 0.693 divided by 2.303. Just solve it, get the value of half-life of the reaction, and I believe it will come out to be 0.3 minutes, right? Yes, people? Yes? I'm sure it's clear to everyone? Absolutely, it's going to be 0.3 minutes. Okay, let's move on to one more then. This is one more similar type of question. What is it? Okay, you guys can solve this question on your own. Few minutes back I gave you one direct result. Just use that direct result and kill this question. A first order reaction has the half-life of 1 minute. The time required for 99.9% completion, right? It's a first order reaction, it's given to me. And I told you a few minutes back, time taken to complete 99.9% of the first order reaction is equal to 10 times the half-life. Half-life is given to us 10 multiplied by, what is half-life? Half-life of this reaction is 1 minute, so the answer is going to be 10 minutes. The question is done and dusted, right? If you remember this result, you are done. If you do not remember this result, then you have to use the general procedure, use the integrated equation, and then solve the equation. Yeah? Perfect? Okay, one more question we have. We are given with a curve between ln AT versus T. Ln AT versus T, right? First of all, what is the integrated rate equation in the form of ln? Ln of AT is equal to ln of A naught minus KT. This is something which I told you a few minutes back. So this minus K, it basically gives me the slope of, ln of AT versus T curve, right? This minus K, it gives me the slope of ln of AT versus T curve, right? See guys, what is slope of ln of AT versus T curve? That is tan of theta. What is theta? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. This is the theta which I'm talking about. If this is 45, this is 90, so this should be 45, so this should be 135. Right people? This should be 135. Correct? So people, slope of ln 80 versus t, that is tan of theta. Theta is 135, right? So tan of 135 degrees is equal to minus k. 135 is minus 1 is equal to minus k. So k value I got to know as 1. Let's say units are in minutes, so it's going to be minute inverse. So I got the k. Why did I calculate k, by the way? Why did I calculate k? Why did I calculate k? Because I want to calculate half-life of this first order reaction. Half-life of this first order reaction is going to be equal to 0.693 divided by k, which is 1. So half-life of the reaction came out to be 0.693 minutes. Right? Or approximately you can take it as 0.7 minutes. You can take it as 0.7 minutes. Right? Approximately you're going to take it as 0.7 minutes. I got the half-life. Why did I calculate half-life? Because I wanted to calculate number of half-lives, which is equal to given time divided by t half. I told you a few minutes back. Given time is how much? It is 3.5 minutes. Divided by half-life is 0.7. The value comes out to be 5. So the number of half-lives are 5. Basically, I need to calculate the concentration of reactant left after 5 half-lives. I need to calculate the concentration of reactant left after 5 half-lives. I told you a few minutes back. 80 is equal to A naught divided by 2 raised power 5. Sorry, 2 raised power n. So it's going to be A naught divided by 2 raised power 5. Right? This is going to be the concentration of reactant left after 5 half-lives, which is A naught divided by 32. I'm sure it's clear to every single guy. Yeah? Right, people? Slope of this curve is equal to minus k because it is ln 80 versus t. If it was log 80 versus t, then the slope would have been minus k upon 2.303. Right? Right, people? Clear to everyone? Absolutely. Let's move on. This is one more question. In what time will the molar ratio of ethylene to cyclobutane be 1? Right? What do I need to see? Understand this question properly, guys. Understand this question properly. Okay? At what time will the molar ratio of ethylene to cyclobutane be 1? Let's assume at time t is equal to 0, the number of moles of cyclobutane are A, so this is going to be 0, right? At some point of time t, let's say out of A moles of reactant, some X moles got converted into products, so I'll be left with A minus X moles of reactant. 1 mole gives 2 moles, so X moles are going to give 2 X moles, right? These are the moles of reactants and products at some time t, right? At some time t, correct? Now we will understand few important things. What do I need to see? At what point of time will the molar ratio of these two be 1? Right? When is going to be the molar ratio of these two 1? Molar ratio of these two will be only equal to 1 if A minus X will be equal to 2X. Then only the molar ratio of, then only the ratio of their moles is going to be 1. Right? Then only the ratio of their moles is going to be 1. So I'm assuming at time t, the moles of reactants and products are equal. What does that mean? That means the ratio of their moles is equal to 1. Right? Okay. So at this point of t, I'll say A minus X divided by 2X is equal to 1. Just a second. At what time the molar ratio of ethylene to cyclobutane? Ethylene's moles are 2X. Cyclobutane's moles are A minus X. This value is equal to 1. So from here, you can say 2X is equal to A minus X. So from here, you can calculate the value of X. X value will come out to be A divided by 3. Right? You got the value of X, A by 3. If you got the value of X, you can calculate the moles of cyclobutane left at time t. It's going to be A minus X, which is A minus A by 3. The value comes out to be 2A divided by 3. These are the moles of reactant. These are the moles of cyclobutane left at time t. Now we use the integrated equation. The question will be done and dusted. I'll say T is equal to 2.303 divided by K. K is 2.3 into 10 raised to power minus 4. Log of A naught divided by 80. A naught is the initial concentration, or you can say initial moles, divided by 80 moles of reactant left at time t, which is going to be 2A divided by 3. This is 2A divided by 3, that 3 comes up, right? This and this got cancelled. So you get the value as this and this got almost cancelled. So this is 10 raised to power 4. It's going to be log of 3 minus log of 2. Right? You all must be knowing the values of log. So log of 3 is going to be 0.47. Log of 3 is 0.3. The value will come out to be 0.17 into 10 raised to power 4, or you can get the value as 1700 seconds. So in 1700 seconds, the moles of cyclobutane and ethylene would have got equal, right? Perfect, people, is it clear? Is it clear to everyone? Absolutely, right? Okay, so let's move on then to one more question. Let's see if we have more questions from this chapter. Yes, we have got one more question. Calculate the activation energy of this reaction. People, it's a simpler one, right? First of all, if you remember your Arrhenius equation says K is equal to A e raised power minus EA divided by RT, right? This is the Arrhenius equation. This is the actual form of Arrhenius equation. If I multiply throughout by ln, it becomes ln of K is equal to ln of A minus EA divided by R multiplied by 1 by T. Okay, right? If I convert the same equation into the logarithmic form, it becomes log of K is equal to log of A minus EA divided by 2.303 R multiplied by 1 by T. Correct? Right, people? So this curve I'm given with between log K versus 1 by T. Log K versus 1 by T. Can I say slope of this curve is equal to minus EA divided by 2.303 R? Absolutely, right? Slope of log K versus 1 by T curve, it is equal to minus EA divided by 2.303 R. And slope of this curve means tan of theta. Tan of theta. Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction, right? And I'm given with theta is equal to tan inverse minus 3. So you can say tan of theta is equal to minus 3, right? What is tan of theta? Tan of theta is the slope of the curve, right? It is the slope of the curve, which is equal to minus 3, right? So minus got cancelled, correct? So from here, you can calculate the EA value, which is the activation energy, which I was supposed to calculate, which is going to be equal to 2.303 multiplied by 3 multiplied by R. Now, depending on the value of R, you need to, it depends on the value of R. Whatever units of activation energy you want, depending on that, you can use the value of R. See, first thing, I need to calculate the value of activation energy in kilojoules, right? So what I'll be doing, I'll be taking the value of R as 8.314, so it becomes 2.303 multiplied by 3 multiplied by 8.314, the value comes in joules, I'll be dividing this term by 1000, then only the value comes in kilojoules, right? This is going to be the answer of the first question. In order to calculate in kilocalories per mole, put the value of R as 2 and at the same time divide by 1000, then only you'll be getting the value of activation energy in kilocalories. I'm sure it's clear to everyone, right? Right, people? It seems the data is over, huh? Okay, so let's move on then. Let's move on, people. Okay, the rate constant of the reaction at 227 degrees centigrade and 427 degrees centigrade are 0.02 second inverse and 0.2 second inverse. Calculate the activation energy of the reaction. It's a simpler one, right? Do remember this equation. Log of K2 divided by K1 is equal to AA divided by 2.303 R, 1 divided by T1 minus 1 divided by T2, right? Rate constant of the reaction on changing the temperature, change from 0.02 to 0.2. So K2 is 0.2 final rate constant, initial rate constant. EA I'm supposed to calculate, R value 8.314, temperature, initial temperature 500 Kelvin, final temperature 700. What do we get finally? We get 700 joules as the answer. I'm sure it's clear. Right? You need to remember this equation, just put the values into this equation and get the answer. That's it. Yeah? Clear, people? Clear to everyone? Yeah? Okay. So with this, your kinetics part is over. I'm sure it would have revised majority of the concepts from the chapter chemical kinetics, right? So should we start with the surface chemistry now? Let's get going with the surface chemistry now. Yes, Samina, everything will be done. No break at all. It's a very simple, it's a theoretical chapter, so I need not to use my pen and everything, right? I'll just change the slides and you guys are going to let me know its answer, right? So, just a second, people. Let me sit and let's solve these questions. Okay. First question, people. Which of the following which of the following characteristic is associated with adsorption? Can you let me know its answer in the chat box? Let me know its answer in the chat box, people. Which of the following characteristics is associated with adsorption? What do you think about this one? During adsorption, let me tell you, delta G, delta H as well as delta S, all the three are negative. So option B is going to be the correct answer of this question. Option B is going to be correct answer of this question. This is something which every one of you would know, correct? Because it's a complete theoretical question, right? Which of the following characteristics is associated with adsorption? So option B is the one which is the correct answer of this question. Okay, what about this one? What do you think about this one, people? What do you think about this one? Physical adsorption of a gaseous species may change to chemical absorption with decrease in temperature or increase in temperature. What do you think about this one? I gave you the first two options. Which one is the correct one? Let me know fast. With a decrease in temperature or increase in temperature? Well, I can see majority of the people are coming up with the correct answer. It's going to be increase in the temperature. With the increase in temperature, physical adsorption of the gaseous species, it may change to the chemical adsorption, right? With the increase in temperature, people, correct? Okay, what about this one? The adsorption of the gas on the solid surface varies with pressure of the gas in which of the following manner? Adsorption of the gas on the solid surface varies with pressure in which manner? As we all know, adsorption is fast in the beginning, right? Then it becomes slow, and finally it becomes independent of the pressure. So option A is the correct answer of this question. Correct? Initially the adsorption is fast because you have got a lot of surface available for adsorption. Then it becomes slow, and at the end it becomes independent of the pressure. I'm sure you all must be knowing this. Okay, the correct option representing a Freundlich's adsorption isotherm. What do you think about this one? X by M represents the extent of adsorption is equal to K P raised power 1 by N, right? P raised power 1 by N. And as you all must be knowing, 1 by N value, it lies between 0 to 1. It lies between 0 to 1. So there is only option in which the power of pressure lies between 0 and 1, right? That's going to be second option. Yes, option B is the one. Right, people, as you can see over here. Okay, let's move on to one more. In Freundlich's adsorption isotherm, the value of 1 by N, this is something which I told you. It lies between 0 to 1 in all the cases. Option 1 is the answer. Right? Okay, which is not correct regarding the adsorption of gas on the surface of solid? Which is not correct, he is saying, people, which is not correct. On increasing the temperature, adsorption increases continuously. Is it the correct statement? Is it the correct statement? No way, right? It is the incorrect statement. On increasing the temperature, adsorption decreases. We know it, right? Yes? Option A is the incorrect statement among all. Rest all the statements are correct. Enthalpy and entropy are negative. Adsorption is more for specific substances. This phenomenon is reversible. Yes, we know it. Okay, one more. Which of the following statements is not correct? The value of equilibrium constant is changed in presence of catalyst. People, have you ever seen the value of equilibrium constant changing on changing the temperature? Sorry, on changing the catalyst? The value of equilibrium constant does not change on changing on adding the catalyst. It is just time taken to attain equilibrium that is reduced. That's it. Yeah? Okay, it's a previous year question. Right, people? Okay? Alright, one more. Hydrolysis of urea is the example of what? Homogeneous, heterogeneous, biochemical, or zeolite. What do you think about this one? It is the example of the biochemical catalysis. It is the example of the biochemical catalysis in which you use enzyme as the catalyst, right? Okay, option C is the one which is the correct answer of this question. Yeah? Okay, moving on to one more. What is the role of molybdenum in Haber's process for the manufacture of ammonia? What molybdenum does? It acts as the promoter, right? It acts as the catalytic promoter. Okay, so option B is going to be the correct answer of this question. The catalyst in case of Haber's process iron, and molybdenum, it acts as the promoter. I'm sure you all must be knowing this. Okay, milk is a colloid in which? Let me know, it's a very simpler one. Let me know its answer, people, fast. Milk is a colloid in which first? In which, absolutely guys, you all are perfectly right, liquid is dispersed in a liquid, right? Liquid is dispersed in a liquid in milk, right? Milk is basically an emulsion in which liquid is dispersed in a liquid. Okay, butter is a colloid formed when fat is dispersed in water, when fat globules are dispersed in water, when water is dispersed in a fat, none of the above, right? Option A or C, what do you think? Option A or C? Option A or C? Fat is dispersed in water or water is dispersed in fat? People, it is water when water is dispersed in fat, okay? Do remember this. In these questions, you might do a silly mistake, okay? So do remember these questions. Okay, the size of colloidal particle, it's a theoretical question, right? 10 raised per minus 5 to 10 raised per minus 7 centimeters. Okay, do remember this. An aerosol is, what is an aerosol? Aerosol is a dispersion of a solid or a liquid in gas, dispersion of solid in liquid, dispersion of liquid in liquid, solid solution. What is this one? Let me know its answer fast. Aerosol is, what is aerosol? Well, people are coming up with the correct answer, and absolutely you all are perfectly right. It's going to be the dispersion of a solid or liquid in a gas, right? Option A is the correct answer of this one. Perfect, guys. Okay, if dispersed phase is a liquid and dispersion medium is a solid, then the colloid is called as? If the dispersed phase is a liquid and dispersion medium is a solid, a colloid is called as, what do we call it? Do we call it as the gel or emulsion? We call it as a gel, people, okay? Right? Dispersed phase is a liquid and dispersion medium is a solid, correct? Alright, hair cream is the example of what? Foam. That's something which you all must be knowing, correct? Emulsions are liquid-liquid colloid systems. Generally, one of the two liquids is water. Okay, hair cream is the example of what? Hair cream is the example of a foam. Okay, one more. Suspensions are, it's a very simple one, visible to naked eye, absolutely option A, right? Okay, surface tension of lyophilic salts is lower than water, right? Surface tension of lyophilic salts is lower than water. These are some very simple and common questions. Lyophobic colloids are reversible or irreversible? Lyophobic colloids I'm talking about, reversible or irreversible? Reversible or irreversible? These are absolutely irreversible, people. Yeah? Lyophobic colloids, these are irreversible colloids. Okay, the formation of micelle takes place only above which temperature? The question from your NCERT, above which temperature? Above Kraft temperature. I hope you know it. Right? The formation of micelles takes place only above Kraft temperature. Okay, one more theoretical question. The moment of colloidal particles towards their respective electrodes in presence of electric field is called as? Do we call it as electrophoresis, electrodialysis? What do we call it as? Electrophoresis or electrodialysis? People, I want answers from everyone. Absolutely, you all are perfectly right. It's going to be electrophoresis, right? Okay, Tyndall effect is shown by sol, solution, plasma, precipitate. What? What is the answer of this question? What is the answer of this question? Tyndall effect is shown by. Tyndall effect is shown by. I want answers from every single guy. It's absolutely going to be sol. Tyndall effect is shown by sol. Okay, the cause of Brownian moment. Heat change in liquid state, conventional currents, the impact of molecules on the dispersion medium, on the colloidal particles. Absolutely, option C is the correct answer. The impact of molecules on the dispersion medium, on the colloidal particles, causes the Brownian moment. Option C is the one which is correct among all, right? One more, people, one more theoretical question. Measuring zeta potential is used in determining which property of colloidal solution? Stability, right? Stability of colloidal particles. More the zeta potential, more the stability of colloidal particle, right? More the zeta potential, more the stability of colloidal particle. Yeah? Something which you all must be knowing. Okay, on which of the following properties does the coagulating power of an ion depend? As per Hardy-Schulze rule. As per Hardy-Schulze rule, people, I want every one of you to give it a try. Let me know first. On which of the following properties does the coagulating power of an ion depend? It depends on magnitude of charge as well as the sign of charge on the ion, right? It is the most appropriate answer is going to be option D. Yes, I'm going to give the PDF of this as well. The most appropriate answer is going to be option D, people. Okay, one more. Which of the following is most effective in causing the coagulation of ferric hydroxide sol? Ferric hydroxide sol, it is the positively charged sol. So in order to coagulate it, you need to add some negatively charged ions, right? So more the negative charge on the anionic part, more is going to be the coagulating power. In which of the following negative charge on the anionic part is going to be more? In option D, where you have FeCN6 tri-negative, right? FeCN6 tri-negative will be the negatively charged part. Correct? Yes, people? Absolutely. Option D is the answer. Okay, which of the following electrolysis is least effective in coagulating ferric hydroxide solution? Ferric hydroxide solution, people. Positively charged sol. In order to coagulate it, you need to add some negatively charged ions, right? Which one is least effective? Which one has got the least coagulating power? Wherever charge on anion is least, that's going to have least coagulating power. KBr is the one in which the charge on anion is -1, right? I'm sure it's clear. The ion that is more effective for coagulation of As2S3 sol is more the positive. See, As2S3 sol, it is a negatively charged sol, right? It is a negatively charged sol. So in order to coagulate it, you need to add some positively charged ions. More the positive charge, more the coagulating power, right? So Al tripositive is the answer. Fog is the colloidal solution of what? Fog is the colloidal solution of what? Let me know. Fog is the colloidal solution of what? Well, people are confused in this, I guess, yeah? People, it's simple. It's liquid and gas. It's option A. It's liquid and gas. Fog is basically a liquid and gas, right? Okay, one more. Which property of colloidal solution is independent of charge on colloidal particles? It is absolutely going to be Tyndall effect. It has got nothing to do with the charge on the colloidal particles, right? So option C, I suppose. Absolutely option C, guys. Yeah. What about the next one? The protection power of lyophilic colloid sol is expressed in terms of. Okay. The protection power of lyophilic colloidal sol is expressed in terms of, right? It's a very important topic given in your NCERT, which is gold number, right? Absolutely, it's gold number. I'm sure it's clear. Yes. One more, people. Which of the following forms micelles in the aqueous solution above certain concentration? Is it pyridium chloride? Is it urea? Is it glucose? Is it dodecyl trimethyl ammonium chloride? It's absolutely going to be dodecyl trimethyl ammonium chloride. Option A is the one which is the correct answer of this question. The question is directly taken from your NCERT as well. Yeah. Okay. Position of non-polar and polar part in a micelle. Polar part at the outer surface and non-polar part at the inner surface. I think this is done, right? Okay. Yes. Basically, head is towards the center and tail is towards the circumference, correct? Right? So polar part at the outer surface and non-polar part at the inner surface, absolutely correct. Okay. Hardy-Schulze rule explains the effect of electrolytes on coagulation of colloidal solution. We know it. According to this rule, coagulation power of cation follows the order, right? Coagulation power of cation. More the charge on the cation, more is its coagulating power. And remember, coagulating power is inversely proportional to coagulation value. Okay? So what is going to be order of this question? It's going to be option C, Al tripositive, Ba dipositive, Na positive, right? Absolutely, guys, you all are perfectly correct. Okay, one more. During dialysis, what happens? What happens during dialysis? Only solvent molecules can diffuse. Solvent molecules, ions and colloidal particles can diffuse. All kinds of particles can diffuse. Solvent molecules and ions can diffuse. What is the answer of this question? What is the answer of this question, people? The answer of this question is going to be option D. Solvent molecules and ions can diffuse, right? It is again the question taken from your NCERT. Okay, among the following, the incorrect statement about colloids is, incorrect statement he is asking. They can scatter light, they are larger than small molecules and have higher molar mass, right? The osmotic pressure of colloidal solution is of higher order than the true solution at the same concentration. Is the option C correct or incorrect? Is the option C correct or incorrect? Check it out. Option C is the incorrect answer among all people. Option C is incorrect, right? Rest all the options are correct. The range of diameter of colloidal particles is between 1 and 1000 nanometer, which is absolutely correct. Okay, so with this, your surface chemistry, which was a theoretical chapter, it is done and dusted. Yeah, I'm sure it would have revised many of the concepts. Yeah? So let's start with the chapter solutions. Right, people? Let's start with the chapter solutions. Okay, after this chapter, I'll be giving you the break, yeah? After this chapter. All right, so let's get going with the chapter called as solutions, and this is the first question on your screen. It's a simple and theoretical question. According to Henry's law, the amount of gas that will dissolve in blood plasma or any other liquid is determined by which of these factors? Solubility of the gas in the liquid, total pressure of the mixture, pH of the liquid, the osmotic pressure of the gaseous mixture. What is going to be the answer of this question, guys? Simple one. Simple one. Let me know its answer. It's going to be solubility of the gas in the liquid, right? Option A is going to be correct answer of this one. Value of Henry's constant Kh increase with temperature? Absolutely. Henry's constant, it varies directly with the temperature. On increasing the temperature, Kh value increases, right? Okay. Kh and temperature, they have got directly proportional relation. Okay. So remember, on increase the temperature, your Kh value, it absolutely increases. Yeah. Okay. The value of Henry's constant Kh is greater for gases with higher solubility, greater for gases with lower solubility. Solubility and Henry's constant, solubility of the gas in the liquid and Henry's constant, they are inversely proportional. They are inversely proportional, right? Yes, people? They are inversely proportional. Option B is the one which is correct. Okay, which of the following factors affect the solubility of the gaseous solute in the fixed volume of liquid solvent? Nature of solute, temperature and pressure. Which of the following affect the solubility of gaseous solute in the fixed volume of liquid solution? Right? Nature of solute, nature of gas, absolutely. Right? Temperature, absolutely. Pressure, absolutely. All the three factors, right? So I can say 1 and 3 at constant temperature. When the temperature of the system is kept constant, I'll say at that time the solubility of the gaseous solute depends on the nature of solute and the pressure, right? So option A is the correct answer of this question. Option A is absolutely the correct one. See, all these factors, they decide the solubility of gas in the liquid. But if I keep the temperature constant, only this factor and this factor plays a role at constant temperature, right? It's a simpler one. So option A is the correct answer. Okay, which of the following graph is correct explanation of the Henry's law? Henry's law. P is equal to Kh multiplied by mole fraction of the gas in the liquid, right? P and mole fraction, partial pressure of gas above the liquid and mole fraction, they are directly proportional. Y is equal to mx form. Y is equal to mx form, right? Right, people? So it's going to be option C, absolutely. Okay, which is the application of Henry's law? Which is the application of Henry's law? This is something which you all can tell me. Which is the application of Henry's law? Soft drinks, right? In which gases are kept at high pressure. Right, people? Soft drinks. Okay, scuba divers may experience a condition called bends. The tanks used by scuba divers are filled with the air diluted with helium, right? Option D is the one which is correct. Option D is the one which is correct, yeah? Absolutely, guys. Absolutely. These are all theoretical questions going on. We'll come into numericals in some time. People living at high altitudes often reported with the problem of feeling weak and inability to think clearly. The reason for this is, at high altitudes, the partial pressure of oxygen is less than that of ground level. Absolutely correct. Option 1. Option 1, absolutely correct, right? No need to think over it. Okay. Okay, the vapor pressure of the solution at a given temperature is found out to be dash then the vapor pressure of pure solvent, lesser than the vapor pressure of, right? When we add a non-volatile solute into a volatile liquid, what happens to the vapor pressure of the solution? Vapor pressure of the solution is always less than the vapor pressure of pure volatile solvent, right? That's something which you all must be knowing. Right, people? Okay, now comes the time for questions. The vapor pressure of two liquids P and Q are 80 and 60 torr respectively. the total vapor pressure of the solution obtained by mixing 3 moles of P and 2 moles of Q would be. Okay, this is a very simple question, right? And you can expect these sort of questions in your NEET 2021. Okay, vapor pressure of the solution will be equal to PA plus PB, right? PA plus PB. So I can say vapor pressure of the solution is simply P naught A chi A plus P naught B chi B, right? P naught B chi B, correct? Simple. See guys, vapor pressure of the solution will be equal to P naught A. P naught A is the vapor pressure of pure liquid A. Okay, let me call it as liquid A and liquid B instead of P and Q, right? P naught is the vapor pressure of A in the pure state, which is given to me as 80 torr. 80 torr multiplied by mole fraction of A in the solution phase. Number of moles of A, which is 3, divided by total moles in the solution phase, that is 3 plus 2, 5, correct? Plus P naught B is the vapor pressure of pure liquid B in the container, in the pure phase, that is 60, multiplied by mole fraction of B in the solution phase, that's going to be equal to moles of B divided by total moles present in the container, right? You need to solve this, get the value. Solve this, get the value. So people are saying option A, right? Yes? So 72 torr, I assume, is coming out to be the answer of the question. Okay. 18 grams of glucose is added to 178 grams of water. The vapor pressure of water for this aqueous solution is. I'm going to fall ill, guys. Yeah? What is the answer of this question? Give it a try. It's a simpler one. 18 grams of glucose is added to 178.2 grams of water. The vapor pressure of water for this aqueous solution is. It's simple. People are saying A confirmed. Is that? Give it a try. Option B? Yeah? It's a simpler one, guys. See. First of all, let's calculate the moles of glucose. Moles of glucose is going to be mass of glucose divided by molar mass of glucose. Then I calculate the moles of water, which is going to be 9.9. So total moles which we have, that is 10. Right? See, basically, we have got aqueous solution of glucose. So basically, we have got a solution which contains water, and in this solution, we have got water and the glucose, right? Glucose is the example of non-volatile solute. So whatever is going to be the vapor pressure of the solution, that is entirely contributed by water, right? Okay, so vapor pressure of glucose over here is going to be 0, right? What is the partial pressure of water? Is going to be P naught of H2O multiplied by mole fraction of H2O in the container in the solution phase. P naught of H2O, as you all must be knowing, standard conditions, right? It's going to be 760 multiplied by mole fraction of water is going to be equal to number of moles of water, which came out to be 9.9, divided by total moles present in the container. Total moles is 10, right? You need to solve this term, get the value of vapor pressure of the solution. It's very, very simple, right? It's very, very simple. It's an easy peasy question. You can say, okay, what about this one, people? PA and PB are the vapor pressures of pure liquid A and B. Okay, see, you all must be knowing vapor pressure of the solution, that's actually equal to PA plus PB, right? If I've added some two volatile liquids, right, the solution which I'll be getting, the vapor pressure of that solution will be equal to PA plus PB, correct? So PA is nothing, that is P naught A multiplied by chi A, and PB is simply P naught B multiplied by chi B, right? This is something which you all must be knowing. So I can write it like this, P naught A multiplied by chi A, and instead of chi B, I'll be writing 1 minus chi A, correct? Right? So what I'll be writing, I'll be further writing it as P naught A multiplied by chi A plus P naught B minus P naught B multiplied by chi A. What all parameters I can take common? I can take chi A common from these two. So I'll be getting P naught A minus P naught B multiplied by chi A plus P naught B is basically the vapor pressure of the solution. Just check, is there any option like this? P naught A minus P naught B plus P naught B. P naught A minus P naught B multiplied by chi A plus P naught B. It's option D which is the correct answer of this question, right? Just keep it as naught, right? Keep this as naught. P naught A minus P naught B multiplied by chi A plus P naught B, right? So option D is the one which is correct answer of this question. A very simple and basic question, right? This question used to come in boards in class 12th, if you remember. Okay, We have got a mixture of ethyl alcohol and propyl alcohol, right? A mixture of ethyl alcohol and propyl alcohol has a vapor pressure of 290 mm of Hg. So basically I've got a solution which contains ethyl alcohol, which I'm representing by A, and propyl alcohol I'm representing by B, correct? Vapor pressure of this solution, which I'm representing by PS, which is going to be equal to P naught A multiplied by chi A plus P naught B multiplied by chi B. This is something which you all must be doing as per the Rod's law, correct? Vapor pressure of the solution I'm already given with 290, right? M of Hg is equal to P naught A. The vapor pressure of propyl alcohol, that means P naught B. P naught B is given to me. This is P naught B. If the mole fraction of ethyl alcohol, that means chi A. This is chi A. This is chi A. Its vapor pressure at the same temperature. Okay, I need to calculate P naught A. So P naught A I'm writing as such. Chi A value is given to me as 0.6, right? P naught B value is given to me as 200. Is that? It's going to be as 200. Chi B will be simply chi A plus chi B is 1. So chi B is going to be 0.4. Just solve it. Get the value of P naught A from here. That's something which I was supposed to calculate. And P naught A is basically the vapor pressure of ethyl alcohol in its pure form. Right? Simple? Absolutely, it's a simple one. Okay, moving on to one more then. A solution containing components A and B follows Raoult's law when all the interactions are same. A interaction is equal to BB interaction is equal to AB interaction, right? Right, people? When AB interaction force remains same as that of A and BB. So option C is the one which is correct, right? Because we are talking about what? A solution following Raoult's law. Okay, which of the following is not correct for the ideal solution? For the ideal solution, as you all must be knowing, delta V mixing, delta H mixing, both are equal to 0, right? But delta S mixing is not equal to 0. Do remember that as well, okay? So, which of the following is not correct for ideal solution? Option C is not correct, right? Option C is not correct at all. An ideal solution is formed when its components have no volume change on mixing, have no enthalpy change on mixing. Both A and B are correct, neither A and B are correct. What is the answer of this question, people? An ideal solution is formed when delta V mixing is 0 as well as delta H mixing is 0, right? That means when there is no volume change and no enthalpy change on mixing. So A and B both are correct. So option C is the answer of the question. Okay, all forms the ideal solution except, all will form ideal solution except people, except which one? Except which one? Except which one? Is it going to be D? Absolutely, you all are perfectly right. All will form ideal solution except ethyl iodide and ethyl alcohol, right? Okay, rest all are going to form the ideal solution in which the interactions will be almost same. Mixtures of ethanol and acetone shows positive deviation. The reason is, in pure ethanol, molecules are hydrogen bonded. Absolutely, this is correct. Option A is correct, right? Option A is correct. Yes? Okay. A mixture of components A and B will show negative deviation only when a mixture of components A and B will show negative deviation when delta V mixing is greater than 0, delta H mixing is less than 0, AB interaction is weaker than A interaction, AB interaction is stronger than A. Okay, option D is the one which is correct. Option D is the one which is the most appropriate, right? Okay, so a mixture of A and B will show only negative deviation if AB interactions are comparatively stronger than that of AA and BB interactions. That's something which you all must be knowing. Which of the following is not equal to 0 for the ideal solution? For the ideal solution, which of the following is not equal to 0? I told you a few minutes back, delta S mixing is not equal to 0. That's always greater than 0. That's always greater than 0, right? Option A is the answer of this question. Rest all the things are 0 for the ideal solution, if I talk. Yeah? Okay, moving on to one more. A mixture of two completely miscible non-ideal liquids which distill as such without change in its composition at constant temperature as though it was a pure liquid. This mixture is known as, what do we call this mixture, people? Azeotrope, right? We call this mixture as azeotropic mixture, right? This is the definition which is directly given in your NCERT, if you remember, right? Absolutely. Okay, according to Raoult's law, relative lowering in vapor pressure of the solute is equal to mole fraction of solute, right? Mole fraction of solute, option C is the one which is correct. All theoretical questions. The relative lowering of vapor pressure is equal to the ratio between number of, the relative lowering in vapor pressure is basically equal to mole fraction of solute, or you can say number of moles of solute divided by total moles present in the solution, or you can say number of molecules of solute divided by total molecules present in the solution, right? Solute molecules to the total solution, to the total molecules in the solution. So option B must be the answer, right? I'm sure it's clear. Okay. Vapor pressure of benzene at 30 degrees centigrade is 121.8 mm of Hg. When 15 grams of non-volatile solute is dissolved in 250 grams of benzene, its vapor pressure decreased to 120 mm of Hg. The molecular weight of solute is, say, which kind of relation I'll be using in this one? I'll be using this relation, for example. P naught A minus PS divided by PS is equal to NB divided by NA. What is NB? Number of moles of non-volatile solute. NA is number of moles of solvent, right? P naught A, vapor pressure of benzene is 121.8. So P naught A is 121.8 minus PS. PS is the vapor pressure of the solution. What is the vapor pressure of solution? 120.2. Okay, divided by 120.2 is equal to number of moles of solute, which is going to be equal to mass of solute, 15 grams divided by molar mass of solute, whole divided by number of moles of A, mass of solvent that must be given to me, 250 grams of benzene, divided by molar mass of benzene, which is 78. You need to solve this equation and get the value of MB, which gives you the molar mass of solute from here, right? Okay, absolutely. So which option comes out to be the correct one? Option A comes out to be the correct one. So finally, you get the molecular weight of solute as 356.2 grams per mole. Yeah? Okay. What weight of non-volatile solute, urea, needs to be dissolved to 100 grams of water in order to decrease its vapor pressure by 20%? And what is the molality of the solution? It's a simpler one. See guys, I have got a solvent. Okay, I have got a solvent, and the solvent is water, right? Vapor pressure of solvent, vapor pressure of water in pure state was P naught A. Now what I'm doing, I'm adding some non-volatile solute to it. Right? How many grams? Some grams of non-volatile solute I'm adding towards water whose vapor pressure was P naught A, right? What happens? The vapor pressure of the solution is reduced by 20%. So initially the vapor pressure of water was P naught A. Now after adding non-volatile solute, the vapor pressure gets decreased by 20%, right? So I'll say vapor pressure of the solution will be equal to, initially the vapor pressure of this pure solvent was P naught A. Now it got decreased by 20%. Minus 20% of P naught A, so the value comes out to be 0.8 P naught A. Correct? This is the vapor pressure of solution because it has got decreased by 20% on the addition of non-volatile solute. Right, people? Yeah. Now, P naught A is the vapor pressure of pure solvent, pure water. 0.8 P naught A, this is the vapor pressure of solution. What do I need to calculate? Mass of non-volatile solute added. I'll be using P naught A minus PS divided by PS is equal to what? Is equal to NB divided by NA. NB is number of moles of non-volatile solute, NA is number of moles of solvent, right? See guys, P naught A I'm writing as such. PS is given to me as 0.8 P naught A. PS is 0.8 P naught A, correct? NB, number of moles of solute. Mass of solute divided by molar mass of solute. Mass of solute I'm representing by WB. Molar mass of solute, that is urea. Molar mass of solute, that is urea, that is 60 grams per mole. Number of moles of solvent, that is mass of solvent, which is 100 grams, divided by molar mass of solvent is 18 grams. So P naught A, P naught A, P naught A everywhere got cancelled. So finally you get something like this. 1 minus 0.8 comes out to be 0.2. Divided by, in the denominator you have got 0.8 is equal to, you need to solve this a bit. It's going to be WB divided by 60 multiplied by 18 divided by 100. So on solving this equation, you get the value of WB from here, right? WB is the mass of non-volatile solute, urea, which I have basically put in water, by means of which vapor pressure got decreased by 20%. I'm sure it's clear. Right, people? So finally you get the answer as 83.3 grams. And once you get the mass of non-volatile solute, you can simply calculate the molality of the solution as well. All the parameters are given. Put it in this equation, get the molality, right? Simple. It is the easy equation, but the calculation is a bit lengthy in this one. That's all. Right? Okay, moving on to one more then. At a given temperature, vapor pressure of pure benzene is 200 mm of Hg. At the same temperature, vapor pressure of the solution containing 2 grams of non-volatile solute in 78 grams of benzene is 195 mm of Hg. Calculate the molar mass of solute. It is again simple. See guys, at a given temperature, vapor pressure of pure benzene I am representing by P naught A. It is given to me as 200 mm of Hg. Right? At the same temperature, vapor pressure of the solution containing 2 grams of non-volatile solute in 78 grams of benzene. So vapor pressure of solution is 195 mm of Hg. What do I need to calculate? I need to calculate the molar mass of solute, right? I need to do the molar mass of solute. Again, you'll be using the same formula. You'll be solving the equation as P naught A minus Ps divided by Ps is equal to NB upon Na. Every single parameter is given to you. You need to put it in this equation, get the value. People, can you solve it afterwards? I mean, is this pattern of question done? Right? Or you want me to solve it? You want me to solve it or not? Because it's a similar type of question, right? You can do it on your own, correct? This question you can do on your own, correct? So finally you get the molar mass of B, molar mass of solute as 78 grams per mole, right? Perfect. Okay, this is one more question. Again, the similar type of question. You can solve on your own, right? Awesome chemistry, no, the formula is correct. You can use that formula as well, right? You can use this formula as well to solve the questions in lesser time. Okay? In NCERT, that is for very, very dilute solutions basically. That's for very, very dilute solutions. The formula which you are talking about, which is given in the NCERT, which is P naught A minus Ps divided by P naught A is equal to NB by Na, right? That's valid for very, very dilute solutions. Okay, so let's move on. This is again a simple question, people. The vapor pressure of an aqueous solution of glucose at 373 Kelvin, right? It's 750 mm of Hg. Calculate the mole fraction and molality. Again, this simple question. See, same thing. P naught A minus Ps divided by P naught A is equal to mole fraction of solute. We know it. P naught A is the vapor pressure of pure solvent that is water. What is the vapor pressure of water at 373 Kelvin? At 373 Kelvin, which is the boiling point of water. Boiling point is the temperature at which vapor pressure becomes equal to atmospheric pressure. Atmospheric pressure is 760, so vapor pressure of pure water is going to be 760 minus vapor pressure of solution is given 750. P naught A, vapor pressure of pure solvent is given. Chi B you'll be getting from here. After getting the chi B, mole fraction of solute, you'll be using the direct result between molality and mole fraction. You'll be using the direct result between molality and mole fraction, right? Once you use this relation, you can calculate molality as well. Yeah, this is again a simple formula based question. Again, the similar type of question, 12 grams of non-volatile solute dissolved in 108 grams of water produces the relative lowering in vapor pressure of 0.1. The molecular mass of solute is again the similar sort of question, right? Again, the similar sort of question. Correct, people? See, it's going to be P naught minus Ps divided by P naught. This is something which we call as the relative lowering in vapor pressure. Its value is given to me as per the equation, that is 0.1. So this value is given to me as 0.1. Correct? This value is given to me as 0.1. Right? Right? So from this you can calculate molality, molar mass of the solute. You can use any of the formula, guys. You can use any of the formula. Your question will be always correct. I mean, your answer will be always correct. Right, people? You can use any of the formula. Whatever formula you want to use, you can do that. Your answer will be always correct in these sort of questions. Which of the following aqueous solution will exhibit highest boiling point? Highest boiling point. More the Van't Hoff factor, right? More the Van't Hoff factor. More is going to be the boiling point. Okay. Which one is going to show maximum Van't Hoff factor? Na2SO4, because it produces maximum number of ions. So option C is going to be the answer of this question. Maximum boiling point of the solution will be shown by 0.01 mole Na2SO4. Correct? Right, people? Yeah? Okay, for an electrolyte, elevation in boiling point is directly proportional to what? Elevation in boiling point, delta TB. It's directly proportional to molality, right? For urea, Van't Hoff factor is 1. It does not dissociate or associate. Okay, what is the answer of this question? It's absolutely going to be molality. That's something which you all must be knowing. Find the weight of sucrose that must be added to 100 grams of water to have the boiling point of solution equal to 100.5 degrees centigrade. It's again a simple question. See, you'll be using a simple formula. Delta TB is equal to KB multiplied by molality, right? Every single parameter is given, right people? Delta TB is the elevation in boiling point. Yeah, what is the elevation in boiling point? So basically find the weight of sucrose that must be added to 100 grams of water. Boiling point of water is 100. For the solution it's 100.5. So how much boiling point has elevated? 0.5 degrees centigrade. Kb is given to me, 0.52. Molality of the solution, mass of solute multiplied by 1000 divided by molar mass of solute, which is the molar mass of sucrose, multiplied by mass of solvent in grams. Mass of solvent in grams is 100. Right? Solve this, get the value of W2 from here. Get the value of W2 from here. Right? You can do it on your own. That W2 is the mass of solvent, mass of solute, which I was supposed to calculate. Find the molar elevation constant. There is a formula to calculate molar elevation constant, and this is the formula R TB square divided by 1000 LV, right? Okay. Well, R value I'm going to use in calories because I'm given with the latent heat of evaporation in calories only. That's why I'm using the R value in calories. Boiling point of the solution I'm given with 60 degree, which is 333 Kelvin. 1000 in the denominator. LV is the latent heat of vaporization, which is 80. Finally, you get the value as 0.0083. Yes? Right? It's again the formula based question. I'm not going to show this one as well. Find the freezing point of the solution obtained by mixing 18 grams of glucose and 90 grams of water. It's again the simpler one. Freezing point of the solution, delta TF, is basically equal to KF multiplied by molality. Freezing point of the solution is going to be equal to freezing point of, depression in freezing point is going to be equal to freezing point of solvent minus freezing point of the solution, which is equal to basically Kf multiplied by molality, which is W2 multiplied by 1000 divided by M2 multiplied by W1 in grams, right? Okay, solvent I'm using as water. Freezing point of water is 0 degrees centigrade minus freezing point of solution I need to calculate. Freezing point of solution I think I need to calculate, right? Yes. Kf value is given to me 1.86. Mass of solute in grams I'm given with, right? How much? Mass of solute is given to me as 18 grams multiplied by 1000. Molar mass of solute, molar mass of glucose, that's 180 multiplied by mass of solvent, mass of water must be given to me. That is 90 grams, right? Just solve this equation, get the freezing point of the solution. It's again simple, right? It's again simpler one. Yeah? Okay. One more question. 1 gram of a non-electrolyte solute was dissolved in 512 grams of benzene. If the freezing point depression constant Kf is equal, the freezing point of benzene will be lowered by. You need to calculate delta Tf. That's it. You need to calculate delta Tf, which is Kf multiplied by molality. Kf is given, molality you can calculate because solute mass is given, solvent mass is given, everything is given, right? Right, people? It's simple. Delta Tf is the depression in freezing point, right? Which is equal to Kf multiplied by molality. Kf is given, molality is also basically given because mass of solute is given, mass of solvent is given. You know the solute, you know the solvent, right? Okay? It is the easy calculation, again the formula based one, right? Every single parameter is given. You need to put all the parameters in this equation. You get the depression in freezing point, correct? You guys are going to do it. Okay. In a 0.2 mole aqueous solution of a weak acid HX, the degree of ionization is 0.3. Degree of ionization is 0.3. Taking Kf for water as this much, the freezing point of the solution will be near 2. Okay, this is the question which we have right now. See, first of all, I'm given the weak acid HX. If it is a weak acid, it won't get completely dissociated into its ions. Its ions are going to be X negative plus H positive, right? These are going to be its ions. HX is a weak acid. Weak acid is a weak electrolyte which remains in equilibrium with its ions. Its ions are H positive aqueous and X negative aqueous, right? Now guys, see, 1 mole of HX gives 2 moles of ions, right? So N value is 2. Alpha value is given to us as per the equation, that is 0.3, I believe, right? 0.3. So first of all, let's calculate the Van 't Hoff factor for this acid. It's going to be 1 plus N minus 1 multiplied by alpha, right? So I is going to be 1 plus N value is 2 minus 1, alpha is 0.3. So it's going to be 1.3. So I value you got. Once you get the I value, you can calculate the depression in freezing point. You can say delta Tf, which is the depression in freezing point, that's equal to I multiplied by Kf multiplied by molality. Molality is also given to me, right? Delta Tf is basically the depression in freezing point, which is the freezing point of solvent. Solvent is water because I'm using aqueous solution. Freezing point of water is 0 degrees centigrade minus freezing point of solution, which I'm supposed to calculate. I value already I've calculated 1.3. Kf value is given to me as per the equation, it's 1.85. Molality of the solution is 0.2. So solve this, get the freezing point of the solution, which you were supposed to calculate, right? Yes, people? Simple? Option D is coming as the answer, yeah? Okay. The molecular weight of the benzoic acid in benzene is determined by depression in freezing point method. Corresponds to? People, when benzoic acid is added to benzene, what happens to benzoic acid? Benzoic acid undergoes dimerization. Benzoic acid undergoes dimerization. Two molecules of benzoic acid, they form one particle, right? Two molecules associate and form one particle. They show the dimerization, right? Okay? This is something which I've told you in the earlier sessions as well. Yeah? The molecular weight of benzoic acid in benzene is determined by the depression in freezing point method corresponding to dimerization of benzoic acid, right? So option B is the correct answer of this one. Okay, a solution of sucrose has been prepared by dissolving these many grams of solute in 1000 grams of water. The freezing point of solution obtained will be, again the same formula, delta TF is equal to Kf multiplied by molality, right? Sucrose does not undergo dissociation, it does not undergo association, so I value is 1, right? I value is 1. So you can use delta TF is equal to Kf multiplied by molality, right? Delta TF will be freezing point of solvent. Solvent is water, so 0 minus freezing point of solution is equal to Kf is given multiplied by molality. You can calculate mass of solute multiplied with 1000 divided by molar mass of solute, which is 342, multiplied by mass of solvent, that is 1000 grams. You can solve it. This is again formula based, right? As you can see over here. As you can see over here, it's again formula based is equal equation. Okay, blood cells retain their normal shape in solution which are isotonic to blood, right? That's something which you all must have studied in your biology as well, right? Blood cells retain their normal shape in the solution which are isotonic to blood. Yeah? Okay. Isotonic solutions have same what? Molar concentration, right? Yes? Absolutely. Molar concentration. Which of the following pairs are isotonic at the same temperature? At same temperature, which of the following are isotonic? So those solutions which are going to provide same number of ions, they are going to be isotonic. See, how many ions will this produce? It will produce calcium dye positive plus 2 times NO3 negative, so totally it is producing 3 ions. Na2SO4, it produces 2 Na positives and 1 SO4, so it again produces 3 ions, right? So this produces 3 ions, this produces 3 ions, so they are going to be isotonic at same temperature. They are going to be isotonic at same temperature because they are producing same number of ions, right? Yes, yes, yes. If Van 't Hoff factor is 1, that means it does not undergo dissociation or association. Yes, you're right. Okay. Osmotic pressure of the solution at a given temperature increase when concentration. Absolutely. Pi is equal to CRT, right? Pi, that is osmotic pressure. That's directly proportional to concentration. On increasing the concentration, pi value increases, osmotic pressure increases. Simple. Right, people? Okay, the Van 't Hoff factor I for a compound which undergoes dissociation in one solvent and association in another solvent respectively is, see, Van 't Hoff factor in case of dissociation. In case of dissociation, I value will be always greater than 1. In case of association, I value will be always less than 1. And neither dissociation nor association, it means I is equal to 1, right? In case of dissociation, I value is greater than 1. In case of association, I value is less than 1. Neither dissociation nor association, I value is equal to 1, right? So you can solve it on your own now. Less than 1 and, sorry, dissociation is greater than 1, association is less than 1. Greater than 1, less than 1. Option C is the one which is correct answer among all, right? Okay, Van 't Hoff factor is given by the expression I is equal to normal molar mass by abnormal molar mass. Absolutely correct. I is equal to abnormal molar mass divided by normal. No way, it's not correct. I is equal to observed colligative property divided by calculated colligative property. Absolutely correct. So A as well as C both are correct. So option D is the one which is correct among all, right? Option D is the one which is correct among all, right? It's a simple question, people, based on the definition of the colligative properties. Okay, we have 3 aqueous solutions of NaCl, right? With the concentration 0.1, 0.010, the value of Van 't Hoff factor. Van 't Hoff factor does not depend on the concentration, right? Does Van 't Hoff factor depend on concentration? It does not depend on the concentration at all. So all the Van 't Hoff factors will be same. So I1 will be equal to I2 will be equal to I3, right? Absolutely, option C is going to be the answer of the question. Right, people? Okay. The values of observed, yes. Now let's try to solve. Let's try to solve from here. The value of observed colligative property, the values of observed and calculated molecular weights of AgNO3 are 92 and 170 grams respectively. The degree of dissociation of AgNO3 is, first of all, let's calculate the Van't Hoff factor for AgNO3, which is going to be equal to calculated molecular mass of it divided by observed molecular mass. What is the calculated molecular mass? That's 170. What is the observed molecular mass? That's 92.64. You can solve it. Let me know the value of I in the chart box. Well, after getting the value of I, what do I need to calculate? I need to calculate degree of dissociation of AgNO3, right? And AgNO3, as you all must be knowing, it undergoes dissociation like this: Ag positive aqueous plus NO3 negative aqueous, right? Okay, right, people? So what is the value of N first of all? See, 1 mole of AgNO3 gives 1 plus 1, gives 2 moles of ions, so N value is 2. Once you get the value of N, you can calculate Van't Hoff factor. I is equal to 1 plus N minus 1 multiplied by alpha, right? So I value you would have calculated, people are saying it is 1.83, right? I value you have calculated as 1.83 is equal to 1 plus N value. N value is 2 minus 1 multiplied by alpha. So from here you can calculate alpha, which is 0.83. So alpha comes out to be 0.83, right? Degree of dissociation, which I was supposed to calculate, alpha. If you were being supposed to calculate percent dissociation, percentage of dissociation is going to be simply 83%. As simple as that. Yeah? Okay, one more. A millimolar potassium ferricyanide solution. Millimolar means concentration of this solution, molarity of this solution is 10 raised power minus 3, right? Potassium ferricyanide. Potassium ferricyanide means K3FeCN6. This is the potassium ferricyanide. Is 70% dissociated. First of all, if it undergoes dissociation, it gets converted into 3 times K positive plus Fe CN6 tri-negative, right? This is how it undergoes dissociation. It is 70% dissociated, that means alpha is equal to 0.7. Alpha is equal to 0.7. Find the osmotic pressure. It's simple, people. See, first of all, let me calculate the Van't Hoff factor. Or before calculating the Van't Hoff factor, let me tell you pi is equal to I multiplied by C multiplied by R multiplied by T. C means molarity. C means molarity of the solution. Let's calculate Van't Hoff factor first of all. See, one mole of this compound gives 3 plus 1, gives 4 moles of ions. So N value is 4 first of all. Let's calculate the Van't Hoff factor. I is equal to 1 plus N minus 1 multiplied by alpha, right? So I is going to be equal to 1 plus N value is 4 minus 1. Alpha value is how much? 0.7, right? 0.7. So it's going to be 3 multiplied by 0.7. 2.1, 2.1 plus 1 comes out to be 3.1. So I value you got to know as 3.1, right? I value you got to know as 3.1. Yes? Lil Cohen is saying I is equal to observed by calculated. That is observed colligative property divided by calculated colligative property. I wrote calculated molar mass divided by observed molar mass, right? So pi I value you got as 3.1. So people, pi value I need to calculate. I value you got as 3.1. C value is given to me as 10 raised power minus 3. R value 8.314. Temperature must be given to me as 300, right? Solve it and get the value of pi as per SI system, because I use the value of R as per SI system, correct? I use the value of R as per SI system. Yeah? Okay, again the simple question this was. Okay, when 12.2 grams of benzoic acid is dissolved in 100 grams of water, the freezing point of the solution was obtained, was found out to be minus 0.93 degrees centigrade. The number of benzoic acid molecules associated, N value you are supposed to calculate. So first of all, you will be using delta TF formula, get the value of I. And after getting the value of I, you'll be writing I is equal to 1 plus 1 by N minus 1 into alpha, right? Okay. Have a look exactly. So I'll be using this formula first of all, delta TF. From here you'll be getting the Van't Hoff factor I. Once you get the Van't Hoff factor I, you'll be writing 1 plus 1 by N minus 1 into alpha, because this is a case of association. I need to get the value of N. I value I got 1 by 2. 1 I'm writing as such. 1 by N minus 1 alpha value we know equal to 1, right? Because it's assuming that 100% association. So N value will be 1. Sorry, alpha value will be 1. So from here directly N value you'll be coming out to be 2, right? So 2 molecules, this is the case of dimerization basically. N value is coming out to be 2. So 2 molecules are associating, forming a dimer. Right? Okay. So with this, your solution chapter is done and dusted. Right? So people, let's have a break. Yeah? What time you want me to start again? What time you want me to start again? Yes, next is D block elements. 1:30? Yeah, 1:30 is the good time. Yeah. So just a second. 1:30, right? I'll start exactly at 1:30 sharp, okay? We'll be starting with the D block elements. Okay, before leaving, can you let me know the answer of this question? The transition element have a general electronic configuration of n-1 D1 to 10, right? This is something which you all must be knowing. Chalo, have lunch and come back soon, yeah? Welcome back, everyone. Welcome back. I hope everyone has joined back, yeah? Right? Everyone has joined back? Yes. People are back, yeah? Just give me a second, we'll be starting. You guys are done with your lunch and everything, yeah? Perfect, perfect, perfect. No, I did not have the lunch. I just had some tea. Okay? Yes, you won, absolutely, but at the end, yeah? At the end, at the end. Okay, so let's get started again then, yeah? So people, excited about the D block, F block elements, yeah? Let me know in the chat box fast. Okay, so let's get going with the D block elements, right? See, this question I told you in the beginning itself, the transition elements have a general electronic configuration of n-1, D1 to 10, ns 1 to 2. This is the general outermost configuration of your transition elements. Perfect? Okay. Correct electronic configuration of chromium. I'm sure you all must be knowing about this. Chromium and copper, they have got the exceptional configuration. Chromium has got 3d5 4s1 and copper has got 3d10 4s1, right? So 3d5 4s1 is going to be the configuration of chromium, which is option B, absolutely your correct answer. Yeah? Moving on to one more. The electronic configuration of copper is 3d10 4s1. 3d10 4s1. It's again going to be option B, right? Yes, people, it's again going to be option B. Okay, the electronic configuration of 4 elements are given below. Which element does not belong to the same family as others? See guys, in the first configuration, the outermost electron is in S subshell. In the second one, again the outermost electron is in S. In the third one, outermost is in P. In the last one, outermost is in S, right? So option C says that it must be a P block element in which the outermost configuration is in P subshell, right? So basically this is a P block element. Rest all the elements are S block elements because the outermost configuration, right? The outermost electron in case of the third configuration is in P subshell. That's why it is the P block element. Rest all the others are S block elements. Okay. Transition metals mostly are paramagnetic because of the incompletely filled d orbitals, right? These are mostly paramagnetic. All of you must be knowing about this as well. Correct? Because of the presence of unpaired electrons in their d subshells. That's something which you all must be knowing. If n is the number of unpaired electrons, the magnetic moment, how do we calculate magnetic moment? Under root of n into n plus 2 Bohr magnetrons, where n stands for the number of unpaired electrons. That's again something which every one of you must be knowing, right? So option A is the correct answer of this one. Magnetic moment is 2.84 Bohr magnetrons. So magnetic moment of some species is 2.84. That means under root of n into n plus 2 is equal to 2.84. What can you conclude from here? Can you let me know how many unpaired electrons will be there? Can you let me know what is the n value right here? Correct? What is the n value, people? What is the n value? How many unpaired electrons will be there? There'll be 2 unpaired electrons, right? Then only root of 2 into 2 plus 2 comes out to be 2.84, right? So n value must be 2. 2 plus 2 is 4, 4 2s are 8, root of 8 will be 2.84. So n value is 2, number of unpaired electrons are 2. In which of the species among all, number of unpaired electrons are 2? If I look at the last one, which is nickel, right? Iron, cobalt, nickel, 3d8 4s2 configuration. Correct, people? But this is Ni di positive, so take 2 electrons out. When you take 2 electrons out, it becomes 3d8 configuration. And in case of 3d8 configuration, there will be definitely 2 unpaired electrons. Correct? So correct answer of this question is absolutely going to be option D. I'm sure all of you must be knowing this. Correct? Very simpler one. Moving on to the next one. The number of d electrons in Fe di positive is not equal to the number of electrons in which of the following? Okay, is not equal to, he is saying. Is not equal to, he is saying. What do you think about this one? What do you think about this one? Is not equal to, he is saying. He's not saying is equal to, he is saying is not equal to. Is not equal to p electrons in chlorine. Is not equal to p electrons in chlorine. Why is that? See, check it out. In case of Fe di positive configuration, how many d electrons are there in total? There are 6 d electrons in case of Fe di positive configuration. In case of chlorine, there are total 11 p electrons, which is not equal to 6, right? Which is not equal to 6. So option A is supposed to be the correct one among all. It is again the very simple question based on the configuration. Okay, what is the correct order of increasing energy of the listed orbitals in the atom of titanium? Right? What is the correct order of the increasing energies? Simple, follow n plus L rule, right? Follow n plus L rule. See guys, if you look at the last option, okay, we are given with 3s first of all. We are given with 3s. N value is 3, L value for S is 0, so 3 plus 0 becomes 3. If we talk about 3p, N value is 3, L value is 1, so 3 plus 1 is 4. If we talk about 4s, N value is 4, L value is 0, so it again comes out to be 4. If we talk about 3d, N value is 3, for D, L value is 2, so 3 plus 2 comes out to be 5. Lesser the N plus L, lower the energy, right? So 3s is going to have least energy. 3s is going to have least energy. Now among these two, which have got same N plus L, just see the N value. N value is lesser for 3p, then comes your 3p, then comes your 4s, and at the end comes your 3d. This is the answer of the question. So option D is the one which is absolutely correct answer of it. Yes? Right? Absolutely guys, option D is the one. Moving on to one more. Scandium is a transition element, but zinc is not. What is the reason for that? What is the reason for that? It's again the easy question, theoretical question. Both scandium and zinc do not exhibit variable oxidation state. Nothing to do with this. Both Sc tripositive and Zn dipositive are colorless. Nothing to do with this. In case of scandium 3d, orbitals are partially filled, but in zinc they are completely filled, right? In zinc there are completely filled d orbitals, which does not make it a transition element. For the element to be the transition, it must have incompletely filled d orbital, right? Okay, scandium, it has got partially filled d orbitals, whereas zinc does not have any unpaired d electron. That's why your scandium is a transition element and zinc is not, right? Option C is the one. Correct, people? Yes? Okay. Which one of the following does not correctly represent the correct order of the property indicated against it? Titanium, vanadium, chromium, manganese, increasing number of oxidation states. Absolutely. Manganese shows maximum number of oxidation states among all, right? Increasing magnetic moment. Absolutely correct. Mn tripositive has got maximum number of unpaired electrons. So magnetic moment will be maximum for Mn tripositive. Increasing melting point. Titanium, vanadium, chromium, manganese. No way. This is the incorrect one. Option C is the incorrect one. Melting point first increases to the maximum, then it decreases, and manganese has got abnormally low melting point among all, right? Manganese has got abnormally low melting point. So option C is the one which is not the correct one as indicated against the property. Yes? Right? This is not the correct order of the melting points, right? Melting point first increases, then it makes a dip, right? So manganese abnormally it has got the low melting point, right? Then chromium, then vanadium, etc. Okay. The catalytic activity of the transition metals and their compounds is ascribed mainly to. What is going to be the answer of this question? The catalytic activity of transition metals and their compounds is ascribed mainly to. What is going to be the answer of this? It is mainly because they have got the ability to adopt variable oxidation states, right? Option C is the one which is going to be the appropriate answer of this one. Yeah? Right, people? Absolutely. Option C is the one. Okay. For the 4 successive transition elements, the stability of +2 oxygen state will be there in which of the following? Okay. We need to arrange them on the basis of the stability of the +2 oxygen state, right? +2 oxidation state. It's simple, right? See guys, have a look. If you talk about Mn dipositive, if you talk about Fe di positive, if you talk about Cr di positive, if you talk about cobalt di positive, right? Mn di positive configuration, it becomes 3d5. It becomes 3d5. It becomes half-filled configuration, which is very, very, very stable. So Mn di positive configuration is absolutely going to be maximum stable among all. So there is only one option which says Mn di positive configuration is maximum stable. So option A must be the answer for this. Right, people? It's again the easy question. Yeah? Okay, one more. Which of the following ions will exhibit color in their aqueous solutions? Which of the following will exhibit color? Color, right? That species which will be containing unpaired electrons will be exhibiting color. So you need to write their configurations, then you need to see which one is going to have the unpaired electrons. The one which is going to contain unpaired electrons will be definitely exhibiting some color, right? So people are saying option B is that titanium tripositive, scandium titanium, 3d2, right? 3d2 4s2, correct? Take 2 electrons out, take 3 electrons out, it becomes 3d1. So there is one unpaired electron in Ti tripositive. So it's absolutely going to have some color, right? Rest in every case, there will be completely filled configuration. See, in case of La tripositive, right? Completely filled configuration. Ti tripositive, one unpaired electron. Lu tripositive, no unpaired electron. Scandium tripositive, no unpaired electron. Only one is having unpaired electron. So that's going to be titanium tripositive. It's absolutely going to show some color, right? Okay, which of the following ions has the configuration of argon 3d6? Argon 3d6. Which one is going to show this configuration? This question was recently asked in your JEE mains as well, right? The current shift of JEE mains. Simpler one. 3d6, argon 3d6. Argon 3d6. See, if we look at the outermost configuration of cobalt, iron cobalt, it's 3d7 4s2, right? It's 3d7 4s2. If I take 3 electrons out from here, it becomes 3d6. So basically, cobalt tripositive shows argon 3d6 configuration. So it's absolutely going to be cobalt tripositive. Again, the easy equation which you can solve, right? Okay. Out of TiF6 dinegative, COF6 trinegative, Cu2Cl2 and NiCl2, the colorless species are. First of all, this is titanium in +4 oxygen state, right? This is cobalt in +3 oxygen state. This is copper in +1 oxygen state, right? And this is nickel in +4 oxygen state, right? Yes. Now you need to have a look on the electronic configuration of Ti +4. You need to have a look on the electronic configuration of CO +3. You need to have a look on the electronic configuration of Cu +1. You need to have a look on the electronic configuration of nickel +4. The one which will be carrying unpaired electron will be having some color. The one which is not carrying any unpaired electron won't be having any color, right? So which one won't be having any color? Cu positive. In case of copper, 3d10 4s1, take 1 electron out, it becomes 3d10 configuration, completely filled, no unpaired electron, it's colorless, right? Okay, if we look at nickel tripositive, iron, cobalt, nickel, right? 3d8 4s2, right? There will be unpaired electrons. If you look at titanium +4, scandium titanium, it is 3d2 4s2. Take 4 electrons out, it becomes 3d0 4s0, so no unpaired electron, right? So it is going to be colorless. This one will be colorless, this one will be colorless. So Ti +4 and Cu +1, this option B is going to be the pair which is going to be colorless among all. Right, people? Absolutely. Moving on to one more, the correct order of decreasing second ionization enthalpy. Decreasing second ionization enthalpy. Which one is going to have maximum second ionization enthalpy? See, if I look at the configuration of Cr positive, Mn positive, right? V positive, Ti positive, right? Now you need to take the electron out from Cr positive, you need to take the electron out from Mn positive, electron out from V positive, electron out from titanium +1, right? Where is it difficult to take the electron out? If you look at the configuration of chromium is 3d5 4s1. If you look at the configuration of Cr positive, it is 3d5 4s0, right? If you want to take the electron out from Cr positive, you have to take it out from this completely stable configuration, right? Which is exactly half filled, which needs lot of energy, right? So I'll say second ionization energy of chromium is maximum among all. And there is only one option which says chromium has got the maximum second ionization enthalpy. So it's option A, which is going to be the correct one among all. Right, people? Absolutely, it's going to be option A. Moving on to one more. Okay, which of the following ions is the most stable in aqueous solution? Most stable in aqueous solution. Which one of the following is going to be most stable in aqueous solution? Let me know fast. Let me know fast. It's a very simple question again. See guys, if you look at the outermost configuration of Cr tripositive, if you look at the outermost configuration of Cr tripositive, see, chromium has got the configuration of 3d5 4s1, right? If you take 3 electrons out, it becomes 3d3 configuration. Now 3d3, right? You can fill these 3 electrons right here in T2g, and this is your Eg, right? So what is the crystal field configuration of Cr tripositive? It's going to be T2g3, right? Okay, it's exactly half filled, which is absolutely going to be the stable configuration among all. If there's a stable configuration, then definitely Cr tripositive will be maximum stable in aqueous solution among all. In all the, if you look at all the other species, they won't get this type of stable configuration. You can check it out afterwards. Yeah? Exactly. Okay, one more. Which of the following pairs in which of the following pairs are both the ions colored in aqueous solution? Colored. That means again you need to find the unpaired electrons. Wherever there will be unpaired electrons, definitely there will be, that species is going to be colored, right? You need to find the unpaired electrons, same procedure you are going to follow, correct? And finally, nickel dipositive will be containing some unpaired electrons, titanium tripositive will be containing some unpaired electrons, right? So they are going to be colored. Yeah? Okay, the same procedure which you guys are following. Alright, the aqueous solution, which one of the following will be colorless? Again, the similar type of question. Again, you need to find the unpaired electrons. If there are unpaired electrons, definitely there will be. If there are unpaired electrons, definitely it will be having some color. If there won't be any unpaired electrons, it will be having colorless. It will be having colorless, right? Yes. So scandium tripositive, it's not having any sort of unpaired electron, so it's going to be colorless among all. Okay. 4 successive members of the first row transition elements are listed below with their atomic numbers. Which of them is expected to have the highest third ionization enthalpy? Third ionization enthalpy. So already 2 electrons are taken out from these species. Now you are going to take the third electron out. If you remember the electronic configuration of manganese, it is 3d5 4s2. If you take 2 electrons out, it is 3d5. Now the third electrons, if you look at the configuration of manganese, it is 3d5 4s2. Take 2 electrons out, right? Now it becomes 3d5. Now take the third electron out. Third electron has to be taken out from 3d5 configuration, which needs a lot of energy. So third ionization energy in manganese will be maximum, right? Absolutely. Yeah, so option C. Okay, the basic character of the transition metal monoxides follows the order. What happens? See, titanium, vanadium, chromium, iron, they belong to same period. As we move from left to right, what happens to the basic character of their monoxides? What happens to the basic character of their monoxides? Does it increase or decrease? It decreases, right? It decreases. So which option satisfies it? It's going to be option A, which is going to be correct one among all, right? Absolutely. One more. The acidic, basic or amphoteric nature of Mn2O7, V2O5 and CRO. See, Mn2O7, it is the acidic oxide, you all must be knowing, right? V2O5, it is the example of the amphoteric oxide, it's given in the NCERT. And CRO, it is the basic oxide. So acidic, amphoteric, basic. Acidic, amphoteric, basic. So option C is the one which is correct among all. Right, people? Absolutely, it's going to be option C. Moving on to one more. See, from this paragraph, the question has been taken. Okay. Which of the following is amphoteric? Which of the following is amphoteric? It is first of all going to be V2O5. V2O5 given in your NCERT, V2O5 is amphoteric. Apart from V2O5, it will be Cr2O3. Cr2O3 and V2O5. Cr2O3 and V2O5, they are going to be amphoteric, right? Okay. I'm not talking about V2O3, I'm talking about V2O5. Right, people? So option A is the one which is going to be correct. Okay. Which of the following shows maximum number of oxygen states? It's absolutely going to be manganese, +2, +3, +4, +5, +6, even +7, right? Maximum number of oxygen state will be shown by manganese. Is there any option as manganese? Absolutely option C. Okay, match the catalyst with the processes. You need to match it. Let me know fast. V2O5, V2O5, V2O5. Oxidation of SO2 in the manufacture of H2SO4, absolutely 1, you are going to connect with 3, right? 2, TiCl4 plus AlCH3 whole thrice. Polymerization of ethylene, absolutely 2, you are going to connect with D. What about the third one? PDCl2, oxidation of ethyne to ethanol, absolutely. Option 4, nickel complexes, polymerization of alkynes, option B. So 1 you are attaching with C, second you are attaching with D, third you are attaching with A, and fourth one you are attaching with B. So option B is the correct answer of this one, right? Right, people? Option B is the correct answer of this one. Okay, name the gas that can decolorize acidified KMnO4 solution. Which gas can decolorize acidified KMnO4? It's going to be SO2. It's a very common question, right? Yes, people, it's going to be SO2. Yeah? Okay, moving on to one more. Which one of the following statements is correct when SO2 is passed through acidified K2Cr2O7? The solution turns blue? No. The solution is decolorized? No. SO2 is reduced? No. Green Cr2SO4 whole thrice is formed. Absolutely, this one is correct. Option D is the correct one among all, right? Option D is the correct one. Correct, people? Okay. When copper is heated with concentrated HNO3, it produces. What does it produce? When copper is treated with concentrated HNO3, it produces what? What does it produce? Let me know fast. This is the question which we have done already. Absolutely, majority of the students are correct. It's going to be CuNO3 whole twice and NO2, right? Absolutely, option A is going to be the correct one among all. NO2 gas is liberated basically, right? It's not only copper. Less active metals like your copper, silver, they react with concentrated acid and forms nitrate, and nitrogen dioxide is liberated. Less active metals, right? Like copper, silver, etc. Okay. The pair of compounds that can exist together: FeCl3, SnCl2, HgCl2, SnCl2, FeCl2, SnCl2, FeCl3, Ki. Well, I think option C must be the answer because both are reducing agents, right? Option C must be the answer because both are reducing agents. Right, people? Absolutely. One more. In acidic medium, H2O2 changes Cr2O7 to CrO5. Okay, oxidation state of chromium in CrO5. CrO5, many a times I've shown you its structure, right? In CrO5 structure, the oxidation state of chromium is +6, right, people? It's +6. Yeah? This is something which you all must know. Okay, the reaction of aqueous KMnO4 with H2O2 in acidic conditions gives. Remember, KMnO4, it converts H2O2 into O2, right? Yes, and itself gets converted into Mn di-positive in acidic medium, right? Itself, it gets converted Mn di-positive, and H2O2, it converts into O2. So what is going to be the answer of this question? It's going to be option B. Okay, German silver is an alloy of. German silver is an alloy of. This is something which you guys are going to tell me, and you need to remember the composition of the German silver as well. Yeah? What is going to be the answer of this question? Is it copper, zinc, silver, or copper, zinc, nickel? Let me know fast. It is going to be copper, zinc, nickel, and do remember its composition as well. In case of German silver, copper percentage is 56, zinc is 24, and nickel is 20%. Do remember this composition. Yeah? Okay, one more. Which of the following combines with Fe di-positive ions to form a brown complex? Right? It is the famous test, if you remember. Right? Correct? It is going to be NO. It's going to be NO, right? Brown ring test you might have heard. Perfect, guys, exactly. On heating chromate with Na2CO3 in air, which of the following product is obtained? When we heat chromate with Na2CO3 in air, which of the following product is obtained? We will be getting Na2CrO4, right? Na2CrO4 is going to be the product. Option D is the one. Option D is the one which will be getting from this reaction, and this is the reaction which is given over here. So you get Na2CrO4, with this you get Fe2O3 and carbon dioxide gas is liberated as well. Again the easy equation, right? Okay, K2Cr2O7 on heating with aqueous NaOH, what does it form? CrO4 dinegative, right? CrO4 dinegative, correct? Okay, CrO3 dissolves in aqueous NaOH to give what? To give what? What is going to be the answer of this question? Again, the similar type of question. CrO3 dissolves in aqueous NaOH to produce what? Absolutely, guys, it's going to be CrO4 dinegative only, right? Basically, it's Na2CrO4. With this, you get water as well. Yeah, these sort of questions we have done in the top 100 series as well. I hope you remember. A blue coloration is not obtained when ammonium hydroxide dissolves in copper sulfate. Copper sulfate solution reacts with K4 FeCN6. Ferric chloride reacts with sodium ferrocyanide, and hydrous CaSO4 is dissolved. Option B must be the answer, right? Right, people? What do you think? Yeah? It's going to be option B. It is basically chocolate in color. You get chocolate precipitate over here. It's not blue colored. It's not blue colored. Okay. Moving on to one more. Reason of lanthanoid contraction. What is the reason for lanthanoid contraction, people? What is the reason for lanthanoid contraction? Negligible screening of f orbitals, right? Option A. Option A is going to be the answer of this one. Reason for lanthanoid contraction is the negligible screening of f orbitals. Okay. Identify the incorrect statement among all. Lanthanoid contraction is the accumulation of successive shrinkages, which is correct. As a result of lanthanoid contraction, the properties of 4D series of the transition elements have no similarity with 5D. Is it correct? Will they have no similarities? Will they have no similarities? No way. They will be having similarities, right? So option B is the incorrect among all, right? Option B is the incorrect among all. Which of the following lanthanide ions is diamagnetic, right? Again, you need to remember their configuration. It's given in the NCERT. That table is given, right? You need to see the unpaired electrons, paired electrons. Wherever you see unpaired electrons, that's going to be paramagnetic. Wherever there won't be any sort of unpaired electrons, it's going to be diamagnetic, and it's going to be YB dipositive for sure, right? Option C is the answer of this question. YB dipositive configuration, there is no unpaired electron. There is no unpaired electron, right? Absolutely. Okay. The reason for greater range of oxidation states in actinoids is attributed to actinoid contraction? No. 5F, 60 and 7S levels having comparable energies. Yes, option B is the correct one. Yes, option B is the correct one, right? Option B is the correct one among all. The reason for greater range of oxidation states in actinoids is due to the reason that 5F, 60 and 7S levels having comparable energy. They have got comparable energies, due to which there is a greater range of oxidation states in actinoids. Yeah? Okay. The electronic configuration of EU with atomic number 63, JD with atomic number 64 and TB with atomic number 65 are. What is going to be the answer of this question? Right? There is only one case in which there is exceptional electronic configuration, that's gadolinium, right? It has got 4f7, 5d1, 6s2 configuration, right? People, what is going to be the answer of this question? Is it going to be C or D? Is it going to be C or D? Yes, this is the this year JEE question. It's going to be option D, people. It's not going to be C, okay? It's not going to be C, it's going to be D. All right, one more. Okay, gadolinium configuration, right? It is 4f7, 5d1, 6s2. So option C is the one. This is something which you all must be knowing. This question has been asked 3 times in your NEET, right? 3 times in your NEET examination, this question has been asked. Okay, actinides are, all are synthetic elements, include element 104. They have short-lived isotopes, have variable valency. They have got variable valency, right? they have the variable valency. Option D is the one which is correct. Which of the following exhibits only +3 oxidation state? It's going to be AC, actinium, right? It only exhibits +3 oxygen state because it attains the stable electronic configuration, yeah? Right? If you take 3 electrons out, it becomes the completely filled configuration, which is the stable one. So option C is the correct answer of this one. The main reason for large number of oxidation states exhibited by the lanthanoids than the corresponding, by the actinoids than the corresponding lanthanoids. More energy difference between 5F and 6D, less energy difference between 5F and 6D, then between 4F and 5D, larger atomic size of actinides, larger atomic size. So what is going to be the answer of this question? What's going to be the answer of this question, people? It's again a simpler one. Let me know fast. It's absolutely going to be option B. Lesser energy difference between 4F and 5D orbitals than between 4F and 5D. Right? 5F 6D and 4F 5D. Correct? The correct order of ionic radii of Y tripositive, La tripositive, Eu tripositive, and Lu tripositive. What is going to be the answer of this one? What is going to be the answer of this one, people? Let me know fast. Again, the simple question. NCRT one, yeah? Absolutely, it's going to be option A only. Sorry, option C. Sorry. I just saw it in the opposite way. Okay, option C is going to be the correct answer of this question. This question is directly from your NCRT again. Right? Okay, which of the following statement is not correct? LaOH is not correct, he is saying. LaOH whole thrice is less basic than LiOH thrice. Is not correct. First option is not correct. LaOH whole thrice is more basic than LiOH whole thrice, right? Option A is the answer of this question. Correct? Option A is the answer of this question. Okay, let's get started with the coordination compounds now. With this, your DNF block, I'm sure, nothing can be asked out of these questions. Go through these questions again after the session, right? Look at the PDF and do remember these questions directly. I'm sure if the question comes from DF block elements, it's going to be one among these only. Right? Okay, so should we start with the coordination compounds, people? Yeah? Yes, magnificent mesh. Okay. Perfect. PDF you'll be getting in the Telegram group. PDF you'll be getting in the Telegram group, guys. You need to, there's a link in the description box of the video. You need to click on that link, get added to the Telegram group and stay updated about the class and everything, right? In that Telegram group only, we'll be sharing the PDF of this session. Okay, let's get going. K4FeCN6, what is it? Double salt complex compound acid base. K4FeCN6, a famous complex compound, right? Famous complex compound, famous coordination compound. According to Lewis, the ligands, they donate a pair of electrons to the central metal ion, right? So the ligands are going to be acting like the Lewis bases, they are going to be basic in nature. Right, people? Okay, ligand in a complex salt. Are the anions linked by coordinate bonds to the central metal atom? Cations linked by coordinate bonds? Molecules linked by coordinate bonds to central metal? Ions or molecules linked by coordinate bonds to the central atom? Option D is the one. Option D is the one which is going to be correct among all, right? Ligands can be ions or molecules which are linked by coordinate bonds to the central metal ion, right? Okay, the ligand is it, what is it? What is its denticity? Tridentate, tetradentate, pentadentate, what? What is it exactly? Which kind of ligand this is? See, there is a lone pair on this nitrogen, right? And these are more 3 nitrogens, right? So 3 plus 1, total there are 4 nitrogens, correct? Total there are 4 nitrogens. Yes? So what is going to be the correct answer of this question, people? What is going to be the correct answer of this one? Is it going to be tetradentate? Absolutely, because you have got 4 coordinating sites over here, 4 nitrogens with 4 lone pairs, right? It can donate all these 4 lone pairs towards the central mat line. So its density is going to be 4 absolutely. So it's a tetradentate ligand. Okay, example of the ambidentate ligand. Which one is the example of the ambidentate ligand? What do you think about this one? Which one is the example of the ambidentate ligand? Which one has got 2 coordinating sites but it uses only one at a time? It is going to be thiocyanate, SCN, right? Option D is absolutely going to be the answer of this question, right? It can coordinate either from sulfur or from nitrogen. Yeah? A bidentate ligand always has bonds formed to 2 mat lines, has the charge of +2 -2, forms complex ions with the charge of +2 -2, has 2 donor atoms forming simultaneously 2 sigma bonds. Absolutely, the bidentate ligand, it has got 2 donor atoms forming simultaneously 2 sigma bonds. Absolutely correct. Yeah? Absolutely correct, guys. Option D is the one. Okay, glycinato. Is this what we call as GLY, right? Yes. Is it a bidentate ligand? Absolutely. This is one coordinating site. This is one more coordinating site. It has 2 donor sites, nitrogen and O negative. Absolutely. So all these things are given correct about the glycinate, right? So all the above is going to be correct. Option D is going to be correct among all. Okay. The correct structure of EDTA. What is the correct structure of EDTA, people? Can you let me know its answer? Can you let me know its answer fast? What is the correct structure of EDTA? Well, the correct structure of EDTA is going to be this one, right? This option C is the correct structure of EDTA. Yeah? There is just a difference between option 1 and option C, right? There is a double bond between these 2 carbons, there is a single bond, but actually in the structure there is a single bond only. Yeah? So option C is the one which is correct among all. Okay, the following ligand is, first of all, see how many coordinating sites are there. 1, 2, on nitrogen there is a lone pair, on this nitrogen there is a lone pair, 1, 2, 3, 4. So it's a tetradentate ligand, right? It is a tetradentate ligand, people. Yeah? So option B is the one which is correct among all. Okay, the coordination numbers are following. Coordination numbers of the following. See, chlorine is a monodentate, En is bidentate, right? We have got 2 En molecules, so 2 2s are 4, 4 plus 1 5. So coordination number in the first case is 5. In the second case, it is the oxalate. It's a bidentate ligand. 3 2s are 6. So 5 and 6 is going to be answer of this question, right? 5, 6 is going to be answer of this question. Yeah. Again, a very common question. This has been asked many a times, right? What is going to be answer of this question? Chromium will show +3 oxygen state in the first case. In the second case, it's going to show 0 oxygen state. In the third case, it is going to show +6 oxidation state, right? Yes. These are basic questions regarding the oxidation states, right? So +3, 0 and +6 are, this is how you calculate the oxidation states, and I'm sure you all must be knowing this, right? I'm sure you all must be knowing how to calculate the oxidation states, right? Okay, this is the solution given. You can check it out. Okay, the coordination number of TH. See, oxalate, bidentate, 4 2s are 8. Water, monodentate. So 2 plus 8 comes out to be 10. So coordination number is going to be 10 in this case. So option B is the one. Option B is the one. Yeah? Okay, which of the following complexes are homoleptic? Homoleptic means where the ligands are of same type, right? Where the ligands are of same type. See, if you look at option 2 and 4, there are different ligands, NH3 and Cl. NH3 and Cl, different ligands. So these are not homoleptic, these are heteroleptic, right? These are heteroleptic. So option 1 and C, these are homoleptic in which we have got same ligands, right? So which one? 1 and 3. 1 and 3. 1 and 3. Where is 1 and 3? Option D. Option D is the one which is correct. Yeah? Okay, one more. Which of the following complexes are heteroleptic? Again, a similar question. So 2 and 4 are going to be heteroleptic. 2 and 4 are going to be heteroleptic. Where do you have different ligands attached? As per IUPAC nomenclature, the name of the complex. What is going to be the name of this complex? It's going to be diamine, but it's A-double-M. It is A-double-M-I-N. Okay? It's going to be diamine tetra-aqua cobalt 3 chloride, right? Diamine tetra-aqua cobalt plus 3 chloride. So option D is the one, right? Be careful with the spelling as well. It is A-double-M. It's not A-single-M. Yeah? I'm sure you are remembering all this. right? Okay. One more, the IUPAC name of this. What is the IUPAC name of this compound, people? IUPAC name of this compound. Let me know fast. First, it's going to be tetraamine. Then you'll be writing nickel. After nickel, you'll write its oxidation state. It's going to be +2, right? Then you'll write tetrachloro. Then you'll write nickelate. Then its oxidation state, which is again +2. So which option satisfies it? Tetraamine, nickel +2, tetrachloro, nickelate +2, right? I mean 2. So option C is the one which is correct among all. Yes? Option C is the one which is correct among all. Okay, IUPAC name of this compound. What is the IUPAC name of this compound? What is the IUPAC name of this compound? Lag. Is there any lag? People, is there any lag? Am I perfectly audible and visible? Okay. All right. What is going to be IUPAC name of this? It's going to be potassium hexachloroplatinate, right? Potassium hexachloroplatinate 4. Yes? So option B is the one which is correct among all. Again, the simple question based on nomenclature. Arva, maybe there will be some connectivity issues from your side. On my side, connectivity is all okay. There is no lag at all, right? I hope you get it. What is the magnetic moment, spin magnetic moment of this COCN6 4 negative? COCN6 4 negative. What is going to be the magnetic moment? What is going to be the magnetic moment? Let me know fast. Simple, under root of n into n plus 2. Calculate the unpaired electrons. See, cobalt over here shows the +2 oxygen state. It shows the +2 oxygen state, right? Iron, cobalt. Cobalt is 3d7 4s2. 3d7 4s2, but if I talk about CO di positive, it's 3d7. Correct, people? It's 3d7, right? So how many unpaired electrons will be there? How many unpaired electrons will be there? Can you let me know? How many unpaired electrons will be there, people? There will be some 2 unpaired. Is it some 2 unpaired electrons? Just a second. Okay, we are supposed to calculate magnetic moment. I thought these are unpaired electrons, right? So basically, Cn is a strong field ligand. It's going to cause the pairing of electron. Due to pairing, there will be only 1 unpaired electron. 1 unpaired electron means 1 into 1 plus 2. That means root 3. Root 3 will approximately come as 1.73. And the answer to the nearest integer is going to be 2 Bohr magnetrons, right? Okay. There won't be 3. There will be 1 unpaired electron because this Cn is a strong field ligand. It will cause the pairing of electrons. See, it has 3d7 configuration, right? It has 3d7 configuration like this. 1, 2, 3, 4, 5, 6, 7. Now there will be pairing of electron. One of the electron will enter here. So there will be only 1 unpaired electron left, right? Yes? Simple? Right, people? Now, moving on to one more. The total number of unpaired electrons present in complex K3Cr oxalate thrice is. What is the answer of this one? What is the answer of this one, people? First of all, you should know what is the oxidation state of this chromium right here. Oxidation state of this chromium will be simply +3, right? Chromium shows the configuration of 3d5 4s1. 3d5 4s1. You need to take 3 electrons out, 1 from here and 2 from here. It becomes 3d3. So there are 3 unpaired electrons, right? 3 unpaired electrons because oxalate is a weak field ligand, right? Yes, a simpler one. A simpler question this is, correct? Absolutely. Okay, let's move on to a few more. The calculated magnetic moments for the species FeCl6 dinegative, COC2O4 trinegative and MnO4 dinegative. First of all, calculate the oxidation states. Iron shows +2 oxygen state right here. Cobalt shows +3 oxygen state right here. Manganese shows +6 oxygen state over here, right? Calculated magnetic moments, right? Calculated magnetic moments. Okay. So first of all, how many unpaired electrons are there with Mn plus 6? Mn plus 6. Manganese has got 3d5 4s1. So take 6 electrons out, it's going to be 3d1, there is 1 unpaired electron. So its magnetic moment is going to be under root of 1 into 1 plus 2, which is going to be 1.73 Bohr magnetrons. Right? It's going to be 1.73. Yes, the question is done. There is only one option which says it. Yeah? There is only one option which says it. Right, people? Option C. And remember at the same time, see, this is cobalt plus 3 oxygen state. Remember, whenever a ligand which will be having the oxygen donor, whenever the oxygen donor ligand, be it oxalate, be it water or anything, whenever the oxygen donor ligand is attached to CO tripositive, at that time this oxygen donor ligand will be acting like the strong field ligand. Take it. Normally this oxalate, it is a weak field ligand, right? But when it will be attached to CO tripositive, it will be a strong field ligand. It is going to cause pairing. It is going to cause pairing. Do remember this thing as well. Yeah? Perfect. So due to pairing, there will be no unpaired electron in CO tripositive. So magnetic moment is going to be 0, right? And in the first one, you can calculate magnetic moment as 4.9. It's a weak field ligand, right? There'll be 4 unpaired electrons. 4 unpaired electrons means under root of 4 into 4 plus 2, right? Which comes out to be 4.90. Okay, the hybridization and magnetic moment of MnCN6 4 negative and FeCN6 tri negative. What is going to be the answer of this question? Yes, Kush, I'll be doing that. What is going to be the answer of this one? Give it a try. Exactly, you can either use VBT or CFT, choice is all yours. Okay, let's check it out exactly. See, the first one, manganese has got the oxidation state of +2, right? If you look at the configuration of Mn dipositive, it's going to be 3d5, 4s0, correct? It's a strong field ligand. It's a strong field ligand, correct? So this is 3d5 configuration first of all. Let me make the 3d5 configuration. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 4 is containing 0 electrons. 4p containing 0 electrons and 4d containing 0 electrons as well. Right, people? Now, Cn, it is a strong field ligand. It is going to cause the pairing of electrons. So 1 electron will enter here, 1 electron will enter here, right? So finally, there will be 1 unpaired electron. And which kind of hybridization will be involved? It is going to be D to sp3 hybridization. D to sp3 and 1 unpaired electron paramagnetic, right? 1 unpaired electron paramagnetic. Yes, I'm talking about this MnCN6 4 negative, right, people? Now, and similarly, FeCN6 tri negative. FeCN6 tri negative. The question says the hybridization and magnetic moment of these species respectively are. These species, that means both the ones will be having same nature, right? Because as per the question. Yes. So both the ones will be having D to sp3 and paramagnetic. D to sp3 and paramagnetic. You can check it out. You can check the second one as well. You can check the second one as well. Right? Option B is the answer of this question. Okay. The pair having same magnetic moment. Same magnetic moment means you need to calculate the unpaired electrons, right? Wherever the unpaired electrons with the central metal ion will be same, that one is going to have, that pair is going to have same magnetic moment, correct? And you all know how do we do it? Can you let me know its answer in the charts? Can you let me know its answer in the charts? See guys, it's simple. If you look at the first case, chromium is in +2 oxygen state, iron over here is in +2 oxygen state, right? Both are weak field ligands. Both are weak field ligands, right? Will there be same unpaired electrons? No way, right? Chromium is basically 3d5 4s1. 3d5 4s1. Take 2 electrons out, it's going to be 3d4. So there'll be 4 unpaired electrons with this Cr dipositive. This Fe dipositive. Oh wait, just a second. Fe dipositive. This is 3d6 4s2. So there'll be again 4 unpaired electrons. So same unpaired electrons. So option 1 only. Option 1 only, right? Option 1 only. Same unpaired electrons means same magnetic moment, right? Okay. The complex showing a spin magnetic moment of 2.82. 2.82 means there should be 2 unpaired electrons, right? Then only spin magnetic moment will come out to be 2.82. Which of the following will contain 2 unpaired electrons? See, nickel with 0 oxygen state, nickel with +2 oxygen state, right? Over here. Okay, the question is done itself, right? It's option B. In the option B, nickel is in +2 oxygen state and attached to a weak field ligand. It will be containing 2 unpaired electrons. So its spin magnetic moment is going to be 2.82. It's a very simple and basic question, right? Few minutes back only we solved this question where Ni dipositive was having 2 unpaired electrons. Okay. The spin magnetic moment value for CrCO6. In case of Cr, the oxygen state right here is 0 because carbonyl is a neutral ligand, right? Chromium, 3d5 4s1, correct? So let me make the 3d5 configuration. 1, 2, 3, 4, 5, and this is 4s1, correct? This is 4p with 0 electrons. This is 4d with 0 electrons, and it's attached with the strong field ligand, so pairing will happen. One of the electron will go here, one of the electron will go here, one of the electron will go here. So there'll be no unpaired electron. If there is no unpaired electron, spin magnetic moment is going to be 0, right? Yes? Right, people? Spin magnetic moment is going to be 0. Simple. Let's move on to one more. Both NiCO4, NiCN4 dinegative are diamagnetic, okay? The hybridization of nickel in these complexes respectively are. Okay, right here nickel is having 0 oxygen state, over here nickel is having +2 oxygen state. Iron, cobalt, nickel, 3d8 4s2, 4p0, 4d0, right? So have a look, exactly this is 3d8 configuration. 1, 2, 3, 4, 5, 6, 7, 8. This is 3d8, this is 4s2. Right? Since it is attached with a strong field ligand, so pairing will happen. One of the electron will go here, one of the electron will go here. So it will be completely paired configuration. Okay, 4s will be containing 0 electrons, 4p will be containing 0, 4d will be containing 0 electrons, correct? Now the coordination number in this case is 4. So this central metal atom, it has to arrange 4 empty orbitals for hybridization, and those 4 empty orbitals are going to be 1s and 3p, so it's going to be sp3 hybridization and diamagnetic at the same time because there is no unpaired electron. Yes? And at the same time, if you look at Ni dipositive configuration, Ni dipositive is 3d8 configuration, right? Ni dipositive means 3d8 configuration. Ni dipositive simply means 3d8 configuration. This is 4s0, 4p0, 4d0. In case of 3d8 configuration, what is going to happen? See, again it's a strong field ligand, pairing will happen. So first of all, just write these 8 electrons, right? Now do the pairing. One of the electron will go here. It's going to be dsp2. So this one is sp3, this one is dsp2. sp3, dsp2. Option B is the one which is correct, right? Right, people? Okay? Absolutely. Moving on to one more. Among the following ions, which one has got the highest paramagnetism? You need to count the maximum number of unpaired electrons with the central metal atom or ion. Wherever the central metal atom or ion has got the maximum unpaired electrons, that is going to exhibit maximum paramagnetism, right? So I think this is something which you can do on your own, right? This is something which you can do on your own. In case of Fe dipositive, there are 4 unpaired electrons, which is maximum among all, so it is going to exhibit maximum paramagnetism, right? Okay? It's going to exhibit maximum paramagnetism, correct? Which of the following is the limitation of valence bond theory? It does not distinguish between weak and strong ligands. This is the drawback of the valence bond theory. It does not give quantitative interpretation of the magnetic data. Absolutely. It does not explain the color exhibited by coordination compounds. Absolutely. All of these. So all these are basically the limitations, the shortcomings of the valence bond theory. Right, people? Okay, among the ligands, NH3, ethylene diamine, Cn negative and CO, the correct order of the increasing field strength. This is something which you must know at least, right? Let me know its correct answer. What is going to be its correct answer? What is going to be its correct answer, people? It's an easy kill question again. Absolutely, perfectly correct you guys are. It's option A, right? This is the spectrochemical series which gives you the order of the ligand field strengths. Okay, CO is a strong field ligand followed by Cn, followed by An, followed by NH3, right? Okay, the correct order of intensity of color. The correct order of intensity of the color. How do we check the intensity of the color? How do we check the intensity of the color? Let me know. See guys, first of all, weak field ligands, do they cause more splitting or less splitting? They cause less splitting, right? Strong field ligands, what do? They cause more splitting. They cause more splitting. Wherever splitting will be less, there only transitions of electrons will be more, and wherever transitions of the electrons will be more, there only intensity of the color will be more, right? There only intensity of the color will be more. See, nickel over here is in +2 oxygen state, nickel over here is in +2 oxygen state, over here again it's in +2 oxygen state, right? Water is the ligand, Cl is the ligand, Cn is the ligand. So the ligand which is going to be the weak field ligand will try to show the maximum intensity of the colors, right? So what is going to be the order then? What is going to be the order? Few minutes back only I told you the order. In case of weak field ligands, splitting will be less, due to which transitions will be more, due to which intensity of color will be more. So absolutely option B is the one which is correct. Option B is the one, right? Because Cl negative is the weak field ligand followed by H2O followed by Cn, right? Okay, in which of the following complexes of cobalt the magnitude of delta naught will be highest? Delta naught, CFSE, in octahedral complexes. Delta naught, it depends on certain parameters. Out of them, the major two parameters are the field strength of the ligand, and the oxidation state of the central metal atom or ion, right? Okay. So first of all, over here the oxidation state of cobalt is +3, right here oxidation state of cobalt is +3, right here oxidation state of cobalt is +3, right here oxidation state of cobalt is +3. So I'm not going to decide on the basis of oxidation state. Let's decide on the basis of the field strength of the ligands, right? Okay. Which is the strongest field ligand among all? Is it going to be Cn negative? Is it going to be oxalate? It's going to be water? It's going to be NH3? It's going to be Cn negative, right? Absolutely A. So it is going to cause more CFSE in case of octahedral complexes, right? So option A must be the answer of this one. Absolutely. Okay, this is the last question of the coordination complexes, people. The crystal field splitting energy for octahedral complexes, tetrahedral complexes is related to, right? Let me know. Delta T is equal to 4/9 delta naught, if you remember. Yeah? Right? 4/9 delta naught. This is something which you all must be knowing, the relation between the two. Okay, let's go on. Let's start with something called as general organic chemistry first, right? Just give me a second. Okay, some people are asking for the break. I'll be giving the break after GOC, okay? First we'll complete GOC, then you guys can take the break, yeah? Or you want the break for 2 minutes? You can take the break for 2 minutes, that's completely fine. You can take the break for 2 minutes, no issues. I can sit for 2 minutes then. Yes, magnificent mess, same top-notch questions it's going to be. Yes, Gagana, it's enough, it's enough, it's enough. It's enough. If you're following top-notch series and this session, it's going to be more than sufficient for you. Guys, just wait for 2 minutes, we'll be starting, yeah? In 2 minutes, we'll be starting. Should we start now? Yeah? Should we start, people? Okay, so let's get going again with general organic chemistry then. Yeah? All right, so the first question which is on your screen. The hybridization of carbon atom in C single bond C, right? In C single bond C of this. What is going to be hybridization of either this carbon or this carbon? Wait, what happened to this? People, what is going to be a hybridization of these two carbon atoms? C single bond C. See, this one is forming 3 sigma bonds, so it's sp2. This one is forming 3 sigma bonds, sp2. It's a simpler basic question, right? sp2, sp2 is going to be answer. Select the molecule which has only 1 pi bond. Which of the molecule has only 1 pi bond? There are 2 pi bonds in case of ethyne, right? This is 1 pi bond and this is C double bond OH, 1 more pi bond, so 2 pi bonds. In this case, there's only 1 pi bond, so option C. Again, the simple question. The total number of sigma and pi bonds in naphthalene. Naphthalene means you need to join 2 benzene rings like this, right? This is naphthalene. So in naphthalene, you can count the total number of sigma and pi bonds. It's very simpler one, right, people? It's a very simpler one. So there will be total 19 sigma and 5 pi bonds in case of naphthalene, right? Just join these 2 benzene rings, right? This is something which we call as naphthalene, correct? Simple. Moving on to one more. 2-pentene contains. What does it contain? 2-pentene. First of all, you should know the structure of pentene. You should know the structure of 2-pentene. This is the structure of pent-2-ene in which the double bond is at carbon number 2, right? So you can calculate the total number of bonds. You can calculate the total sigma bonds, total pi bonds, right? You can do it on your own. It's a very simpler one again. Right? So finally, when you count it, you will be calculating the total number of sigma bonds as 14, total number of pi bonds as 1. Yeah? Okay. The number of primary, secondary and tertiary carbons in 3,4-dimethylheptane. First of all, you should know the structure of 3,4-dimethylheptane. Then only you can tell me how many 1 degree carbons, 2 degree, 3 degree carbons are there. Right? So first of all, if you look at this carbon, just on one side of it, the carbon chain is attached, so it's going to be 1 degree carbon. If you look at this carbon, on 2 sides of it, carbon is attached, so it's 2 degree. If you look at this carbon, on 3 sides of it, this one and this one, right? So it's going to be 3 degree carbon. This is again going to be 3 degree. This carbon, on both the sides, carbon chains are attached, right? Carbons are attached, so it's 2 degree. This is 2 degree, this is 1 degree. This is 1 degree, this is 1 degree, right? So this is a very basic question, and all of you must be knowing this. I'm sure about it. What is the IUPAC name of tertiary butyl alcohol? Right? This is the question. These are the simple questions, people, based on the nomenclature. If you look at the tertiary butyl alcohol, it's absolutely going to be 2-methyl propane 2-ol, right? Okay. I'm not going to solve these sort of questions. These are very, very simple, and you all must be knowing these, right? IUPAC name of this compound, right? Can you let me know what is the IUPAC name of this one? Let me know in the charts fast. These are easy questions. What is the IUPAC name of this one? Well, majority of the people are correct. It's absolutely going to be 3-methyl. Say 1, 2, 3. At this third you have got methyl group. It's absolutely going to be 3-methyl pentane, and at the carbon number 3 you have got alcohol group attached. It's going to be 3-ol. Correct? Yes, simpler one. IUPAC name of this. What is going to be IUPAC name of this compound? Right? First of all, you should select the longest carbon chain. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So 10 carbon atoms are there in the longest carbon chain, and at carbon number 2 there is a methyl group, and at carbon number 8 there is one more methyl group. So it is going to be 2,8 dimethyl, 2,8 dimethyl. At carbon number 4 there is a double bond, right? At carbon number 4 and carbon number 6 there is a double bond. So the name of the compound is going to be 2,8 dimethyl 4,6 decadiene. A simple question this is, right? Okay. All right, arrange the following species in the stability order. How do we see the stability of the charges on these species over here? See guys, first of all, this is the negative charge on nitrogen, negative charge on phosphorus, negative charge on arsenic, negative charge on antimony, right? Okay. Let's compare the stability of these charges on these elements. How do we do it? See, nitrogen, phosphorus, arsenic, antimony, they belong to the same group. And whenever you need to compare the stability of the charges on the elements which belong to the same group, we do that on the basis of volume charge density. Volume charge density is basically equal to charge present on the species divided by size of the species. As simple as that, right? Okay. Remember, the species which has got lesser volume charge density will have lesser potential energy. That means will have more stability. Do remember this. And this is the rule which I'll be using for the elements which belong to the same group. Whenever you need to compare the stability of the charges on the elements which belong to the same group, you will be comparing the stability on the basis of something called as volume charge density. Lesser the volume charge density, more the stability, in short, right? Check it out now. See, nitrogen having negative charge, phosphorus having negative charge, arsenic having negative charge, antimony having negative charge, right? This one is having maximum size. Maximum size means least volume charge density. Least volume charge density means more stability. So this is going to be the stability order, right? This is going to be the stability order, 4, 3, 2, 1. Yes? Now, if you look at the second case, oxygen carrying negative charge, sulfur carrying negative charge. Oxygen and sulfur, same group, volume charge density, right? I'll be comparing the stability of these two charges on the basis of volume charge density, correct? Sulfur has less volume charge density because of its more size, right? So this is going to be more stable, 2, 1, right? Right, people? Simple, correct? What about the third one? See, carbon carrying the positive charge, this is carbon carrying positive charge, this is carbon carrying positive charge, right? This is single bonded carbon, this is double bonded, this is triple bonded. The electronegativity of triple bonded carbon is definitely more due to more S character, right? Right, people? Electronegativity of a triple bonded carbon is definitely more, right? And remember, positive charge on more electronegative element is less stable. Positive charge on more electronegative element is less stable, whereas negative charge on more electronegative element is more stable, right? Positive charge on more electronegative element is less stable. So this is the order. This is the stability order, right, people? Similarly, this carbon is carrying the negative charge, this carbon carrying negative, this carbon carrying negative. This is single bonded carbon, double bonded carbon, triple bonded carbon. So this carbon is maximum electronegative, and negative charge is more stable on more electronegative element. So this is the stability order. Yeah, I'm sure this is clear. 3 to 1. Right, people? Absolutely. Moving on to a few more questions on the basis of same concept. Have a look on this one as well. See, this is the carbon carrying positive charge, nitrogen carrying positive, oxygen carrying positive, fluorine carrying positive. Remember, whenever you need to compare the stability of the charges on the elements which belong to the same period, at that time, electronegativity dominates over volume charge density. At that time, electronegativity dominates over volume charge density. Right? Remember, negative charge is more stable on more electronegative element. Right? Positive charge is more stable on less electronegative element. Right, people? Now have a look. Carbon, nitrogen, oxygen, fluorine, they belong to same period. I'll be discussing the stability of these charges on the basis of what? On the basis of electronegativity, right? Positive charge is more stable on less electronegative element. So this is the stability order. This is the stability order. What about the second one? Carbon carrying negative, nitrogen carrying negative, oxygen carrying negative, fluorine carrying negative. Carbon, nitrogen, oxygen, fluorine belong to the same period. Electronegativity, right? Negative charge is more stable on more electronegative element. This is the stability order. Sulfur with negative, chlorine with negative. Sulfur, chlorine, same period. Electronegativity dominates. Electronegativity dominates, right? Which one is more electronegative, sulfur or chlorine? Sulfur or chlorine, which one is more electronegative? Chlorine is more electronegative, so this was the order, right? Oxygen with negative, sulfur with negative, Se negative, Te. All these elements, they belong to the same group. Volume charge density dominates. More size, less volume charge density, more stability, right? This is the order. Right, people? Clear to everyone? Yeah? Absolutely. Okay, let's move on to a few more questions then. This is our 502nd slide. Yeah? Okay. Right? You can see the slide number, people. This is 502nd slide number. So till now we have completed some 501 slides. That's wonderful. That's great. Okay. Fine. See guys, these are cyclic species over here, right? These are cyclic species over here. Now, first of all, I need to compare the stability of these charges again, right? It's a 3-membered ring, this is the 4-membered ring, 5-membered ring, 6-membered ring, right? Okay. Remember, 3-membered ring will be under maximum strain, due to which this carbon is maximum electronegative among all these selected carbons because of more angle strain in the structure. Okay, and negative charge is more stable on more electronegative element. So what is going to be the stability of the charges? This is the stability of the charges, right? Positive charge is more stable on less electronegative element. This is going to be the order, right? Right, people? Yes? Moving on to a few more. Okay, arrange the following as per their acidic strength, right? As per their acidic strength. So first of all, if I'll be having an acid HX, let's assume I have got the acid HX. An acid donates H positive. We all must be knowing. After donating H positive, this HX gets converted to X negative. If this is the acid, after the loss of H positive, it gets converted to X negative. X negative is something which I call as conjugate base. It is basically the conjugate base of this particular acid. It is the conjugate base of the particular acid, right? It is the conjugate base. This X negative is the conjugate base of this HX. Now, stability of the conjugate base decides the acidic strength of this acid. More is the stability of the conjugate base, more is going to be the strength of the acid, right? Now see, I need to compare the acidic strength of these two species over here. Just make their conjugate bases first. Its conjugate base is going to be RO negative. Its conjugate base is going to be RS negative, right? After the removal of H positive, right? Now, oxygen carrying negative charge, sulfur carrying negative charge. Oxygen, sulfur, same group, volume charge density dominates. More size for sulfur, less volume charge density, more stability. So this is the stability order of the conjugate bases, and whatever is going to be the stability order of the conjugate bases, same is going to be the acidic strength order, right? Same is going to be the acidic strength order. Right, people? Clear? What about this one? Again, make their conjugate bases. Take H positive out. When you take H positive out, you get something as CH3 negative. Take H positive out, you get something as NH2 negative. Take H positive out, you get something as OH negative. Take H positive out, you get something as F negative. Right? These are the conjugate bases which I formed. C with negative, N with negative, O with negative, F with negative, right? All these elements, carbon, nitrogen, oxygen, fluorine, they belong to same period. And along the period, whenever we need to compare the stability of the charges, electronegativity dominates. Negative charge is more stable on more electronegative element, right? So this is the stability order of their conjugate bases, and whatever is the stability order of their conjugate bases, same is going to be the acidic strength of these acids. Yes? Simple. Correct? What about the next one? Just take H positive out, negative charge on this carbon. Take H positive out, negative charge on this carbon. Take H positive out, negative charge on this carbon, right? This is triple bonded carbon, which is more electronegative, and negative charge is more stable on more electronegative element, which makes this acid maximum acidic, right? Okay. Now people, take this H positive out, there's a carbon with a negative charge. Take the H positive out, there's a nitrogen with a negative charge. Okay. What is the hybridization of this carbon? This is sp. What is the hybridization of this nitrogen? This sp3. Remember, electronegativity of sp hybridized carbon is more than that of electronegativity of sp3 hybridized nitrogen, right? Which makes the conjugate base of first more stable, which makes the first acid more acidic, right? Do remember this thing as well. I'm sure it's clear. I'm sure it's clear, right? Okay, perfect. Okay, arrange the following according to their minus I power. Arrange the following according to their minus I power. It's a simpler one again. Minus I power, right? Let me have some water first, then we can do these questions. Okay. Arrange the following according to their minus I power. See, let's assume fluorine is attached with a carbon chain. Let's assume this oxygen is attached with a carbon chain. This nitrogen is attached with a carbon chain. Over here, fluorine is attached with a carbon chain. More electronegative. It will attract the sigma electron density maximum towards itself. So it is going to show maximum minus I power. Remember, minus I power of cationic group is always greater than the minus I power of the neutral group. Okay. Cn. This carbon sp hybridized, sp2 hybridized, sp3 hybridized. So this carbon is basically attached to the carbon chain. This carbon is attached to the carbon chain. This carbon is attached to the carbon chain, right? So this carbon, being more electronegative, will attract the sigma electron density maximum towards itself, due to which it is going to show maximum minus I power among all. Okay. What about this one? See, this bond is polar between carbon and oxygen, due to which oxygen will get delta negative, carbon will get delta positive. This again, nitrogen delta negative, carbon delta positive, right? Now we will see. Understand? See, oxygen being more electronegative, that means the magnitude of positive charge on this carbon will be absolutely greater than the magnitude of positive charge on this carbon, right? If magnitude of positive charge on this carbon is more, that means this carbon is comparatively more electron withdrawing than this carbon, right? Due to which it makes it more minus I showing, right people? Simple. Again, it's simpler one, right? Okay, let's move on to a few more. Arrange the following as per minus I power. Which one is going to have more minus I among the two? Let me know fast. Which one is going to show more minus I? Which one is going to have more minus I? People, it's simple, right? This is NF3 positive, this is NH3 positive, right? Absolutely the first one. Yeah? Absolutely the first one. Nitrogen carrying positive, phosphorus carrying positive, AS pair carrying positive, antimony carrying the positive, right? Yes. Positive charge on more electronegative element makes it more electronegative, which makes NH3 positive to show maximum minus I. Okay. OH2 positive, SH2 positive, SEH2 positive, TH2 positive. What about this one? Again, this is going to be the order, right? This is going to be the order. Nr3 positive and NH3 positive. Nr3 positive is going to show more minus I due to more steric hindrance, right? Due to more steric repulsions between the alkyl groups, which makes the bond angle to increase. And as the bond angle increases, electronegativity of the nitrogen increases, right? Which makes this nitrogen to be more electronegative than that of this nitrogen, correct? Due to which this nitrogen shows more sigma electron withdrawing power towards itself, which makes Nr3 positive to show more minus I power, right? I'm sure it's all clear to you, right people? This is one case which I want you guys to remember, right? Nr3 positive shows more minus I than that of NH3 positive, correct? Correct people? Okay, moving on to one more. Polarization of electrons in acrolein may be written as. What do you think about this one? Polarization of electrons in acrolein may be written as. What do you think about this one? Well, I think option D must be the answer, because CHO shows minus I power, due to which oxygen gets the delta negative, right? So option D must be the answer of this one. Yes? Okay, the increasing order of stability of the following free radicals. Stability of free radicals depends on hyperconjugation. More the hyperconjugation, right? More is going to be the stability, right? But people, see, this carbon has got 1 electron over here, this carbon has got 1 electron over here, this carbon has got 1 electron, this carbon has got 1 radical. See guys, this radical is in conjugation with 2 phenyl rings. This radical is in conjugation with 3 phenyl rings, right? So this radical and this radical, they can participate in the resonance. So these 2 radicals are resonance stabilized. Now among these 2, which one is more resonance stabilized? This one is more resonance stabilized. So this one is going to be maximum stable among all, followed by this one. So this one, then this one. Now after that, among these 2, you can check on the basis of hyperconjugation. There are some 9 alpha hydrogens, there are only 6 alpha hydrogens. More the alpha hydrogens, more the stability. So this one is more stable, followed by this. So option B is the one which is correct, right? Right, people? Yeah? Absolutely. Moving on to one more. Okay, arrange the following according to their stability order. Well, you can use either inductive effect or you can use the hyperconjugation. The choice is all yours. Over here, how many alpha hydrogens? 0 alpha hydrogens. How many alpha hydrogens for this carbocation? 3 alpha hydrogens. How many alpha hydrogens for this carbocation? 3 and 3, 6 alpha hydrogens. What about this one? 3, 3, 6, 3, 9. 9 alpha hydrogens. More the alpha hydrogens, more the hyperconjugating structures, more the dispersion of charge, more the stability. So what is going to be the stability order? This is the stability order, right? This is the stability order 4, 3, 2, 1. What about the second one, people? These are carbanions, right? See, this group is going to show plus I. Over here we have got 2 groups showing plus I. Over here we have got 3 groups showing plus I. More the plus I groups attached to the carbanion, less is going to be the stability. More the plus I groups attached with the carbanion, less is going to be the stability. So this is the stability order. Right, people? Clear to everyone? Perfecto. Moving on to one more. Okay. Arrange the following according to their stability order. Again, these are the carbocations. I need to arrange them on the basis of their stability order. Again, you are going to check the alpha hydrogens, right? This is the carbon carrying the positive charge. How many alpha hydrogens it has? See, this is the alpha carbon. So only 1 alpha hydrogen, I must say. So this carbocation is stabilized by 1 alpha hydrogen. This carbocation, it is stabilized by 1, 2, 3, 4, 5, 6, 7. 7 alpha hydrogens, right? These are all the hydrogens basically. These are all the alpha hydrogens. These are all the alpha hydrogens. What about this one? 1, 2, and 3. This carbocation is stabilized by only 3 alpha hydrogens. More the alpha hydrogen stabilizing the carbocation, more the stability of it, right? So what is going to be the stability order? It's going to be 2, 3, 1. 2, 3, 1. This is the stability of the carbocations. I'm sure it's clear. Right? What about the next one, people? NO2CNF. NO2CNF, right? Right? Electron withdrawing groups, they decrease the stability of the carbocation. They decrease the stability of carbocation. Now, which one is more electron withdrawing among all? NO2 is more electron withdrawing. So, if it is more electron withdrawing, it will destabilize this carbocation to the maximum. So, what is going to be the stability order? What is going to be the stability order? What is going to be the stability order then? It's very simple now, right? It's absolutely good. This one is going to be, this carbocation is going to be maximum stable, followed by this one, followed by this one, as simple as that. Right, people? I'm sure it's clear to everyone, yeah? Right? Okay, moving on to a few more questions. Arrange the following according to their acidic strengths. You need to arrange them on the basis of their acidic strength. How do we check the acidic strengths, first of all, of different acids? How do we check it? Simply, you are going to make the conjugate base. When you make the conjugate base, depending on the stability of the conjugate base, you can see which acid is stronger. As simple as that. Check it out. See guys, you can take this H positive out, there will be negative charge on this oxygen. Take this H positive out, negative charge on this oxygen, right? Yes, after taking the H positive out, there will be negative charge on this oxygen. After taking the H positive out, there will be negative charge on this oxygen, right? Now check it. Now check it, people. Now check it. See, fluorine is closer towards this negative charge as compared to this fluorine, right? So this fluorine, I'll say this fluorine or you can say it like this, negative charge on this oxygen, negative charge on this oxygen will be dispersed the maximum, right, due to the minus I power of this fluorine, which is more close towards this oxygen as compared to this fluorine, right? So conjugate base, this conjugate base, the first conjugate base is going to be more stable, so acidic strength is going to be this one. This is with the order of acidic strength, right? Okay, simple? Absolutely, people. Alright, if you look at this one, take the H positive out, negative charge on this oxygen, take the H positive out, negative charge on this oxygen, take the H positive out, negative charge on this oxygen, take the H positive out, negative charge on this oxygen, right? Now, as I told you, see, this is a three-membered ring, which is under more strain, which makes this carbon to be more electronegative as compared to this carbon, as compared to this carbon, as compared to this carbon, right? So where is going to be the negative charge more stable? I'll see negative charge is going to be more stable in this case, in the first case. So conjugate base is most stable in the first case. So first one is going to be more acidic, then the second one, then the third one, then the fourth one. This is the order, right? Absolutely. Perfect. Moving on to a few more. CHF3, CHCl3. What do I need to check? Arrange the following according to their acidic strengths. What you guys are going to do, again you are going to take H positive out. If you take H positive out, the conjugate base becomes CF3 with a negative charge. The conjugate base after taking H positive out, it's going to be CCl3 with a negative charge, right people? Okay, now check the stability of these conjugate bases. Check the stability of these conjugate bases and let me know. People, see, carbon is having negative charge right here, carbon is having negative charge right here. Fluorine does not have any empty orbitals, whereas chlorine has got empty d orbitals. Can I say over here in this case, there is a case of back bonding, there can be the possibility of back bonding. And back bonding in case of CCl3 in B negative makes it more stable conjugate base. So more the stability of the conjugate base, more is going to be the acidic strength. So this is the acidic strength, right? Absolutely due to the back bonding. Yes, exactly. Similarly, take this H positive out, negative charge on this carbon, take this H positive out, negative charge on this carbon, right? Now, in this case, there is the possibility of back bonding because sulfur contains empty d orbitals. Oxygen does not contain. So conjugate base of the first one is more stable. That means the first acid is going to be more acidic than that of second one, right? Perfect. Yes. Okay, moving on to a few more questions. Okay. Arrange the following according to their basic strength. We need to arrange the following according to their basic strength. Okay. Among first and second, see guys, this is sp3 hybridized nitrogen, right? Okay. Yeah. What about this one? This is 1, 2, 3. This is sp2 hybridized nitrogen. So which nitrogen has got more S character? This nitrogen has got more S character. More the S character, more the electronegativity. So this nitrogen is more electronegative. If this nitrogen is more electronegative, the availability of the lone pair, will be less in the second case, right? Because this nitrogen is more electronegative. Yeah. If the availability of the lone pair is less in the second case, that makes first one more basic than that of second one. Yeah. Right? As simple as that. Over here, this nitrogen has got the lone pair. Even this nitrogen has got the lone pair. So this is my basic site first of all. This is my basic site. Chlorine attached at the meta position, fluorine attached at the meta position. Which one shows more minus I? Fluorine shows more minus I. Fluorine is more electron withdrawing, right? Which makes the availability of lone pair on this nitrogen the least among the two. So this is the basic strength. This is the basic strength, right? Right, people? Simple again. Yeah? Correct? Okay. This is sp hybridized. This is sp2. This is sp3. More S character, more electronegative, less availability of lone pair, less basic strength. So this is the basic strength order. Right? You can let me know in the chat box if every single thing is clear till here. Right, guys? Just give me a second. Perfect. All right, let's move on then. Let's move on to a few more questions. Okay. Which of the following molecules will show resonance? Will show resonance. What do you think about this one, guys? Which of them will show resonance? See, no doubt, as you can see, this is pi, this is sigma, this is positive charge, right? So as per the common sense, it should show resonance, pi, sigma, positive charge. But this nitrogen, does it contain the empty orbital? It does not contain any empty orbital. For the conjugation to be there, it should be pi, sigma, and the vacant orbital, right? There is no vacant orbital with this nitrogen. So it is absolutely not going to show any sort of resonance. Yeah? What about the second one? What about the second one? This phosphorus, absolutely, it has got the empty vacant orbitals, right? So it is pi, sigma, vacant orbital. It is going to show resonance. This negative charge, it's not present in the p orbital. It's not present in the pure p orbital. It is present in the sp2 hybrid orbital, right? This negative charge is present on the plane. It is not present perpendicular to the plane. Even this positive charge, sp2 hybrid orbital. This radical, sp2 hybrid orbital. So neither this one, nor this one, nor this one are going to show resonance. There is only one molecule which is going to show resonance among all. Yes, I'm sure it's clear. Right, people? Absolutely. Moving on to a few more cases. All right. Which of the following molecules will show resonance? Will show resonance. All right. Let's check it out too. The first one, this is pi, this is sigma, this is positive charge. I mean, this p has got the vacant orbital over here, vacant p orbital. I mean, vacant d orbital it has, right? Okay. This is pi, sigma, vacant orbital. It's going to show resonance. This is pi, sigma, this sulfur, it has got the vacant orbital. Pi, sigma, vacant orbital, it's going to show resonance. In the next case, pi, sigma, this boron, it has got the vacant p orbital because its octet is not complete, right? Boron is attached to two hydrogen atoms. 1, 2, 3, 4, 5, 6. Only 6 electrons in its outermost shell. So there will be a vacant orbital, right? So pi, sigma, vacant orbital, conjugation. Yes, resonance. In this one, in the last one, will there be any resonance in the last one? What do you think? Will there be any resonance in the last one? What do you think? The octet of this boron is complete. It's carrying the negative charge, right? The octet of this boron is complete. Yes, there is no vacant orbital. If there is no vacant orbital, it's not going to show any sort of resonance. So among all these four, first three are going to show resonance and the last one is not going to show any sort of resonance, right? Yes, people? Okay. Give the correct order of the following resonating structures. You need to arrange them on the basis of stability order. First of all, how many sigma bonds? 1, 2, 3, 4. 4 sigma bonds. Right here, 4 sigma bonds. Right here, only 3 sigma bonds. Lesser the sigma bonds, lesser the stability. So 3 is going to be least stable among all. 3 is going to be least stable among all. Now in first and second, have a look. Nitrogen carrying the positive charge, nitrogen carrying the positive charge. Over here, nitrogen carrying the negative charge, carbon carrying the negative charge. Negative charge is more stable or more electronegative element, right? So first one is going to be maximum stable, followed by 2, followed by 3. This is the order. Yeah? Right, people? Perfecto. Moving on to a few more. Okay, give the correct stability order of the following resonating structures. First of all, I'll be counting the sigma bonds. Check it out. 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Right? More the sigma bonds, more the stabilities. 3 is more maximum stable. 3 is maximum stable among all. 3 is maximum stable. Now among first and second. First does not carry any charge. So first is going to be more stable than that of second. So 3, 1, 2 is going to be the stability order. 3, 1, 2 is going to be the stability order. Isn't it simple, people? Isn't it simple? What do you think about this one now? Yeah? Absolutely. Moving on to a few more. Okay, determine the order of stability of the following resonating structures. So you can solve it on your own, I believe. Yeah? First one does not carry any charge, so first one is maximum stable. Among this one and this one, less the charge separation, more the stability, right? Less the charge separation, more the stability. So 1, 2, 3 is going to be order. 1, 2, 3 is going to be the order. Yeah? Okay, which of the following has the shortest CCl bond length? CCl bond length. Okay, can I say in the first case, this is sigma, this is pi, this is sigma. Then in the NO2, there is again one more pi, okay? So in the first case, there is the extended conjugation, I must say among all. There is the extended conjugation. Due to the extended conjugation, due to the presence of this NO2, I must say double bond character between this carbon and Cl will be more the double bond character, less the bond length. So least bond length between carbon and chlorine will be there in the first case. In all the other cases, there is no extended conjugation. If there is no extended conjugation, there won't be any sort of extra double bond character. If there won't be any sort of extra double bond character, there won't be, nothing will happen to the bond length. Yes? Clear to everyone? I'm sure it's clear. Right, people? In the first case, due to the presence of NO2, this becomes the case of extended conjugation. Due to the extended conjugation, this single bond is going to get more double bond character. And if this single bond gets more double bond character, I must say this CCl bond length is going to be the least among all. Yeah? Right, people? I'm sure it's clear. Moving on to one more. The most unlikely representation of the resonating structures of para-nitrophenoxide ion. Okay, which of the following is the most unlikely representation of the para-nitrophenoxide ion? What do you think? What do you think about this one, people? Give it a try. It's again a simpler one. See, nitrogen cannot exceed its covalency beyond 4. We know it, right? If you look at this option, people, in this option, nitrogen is forming 2, 2, 4, 5 bonds. Have you ever seen nitrogen forming 5 bonds? No way, right? So option C is not going to be any sort of resonant structure among all. Yes? I'm sure it's clear. Okay, which among the following is more stable? Which among the following is more stable? Let me know its answer fast. Which of the following is more stable? See guys, over here, this is lone pair, this is sigma, this is pi, this is sigma, this is pi, right? Okay. Over here, this lone pair, it is simultaneously in conjugation with this pi bond as well as this pi bond, right? Yes. So, do we call this as extended conjugation or cross conjugation? We call this as cross conjugation. This is called as cross conjugation, if you remember. This is something which we call as linear conjugation, right? Extent of resonance in linear conjugation is more than that of extent of resonance in cross conjugation, which makes first one more stable than the second one. As simple as that, right? What about the next case? This pi bond is simultaneously in conjugation with this pi bond as well as this pi bond, right? So this is the case of cross conjugation. This is the case of cross conjugation. What about this one? Pi, sigma, pi, sigma, pi, sigma, right? Okay, this is again the linear conjugation. Extent of resonance in linear conjugation is more the resonance, more the stability. So this is the stability order, right? Simple again. Yeah? Absolutely. Moving on to one more then. Okay, among the following, okay, arrange the following in the stability order. I'm going to arrange the following in the stability order. Okay. Negative charge on this carbon, this. Okay. See guys, how do we solve this question? Remember, negative charge carrying capacity of one oxygen is greater than the negative charge carrying capacity of 10 carbon atoms. So you can compare the stability. Guys. Negative charge carrying capacity on one oxygen is far greater than the negative charge carrying capacity of carbon, right? So you can think on your own how much stable negative charge will be there on oxygen as compared to carbon. Yeah? Okay? Now see, in the first case, there can be resonance. Due to resonance, this negative charge can come here, right? In the second case, there can be resonance. Due to resonance, this negative charge can come here, right? In the next one, there can be resonance, and due to resonance, this negative charge can come over here on this nitrogen. In the next one, due to the resonance, negative charge can come on this oxygen as well, right? Similarly, this negative charge can come here. This negative charge will come here in the form of pi bond. This bond will break in this direction, so that there'll be negative charge over here, right? Then this negative charge will form a pi bond over here. There'll be negative charge at this para position, then again at ortho position, and so on. That's something which you all must know, right? Now guys, see. Now guys, understand. See, there is only one case in which negative charge is coming on two oxygen atoms. There's only one case in which negative charge is coming on two oxygen atoms, and we already know the negative charge carrying capacity of oxygen, right? Since the negative charge is coming on two oxygen atoms due to resonance, right? So I must say D must be the maximum stable among all, right? So D must be maximum stable among all, followed by, say, take the D aside. D is done, right? Now after D, this is having the oxygen, this one is having the oxygen. This oxygen is carrying negative charge, this oxygen is carrying negative charge. But apart from these negative charge carrying oxygen atoms, I'll say extent of resonance is more in this case, right? Extent of resonance is more in this case. So E is definitely going to be more stable, then comes your B. So take these two out. Now which all are left? This one and this one. See, negative charge is coming on nitrogen, which is absolutely more electronegative. So absolutely C is going to be more stable. Now among A and F, where will be the resonating structures more? In F, resonating structures are more, so F is going to be more stable, then at the end comes A. So this is the stability order, yeah? I'm sure it's clear to everyone. I'm sure it's clear to everyone, right? D, B, C, F, A is going to be the order. Correct, people? Okay, let's move on to a few more then. Alright, compare the acidic strength of hydrogens. You need to see which hydrogen is more acidic. Which hydrogen is more acidic, right? So what you are going to do? See guys, I'm given these 4 hydrogens. I need to see which hydrogen is more acidic among all. See what I'll be doing. Just take the H positive out, there'll be negative charge on this oxygen. Take this H positive out, negative charge on this sulfur. Take this H positive out, negative charge on this oxygen. Take this H positive out, negative charge on this nitrogen, right? Now this oxygen carrying the negative charge can show resonance, and this negative charge can come on this oxygen as well, right? So over here, 2 oxygens are carrying negative charge due to resonance, right? 2 oxygens are carrying negative charge. Yes, okay, right people? So can I say after the removal of H positive, the conjugate base which I have, that is more stable? So this H positive is going to be maximum acidic, because after its removal, the base I'm left with, that is more stable, right? So 4 is going to be maximum acidic, followed by 3, right? Followed by 3. Among this sulfur and oxygen, they see sulfur carrying negative, oxygen carrying negative. Do they belong to same period or same group? They belong to same group, right? And in the group, volume charge density dominates, right? Less volume charge density due to more size. Sulfur has got more size, less volume charge density, more stability, right? So negative charge on sulfur is more stable than that of negative charge on this oxygen over here. Yes, so this acid, this H positive is going to be more acidic than that of second. So third is going to be more acidic than that of second, right? Now among 2 and 1, oxygen carrying negative, nitrogen carrying negative. They belong to same period, electronegativity dominates. Negative charge is more stable on more electronegative element, right? So negative charge on this oxygen is going to be more stable. So this H positive is going to be more acidic. Absolutely, 2 is going to be more acidic than 1. So 4, 3, 2, 1 is the order. Yes, I'm sure it's clear. Right, people? Yeah? Perfect. Let's move on to more. Let's move on to more questions. Okay. What is the correct increasing order of bond lengths of bonds indicated as 1, 2, 3, 4? 1, 2, 3, 4. Right. Can you let me know its order, people? Can you let me know its order? See, fourth one is carrying the triple bond. Fourth one is carrying triple bond, so minimum bond length. Fourth one is going to have minimum bond length, right? Fourth one is going to have minimum bond length because of the presence of triple bond, right? Now 1 and 2. 1 is the double bond, 2 is the single bond. Double bond will be shorter, right? Okay, so I'll be giving preference to 1, then 2, then 3. So option D is the one which is correct among all. Yeah? Again a simple question. I'm sure it's clear. Right, people? So option D is the one which is going to be the correct one among all. Yeah? I'm sure it's clear. Let me move on directly to one more. Okay, this is one more question, guys. You can solve it on your own. It's a very simple one. Arrange the following in order of their mesomeric power. Basically, you are going to arrange them on the basis of their plus m power. You are going to arrange them on the basis of their plus m power, right? What is going to be the answer of this question? I'm waiting for your answers. You guys can let me know its answer. Remember, plus m power of n ionic groups. Plus m power of n ionic groups is always greater than the plus m power of neutral groups. Right? Do remember this thing. That means, see, this is an ionic group, this is the anionic group. These two are neutral groups. So plus m power of first and second is absolutely going to be more than that of plus m power of 3 and 4. Now among first and second, which one is going to have more plus M power? See, over here oxygen is carrying negative charge, over here nitrogen carrying negative charge, oxygen more electronegative. It's not going to, the lone pair over here is not going to be more available than that of this lone pair, right? Wherever the lone pair is more available for resonance, so you will say there only that group is showing plus M, more plus M. So 2 is going to show more plus M, followed by first one. Now among these three, again nitrogen, then comes the oxygen. 2, 1, 4, 3 is the order. 2, 1, 4, 3 is the order. I'm sure it's clear, right? Yes, people. So basically what happens in this case? See, this O negative, it's attached with the conjugated system. Let's say it's attached with the benzene. Conjugated system. This is attached with the conjugated system, which is benzene. This is attached with the conjugated system, which is benzene, right? Now see where the resonance can happen easily. There only plus M power of these is going to be more, right? Yes, the resonance can happen in case of second one easily, right? Because first thing, it is the anionic group. Second thing, this nitrogen is not more electronegative than of this oxygen. So availability of this lone pair for conjugation is more, for resonance is more. Yeah? Right, people? Surender, no effect. Okay, now what about this? What about the next one, people? See, let's assume this OH is attached with the conjugated system. This sulfur is attached with the perfect conjugate system. This SC is attached with the perfect conjugate system, right? Now, there are 2 lone pairs on this oxygen, there are 2 lone pairs on this sulfur, there are 2 lone pairs on this SC over here, right? Now, it can participate in the conjugation, it can participate in the resonance, this can participate in the resonance, right? Now, when the resonance will happen, there'll be 2p overlap basically between oxygen and the carbon of conjugate system. Over here, it's going to be 2p, 3p overlap. Over here, it's going to be 2p, 4p overlap, right? Most efficient overlap is 2p, 2p overlap, right? If most efficient overlap is 2p, 2p overlap, I'll say extent of resonance in this one is going to be more. The ease of resonance, the ease of conjugation is more in the first one, right? So plus M power of first one is more than second than that of 3, right? So 1, 2, 3 is going to be the order of this one. Yes? I'm sure it's clear. Yeah? Right, people? Let's move on to a few more. Okay. Arrange on the base of Kb. More the Kb, more the basic strength, right? More the Kb, more the basic strength. And remember, basic strength is directly proportional to plus effects. And plus N dominates over plus H, which dominates over plus I. This is something which you all must be knowing, right? See, the first one, this is something which everyone knows. This is guanidine, which is maximum basic, right? This is maximum basic. So I'm not going to compare this with anyone. This is maximum basic. Okay, this OH, it's going to show plus R, yeah, plus M, I can call it. Yes, this CH3, it's going to show plus I. Yes, this Cn, it's going to show minus M. See, this is the common group this is the site, this is the basic site which is common to everyone, right? That's why this is showing plus I, this is showing plus M, and this is showing minus M, right? Okay. Now, first one is maximum basic. That's something which I already know. Now, among second and third, which one is more? Second is going to be more, then comes your third, then comes your fourth. So this is going to be the order of basic strength. Yes? Right, people? I'm sure it's clear. Moving on to one more. Arrange the following on the base of Ka value. Remember, more the Ka value, more the acidic strength. Right? More the Ka value, more the acidic strength. And acidic strength of the acids is directly proportional to electron withdrawing groups. Right? Or I can say acidic strength of the acid is directly proportional to what? It is directly proportional to minus effects. And remember, minus M dominates over minus H, minus M, H dominates over minus I. Do remember this as well. Yes? See guys how it's done. First of all, select the common site. This is the common site. This is the reference OH. Now, this nitro attached at the para position, it's going to show minus M. It's going to show minus M, right? Cn attached at para position, minus M. Fluorine attached at the para position, right? Yes, fluorine is going to operate. It's going to operate minus I plus M. But you all must be knowing, inductive effect vanishes after third carbon, right? Okay. Similarly, this chlorine, it can operate minus I plus M, right? Now we will first of all see minus M, minus M. Which one shows more minus M? Nitro shows more minus M. So I'll be giving priority to the first one, then comes the second, because these two are showing minus M, right? Remember, in case of parafluorophenol and parachlorophenol, this chlorine, it shows more electron withdrawing nature than that of this fluorine. Remember, in case of parafluorophenol and parachlorophenol, this chlorine shows more electron withdrawing nature, right, as compared to fluorine. So I'll give priority to 4, then I'll be giving priority to 3. So 1, 2, 4, 3 is going to be the order. Yeah? Do remember this thing as well. Right, people? Okay. Moving on to a few more questions. Identify the molecules, whether they are aromatic, anti-aromatic, non-aromatic. Okay, first thing. For the molecule to be aromatic, it must be cyclic. There should be complete cyclic conjugation. Every atom should be sp2, or I can say it should be planar structure. It should be a planar structure, right? It should follow Huckel's rule. 4n plus 2 pi electrons should be involved in the complete cyclic conjugation. Then only we say the molecule is aromatic, right? And for the molecule to be anti-aromatic, what are the conditions? It should be cyclic, complete cyclic conjugation, planar, but there should be 4n pi electrons involved in the complete cyclic conjugation. If the molecule is neither aromatic nor anti-aromatic, then it's going to be non-aromatic. And remember, stability of aromatic molecule is always greater than the stability of non-aromatic molecule, which is always greater than the stability of anti-aromatic molecule. Do remember this thing as well, yeah? Now the question is done and dusted. Have a look. See guys, every carbon over here is sp2. There are 2, 2, 4. There are 4 pi electrons in complete cyclic conjugation. Over here, 2, 4, 6. 6 pi electrons involved in the complete cyclic conjugation. This one is sp3, so it is going to be non-planar. Non-planar means non-aromatic, right? This one is sp3, non-planar, non-aromatic, right? Leave the last case aside, okay? See guys, 4 pi electrons means anti-aromatic. 6 pi electrons, aromatic. This one, non-aromatic. This one, non-aromatic. What about the next one? See guys, next one I can make like this as well. Right? It's one more resonating form of this one. See guys, this molecule is aromatic. This molecule is anti-aromatic, right? See, the first one, this circle, this ring is aromatic. This one is anti-aromatic. Aromatic plus anti-aromatic, it makes the overall molecule as anti-aromatic. So this molecule is anti-aromatic, right? Yes? Right, people? Right, yes? Yeah, perfecto. Okay, what about these? See, first of all, if I'll ask you what is the hybridization of this sulfur, see, one of the lone pair is participating in the resonance, right? So I'm not going to count this lone pair for hybridization. Hybridization of this sulfur is sp2. Every atom is sp2. So 2, 4, 6. 6 pi electrons involved in complete cyclic conjugation. What about this one? 2, 4, 6. This is 8. This is 10. 10 pi electrons involved in the complete cyclic conjugation. What about this one? This is sp3, non-planar, so non-aromatic. This is sp3, non-planar, non-aromatic, right? So 6 pi electrons means aromatic. 10 pi electrons means aromatic. This one is non-aromatic. Even this one is non-aromatic, right? Done and dusted. Right, people? You can let me know in the chat box if it's clear. You can let me know in the chat box if it is clear till now. Yeah? Okay. How many of these compounds are aromatic? Again, the similar sort of question. See, this is sp2, this is sp2, this is sp2, only 2 pi electrons. 2, 4, 4 pi electrons, right? 4 pi electrons, correct? Yeah? What about this one? 2, 4, 6, 6 pi electrons. 2, 4, 6, 6 pi electrons, correct? What about this one? 2, 4, 6, 6 pi electrons, 2, 4, 4 pi electrons, 2 pi electrons, right? Now check it out. 2 pi means aromatic. This one anti-aromatic. This one aromatic. This one aromatic. This one aromatic. This one anti-aromatic. This one aromatic, right? Done? So how many of them are aromatic? 1, 2, 3, 4, 5. There are 5 species among all which are aromatic, right? I'm sure it's clear. I'm sure this is clear to everyone, right, people? Yeah? Okay, moving on to a few more. Okay, arrange the following as per their stability order. This question we have done many a times now. These are all the carbocations. Stability of the carbocations depends on the hyperconjugating structures, and hyperconjugating structures depends on the alpha hydrogens. So over here we do not have any alpha hydrogens stabilizing this carbocation. There are 3 alpha hydrogens stabilizing this carbocation, and these are 3 alpha hydrogens. There are 2 alpha hydrogens stabilizing this carbocation. More the alpha hydrogens stabilizing the carbocation, more is the stability of the carbocation. So 2 followed by 3 followed by 1. This is the stability order, right? Yes, people? Right? Absolutely. Okay, what about this one? This is the carbocation, this is the alpha carbon, and there is only 1 hydrogen attached. So this carbocation is stabilized by only 1 alpha hydrogen. What about this carbocation? This alpha carbon with which 2 hydrogens are attached, 1 hydrogen. So this carbocation is stabilized by 3 alpha hydrogens. This carbocation is stabilized by 1, 2, 3, 4, 5, 6, 7. 7 alpha hydrogens. More the alpha hydrogen stabilizing the carbocation, more the stability. So 3 is going to be maximum stable, followed by 2, followed by 1, right? See, 3 to 1 is going to be the order. 3 to 1 is going to be the order. Right, people? I think we did this question already. This question is repeated, I believe. Yeah? Okay. Arrange the following as per their KB order. Remember, more the KB, more is going to be the basic strength. More is going to be the basic strength. And remember, basic strength of the base is directly proportional to plus effects. And plus M dominates over plus H dominates over plus I. That's something which you all must be knowing, right? Right, people? Yes? Now check. See, select the common site, select the reference. I've selected my reference, right? This CH3 is attached at the para position. It's going to show plus H, plus hyperconjugation. CCl3 minus hyperconjugation, minus H. CH3 attached at the meta position. It's not going to show hyperconjugation, it's going to show plus inductive effect, right? This CCl3, it's going to show minus inductive effect, right? Now arrange them. Plus H dominates over everyone. So first one is maximum basic, followed by third, right? Followed by third, yes, followed by fourth, followed by second. So 1, 3, 4, 2 is going to be the order. Basic strength order. I'm sure it's clear. Right, people? I'm sure it's clear. Yeah? Clear to everyone? Okay, let's move on then. Let's move on to a few more questions. Alright, arrange the following according to their Ka order. Acidic strength order, people. Acidic strength. More the Ka, more the acidic strength, right? More the Ka value, more is the acidic strength. This is something all you must be knowing, correct? Now, let me tell you, acidic strength is directly proportional to minus effects. Remember, in case of minus effects, minus M dominates over minus H dominates over minus I, right? This is something which you are going to take in consideration. First of all, reference. This is my reference. I'm selecting the common site everywhere, right? This CH3, it's present at the para position, so it's going to show plus H effect. This is going to show, this CH3 is attached at the meta position, so plus I. It's going to operate plus I. This is going to operate minus H. This is going to operate minus H. This is going to operate minus I. Correct? Now, people, is there anyone operating plus M? No one is operating plus M or minus M, right? I told you acidic strength is directly proportional to minus effects. Since no one is operating minus M, give the priority to minus H. So which all are operating minus H? This one and this one. And remember, minus H power of CBr3 is more than that of minus H power of CCl3. So 4 is going to be more basic than that of third. 4 is going to be more basic than that of third. Then I'll be giving preference to fifth one. Then I'll be giving preference to second one. Then I'll be giving preference to first one. This is the order. Right? First one is the least because it's showing plus H. Right? Plus H decreases the acidic strength. Plus effects, they decrease the acidic strength. Right? We know it. Correct, people? Okay, moving on to a few more. Compare the stability of the following carbocations. Okay, stability of the following carbocations, right. So first of all, is the first molecule, is it aromatic, anti-aromatic or non-aromatic? See, this is sp3, non-planar, so non-aromatic. 2, 4, 4 pi electrons, anti-aromatic. Right? This one, oxygen is having 2 lone pairs, out of which one will participate in the conjugation. 2, 4, 6. 6 pi electrons involved in the conjugation. So this one is aromatic, this one is anti-aromatic, this one is non-aromatic. And we know stability of aromatic compound is maximum, followed by non-aromatic, followed by anti-aromatic. Right? Now arrange it. So it's going to be 3, followed by 1, followed by 2. So 3, 1, 2 is the order. 3, 1, 2 is the order, right? Yes, Santosh, this is the streaming going from last 5 or 6 hours. 6 hours or 5 hours? It's been 6.5 hours now. Wow, nice. Okay, let's move on to a few more. Let's take a few more questions. Okay. CH3CH2OH and CH3OCH3. This is very common question, very simple. Let me know. Are these the example of chain, functional, position or meta? These are the examples of functional isomers, right? You have got OH and OCH3 over here, right? Right, people? These are functional isomers, nothing to do with this. Okay. Identify the following among them as chain and position isomers. See, there's a rule to check that. That's something which we call as AB rule or CS rule, whatever you can call it. CS. C stands for number of carbon atoms. Number of carbon atoms present in the parent chain. Present in the parent chain. S is basically number of substituents. Number of substituents starting with carbon. Starting with carbon. Number of substituents starting with carbon, right? Remember, for two molecules, if the value of CS comes out to be same, two molecules having the same value of CS, they are going to be position isomers. Two molecules having different value of CS will be chain isomers, right? Now, let's get the numbering. Let's call this as carbon number, okay, wait. Let's call this as carbon number 1, 2, 3, 4, 5, 6, 7, 8. So how many carbon atoms are there in parent chain? There are 8 carbon atoms in parent chain. So C value is 8. Is there any substituent? There is no substituent starting with carbon. So CS value is 80 in this case, right? Now start the numbering over here as well. 1, 2, 3, 4, 5, 6, 7, 8, right? So number of atoms in the parent chain, 8. Number of carbon atoms in the parent chain, 8. No substituent. So CS value is 80. When the CS value for two molecules comes out to be same, they are going to be position isomers. So first two are position isomers, right? Simple. First two are position isomers. Yes? Right? Now, what about the second one? 1, 2, 3. 3 atoms in the parent chain, and there are 3 substituents starting with the carbon, so CS value is 33. What about this one? 1, 2, 3, 4. So 42 is the CS value. CS value is coming out very different. So these two are chain isomers. These two are chain isomers. I'm sure you got it. Yeah? What about this one? What about this one? Just a second, people. What happened to this? Okay. All right. Give the numbering first of all. 1, 2, 3, 4, 5, 6. There are 6 carbon atoms in the parent chain. How many substituents? 1 substituent starting with carbon, so CS value is 61. Similarly, 1, 2, 3, 4, 5, 6. CS value is 61, right? CS value is 61, correct? Chain or position? Chain or position? CS value is same, right? CS value is same. These are going to be position isomers, right, people? What about this case? What about this case? 1, 2, 3, 4, 5, 6, 7, 8. So number of carbon atoms in the parent chain 8. 2 substituents starting with carbon, so 82 is the CS value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 carbon atoms in the parent chain, no substituent, 100. CS value is different, so these are chain isomers. Right? These are chain isomers. I'm sure it's clear. Okay, what about this one? Draw the tautomers of the following. Okay, this is the C double bond O. This is the alpha carbon. It must be sp3 hybridized, then only I can draw its tautomer. So first one is not going to show any sort of tautomerism, right? Okay, this CH3 I'm going to write as CH2 single bond H, right? CH2 single bond H. So this is my reference, C double bond O. This is alpha carbon and this is sp3. It is going to exhibit tautomerism, right? It's going to exhibit tautomerism, correct? What you are going to do is, you are going to take this bond over here, break this bond in this direction and attach this hydrogen with the oxygen. So you get something as CH2, double bond C, single bond OH, and this is H. This is the enol form of this keto form, right? This is basically keto enol form, right? Yeah? Right, people? Yes. Okay, what about the next one? This is the reference. This is alpha carbon, but this sp2, no tautomerism, right? See, this is my reference, C double bond O. This one is sp3. You can take hydrogen out from here. So what is going to be the tautomer over here? It's C with oxygen. It's going to be a hydrogen. This is double bond. Then there is that ring like this. Okay, so these are the tautomers of each other. Yeah? Right, people? I'm sure it's clear. Moving on to one more. Which of the following compounds do not undergo enolization? First one will undergo enolization. This is C double bond O, this is alpha carbon, this is sp3. You can take one of the hydrogen out, you can put a double bond over here and attach one hydrogen with this oxygen. So this one will undergo enolization. Even this one will go. This is sp3 carbon containing one hydrogen, right? You can take the hydrogen out, put a double bond over here, break this bond in this way, put one hydrogen with this oxygen, you'll be getting its type tautomer. In this case, even there are two hydrogens attached with this carbon over here. If I'll represent one hydrogen, take this hydrogen out as H positive. If you take hydrogen out as H positive, there'll be a negative charge over here. There'll be a negative charge over here. Now this negative charge can participate in the resonance. This negative charge can come to ortho position. This can come over here. The negative charge finally reaches at oxygen. So this O negative finally takes H positive from the medium. So it becomes OH. So finally, what kind of structure do you get? What kind of structure do you get? You get something like this. This is this, this is this, this is something like this, you get OH, right? This is something which we call as spaced tautomerism. In option C, this is something which we call as spaced tautomerism, if you remember, right? In this one, this is sp2. See, this is the carbonyl group, this is the carbonyl group, right? This is sp2, this is sp2, this is sp2, this is sp2. So it's not going to undergo any sort of enolization at all, right? I'm sure it's clear. Right, people? Okay. All right, draw the most stable and least stable forms of the following, right? Draw the most stable and the least stable forms of the following. Okay, I'm looking at this molecule along this carbon, alpha, beta. Okay, if you look at this molecule along this carbon, I mean, in this direction, you can see only this carbon won't be visible to you. If I look at this molecule along this way, I can only see this carbon I cannot see. The carbon which I can see, that's something which I'm representing by a dot. This carbon I can see, I'm representing this by a dot. With this carbon, you have got chlorine attached and two hydrogens. I'm going to place this chlorine and hydrogens at around 120 degree apart. At around, I'm saying, okay? Right? Now this carbon is something which you cannot see. That carbon which you cannot see, that is something which I'm representing by a circle, right? With this carbon, you have got chlorine attached and two hydrogens attached. For example, this is chlorine, this is hydrogen, correct? Right? Which form is this? See guys, what is the dihedral angle over there? It is 60 degree. So is it going to be staggered? Absolutely, it's going to be staggered. Right? Absolutely, it's going to be staggered. Yes. And it's going to be the maximum stable. It is the anti-form, right? It is the anti-form. Two bulky groups are present on the opposite side. Right? It's going to be the maximum stable. And which one is the least stable one? If you rotate this circle 180 degree, what do I get? What do I get? I get eclipsed form, right? Yes? I get eclipsed form. I get fully eclipsed basically, which is highly unstable, right? So this is the most stable form. And what is its, see, if I rotate this circle at an angle of 180 degree, this is the circle which I'm rotating at an angle of 180 degree. So this chlorine will come here. This chlorine will come here. This hydrogen will come here. This hydrogen will come here, right? I've done nothing with the carbon which I can see, which I'm representing by this, okay? With this carbon, this is chlorine, right? This is hydrogen, correct? So this is basically fully eclipsed, right? The dihedral angle is 0 degree, it's fully eclipsed, which is very, very stable. So this is least stable form, this is most stable form, right? Perfect. Yes, people, I'm sure it's clear. Okay, one more we have. Okay, I need to form the most stable and least stable form along this alpha and beta carbon. Okay, let me look at this molecule in this way from alpha to beta. I can see only this carbon, that carbon which I can see, I'm representing that by a dot. With this carbon, you have got phenyl attached, hydrogen attached, and CH3 attached. So for example, this is pH, right? Place the CH3 and hydrogen at approximately 120 degree apart, yeah? Now, this is the carbon which you cannot see, that carbon which you cannot see, represent that by a circle, right? With this carbon, you have got 2 hydrogens and 1 phenyl. This is 1 pH, and these are 2 hydrogens, right? Over here, you can see the dihedral angle is 60 degrees, so it is staggered, and the bulky groups are on opposite sides. So it is basically the NT form, which is the most stable, yes? Which is the most stable? I'm sure it's clear. Right, people? Yeah? It is the most stable. If you want to draw the least stable form, just rotate this circle, for example, or rotate the carbon in the middle, which I'm representing by dot. Rotate any one 180 degree apart, you'll be getting the fully eclipsed form, and that fully eclipsed form is going to be minimum stable, right? Yes, people? I'm sure it's clear. Yeah, this is the staggered NT form, this is the fully eclipsed form, right? In which the bulky groups are on one side. Okay, what about this one? Draw the most stable form by using Gauge effect, right? Absolutely, you're going to use Gauge effect over here. See, I'm going to make the most stable form, right, along this alpha and beta position, right? So first of all, let me look at this molecule in this way. So I can see only nitrogen. So nitrogen is there, right? With this nitrogen, there is a lone pair. There are 2 hydrogens. For example, this is the lone pair, and these are 2 hydrogens placed at around 120 degree apart, right? Now people, this carbon is something which you cannot see. That carbon which you cannot see, you will be representing that by a circle, right? With this carbon, you have got 2 hydrogens and 1 CH3, right? With this carbon, which you cannot see, there is 1 bulky group. And remember, as per Gauge effect, bulky group you are going to place at the Gauge position. This is the Gauge position with respect to lone pair, right? There are 2 hydrogens as well. This 1 hydrogen, this 1 more hydrogen. This is the Gauge form, which is the most stable form of this molecule, right, people? Yes. Yeah? No, Satvik, this is not deleted. Who told this? Okay. We'll complete GOC, then we'll take a break. We'll take a break for 20 minutes, right? But after completing GOC. Okay? Now we have to draw this form. Okay? Now let me look at this molecule. This is my line of sight. This is my line of sight. Okay? I can see oxygen. This is oxygen. This is not circle, this is oxygen, right? With those oxygen, you have got 2 lone pairs attached, right? Let's say this is 1 lone pair. 1 more lone pair is over here. And we have got 1 CH3 group. This is 1 CH3. Correct? This carbon you cannot see. So I'll be representing this carbon by a circle. So this is the circle, right? With this circle, you have got 2 hydrogens attached, right? Now, 2 hydrogens and 1 bulky group. Bulky group I'm going to place at the Gauge position. Now this is the Gauge position, this is the Gauge position, right? But over here, if I place the bulky group at this Gauge position, repulsions will be minimized, right? So you are going to place hydrogen over here, you are going to place hydrogen over here. So this is going to be the most stable form. This is going to be the most stable form. This is going to be the most stable form. Yeah? Okay, which of the following is the most stable conformation of N-butane? N-butane most stable conformation. N-butane most stable conformation. I think this one. Dihedral angle over here is mentioned as 60 degree, right? And at the same time, it is the NT form. Yeah? Bulky groups are placed at 180 degree apart. You can say at the opposite ends. So C is going to be most stable, right? Yes, people? So C is going to be more stable. Now, which of the following can show geometrical isomerism? Which of the following can show geometrical isomerism? Now, first of all, for the molecule to show geometric isomerism, few conditions are there which must be satisfied. What are those conditions? If you select two centers in a molecule, let's say these are the two centers which I'm selecting in the molecule, right? First condition, there should be a restricted rotation between these two centers, right? Restricted rotation between these two centers. I mean, this bond should not rotate at all. Point number one. Point number two, these four terminal bonds, they should be either present on the same plane, or the plane containing these two bonds and the plane containing these two bonds, those two planes should be parallel, right? And at the same time, with this center, two different groups should be attached, and with this center, two different groups should be attached, right? Then only we say the molecule shows the geometrical isomerism, right, people? These are the three conditions which a molecule must follow, then only it can show the geometrical isomerism, right? Okay. For example, I'm selecting these two centers. You have got two hydrogens attached with this one. You have got these two hydrogens attached with this one. No doubt between these two centers, rotation is restricted. Otherwise, the ring will break, right? But two same groups are attached, so no geometrical isomerism. What about this one? If you select this center, restriction is rotated. Otherwise, the ring will break. This is hydrogen. This is hydrogen. Two different groups attached. Absolutely, it's going to show geometrical isomerism. What about this one? What about this one, people? Select these two centers, right? One hydrogen, there is one hydrogen as well. Okay, one different group, it is going to show. What about this one? This is hydrogen. For example, these are two hydrogens. I've selected these two centers, right? It's not going to show because two same hydrogens are attached with the same center, right? See, this nitrogen has a lone pair. This nitrogen has a lone pair as well, right? This carbon has got the hydrogen attached. So, two different groups, I'm considering the lone pair as the group, and restriction is already rotated, so it's going to show geometrical isomerism. This is showing this is hydrogen and methyl with this carbon, hydrogen and ethyl with this carbon, two different groups with the same center, absolutely it will show. Right? If you select this one and this one, these two centers, rotation is definitely restricted, but two same groups with the same carbon, no way, right? What about this one? Absolutely it's going to show, yeah? Right? Right, people? I'm sure it is clear to everyone. Yeah? Perfect. So how many of them will show GI? This one, and the last one, right? They are going to show GI. I'm sure it's clear. So with this, your geometrical isomerism, your general organic chemistry is over. Now, we'll be starting the hydrocarbons, but hydrocarbons will be starting after the break. What is the time now? It is 3:49. I'll see you all again at, it's a tea break for you, yeah? It's a tea break. What time you guys are going to be back? 5:10? Okay. Tea break till 5:10. I'll see you all again at sharp 5:10, okay? Perfect? Right? So I want every one of you to join back at 5:10. Till then, you guys carry on. Okay? Sorry, it's not, wait. It's not 5:10, it's 4:10. Oh, sorry. Right? It's 4:10. कुछ लंबी ब्रेक दे दी थी मैंने कुछ लंबी ब्रेक थी. It's 4:10. Guys, am I audible again? Am I audible? Just let me know in the chats. Yeah? Okay, just a second. All right, so let's continue then. Yeah? Yes, I'm done with my tea. Are you guys done with your tea, snacks, whatever? Perfect. All right, so let's get going now with the hydrocarbons, yeah? After hydrocarbons, we'll be having the haloalkanes arenes, right? Okay, let's get going then with the first question from the chapter hydrocarbons. Which catalyst is used to prepare alkanes from unsaturated hydrocarbons? This is something which you all must be knowing, right? Which catalyst is used to prepare alkanes from the unsaturated hydrocarbons? It's absolutely going to be option A, yes? Okay, from unsaturated hydrocarbons to alkanes, which catalyst do we need? It is absolutely going to be option A, right? Okay, so this is the unsaturated this is the alkene first of all. I'm doing its hydrogenation in presence of Raney nickel, platinum or palladium. What do we get? We get alkane as the product, right? This is something which you all must be knowing, correct? X and Y respectively are, first of all, alkyne will get converted into alkene, and then alkene will get converted into alkane. So what is going to be answer to the question? First alkene will get formed, then alkane will get formed. Alkene and alkane are going to be your X and Y in this case. So option C is the one which is correct answer of this question, right people? Okay, as you can see, this was your alkyne, right? Now break one of the pi bond. In place of the pi bond, put 2 hydrogens. In place of one more pi bond, put 2 more hydrogens, and finally you get alkane as the product, right? Okay, for the conversion of alkane to alkene, if we use ordinary nickel, then the reaction occurs at which temperature? For the conversion of alkane to alkene, if we use ordinary nickel, then the reaction will definitely occur at 523 to 573 Kelvin. This is something which you all must be remembering, right? From alkene to alkene, if we are using ordinary nickel in place of the Raney nickel, we have to give the temperature between 523 to 573 Kelvin, right? The hydrogenation of the unsaturated hydrocarbon using ordinary nickel at the temperature of about 523 to 573 Kelvin is known as, what do we call this reaction as? This reaction is called as Sabatier-Sanders reaction. Yes, the reaction which I showed you before. This reaction. From alkene to alkane in presence of ordinary nickel, keeping the temperature 523 to 573, this reaction particularly is called as Sabatier-Sanders reaction. Okay, all of you must be knowing this as well. One more, syn addition of cis alkane leads to the formation of it leads to the formation of, does it form enantiomers? I don't think so. Does it form mesocompounds? Yes, it forms the mesocompounds, right? So mesocompounds we get when we do the syn addition of cis alkene in presence of nickel, platinum, right? Yes? Okay. So these are the mesocompounds basically which we get from cis alkene. When we do its hydrogenation in presence of nickel, it follows the syn addition, correct? CSM, cis, syn, meso. Exactly, Karthik. Syn addition of transalkene in presence of nickel, platinum leads to the formation of, what is going to be answer of this one? Is it going to be again mesocompounds or enantiomers? Is it again going to be mesocompounds or enantiomers? Now it's going to be enantiomers, right? Syn addition of transalkene in presence of nickel, platinum, it leads to the formation of enantiomers, right? Okay, and finally you get the reciproc mixture. Okay, you get the enantiomers in the equimolar proportion. Okay, the product in the following reaction. What is going to be the product in the following reaction? See guys, I'm using one equivalent of hydrogen. I'm using one equivalent of hydrogen in presence of nickel, providing some heat, right? Right, people? Let me know the answer of this question. First of all, either you are going to break this pi bond or you are going to break this pi bond. Now, which pi bond you are going to break? Remember, stability is inversely proportional to reactivity, as you all must be knowing. Yes. So that pi bond which will be more stable, that is going to be least reactive. So first of all, I need to compare the stability of these pi bonds. So this pi bond, it is stabilized by, these are 3 alpha hydrogens over here, these are 3 alpha hydrogens, these are 2 alpha hydrogens. So this pi bond is stabilized by 3, 3, 6 to 8 alpha hydrogens. And this pi bond, it is stabilized by only 2 alpha hydrogens. Right? So this pi bond is least stable. Right? This pi bond comparatively is less stable. So I'm going to break this pi bond. Which one? I'm going to break this pi bond, and in place of this pi bond, I'm going to attach 2 hydrogens. So the product is going to be option A. Yeah? Product is going to be option A. Perfect. When did I start the session? I started the session at 9 a.m. in the morning, I think. Yeah? Okay, let's move on then. Let's move on, people. This is one more question. The product in the following reaction. What is going to be the product in the following reaction? Either you are going to break this pi bond or this pi bond. Let me tell you, triple bond is more reactive than that of double bond. Yes. Yes, triple bond is more reactive. So I'm going to break this bond. I'm going to break one of the pi bond, and in place of this pi bond, I'm going to place 1 hydrogen on this carbon, 1 hydrogen at this carbon. So I get CH2 double bond CH, single bond CH, double bond CH2. So what is the product? What is going to be my product, people? It's absolutely going to be option C as the product, right? Triple bonds are more reactive than the double bonds, so hydrogenation occurs at the triple bonded carbons. Yes? Perfect. Okay. The Lindlar's catalyst is, which one of the following is the Lindlar's catalyst? Which one of the following is the Lindlar's catalyst? Option B, which is palladium CaCO3, it is the example of the Lindlar's catalyst, right? Option B is the answer of the question. Okay, Rosenmund's catalyst, it's going to be palladium BaSO4, this is the Rosenmund's catalyst, right? Yes, this is the Rosenmund's catalyst. I'm sure you all must be knowing this. Yes, people? Okay, moving on to one more. The product in the following reaction. In the following reaction, what is going to be the product? We are using alkyne. We are doing its hydrogenation in presence of Lindlar's catalyst. So what happens? Over here, we have got limited supply of hydrogen. We have got limited supply of hydrogen over here. So your alkyne gets converted into alkene. It does not further get converted into alkane because of the limited supply of hydrogen. So what do we get over here? We get cis alkene as the product. Right? We get cis alkene as the product. As simple as that. The best catalyst known for hydrogenation. Which one is the best catalyst known for hydrogenation? This is something which all must be knowing. Let me know fast in the chat box. The best catalyst known for hydrogenation. Is it going to be Wilkinson's catalyst? Yes, absolutely, it's going to be Wilkinson's catalyst, option A. Right, people? And this is tris-triphenyl phosphine. This is rhodium chloride. This is the structure of it. So this is something which we call as Wilkinson's catalyst, which is the best catalyst known for the hydrogenation. Okay, the product in the following reaction. I'm again doing the hydrogenation, correct? See, this three-membered ring, it is under angle strain, right? It is unstable, you can say. It is under angle strain. So in order to remove that angle strain, what we are going to do is, we are going to break one of the bond. Just break one of the bond in this way. Okay, right? After breaking one of the bond in this way, attach one of the hydrogen at this position, one of the hydrogen at this position. What do we get? We get CH3, CH2 and CH3. CH3, CH2 and CH3. This is the product. Yeah? This triple bonded carbon, it is under angle strain. That's why one of the bond has broken down, and in place of this, you are going to attach one hydrogen. Over here, you are going to attach one hydrogen. So option A is the one which is correct. Okay. This is the 4-membered ring. Again, 4-membered ring is under angle strain. Again, 4-membered ring is under angle strain. So what is going to happen? Just break one of the bond. Just break one of the bond. After breaking one of the bond, just place one of the hydrogen over here, one of the hydrogen over here. What do we get? We get CH3, CH2, CH2, CH3, right? So what is going to be the answer of this question? It's going to be option C. From cyclic to linear. From cyclic to linear. But it happens only in 3-membered and 4-membered rings. Okay, it does not happen in 5-membered rings. 5-membered ring is comparatively stable than that of 3-membered and 4-membered. Okay? Alright. See, this is the 5-membered ring. Will the same thing happen over here? Are you going to break one of the bond? Are you going to break one of the bond? Can you let me know in the charts? You're not going to break one of the bond over here because it's comparatively stable. There will be no reaction at all. When you use 5-membered ring or 6-membered ring, there will be no reaction at all. So option D is the answer of the question. Yeah, no reaction at all. Perfect. Again, this is a 6-membered ring. It is stable. No need to break bond or something. So it is not going to undergo any addition of hydrogen reaction, right? Yes, people. So again, no reaction. 5 and 6-membered rings, they are comparatively stable. Okay. The products formed in the following reaction, right? We have got alkyl halide in presence of what? Dry ether. What do we get? So take 2 times NaX out. Take 2 times NaX out. Attach this R with R. You get alkane. So RR plus 2 times NaX. So option A is the product, right? Yes. Simpler one again. It is the example of which reaction? What do we call this reaction, people? We call this as Wurtz reaction, yeah? Wurtz reaction is used for the preparation of? Wurtz reaction is used for the preparation of what? Let me know. It is used for the preparation of symmetrical or unsymmetrical? It's used for the preparation of symmetrical alkanes only, okay? Wurtz reaction is used for the preparation of symmetrical alkanes only. Perfect. Which of the following alkanes can be prepared as the major product in the Wurtz reaction? In the Wurtz reaction, we get symmetrical things, okay? Now, how you are going to identify it? See, over here you have got 1 carbon, over here you have got 2 carbons, over here we have got 3 carbons, right? Over here 1, 2, 3, 4, 5 carbons, okay? Over here in this one, 1, 2, 3, 4, 5, 6 carbons. Over here, 6 carbons again. Over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Wherever there are even number of carbon atoms, that is going to be the major product through Wurtz reaction. Even number of carbons, guys. So this can be the major product. This can be the major product. This is going to be the major product as per Wurtz reaction. Even this is going to be the major product as per Wurtz reaction. Even number of carbon atoms, right, are going to give you the major products in case of what? In case of the Wurtz reaction, correct? Complete the following reaction. You need to complete the following reaction, people. What about the first one? How you are going to do it? What you simply are going to do, you are having alkyl halide in presence of dry ether. What you are going to do is, just break this bond. I'm not showing you the mechanism. I'm telling you how to form the product. Just break this bond, get the free radical over here, right? So over here we got a free radical CH3CH2. CH3CH2 radical we got. So there won't be only one radical like this. There will be a lot of radicals like this. So one of CH3CH2 radical is going to combine with another CH2CH3 radical, right, by means of a single bond, and they are going to lead to the formation of butane, right? So this is going to be the product. This is going to be my product. Yes? What about in this one? What about in this one? First of all, break the RX bond. Break the RX bond, get the radical on this carbon. Break the RX bond, get the radical on this carbon. So how many different types of radicals do we have? We have got 2 radicals. Yes, this is 1 radical. This is 1 more radical. See, one possibility is this ethyl radical is going to combine with one of its own kind, right? So it's going to be CH3, CH2 radical will combine with one more CH3, CH2 radical, right? And they will form a sigma bond, they'll form a butane over here. This is one of the possibility. Second possibility is this methyl radical can combine with one more methyl radical like this. Okay, then they can form a sigma bond. Yes, so ethane, one more product. And the last probability is one ethyl radical will combine with one methyl radical. Okay, so what do we get at that time? Your ethyl radical CH3, CH2 radical is going to combine with CH3 radical and just combine them. This is one more product. So 3 products we got in this case. 3 products we got in this case, right? Okay, you see, you need to check the possibilities, right? You need to check the possibilities. Over here, we had 3 possibilities of forming the products. So I made the 3 products in this case. What about this one? Just break this RX bond. I broke this RX bond. Free radical gets generated at this carbon, right? So one of this free radical we can combine with one more free radical of its own kind, right? So there'll be a sigma bond between these 2 carbon atoms. Yes. Okay, so finally you get something like this. This is the product. This is the product, right? Right, people? This is the product. Yeah? Perfect? Absolutely. Moving on to one more. See guys, in this case, again do the same procedure. Break this RX bond, break this RX bond. Get the radical over here, get the radical over here. Join these 2 radicals and finally what do we get? Finally, what do we get? Join these 2 radicals, you get the product in this way. This is the product which you get. Yeah. What about in this case? Break this bond, get the radical, join them. You get CH2 double bond CH2 as the product. Yeah. Right, people? I'm sure it's clear. Right? Okay. Moving on. In Kolb's electrolytic method, the product evolved at anode and cathode. At anode, carbon dioxide gets liberated, and at cathode, hydrogen gas gets liberated. I hope you remember the mechanism which I have shown you in the actual classes, right? Okay, carbon dioxide gets liberated at anode and hydrogen gets liberated at cathode in case of Kolb's electrolytic method, right? And this is the reaction. At anode, carbon dioxide is getting liberated, and at cathode, hydrogen gas is getting liberated. Right, people? Okay. All right, complete the following reactions. How you are going to complete these reactions? Complete these following reactions, people. Complete these following reactions. What is going to be the product in the first case? What you are going to do? Again, the same procedure you are going to do. I'm not showing the mechanism, I'm showing you how to make the products, right? Break this bond between methyl and this C, between C and this C, okay? Get the radical over here on methyl. So one of the methyl radical will combine with one more methyl radical, and you get ethane as the product. You get C2H6 as the product, yeah? Similarly, break this bond, get the radical over here, form a double bond. So this is going to be CH2, double bond CH2, this is the product, yeah? Again, what you are going to do, break this COK, get the radical and join them. Okay, so you get CH, triple bond CH, right? In the last case, break the CONA, get the radical over here, Now, 1, 2, 3, 4, 5, 6, right? Okay. Now, these two are going to combine. They are going to lead to the formation of the cyclic ring. Okay. So you get something like this. 6-membered ring you got. Cyclohexane you got, right? Cyclohexane you got in this one. Yeah? Clear to everyone? Absolutely. Okay, few more. Complete the following reactions as per this Kolb's electrolytic method is concerned. What you are going to do, again the same procedure, break this bond, get the radical. Now people have a look. What is going to happen? See, this radical is in conjugation with this pi bond, even this radical is in conjugation with this pi bond. So what is going to happen? Just break this bond in this way, okay? So what you'll be getting over here, 1, 2, 3, 4, right? It's a 4-membered thing. On every carbon you got the radical, right? On every carbon you got the radical. If you join these two, bus, this is the product, right? This is the product, right? 1,4-butadiene. Similarly, what happens in this case? Break this one, get the radical over here, join these two. So this is the product. Yeah? Correct? What about the next one? Break this bond, get the radical over here, and join these two radicals. So you get finally this structure. Or you can make it like this. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Correct? You can make this structure like this. You can make the structure like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since you have joined carbon number 1 with carbon number 6, and over here again you have joined carbon number 1 with carbon number 6, and total there are 10 carbon atoms basically. So you get bicyclo compound over here. Yeah? Okay, few more. Heating carboxylic acid with soda lime results in, you tell me guys, heating carboxylic acid with soda lime, it results in what? Decarboxylation, yeah? Absolutely, it results in the decarboxylation, right? See, you had RCOH, simply you took this CO2 out. Right? Okay, and you attach this R directly with hydrogen, right? And this is something which we call as Oakwood process, in which decarboxylation happens, right? And do remember, its proportion as well, it's 1:3. Calcium oxide plus NaOH, its proportion is 1:3 over here. Okay, rate of decarboxylation is directly proportional to, What do you think? What do you think about this one? Rate of decarboxylation is directly proportional to stability of carbanion or stability of carbocation? Stability of carbanion or stability of carbocation? Guys, it is the stability of the carbanion which gets formed due to the rate determining step. Okay, rate of decarboxylation depends on the stability of the carbanion which we get in the rate determining step. Okay, I'll be giving you certain examples. Yeah, see, arrange the following in the rate of decarboxylation. Arrange the following in the form of rate of decarboxylation. So first of all, just take this COH out, get the carbanion over here. Take this COH out, get the carbanion over here. Take this COH out, get the carbanion over here. Now, which carbanion is more stable? See, over here, negative charge is present on sp3 hybridized carbon. This negative charge sp2, this negative charge sp hybridized carbon, more s character, more electronegative. Negative charge is more stable on more electronegative. So this carbanion is more stable. So this is going to be the order of rate of decarboxylation 3 to 1. Right? Simple. Okay, arrange the following in the order of rate of decarboxylation. So first of all, make the carbanions. Take this COH out, get the carbanion over here. Take this COH out, get the carbanion over here. Take this COH out, get the carbanion over here, right? Now see the stability of these carbanions, right? This NO2 will operate, it's electron withdrawing basically, right? It will operate minus M. This OMe, it will operate plus M, right? Over here, nothing. And remember, carbanions are stabilized by minus effects, and minus M dominates over minus H dominates over minus I, right? So where is going to be the rate of decarboxylation maximum? First, followed by third, followed by 2. 1, 3, 2 is the order. Right, people? Yes? Okay, moving on to one more. Arrange the following in the order of rate of decarboxylation. Take this COH out, get the carbanion over here. Take this COH out, get the carbanion over here, right? Okay, the carbanion which I got the carbanion like this. Over here, I got the carbanion like this. Right? So over here, every carbon is sp2 hybridized. Over here, every carbon is sp2 hybridized. There are 4 pi electrons involved in the complete cyclic conjugation. There are 6 pi electrons involved in the complete cyclic conjugation. So this carbanion is aromatic. This is anti-aromatic. Aromatic ones are more stable. So this carbanion is more stable, right? So this is the order of the rate of decarboxylation 2, 1. Right, people? Simple? Yeah? Okay, moving on to one more. This is one more. Complete the following reaction. How do we complete these reactions? Awkward process, people, awkward process, right? How do we complete these reactions? First of all, you need to take this COH out. After taking this COH out, there'll be a negative charge over here. So you got something like this. You got something like this with a negative charge, right? Now this carbon with a negative charge, right? It's going to take H positive out from the medium, right? And H positive gets attached with this like this. So this is the product finally. So make the carbanion, take the H positive out from the medium, that's all. This is R COH. Take this COH out, negative charge on this carbon. This R negative is going to take H positive from the medium, so this is the product, yeah? Similarly, break this one, take this COH out, get the negative charge over here, right? And this is going to take what? It's going to take H positive out from the medium, so it's going to H like this. So this is the product, right? I'm sure it's clear. Okay, what about in these cases? What about in these cases? What do you think about this one? What do you think about this one? In the first case, take the COH out, get the negative charge over here. This Br will leave as Br negative, so there will be a positive charge over here. Make a double bond between these two, so you got the product. This is CH3, this is CH3, this is CH, this is double bond, this is CH2. This is my product over here, right? Okay. Now in this case, take this COH out, negative charge on this carbon. Br will leave as Br negative, so positive charge on this carbon. Now attach this carbon with this carbon, what do we get? 1, 2, 3, 4, 5. 5-membered ring I will be getting. I'll be getting 5-membered ring like this. That's all. Yeah? In the next case, see, take this COH out, get the negative charge over here. Br will leave as Br negative, so there'll be a positive charge over here, right? Okay. Now, let's call this as carbon number 1. Let's call this as 2, 3, 4, 5, 6, right? 7, 8, 9, 10. you're going to attach carbon number 1 with carbon number 6, right? So finally, how you are going to represent it? In the similar way which I have shown you, a few minutes back, right? Okay, let's call this as carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since you have attached carbon number 1 with carbon number 6, so over here also you have attached carbon number 1 with carbon number 6. So this is the product, right? Bicyclo compound you got again. Right, people? Yeah? Okay. All right, the following reaction is the example of, what is this reaction all about? This is the example of what, people? Let me know fast. The following reaction is the example of what? Free radical substitution, right? Yeah? Just a second, I'll turn the fan on. Just a second, guys. Okay, so the following reaction, it is absolutely the example of the free radical substitution reaction, yeah? Okay, in halogenation of alkanes, which step is exothermic? What about this one, people? During the halogenation of alkanes, which step is exothermic? You guys can let me know its answer. Let me know its answer, people, fast. In the halogenation of alkanes, which step is exothermic? Is it chain initiation or chain propagation? It is chain propagation step which is exothermic in the halogenation of alkanes, right? So remember this thing as well. This is something which we have discussed in detail if you remember, right? Chain propagation step, this is exothermic in this one. Okay, how many monochlorinated products are possible? How do we check this? How do we check this? How do we check the number of monochlorinated products? See guys, how do we check it? First of all, have a look. See, first of all, let me tell you, these 3 hydrogens and these 3 hydrogens, they are of same type. Why they are of same type? If you look at the surrounding of this carbon, there are 3 hydrogens attached. With these 3 hydrogens, you have got CH2, CH3. This is the surrounding of this carbon. What about surrounding of this carbon? This carbon has got the same surroundings. It has got 3 hydrogens attached and CH2, CH3. Okay, well, you can see surrounding of this carbon and surrounding of this carbon both are same. So these 2 carbons are of same type. So hydrogens attached to these 2 carbons are of same type. Okay, so these 6 hydrogens, these 3 and these 3, they are of same type. But these 2 hydrogens, they are going to be of different type, right? Because surrounding of this carbon is going to be 2 hydrogens, 1 CH3 and 1 more CH3. You can check surrounding of this carbon is different, right? So how many different types of hydrogens do we have? These 6 are of one type, these 2 are of one more type. So 2 types of hydrogens we have in this case. So 2 types of products will get formed. 2 types of monochlorinated products will get formed. Either you take hydrogen out from these 6 hydrogens or you take hydrogen out from here, right? So in the first case is going to be CH2Cl, CH2Cl, then the rest is same, CH2, CH3, right? Okay, what about the second one? Second one is going to be CH3. Just take hydrogen out from here, it becomes CH. With this carbon you attach chlorine and over here you have got CH3. So 2 monochlorinated products are possible. 2 types of monochlorinated products are possible. Yeah. What about the next case? See guys, these 3 hydrogens and these 3 hydrogens, they are of same type. Similarly, these 2 hydrogens and these 2 hydrogens are of same type. Now replace any of these 6 hydrogens which are represented by red colored line, replace any one of the hydrogen by Cl. So my first product is going to be, let's say this is CH2, I'm replacing one of the hydrogen from here only, attach Cl. Now rest things are same. This is CH2, this is CH2, this is CH3. This is one of the product. What is second type of product? Among these hydrogens, replace one hydrogen with chlorine. So you get CH3. This is CH, I'm attaching chlorine over here. This is CH2, this is CH3. So 2 monochlorinated products I got in this case as well. Yeah, I'm sure it's clear. Right, people? Absolutely. Moving on. Okay, give the reactivity of hydrogens towards halogens. Give the reactivity of hydrogens reactivity of hydrogens towards halogens in the following. What do you think? What do you think about this one, people? Let me know its answer fast. Reactivity. What is going to be the reactivity of hydrogens towards the halogens in this case? Which hydrogen is going to be more reactive? Simple. So first of all, how I'm going to take it? If I take hydrogen out, right? See, if I break one of the carbon-hydrogen bond, I'll be getting a radical over here. I'll be getting the radical over here. Now see, this radical, it is stabilized by how many alpha hydrogens? This radical, it is stabilized by only this alpha hydrogen, correct? So it is stabilized by only one alpha hydrogen. If I break this CH bond, I'll be getting a radical over here. This radical is stabilized by 3 to 5, 5, 3, 8 alpha hydrogens. 8 alpha hydrogens, right? If I break this CH bond, I'll be getting a radical over here. This radical is stabilized by only one alpha hydrogen, this alpha hydrogen. If I break one CH bond over here, this radical is stabilized by 3 plus 1, 4 alpha hydrogens. This one is stabilized by 2 alpha hydrogens, right? Okay. Right? Now you tell me the reactivity. Which radical is going to be more stable? B, right? So this hydrogen is going to be more reactive. This hydrogen is going to be more reactive. B is going to be maximum reactive. Followed by C, followed by D, followed by A and E. They are going to be equally reactive. This is the order of reactivity of these hydrogens towards halogens, right? B, C, D, A, E. Correct? I'm sure it's clear. Right, people? B, C, D, A, E. Okay. Direct iodination of alkane is not possible. Statement number 1, that's absolutely correct. Direct iodination of alkane is not possible. Direct iodination of alkane leads to the formation of HI, which is a strong reducing agent. Absolutely. Both the statements are correct, right? Yeah? If we do the direct iodination of alkane, it leads to the formation of HI, right? And that HI is basically a strong reducing agent. I hope you know it. So both the statements are absolutely correct over here, right? See, if you do the direct iodination of this methane, you get CH3I. With this, you get HI, which is a strong reducing agent, right? Which is a strong reducing agent, correct? Okay. What is the work of the reducing agent? It reduces others, itself undergoes oxidized, right? So by the formation of this HI, what is going to happen? By the formation of this HI, the reaction will again lead to the it will again proceed in the backward direction. So my main point is to consume this HI from here so that the reaction does not favor in the backward direction, right? So in order to carry out this reaction, I take either HiO3 or HNO3 or HGO, right? Which reacts with HI and lowers down the concentration of HI on the product side, right? So the reaction moves in the forward direction, right, people? Yeah? So this reaction is done in presence of HiO3 or HNO3 or HGO, right? Which react with HI so that HI concentration gets decreased, right? So that HI gets consumed and the reaction favors in the forward direction, right? This is something which we have discussed in detail in the actual sessions, all right. The product in the following will be isomerization reaction, yeah? What is the product in the following? Let me know fast. Let me know fast, people. What is the product in the following reaction? What is going to be the product in the following reaction? Isomerization reaction it is, right? Okay. So from N-butane, what you guys are going to get? Absolutely, you are going to get isobutane. Yeah. Let me show you the exact reaction over here. See, this is the isobutane which you are getting over here, right? From N-butane in presence of anhydrous Cl3HCl, keeping the temperature 573, pressure 35 atm, you get isobutane as the product. This is the example of the isomerization reaction. This is something which we have discussed in detail. So from N-hexane, what all things do we get? From N-hexane, again you are going to do the isomerization, right? You are going to make its isomers. You can let me know the answer properly. Yeah? Let me know what are going to be the products in this one. Again, you are using the same reagents. Just convert it into their isomers. So you get 2-methylpentane and 3-methylpentane as the products in this case, right? Okay, what about this one? N-heptane. N-heptane in presence of Cr2O3, Al2O3, right? What do we get in this case? What do we get in this case? First of all, this is CH2, this is CH2, this is CH3, right? So I can write it as CH, this is one more H, this is CH2, this is one more H, correct? If I break this bond, put a radical over here, put a radical over here, then join these two radicals, what I'll be getting? I'll be getting something like this. Okay, I'll be getting, this is CH3, this is CH3, and at every carbon over here, there are two hydrogens attached, okay? Now after this, something called as aromatization will happen, due to which at every carbon in the ring, one of the hydrogen will leave, and finally, you get this as the product, which is called as toluene after the aromatization, right? This is something you will be getting. Toluene you will be getting as a product, right? This is a simpler one. Okay, so first from N-heptane you got methyl cyclohexane. Then finally you get toluene as the product, right? Okay, pyrolysis of alkanes follows what? Pyrolysis of alkanes, what does it follow? This is something which we have discussed again long back, if you remember. Pyrolysis of alkane follows what? Does it follow free radical mechanism? Does it follow free radical mechanism? Yes, it follows free radical mechanism, okay? These three statements, do remember these 3-4 statements, okay? Decomposition of a compound by the application of heat is something which we call as pyrolysis. But particularly when we do the pyrolysis of alkanes is something which we call as cracking. These statements are given in your NCERT, right? These statements are given in your NCERT, right? And over here, it involves the breaking of CC bond and CH bond. It follows free radical mechanism. This is something which we all must know. Okay, E1 reaction of alkyl halide follows E1 reaction, people. E1 reaction, one step or two step. E1, it is a two-step mechanism, right? It's a two-step mechanism, right? What are the two steps? First, what happens? CX bond is broken down, ionization step happens. First step is called as ionization step, in which you get the carbocation. Then if there is a possibility of rearrangement of carbocation can happen, and at the end, from the carbocation, you get the alkene, right? Okay. Rate of E1 is directly proportional to the dielectric constant of solvent, which is absolutely correct. Statement number 1 is correct. Rate of E1 is directly proportional to the stability of carbocation formed during rate determining step. Absolutely, both the statements are correct, right? Both the statements are absolutely correct. Yeah? Right, people? Arrange the following in the rate of E1. In the rate of E1. Break it, get the carbocation over here. Break it, get the carbocation over here. Break it, get the carbocation over here. Now, which carbocation is more stable? This is 3-degree carbocation, which is more stable. So, this is going to be the order of the substrates towards E1. Order of the rate of the substrates towards E1. 3 to 1 is going to be the order, right? Okay. All right, what about this one, people? See, if you break this one, you get carbocation right here. If you break this one, you get carbocation right here. If you break this one, you get carbocation right here. Everywhere, you are getting 3-degree carbocations, right? So you cannot decide on the basis of carbocations. Over here, iodine leaves as Io negative. Over here, bromine leaves as Br negative. Over here, chlorine leaves as Cl negative, right? And I negative has got the better leaving ability, followed by Br negative, followed by Cl negative. And whatever is going to be the order of leaving ability, same is going to be the order of the substrates towards the rate of E1. Correct? Yes? 1, 2, 3 is going to be the order. Alright, the major product formed in the following reaction. What is going to be the major product formed in the following reaction? I do not remember which question number it is. Yeah, I do not remember it. The major product formed in the following reaction. What is the major product formed? It is simple, guys. See what you guys are going to do. You are basically doing the E1 reaction, right? So what you'll be doing? See, this X will leave as X negative, right? X will leave as X negative. There'll be a positive charge on this carbon. right? This is what I'll be calling as alpha carbon. Yeah, that carbon which is directly attached with the halogen, I'm calling it as alpha. This is beta, right? Now take one of the hydrogen out from beta position, right? So you get two types of products in this case. If you take this H positive out, there'll be a double bond over here. If you take this H positive out, there'll be a double bond over here. Now which one is the major product? More substituted one is going to be the major product as per your SADSIF, right? Yes? Okay, so what is going to be the major product in this case? It's going to be CH3. This is simply CH. This is double bond. This is CH. It is single bond, CH3. This is the major product, or you call it as the SADSIF product as well. Which one is the minor product? Minor product is the one in which double bond will be here, right? You get CH2, double bond. This is CH. This is CH2. This is CH3. This is what we call as Hoffman product, which is the minor product. Why this is minor? Why this is major? Because this double bond is stabilized by more alpha hydrogens, 6 alpha hydrogens. This double bond, it is stabilized by only 2 alpha hydrogens, right? That's why this is the major product and the other one is the minor product, right? Yes, people? Simple. Let's move on. Okay, the major product in the following reaction. This X leaves as X negative, there will be a positive charge over here. So which type of carbocation I got in this case? Have a look. This is my carbocation which I am getting. This is CH3, this is C, this is CH3, this is one more CH3, right? This is CH2 with a positive charge, right? Let's call this as carbon as 1, let's call this as 2. So if I do the 1,2 methyl shift, what will happen? This is currently 1 degree carbocation. If I do 1,2 methyl shift, I'll get 3 degree carbocation like this. This will be CH3. This will be carbon. Over here, this is CH3. This is nothing. This is a positive charge. This will be CH2. This will be CH3. So from 1 degree to 3 degree carbocation, right? 3 degree carbocation is definitely very stable than that of 1 degree. So this rearrangement will happen. 1,2 methyl shift over here is happening, right? Due to which stability of carbocation is increasing. Now, what will happen after this? This is the alpha carbon. This is beta. You're going to take beta hydrogen out. You'll be getting two products. One is going to be major, one is going to be minor. Which one? I need to make the major product, I guess, right? The major product. So I'll be taking this beta hydrogen out. So there'll be a double bond over here. So you get CH3, right? This is C. This is CH3, right? This is going to be double bond. This is CH. This is going to be CH3. This is the SADSIF's product. This is the major product because this double bond is stabilized by more alpha hydrogen. So which option satisfies it? You can check the options, right? This is the product. Correct? Right, people? Yeah? So it's option B, it seems. Okay. E2 reaction of alkyl halides follows E2. One step, right? It's a one-step mechanism. Right? As you all must be knowing. E2 is the one-step mechanism which occurs via transition state. Yeah? It occurs via transition state. This is something which you all must be knowing. What is this? The answers already are given. Arrange in the order of E2 reaction. Again, over here, iodine leaves as I negative, bromine leaves as Br negative, and chlorine leaves as Cl negative, right? Leaving ability of I negative is more. So this is basically the rate of reactivity of these substrates towards E2 reaction, right? Yes? Rate of E2 of any substrate is directly proportional to leaving ability of the groups in the substrate. Okay. All right, what about this one? We will arrange the following in decreasing order of the rate of reactivity towards E2. Rate of reactivity towards E2. How you are going to do it? What is going to be the answer of this question? Let me know fast now. Right? Let me know fast. So people are saying 1, 2, 3. Exactly, people, right? How you guys are going to do it? It's not going to be 1, 2, 3, it's going to be 3, 2, 1. First of all, you'll be making the products. First of all, you'll be making the products, right? First of all, you'll be making the products. After making the products, this is the product. This is the product in the second case, and this is the product in the final case, right? I'm talking about the major product, right? Now, what you're going to do is, you'll be seeing the stability of the pi bond, right? See, this pi bond is stabilized by 3 alpha hydrogens, this pi bond is stabilized by 6 alpha hydrogens, and this pi bond is stabilized by 9 alpha hydrogens, right? Okay? Yeah? So what is going to be the answer now? What is going to be the answer now? Right? This product is maximum stable, correct? So this one is going to be more reactive towards E2 because the product formed is more stable, followed by the second one, followed by the first one, right? Product I told you how to make. Already I told you how to make the products, right? Correct? I'm sure it's clear. Okay. Arrange the following in decreasing order of rate of reactivity towards E2. Rate of reactivity. How you are going to check it? Make the products first. How you are going to make the products? How you are going to make the product? This Cl will leave as Cl negative, right? There will be a positive charge over here. There will be a positive charge over here. This is alpha carbon. These two are beta carbons. These two are beta carbons. Take one of the hydrogen out from beta carbon, put a double bond over here. Right? This is the product which I got. In this case, this Cl leaves as Cl negative, there will be a positive charge over here. Take this H positive out, there will be a double bond over here, right? This is the product. This is the product, correct? Similarly, take this Cl as Cl negative, there will be a positive charge over here. This is now beta carbon, this is now beta carbon. If I take H positive out from here, right, I'll be getting something like this, which is somewhat resonance stabilized. This is pi, this is sigma, this is pi, this is the product. What about in this case? Take Cl out as Cl negative, positive charge over here. This is alpha carbon. Take H positive out from this beta position, right? There'll be a double bond over here. Correct? Now check the stability of these products. Check the stability of these products. Which one is going to be more stable? See, first of all, this is aromatic as well as it shows resonance. It only shows resonance. So this product is maximum stable. This product is maximum stable. So this one is maximum reactive towards A2, right? So 1, 2, 3, 4. Fourth one is maximum reactive, followed by the third one, because in this there is resonance, right? Now this pi bond, it is stabilized by how many alpha hydrogens? See, this is alpha carbon, this is alpha carbon. So 2 alpha hydrogens like this, 2 alpha hydrogens over here. So this pi bond is stabilized by 4 alpha hydrogens. This pi bond, it is stabilized by these 3 alpha hydrogens, these 2 alpha hydrogens, right? And these 2 alpha hydrogens. So 3 to 5 to 7, 7 alpha hydrogens, right? So maximum reactive was 4, then 3. Among first and second comes the first, then comes the second, right? This is going to be the order. 4, 3, 1, 2 is going to be the order. I'm sure it's clear, right? Right, people? Okay. All right, the major product formed in the following reaction will be alcoholic KOH you are using, right? What is going to be the product in this case? The major product I'm talking about. What is going to be the major product, people? The similar way you are going to make the products. The similar way you are going to make the products, right? This X will leave as X negative. There will be a positive charge over here. Take either this beta hydrogen out or this beta hydrogen out. If you take this beta hydrogen out, there will be a double bond between these two positions, right? That's going to be more stabilized by the alpha hydrogens. Okay, so major product is going to be CH3. This is going to be CH. There will be a double bond over here. This is CH. This is CH3. This is the major product, which is basically the state of the product. Yeah. So option 2 is the one. Simply, you need to take halogen out from alpha carbon and make a double bond between alpha and beta carbon. That's it, right? Make a double bond between alpha and beta carbon. That's it. Correct? Okay. All right. Now, whatever questions we saw till now, in every equation, your Sedgwick product was the major product, right? In A2 mechanism, generally Sedgwick's product is the major product. But there are some exceptions in which Hoffman product becomes the major product. What are those exceptions? When you have got the poor leaving group as F, right? F is considered as the poor leaving group. It leaves as F negative, okay? When you'll be having the poor leaving group as F, at that time, remember, Hoffman product becomes the major one. Okay, so what is going to be my Hoffman product? Take this fluorine out as F negative, put a double bond between these two. So Hoffman product is going to be CH2, double bond CH, single bond CH2, single bond CH3. Right? This is basically the Hoffman product, which is the major product in this case when you have got a poor leaving group like fluorine. Yeah? Right, people? So what is the answer of this question? Answer of this question is going to be this one. Yeah? Option A. Correct? Similarly, when the leaving group is bulky, at that time again Hoffman product dominates. And what is going to be the Hoffman product? Put the double bond between these two carbons, that's it. So it's going to be CH2, double bond, this is CH, this is CH2, this is CH3. This is my Hoffman product, which is again going to be the major product, right? Yeah? Right, people? Similarly, when you have a bulky base, this is a bulky base, right? In presence of a bulky base, again Hoffman product dominates, right? What is going to be my Hoffman product? Take this Br out as Br negative, put a double bond between these two carbons, it becomes CH2, this is double bond, this is CH, this is CH2, this is CH3, right? This is the major product in this case, which is the Hoffman product, right? Right, people? So option A is again the answer. Correct? Now, the major product in this case, what is going to be major product in this case? See guys, if I take, see this is the alpha carbon first of all, if I take Br out as Br negative, there will be positive charge over here on this alpha carbon. Yes? Or I'm saying like this, see this is beta carbon, this is beta carbon. Take Br out as Br negative. Now either you are going to make a double bond over here or you are going to make a double bond over here, right? Now, which one is going to be the major product? If I put a double bond over here, what I'll be getting? See, this is CH2, already there was a double bond between CH, correct? Now it's going to be CH, correct? This is double bond, this is CH, correct? This is single bond, this is CH, over here there is CH3, over here this is CH3. This is one of the products which I got. Is this going to be major or minor? See guys, this is pi, this is sigma, this is pi, conjugation is happening, so this one is going to be the major product over here, right? The other product in which the pi bond is going to be between these two carbons, that's going to be the minor product in this case, right? Do remember these things. Clear to everyone? Yeah? Right, people? I'm sure it's clear. Exactly. So what is going to be the answer of this question? It's going to be option C. Match the product. It's going to be option B. Okay, so with this, your hydrocarbon part is over. Yeah? Right? With this, your hydrocarbon part is over. Yes, exactly. 8 hours are nearing. So let me sit for 2 minutes. Let me talk to you guys for 2 minutes so that I can take some rest as well. Okay. So now the next chapter is going to be Haloalkanes and Haloarenes. Yeah? Amar, we did the beta elimination only in the previous one. We did the beta elimination only, right? But we did the beta elimination in such a way that resonance is established in the product. That's all. That's great, Deepika, that's great. How many slides are left? There are many slides left. There are many slides left. Yes, Asif, we can do that. Yeah, we can do that. PDF you'll be getting in the Telegram group, guys. PDF you guys are going to get in the Telegram group. NEET difficulty level, it's going to be very simple. Trust me on that. It's going to be very, very simple. You're going to kill it. Abhinay, I have no idea. Hello, Vignesh, what's up? Gayatri, I have no idea. Let's see what's going to happen. Guys, we'll start at 5:10, okay? We'll start at 5:10. Till then, you guys also can take rest. Sir, say Vanakam. Vanakam, Tibika. PDF you'll be getting in the Telegram group. There's a link in the description box of the video, okay? There's a link in the description box of the video. Awesome Chemistry, I'm from Srinagar, Jammu and Kashmir, bro. Yes, Naresh, absolutely. I have no idea like why zoology classes are not happening on this channel, right? Maybe in coming days you'll be getting it. No, Gayatri, I do not know Tamil, but I can understand a bit of Tamil. Short questions will be done day after tomorrow. Day after tomorrow, I'll be taking either mega mock test or short. So should we start again, guys? Should we start again? Yeah? Okay, let's get started then. I think first few questions of haloalkanes arenes will be memory based questions. So you guys can let me know the answer of these questions, then I'll start, right? Which of the following is a primary halide? Can you let me know its answer in the chat box? I'm looking at your chats only. Which of the following is the primary halide? Waiting for your answers. All right, exactly. Majority of the students are coming up with the correct answer. It's absolutely going to be neohexyl chloride. And this is the structure of neohexyl chloride, which I've already given, in which chlorine is attached with the 1 degree carbon, right? Chlorine is attached with the 1 degree carbon. Yes, so it is going to be 1 degree halide, or you call it as primary halide, correct? One more similar sort of question. When two halogen atoms are attached to same carbon atom, then it's called as, what do we call it as? Do we call it as vicinal dihalide or geminal dihalide? What do we call this? When two halogens are attached to the same carbon, we call it as geminal dihalide, right? Okay. Yes. Okay. Which of the following is the geminal dibromide? Can you let me know its answer? Which of the following is the geminal dibromide? In which of the following two bromine atoms are attached with the same carbon? You can check it out. Option B. In option B, two bromine atoms are attached with the same carbon. Right, people? So it's going to be a geminal dibromide. Okay, IUPAC name of this compound. What is it going to be? What is it going to be? It is going to be 2-chloro-2-methyl propane, right? There will be 3 carbons in the parent chain, right? There will be a substituent CH3 present at carbon number 2, and at carbon number 2 there will be chlorine as well. So 2-chloro-2-methyl propane. Okay. What about the IUPAC name of this compound, people? Can you let me know fast? Can you let me know fast? Can you let me know fast? It's going to be 2-bromo, right? Yes? Is it going to be 2-bromo 1-chlorobutene? Is it going to be 2-bromo 1-chlorobutene? What do you think? Absolutely, right? Yes, it's going to be 2-bromo 1-chlorobutene. Okay, IUPAC name of this one. Are we going to start the numbering from left to right or right to left? We'll be doing the numbering from left to right. We'll be doing the numbering from left to right. It is going to be 3-chloro-prop-1-ene. Right? It's going to be 3-chloro-prop-1-ene. Yeah? Okay, which of the following is the 2-degree? Which of the following is the 2-degree one? Which of the following is the 2-degree halide? Can you let me know first? It's again the similar one. Which one is 2-degree one? Which one is the 2-degree halide, people? Absolutely, all of you are perfectly right. It's going to be isopropyl chloride, which is the 2-degree halide among all. Yes? These are all memory-based questions, people. CX bond is strongest in. CX bond. Is CCl bond strong, CBr, CF or CI? Which bond is more strong? Well, fluorine being more electronegative, I must say CF bond will be the strongest among all. So option C must be the answer, yeah? Okay. Which of the following will have the maximum dipole moment? This question we have done in chemical bonding as well. CH3Cl will have the maximum dipole moment, right? It looks like CH3F has, but CH3Cl has the maximum dipole moment, right? Because the dipole moment, it is the product of charge and as well as distance, right? It depends on 2 factors, yeah? And overall for CH3Cl, it comes out to be maximum. Right, people? Okay, Lucas reagent is. This is something which you all must be knowing. Which one is the Lucas reagent? Can you let me know fast in the chat box? Which one is the Lucas reagent? Some people are coming up with option B, some people are coming up with option A, and let me tell you, it's absolutely going to be option B. It is the equimolar mixture of HCl and anhydrous ZnCl2, right? Okay. Okay, the reaction of 1-degree and 2-degree alcohols with Lucas reagent to form alkyl halides. What do we call this process? Do you remember what do we call this process, people? It's called as Gru's process, right? In all the questions, option B is coming as the answer, yeah? Right? The reaction of 1-degree and 2-degree alcohol with the Lucas reagent to form alkyl halides is called as Gru's process, okay. What is going to be the product in the following reaction? What is going to be the product in the following reaction? Just a second. Okay, what is the product of the following reaction? Just replace OH. In place of OH, place Cl. That's it. CH3CH2Cl is the product. Yeah? It's option A. Simple. Just replace OH. In place of OH, place Cl. That's it. Yeah? Okay. What is going to be the product in this reaction? Again, replace OH by Cl. Again, replace OH by Cl. Yeah, so option 1 is going to be the answer of this question. Again, option A. Right? Okay, primary alcohols react with halogen acids by. Primary alcohols, guys, primary alcohols. Do they react by SN1? No, they do not react by SN1. They react by SN2 mechanism, right? But not all the primary alcohols. Yeah, they react by SN2 mechanism in general. Right? Because if they react by SN1 mechanism, they lead to the formation of carbocation, which is going to be 1 degree carbocation, highly unstable. So it's going to be SN2, absolutely. Okay, 2 degree and 3 degree alcohols react with halogen acids through. It is going to be SN1, right? Because you get 2 degree carbocation and 3 degree carbocation if your 2 degree and 3 degree alcohols react with halogen acids, which are comparatively more stable. Absolutely, you all are right. It's going to be option 1, SN1. Okay, branched 1 degree alcohol. Now this is the one which I was talking about. Branched 1 degree alcohol react with halogen acids by. If you have the branched 1 degree alcohol, right, it reacts with the halogen acids by SN1 mechanism, right? Because you get the carbocation which undergoes rearrangement, yeah, which leads to the formation of more stable carbocation, and finally the reaction takes place through SN1 mechanism. Right, people? Okay, what about this one? Lucas reagent is used to distinguish 1 degree, 2 degree and 3 degree alcohols. This is something which you all must be knowing. Lucas reagent, right? It's used to distinguish. Option B. See, when 1 degree alcohol is treated with Lucas reagent, there will be no turbidity, right? At room temperature. When 2nd degree alcohol, 2 degree alcohol is made to react with Lucas reagent, turbidity appears after some time. And when 3 degree alcohol reacts with Lucas reagent, turbidity appears immediately, people. Yeah? The product formed in the following reaction. What is going to be the product in the following reaction? Alcohol plus PCl5. It will form POCl3, HCl as well as RCl, right? So option 1 is going to be the answer of this question. Yeah? Right? Absolutely. The best method for conversion of an alcohol into an alkyl chloride is by treating the alcohol with. The best method for the conversion of an alcohol to alkyl chloride is by treating the alcohol with SOCl2 in presence of pyridine, because you get the other two as the gaseous products like this. Have a look. SO2 is a gas, HCl is a gas which you are getting as the product, right? So they directly escapes out and you get the alkyl halide as the product. Yes? Hope you remember Darzan's process. Reaction of alcohol with thionyl chloride is known as, let me know fast. Reaction of alcohols with thionyl chloride. The reaction which I told you a few minutes back. It is what we call as Darzan process, yeah? Absolutely, Darzan process is going to be. Okay, the product formed in the following reaction, what do we get? What do we get? We will be getting definitely two products. One is going to be orthochlorotoluene and one is going to be parachlorotoluene, in which parachlorotoluene is going to be the major product, right? Parachlorotoluene is going to be the major product, right? Sorry. Right, people? Okay. We are starting with aniline. We are doing its diazotization. We'll be getting benzene diazonium chloride. And once you get the benzene diazonium chloride, in the benzene diazonium chloride, you are going to replace N2Cl by X. So finally you get aryl halide. So first you get benzene diazonium halide, and then after that you get aryl halide. Simple. Correct? So option B must be the answer of the question. Right, people? First reaction is diazotization, in which you get benzene diazonium halide as the product, right, which is X. And X further on reaction with Cu to X2, it leads to the formation of aryl halide, in which is basically the Sand-Meier's reaction, yeah? Okay, iodobenzene is prepared from benzene diazonium chloride and potassium iodide, yes? Potassium iodide, correct? Right, people? Okay, the addition of bromine in CCl4 to an alkene leads to the formation of what? What does it form? Vicinal dibromide or geminal dibromide? What do you think about this one? Vicinal or geminal? Absolutely, guys, it's going to form the vicinal dibromide. Absolutely, you all are perfectly right. Yeah? Okay, the addition of bromine in CCl4 to an alkene resulting in the discharge of what? Reddish brown color of bromine, right? It's a very common question, NCERT based, right? Okay, the reaction of alkyl chloride or bromide with sodium iodide in dry acetone is known as, what do we call this reaction? Do we call it as Finn-Klissner reaction or Schwarz reaction? I'm directly giving you two options. I'm already removing two, right? We call absolutely this reaction as Finn-Klissner reaction, in which your alkyl chloride or bromide is made to react with sodium iodide, leads to the formation of alkyl iodide as the final product, right? Which of the following reagents may not be used to convert alkyl chloride and alkyl bromide into alkyl fluoride? People, which kind of reaction? What do we call this reaction in which alkyl chloride and alkyl bromides are converted into alkyl fluorides? Can you let me know in the chats? What is that reaction called? We call it as the Schwarz reaction. And in the Schwarz reaction, either you use Hg2Cl2 or you use SBF5 or you use AgF. But CaF2 is not used in the Schwarz reaction, right? CaF2 is not used in the Schwarz reaction. The decreasing order of boiling points. Just look at the molecular mass. Wherever molecular mass is more, there only boiling point is going to be more. So Ri will have more boiling point, followed by Rbr, followed by Rcl, followed by Rf. Simple. Yes? What is going to be the product of this reaction through SN1? Product of this reaction through SN1. So first you will make the carbocation, and after making the carbocation, what you are going to do? After making the carbocation, what you guys are going to do? What is going to be the product? See, in case of SN1, first of all, just break this bond, get the carbocation over here, right? So your OH is going to get attached finally at this carbon. So finally you get CH3CH. With this CH you have OH attached, then CH2, CH2, CH3. Option A is the one which is correct among all, right? Option A is the one. Okay, what about the next one? So first of all, see, first of all ionization happens, right? Ionization happens due to which carbocation is generated. After carbocation, hydrolysis happens, right? So OH gets attached at the carbocation position. Yeah? What about this one? If this substrate undergoes SN1 mechanism, what is going to happen? So break this bond, get the carbocation over here, right? Now, what kind of carbocation I got? This is CH3, this is carbon, this is CH3, this is one more CH3, right? This is CH2 with a positive charge, correct? This is 1 degree carbocation. Let me call this carbon number 1, this is 2. If I do the 1,2-methyl shift, if I do the 1,2-methyl shift, what I'll be getting? I'll be getting CH3, this is carbon with CH3 over here, this is a positive charge on this carbon, this is CH2, this is CH3. So from 1 degree you got 3 degree carbocation, right? Now in presence of water, what you'll be getting finally, you are just going to erase this positive charge and over here you are going to attach OH. This is the final product which you'll be getting. Is there any option like this? CH3, C, CH3, OH, CH2, CH3. It's absolutely going to be option A only. Correct, people? Yeah? It's absolutely going to be option A only. Perfectly done. Okay. Moving on to one more question. Wait, why it's not working? Okay, moving on to one more question, people. All right. What will be the product through SN1? What will be the product through SN1? What you are going to do, this is a 4-membered ring, right? Break this bond, first of all, get the carbocation over here, right? Whenever you'll be having a carbocation directly attached with 4-membered or 5-membered ring, at that time ring expansion will take place, right? You all must be knowing this. Whenever a carbocation is directly attached with the 4-membered or 5-membered ring, at that time ring expansion is going to take place. So 1, this is 2, this is 3, this is 4, this is 5. How ring expansion is going to take place? Just break the 2,3 bond. Just break the 2,3 bond. Okay. get the carbocation at carbon number 2 and join 1,3 bond. Okay, so what do you get finally? What do you get finally? This is your CH2, correct? This is something which I'm making as such. This is something which I'm making as such, correct? This is the positive charge over here, right? This is the carbocation. I got the 5-membered ring. I got basically the 5-membered ring. This is basically a 5-membered ring, correct? Once you get the 5-membered ring, then in presence of water, just attach OH over here. This is your final product. Simply remember, whenever carbocation will be directly attached to 4 or 5-membered ring, at that time, what happens? Ring expansion takes place, right? So option A is the correct answer of this question. Sure, it's clear to everyone. Okay, what about the next one? What about the next one, people? First, break this bond, get the carbocation over here. Whenever carbocation will be the part of 4-membered or 3-membered ring. Whenever carbocation will be the part of 4-membered ring. Over here, carbocation is the part of 4-membered ring. At that time, ring contraction takes place. This is 1, this is 2, this is 3, this is 4. Again, break the 2,3 bond, make 1,3 bond, right? Break 2,3 bond, make 1,3 bond, and at carbon number 2, you'll be getting a positive charge. So what you'll be getting over here, I'll be getting something like this. This is CH2 with a positive charge, correct? Okay, now, in presence of water, this CH2, OH gets attached with it, right? You get cyclomethyl propyl carbocation, which is very, very stable, correct? And finally, OH gets attached at this carbon. So which option satisfies it? It's going to be option C. Yeah? Absolutely. Ring contraction. Okay. Arrange the following in the order of their decreasing reactivity. Again, you have got I negative as the leaving group. Iodine leaves as I negative, bromine leaves as Br negative, chlorine leaves as Cl negative, right? And the leaving ability of I negative is more, followed by Br negative, followed by Cl negative. So the reactivity of first is more than that of second, more than that of third, right? Yes? I'm sure it's clear. Okay, one more, people. This is one more. SN1 reaction on optically active substrate mainly gives. SN1 reaction, mainly it gives. Retention happens, inversion happens, or you get the racemic product, or you get no product. What do you think? What do you think, people? What do you think? Absolutely, in this case, during SN1, you get the racemic product, right? Okay, you get the enantiomers in equimolar proportion. All right, racemic compound has equimolar mixture of enantiomers. Absolutely correct. Yeah, absolutely correct. In SN1 reaction, racemization is directly proportional to stability of carbocation. First statement is absolutely correct. This is absolutely correct. In SN1 reactions, racemization is directly proportional to stability of carbocation. Second statement says in SN1 reaction, racemization is directly proportional to strength of nucleophile. No, racemization is inversely proportional to stability of nucleophile. This is the actual statement. This is the actual statement. So first statement is correct, second statement is incorrect, right? Okay. First one is correct, second one is incorrect. So option A is the one which is going to be correct answer of this question. Right, people? Okay, SN2 mechanism proceeds through the intervention of what? Okay, SN2, it occurs via transition state. We know it, correct? There is no need to think a lot about this one. Option B, correct? This is the transition state, unstable transition state, you can say. Arrange the following in the decreasing order of SN2. Again, a very simple question. See, guys, break this bond, get the carbocation over here. 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 Now compare the stability of carbocations. Compare the stability of carbocations. Compare the stability of the carbocations. See, guys, the last one is a 3-degree carbocation, right, which is more stable. So what is going to be the reactivity order? This is going to be the reactivity order, right? Oh, there's a super chat something. Hey man, I really don't know who you are, but please go and take rest, buddy. Thanks, man. Perfect. So this is going to be the reactivity order. Okay, Arrange the following in order of the rate of SN2 reaction. Rate of these substrates towards SN2 reaction. Rate of these substrates towards SN2 reaction. Right? Rate of these substrates towards SN2 reaction. Correct? It's a nucleophilic reaction basically. It's a nucleophilic substitution reaction. So over here we have got a leaving group. Over here we have got a leaving group. Right here there is electron withdrawing group as well. Nucleophile, which is a nucleus loving species, it is going to attack at that substrate faster, which will be more electron deficient. Now which one among the two will be more electron deficient? The second one will be more electron deficient because electron withdrawing group is attached. So this is going to be the order. BA is going to be the order, right? Right, people? Yeah? Okay, what about this one? Give the correct order of reactivity towards SN2. Again, the same thing. This CH3, it's electron donating group, right? It's electron donating group. This NO2, it's electron withdrawing group. Nucleophile is going to attack at that position where the electron density will be less. Electron density will be less in the second case. So this is going to be the order of reactivity. BA, right? Absolutely. Okay, the reaction is described as what is happening basically? What is happening basically? Retention or inversion? Inversion is happening, right? And inversion happens in which configuration? SN2 or SN1? SN2 or SN1? Inversion happens in? Absolutely SN2, right? So answer of this question is absolutely going to be SN2 because inversion of configuration is happening. You can see, yeah? Okay, the mechanism of this reaction, 1 and 2 are respectively. Mechanism of this reaction, 1 and 2 respectively. Let me know first. Let me know first. What is going to be the answer? What is going to be the answer of this question? People, the first one will undergo SN1, the second one will undergo SN2, right? You need to remember one statement over here. See, a strong nucleophile, it favors SN2 reaction, a weak nucleophile favors SN1 reaction. This one is a strong nucleophile, right? This one is a weaker nucleophile, that's all. Right? A strong nucleophile favors SN2, a weak nucleophile favors SN1. That's all. Okay. Which of the following is an optically active compound? Which of the following? It should be 2-chlorobutane, which contains 1 chiral carbon, right? Yes? Which of the following is the optically active compound? It should be 2-chlorobutane. Correct? Because it contains 1 chiral carbon. This is the chiral carbon on which towards this carbon you have got 4 different groups attached. Yeah, so it's going to be optically active. Okay, which of the following pairs of the compounds are enantiomers? Which of the following pairs are enantiomers? Can you let me know its answer fast? Which of the following pairs of compounds are enantiomers? What do you think about this one? Non-superimposable mirror image. Non-superimposable mirror image. If you look at option B, we have got non-superimposable mirror image, right? Option B, these are non-superimposable mirror image which we have, yeah? Okay, a Grignard reagent may be made by reacting magnesium with methylamine, diethyl ether, ethyl iodide, ethyl alcohol. So what is going to be the answer, people? What is going to be the answer of this question? Fast guys. How do we make the Grignard reagent? Grignard reagent can be made by reacting magnesium with ethyl iodide, right? Ethyl iodide. This is ethyl iodide with magnesium. You get something as CH3CH2 MgI, which is ethyl magnesium iodide, or you call it as the Grignard reagent in short. Okay, chlorobenzene reacts with magnesium in dry ether to give a compound A, which further reacts with ethanol to yield what? What do you think? First, I'm starting with chlorobenzene. It reacts with magnesium in dry ether to give a compound A, which further reacts with ethanol to yield what? I think it should yield benzene, right? Absolutely, guys, you all are perfectly right. Let's exactly see. This is chlorobenzene in presence of dry ether. You get the Grignard's reagent, C6H5MgCl, which on reaction with this alcohol leads to the formation of benzene over here, right? Okay, this is something which we have discussed in detail, if you remember. Okay, an alkyl halide reacts with metallic sodium in dry ether. The reaction is called as, what do we call this reaction, guys? This is something which we have discussed long back. What do we call this reaction? Alkyl halide reacts with the metallic sodium in dry ether. What do we call it? Do we call it as Wurtz reaction? Yes, we call it as a Wurtz reaction. Alkyl halide plus sodium in presence of dry ether. Take this twice NaX out, you get alkane RR as the product. That's all. That's all. Okay, what about this one? Aryl halides are less reactive. Aryl halides are less reactive towards nucleophilic substitution as compared to alkyl halides. Why is that? Because aryl halides are resonance stabilized. CX bond. In order to break CX bond in aryl halides, it's difficult because of the partial double bond character, right? Okay. So that is the reason. That is the reason for it. All right. So CCl bond of chlorobenzene in comparison to CCl bond in methyl chloride is. What do you think about this one? What do you think about this one? What do you think about this one? CCl bond of chlorobenzene. Okay, in comparison to CCl bond, okay, in case of chlorobenzene, there will be a partial double bond character, right? There will be a partial double bond character. So CCl bond in chlorobenzene will be shorter and stronger, right? Shorter and stronger. So option C. Okay, the Blow reaction requires which reaction conditions? This reaction, chlorobenzene on reaction with NaOH, it happens when the temperature is kept 623 and pressure is kept 300, right? Okay, these are all some basic questions. Just a second. Okay. At what position the presence of electron withdrawing group NO2 increase the reactivity of haloarene? Absolutely ortho and meta position. When the NO2 gets attached at ortho and the meta position, then only it can show minus M effect, right? Then only it can show minus M effect, due to which electron density in the ring decreases to the maximum, which makes it highly favorable for the attack, right? So ortho and para position, option D is the one. Correct, people? Okay, the reaction of chlorobenzene with Cl2 in presence of anhydrous FeCl3 leads to the formation of what? Let me know its answer. Major product, guys. See, first of all, you'll be getting ortho product as well as para product, but para product is going to be major. So you get 1,4-dichlorobenzene as the para product, sorry, as the major product. 1,4-dichlorobenzene, yes? 1,4, not 1,3. 1,4. See, this is 1,4-dichlorobenzene, this is 1,2-dichlorobenzene, right? Okay, due to the less steric hindrance over here, this is going to be major, this is going to be minor. Okay, on nitration of chlorobenzene, the major product formed is. Again, you'll be getting ortho product as well as para product, but para product is going to be more stable. That's going to be major product. So what is going to be the answer? It's going to be 1-chloro-4-nitrobenzene, right? 1-chloro-4-nitrobenzene is going to be the major product. Yeah, 1-chloro-4-nitro is going to be the major product because of less steric hindrance. Correct? On sulfonation of C6H5Cl, benzene sulfonic acid is formed. Meta-chlorobenzene sulfonic acid is formed. Ortho-chlorobenzene sulfonic acid is formed. Ortho and para benzene sulfonic acids are formed. What is the answer of this one, people? It's absolutely going to be option D, right? You get ortho products as well as para products, in which para product is going to be major. Yeah? Okay, let's see if we have more from this. Okay. Which of the reaction is the example of the Friedel-Crafts reaction? So Friedel-Crafts reaction, this is C6H6 plus CH3CH2Cl in presence of anhydrous AlCl3 gives this. Okay, option A. First reaction is the example of the Friedel-Crafts reaction, as you can see, right? Right, people? First reaction directly is the example of the Friedel-Crafts reaction. Yeah? Okay. Benzene reacts with CH3Cl in presence of anhydrous AlCl3 to form what? Benzene, when it reacts with CH3Cl in presence of anhydrous ClCl3, Friedel-Crafts reaction, it leads to the formation of what? Toluene? Yes? It will lead to the formation of toluene. Let me show it to you. Just a second. This is benzene in presence of CHCl3, right? In presence of anhydrous AlCl3, it leads to the formation of this toluene over here. Correct? Benzene reacts with CH3COCl in presence of anhydrous AlCl3 to form what? What does it form? It is a simpler one. Absolutely, you'll be getting estrophenone, right? But is it going to be 2-chloroacetophenone, 4-chloro or 3-chloroacetophenone? Again, a simpler one, guys. You should know this, right? You should know this. The major product is going to be 4-chloroacetophenone, right? Because of the less steric hindrance. Okay, a mixture of alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether. This reaction is called as, what do we call this reaction? Do we call this as Wurtz-Fittig reaction? Do we call this as Wurtz-Fittig reaction? Yeah? Right? This is absolutely called as Wurtz-Fittig reaction. Okay, when two aryl compounds are joined and treated with sodium in dry ether, the product formed is, it is going to be diphenyl, yeah? It is going to be diphenyl. Absolutely, it's going to be diphenyl, and the reaction is Fittig reaction, absolutely. When 2-bromobutane reacts with alcoholic KOH, the reaction is called as 2-bromobutane reacts with alcoholic KOH. It is the example of what? Dehydrohalogenation reaction. Is that? Right? It is the example. See, this is 2-bromobutane. So from alpha position, bromine leaves as Br negative. From beta position, you are taking hydrogen out, right? So it is basically dehydrohalogenation reaction, which leads to, it is basically beta elimination, right? Okay, so it leads to the formation of two products. One is going to be major, one is going to be minor. That's something which you already know. Elimination of bromine from 2-bromobutane results in the formation of what? Predominantly, you have to say, predominantly. From 2-bromobutane, elimination of bromine from 2-bromobutane, what it will lead to the formation of? What it will lead to the formation of? See guys, if you look at 2-bromobutane, right? This is 2-bromobutane, correct? So first of all, this is the alpha carbon. Take this Br out as Br negative. So there will be a positive charge over here, right? This is alpha carbon. This is beta carbon. So if you take H positive out from this beta carbon, there will be a double bond over here, and the product is going to be this one. This is going to be the product, right? This is CH and this is CH3. This is going to be one of the product. What is going to be the second product? Second product is take H positive out from this beta position, there will be a double bond over here. So it's going to be CH, it's going to be CH, it's going to be double bond CH2, it is single bond CH2, single bond CH3. One of them is going to be major, one of them is going to be minor. See, this double bond is stabilized by more alpha hydrogens, 3 and 3, 6 alpha hydrogens. This double bond is stabilized by only 2 alpha hydrogens. So wherever double bond is stabilized more, that's going to be major. So this one is the major product, the first one, right? First one is going to be the major product. So it's going to be predominantly what? But-2-ene, correct? According to Sadzif. Okay, reactivity order of halides for dehydrohalogenation. Ri will be maximum reactive, followed by Br, followed by RCl, followed by Rf, right? Ri, Rbr, RCl, Rf, right? That's something which you all must be knowing. Okay, arrange the following alcohols in increasing order of the reactivities towards the reaction with HCl. So they will undergo SN1 mechanism. When they will undergo SN1 mechanism, there will be a carbocation right here, there'll be a carbocation right here, there'll be a carbocation right here. Now see the stability of carbocation. This carbocation is maximum stable because this positive charge is in conjugation with 3 phenyl rings, maximum stabilized. So 3 is going to be maximum reactive, followed by what? Now among these, this carbocation is stabilized by 9 alpha hydrogens, this carbocation is stabilized by 6 alpha hydrogens. So second one, then comes the first one. So 3 to 1 is going to be the order. Right, people? It's simple. Let's move on to one more. Okay, elimination reaction of 2-bromopentane to form pent-2-ane. What all things it follow? Is it going to be beta elimination reaction? Is it going to follow Zaitsev's rule? Is it going to show dehydrohalogenation? Is it going to be dehydration? What it's all about? See, the first one is absolutely correct. It is the beta elimination, right? It is the beta elimination. This is something we have seen a lot of examples till now. It's going to follow this Zaitsev's rule, absolutely. Dehydrohalogenation, absolutely. Dehydration, no way. So A, B, and C are going to be answers of this question, right? Right, people? Simple? Yeah? Perfect. Okay, which of these can be used as moth repellent? What is going to be the answer of this one? It's a memory based one. Kill it. Is it going to be hexachloroethane? Is it going to be hexachloroethane? Yeah? Absolutely, it's going to be hexachloroethane, people. Correct? These are all memory based questions. Okay, Freon, difluoromethane is used in refrigerators. That's something which you all know. Which of the following is used as fire extinguisher? It's going to be CCl4, right? Yes. Phosgene, it is going to be carbonyl chloride, COCl2. So with this, your haloalkane arene is over. Correct? With this, your haloalkane arene is over. I'm sure it's clear. So people do remember all this. Do remember all this. So let's take a break, guys. Right, then we'll be starting with the mole concept, right? So the time currently is 5:48. I'll see you guys exactly at 6:05, yeah? I'll see you guys exactly at 6:05. Break till 6:05, then we'll be starting with the mole concept, right? Correct? We'll be starting with the mole concept. You guys can carry on till now. I'll see you guys exactly at 6:05 sharp, huh? So am I audible again? Yeah? What is going on in the chat box? Just give me a second. All right, just a second, people. Just a second. We'll be starting with the mole concept. Yeah? Yeah. Flood the chat box. Exactly. Flood the chat box. Are you guys ready to kill the mole concept now? Yeah? Right, people? Are you guys ready to kill the mole concept? Perfect. So, buzz. Thank you. Now let's get started with the mole concept, right? The break is over. I think you guys will be all fresh now. Okay. The first question on the screen. The question was asked in 1999, AIMS and 2002, right? See guys, the weight of one molecule of the compound C60H122 is, okay, what is going to be the answer of this question? See how do we solve it. First of all, as you all must be knowing, 1 AMU, 1 atomic mass unit, is nothing that is 1/12 of mass of carbon-12 atom, which is basically equal to 1.66 into 10 raised power minus 24 grams, right? That's something which you all must be doing. First of all, what I'll be doing, I'll be calculating the molecular mass of this compound. So I'll say the molecular mass, that means the mass of one molecule of this compound, it is going to be equal to carbon, its atomic mass is 12, multiplied by 60, right? Plus hydrogen, its atomic mass is 1, multiplied by 122. The value comes out to be, this is going to be 720 plus 122. What it comes exactly? This comes out to be 842 AMU. Or you can say 842 U, or you can say 842 Dalton, right? So I can say one molecule of this is 842 times heavier than 1 AMU, or I can say one molecule of this is 842 times heavier than 1/12 of mass of carbon-12 atom, right? Now, molecular mass of the substance I got, that means mass of one molecule I got as 842 AMU, which can be written as 842 multiplied by 1 AMU, and 1 AMU value, you already know that is 1.66 into 10 raised to the power minus 24 grams. So this is basically the mass of one molecule of it in grams, which I was supposed to calculate, right? Yes? Right, people? Simple? Let's move on to one more question. This was the mass of one molecule of it in grams, right? Right, people? Yeah. Wait, what did I do? What was I supposed to calculate? Just a second. The weight of one molecule, right, of a compound is, exactly, that's going to be the answer of the equation. Let's move on to one more. If Na is the Avogadro's number, then the number of valence electrons in 4.2 grams of nitride ion is. So basically, I'm given with 4.2 grams of nitride ions, and I'm supposed to calculate the number of valence electrons in it, right? So if I take one nitride ion, correct? In one nitride ion, there will be total how many electrons? How many electrons will be there in one nitride ion? Can you let me know? There will be total 10 electrons. Yeah? One nitrogen has got the atomic number of 7, as you all must be knowing. So one atom of nitrogen contains 7 electrons. So 7 plus 3 comes out to be 10 electrons. So total there are 10 electrons, correct? The number of valence electrons. So, okay. Out of these 10 electrons, 2 electrons will be in the first shell, 8 electrons will be in the second shell, and these 8 electrons are something which I'll be calling as the valence electrons, right? Yes. So people, one nitride ion basically contains 8 valence electrons, correct? One nitride ion, it contains 8 valence electrons. So I'm given with the mass of nitride, which is 4.2 grams. So first of all, I'll be calculating the number of moles of nitride. It is going to be equal to mass of nitride divided by molar mass of nitrogen. That comes out to be 14. The value is going to be 0.3. So 0.3 moles of nitride ions do we have? Yeah? Okay. I got the number of moles of nitride. Let me calculate the number of nitride ions. Number of nitride ions is going to be equal to 0.3 multiplied by Avogadro's number. So these many nitride ions we have. Correct? Now we got to know one nitride ion, it contains 8 valence electrons. One nitride ion, it contains 8 valence electrons. So 0.3 Na nitride ions will be containing 8 multiplied by 0.3 Na, which comes out to be 2.4 Na valence electrons. So basically 2.4 Na valence electrons are present in 4.2 grams of nitride. Okay, as simple as that. This is something which we are supposed to calculate, right? Right, people? Clear to everyone? Let's move on to one more. It was a very simple question. So 2.4 Na valence electrons will be there in 4.2 grams of nitride. All right, the element X has the following isotopes, right? We are supposed to calculate the average atomic mass of the element. See guys, it's a simpler one. The question was asked somewhere in AIPMT 2007. We have got the element X. It has got 3 isotopes, correct? One is X200, one more is X199, and one more is X202. These are the 3 isotopes of the element. And at the same time, I'm given with the percentage abundances of all the isotopes. Percentage abundance of the first one is given to us as 90, second one is given to us 8, third one it's given to us as 2. Remember, this is the value of M1 basically, this is the value of M2, and this is the value of M3, correct? Percentage abundances we represent by A, B, and C. What I'll be doing, I'll be calculating the average atomic mass of the element which has got isotopes, correct? And average atomic mass is calculated by the simple formula. What is the formula? It is going to be M1 multiplied by A plus M2 multiplied by B plus M3 multiplied by C divided by A plus B plus C. That's all. So M1 multiplied by A, it's going to be 200 multiplied by 90 plus M2 multiplied by B. It's going to be 199 multiplied by 8 plus M3 multiplied by C, which is going to be 202 multiplied by 2 divided by A plus B plus C. A plus B plus C comes out to be 100. You need to solve it and get the value of average atomic mass of this X, which has got 3 isotopes, which I was supposed to calculate as per the equation, right? Right, people? Very simple and basic. Okay, moving on to one more. This is one more question. At 27 degrees centigrade and 180 M pressure, a given mixture of O2 and SO2 contains gases in 2:1 volume ratio. Calculate the number of moles present in 20 grams of the mixture. 20 grams of the mixture. See how I'll be solving this question. See how I'll be solving this question. Have a look, guys, properly. So basically, I've got a container. In this container, what do I have? In this container, I have got O2, and at the same time, I have got SO2. We have got 2 gases in the container. So basically, I've got a mixture of gas. And this mixture of gas is present at constant pressure and temperature, right? The pressure and temperature of this mixture is kept constant, right? It does not change at all. It is kept constant, correct? Now we will have a look. Have a look properly what I'm going to do. See, first of all, the total mass of the mixture is given to me as 20 grams, right? Mass of the mixture is given to me as 20 grams, correct? Mass of the mixture is given to me as 20 grams. What do I need to calculate? I need to calculate total moles present in 20 grams of mixture, which is going to be equal to given mass of mixture divided by molar mass of the mixture, and molar mass of the mixture is something which we call as average molar mass of it, right? MAV. Yes? So mass of the mixture I'm given with, that's 20 grams divided by MAV. I need to calculate average molar mass of this gaseous mixture. I need to calculate, right? Okay, average molar mass of this gaseous mixture I need to calculate. Now the point is, how do we do it? Understand. Let me call this as gas 1. Let me call this as gas 2. What is the molar mass of oxygen, which I represent by M1? It is 32 grams per mole. What is the molar mass of SO2? As you all must be knowing, 64 grams per mole. I'm given with the volume ratio of both. I'm given with their volume ratio as 2:1. I'm given with the volume ratio as 2:1. Let me call this as V1. Let me call this as V2. People, I have told you in the last session itself how to calculate average molar mass of the mixture which is present at constant pressure and temperature. Yes? Right? Right, people? So let me calculate first of all the M average molar mass of the gaseous mixture which is present at fixed pressure and temperature. It's going to be simply equal to M1 V1 plus M2 V2 divided by V1 plus V2. This is how you'll be calculating the average molar mass of the mixture. And it's going to be equal to M1 multiplied by V1, 32 multiplied by 2, that's 64, plus 64 multiplied by 1, that's 64, divided by 2 plus 1 is 3, so 128 divided by 3 grams per mole is basically the average molar mass of the mixture. So I got the average molar mass of the mixture. Now let's calculate the total moles present in the mixture, which is going to be equal to given mass of the mixture divided by average molar mass of the mixture, which is 128 divided by 3, value comes out to be 60 divided by 128. So these many total moles are present in 20 grams of the mixture, which I was supposed to calculate. I'm sure it is clear to everyone, right? Right, people? Clear to everyone? Yeah? Wonderful. Okay, let's move on to one more. This is one more question, guys. This is something which is a simpler one again. So basically, again, I'm given with a mixture of gases. I'm given with carbon dioxide, and with this carbon dioxide, you are given with oxygen. Correct? You are given with oxygen. And at the same time, let me call this carbon dioxide as gas 1, let me call this as gas 2. Correct? I'm given with the mole percent of carbon dioxide as well as mole percent of oxygen. Well, mole percent of carbon dioxide is given to me as 60, mole percent of oxygen is given to me as 40. Well, if you know the mole percent of these gases, you can calculate their mole fractions. So mole fraction of gas 1 is going to be 60 divided by 100, which is 0.6. Mole fraction of gas 2 is going to be 40 divided by 100, which is 0.4. What I need to calculate? I need to calculate average molar mass of the mixture. There is a one simple formula to calculate average molar mass of the mixture, which is M1 multiplied by Chi1 plus M2 multiplied by Chi2. That's all. What is the value of M1? M1 is the molar mass of gas 1, carbon dioxide, which is 44. What is the value of Chi1? Chi1 value is 0.6, right? What is the M2 value? M2 value is molar mass of oxygen, that is 32. What is Chi2 value? That is 0.4. You need to solve it. You'll be getting the value, I think something as 39 grams per mole, right? This is the average molar mass of the gaseous mixture which we have in the container, for which I was supposed to calculate the average molar mass. Clear to everyone? Right, people? Yeah? Perfect, that's great. Okay, let's move on to one more then. This is one more question, guys. A simpler one based on the limiting reagent concept. See, I'm starting with H2 gas. I'm making this H2 gas to react with Cl2 gas, right? And everything happens at STP. It will lead to the formation of HCl gas, right? This is the reaction which is taking place. First of all, what I'll be doing is I'll be balancing the reaction. This should be simply 2 times. Stoichiometric coefficient, right here is 1, right here is 1, right here it is 2, okay? Right? Now, people, have a look. I'm given with 22.4 liters of H2 gas. How many moles of H2 gas are given with, right? We are given with basically 1 mole of H2 gas, because 1 mole of any gas at STP occupies 22.4 liters. So basically I'm given with 1 mole of H2 gas, right? Or you can do one thing, 22.4 given volume of gas divided by 22.4, value comes out to be 1, right? Given volume of gas 11.2 divided by 2 and 22.4, value comes out to be 0.5. So I'm given with 0.5 moles of Cl2 as well. This will be 0 because the reaction has not started, right? Now, people, understand. What do I need to calculate? The number of moles of HCl formed. So first of all, I need to know which one is the limiting reagent among the two. How do we identify the limiting reagent? Divide the moles of reactants by their respective stoichiometric coefficients, right? Value comes out to be 1, this value comes out to be 5. Lesser value 1 is going to be my limiting reagent. So Cl2 is my limiting reagent. That means H2 is my excess reagent, right? So I got to know which one is the limiting reagent. Cl2 is the limiting reagent. If Cl2 is the limiting reagent, it would be completely consumed in the reaction. I'll be left with 0 moles of Cl2 at the end of the reaction, right? And we know entire product is decided by the limiting reagent. Have a look. 1 mole of Cl2 gives 2 moles of HCl. So 0.5 moles of Cl2 will give 0.5 multiplied by 2. The value is going to be 1 mole of HCl. So finally, 1 mole of HCl will get formed at the end of the reaction. That's something which I was supposed to calculate. Right? Clear to everyone? Right, people? Exactly. So let's move on to one more then. Let's move on to one more. This is one more question. It is a very simple and ordinary question. See guys, I'm given with KClO3, right? I'm given with KClO3. We are heating this KClO3, and when KClO3 is heated, it gets converted to KCl solid, and with this you get oxygen gas as well. Let's first of all balance the reaction. This should be 2 times, this should be 2 times, this should be 3 times, right? I'm given with some 12.25 grams of KClO3. So first of all, let me calculate the number of moles of KClO3 which we have, which is going to be equal to mass of KClO3 divided by molar mass of KClO3. The value comes out to be 0.1. So basically these many moles of KClO3 we have, right? Okay, now we will have a look. Can I say from the stoichiometry of the reaction, 2 moles of KClO3 gives 3 moles of oxygen. 1 mole of KClO3 gives 3 by 2 moles of oxygen. So I can say 0.1 moles of KClO3 should give me 3 by 2 multiplied by 0.1. Value comes out to be 0.1 moles of oxygen. So finally you got to know 0.15 moles of oxygen are liberated, right? But am I supposed to calculate moles of oxygen liberated? Mass of oxygen liberated. I need to calculate the mass of oxygen liberated. And mass of oxygen liberated will be equal to number of moles of oxygen liberated multiplied by molar mass of oxygen, that is 32. The value will come out to be 4.8 grams. So these many grams of O2 are basically getting liberated at the end of the reaction, right? Clear to everyone? Right, people? Okay, let's move on to one more question then. This is one more question. The number of moles of hydrogen molecules required to produce 20 moles of ammonia. It's a simple question, guys. See, N2 reacting with H2 leads the formation of NH3, right? Leads the formation of NH3. Let's try to balance the reaction. This should be 3 times, this should be 2 times, right? The number of moles of hydrogen required to produce 20 moles of ammonia. Can I say 2 moles of ammonia are produced from 3 moles of hydrogen? 2 moles of ammonia are produced from 3 moles of hydrogen. Can I say 1 mole of ammonia is produced from 3 by 2 moles of hydrogen? Can I say 20 moles of ammonia will be produced from 3 by 2 multiplied by 20? The value comes out to be 30 moles of hydrogen, right? So basically 30 moles of hydrogen are required to produce 20 moles of ammonia. Correct? That's it. That's it, right? 30 moles of hydrogen are required to produce 20 moles of ammonia. That's something which I was supposed to check, and the question is done and dusted, right? Perfect. Yes? Clear. Shashwat, this is the English channel, bro. I'm not supposed to talk in Hindi. Yeah, this is the English channel. This channel is particularly for the students who cannot understand Hindi. Okay? Moving on to one more then. This is one more question. Calculate the mass of H3PO4 which contains 0.25 moles of oxygen atoms, right? See guys how this question is to be solved. If I'll be having 1 mole of H3PO4, 1 mole of H3PO4, it contains some 4 moles of oxygen atoms, right? Right? It's simple. 1 mole of H3PO4, it contains some 4 moles of oxygen atoms. What I'll do is, I'll just reverse the same thing. Can I say 4 moles of oxygen atoms, 4 moles of oxygen atoms are present in 1 mole of H3PO4, right? 1 mole of H3PO4. I can say something like this, right? Yes? Right? 4 moles of oxygen atoms are present in 1 mole of H3PO4. So I can say 1 mole of oxygen atoms are present in 1 by 4 moles of H3PO4, right? So 0.25 moles of oxygen atoms, 0.25 moles of oxygen atoms will be present in 1 by 4 multiplied by 0.25 moles of H3PO4. So basically, these are the moles of H3PO4 which contains 0.25 moles of oxygen atoms, right? So I got the number of moles of H3PO4. how many moles of H3PO4 contains 0.25 moles of oxygen atoms? It's going to be 1 by 4. This is 1 by 4, so 1 by 16. 1 by 16 moles of H3PO4 contains 0.25 moles of oxygen atoms. But am I supposed to calculate? Am I supposed to calculate the moles of H3PO4 or mass of H3PO4? I need to calculate mass of H3PO4. So I'll be writing mass of H3PO4, which contains some 0.25 moles of oxygen atoms, is going to be equal. Moles of H3PO4 1 by 16 multiplied by molar mass 98. The value will be approximately 6.1 grams, right? So 6.1 grams of H3PO4 will be actually containing 0.25 moles of oxygen atoms, right? Yes, the equation is done and dusted. Yes, people? Anushka, there is a problem from your end only. On my side, screen is all clear. I can see the screen in front of me. Yeah? You just refresh your page or do whatever. Right? Or just increase the video quality or something, it'll be fine. Perfect. One more question, guys. One more question again from the stoichiometry. Simpler one. Yeah? Simpler one. 3 times NO2 plus H2O liquid gives 2 times HNO3 aqueous plus NO. How many grams of NO2 are required to produce 25.2 grams of HNO3, right? How many grams of NO2 are required to produce 25.2 grams of HNO3 at STP, right? Okay. So first of all, what is the molar mass of NO2? Nitrogen has got the molar mass of 14. O2 has got the molar mass of 32. Value comes out to be 4 to 6, 46. So 46 grams is the mass of 1 mole of NO2. But right here, do we have 1 mole of NO2? No, we have 3 moles of NO2. So multiply this term by 3. So what is going to be mass of 3 moles of NO2? 3, 6, 18, right? 3, 4, 12, 138. So mass of 3 moles of NO2 is simply 138 grams, right? Similarly, what is the mass of 2 moles of HNO3? Mass of 1 mole of HNO3, that's something which we call as molar mass of HNO3, which is 63 grams. 63 multiplied by 2 comes out to be 126 grams. 126 grams is the mass of 2 moles of HNO3, right? Yeah? Okay, 126 grams is the mass of 2 moles of HNO3. Now people have a look. Can I say 126 grams of HNO3 are produced from 138 grams of NO2? Absolutely. So 1 gram of HNO3 is going to get produced from 138 divided by 126 grams of NO2, correct? So can I say 25.2 grams of HNO3 will be produced from 138 divided by 126 multiplied by 25.2 grams of NO2. So these many grams of NO2 are required to produce 25.2 grams of HNO3. The equation is done and dusted, right? Yes? Right, people? Clear to everyone? Shashwat is asking, sir, where I have to go for Hindi? There is one more Hindi channel for us in Vedantu for the NEET students. That is Vedantu NEET Made Easy, right? Okay, you can go there. That is the Hindi channel, right? The teachers are brilliant. You'll definitely have fun. Okay, so people, this is the mass of NO2 which is required to produce 25.2 grams of HNO3. That's something which I was supposed to calculate, right? Okay. Perfect. Rakshit, you can just drag the video a little back. It will be a replay for you. Okay, fine. So finally the answer comes out to be 27.6 grams. So 27.6 grams of NO2 are required to produce 25.2 grams of HNO3 at STP, right? This is one more question from the concept of limiting reagent, right? Yes? Right? See guys, how do we solve this? I'm given the reaction and the reaction is given in the balanced form, right? Initially at time t is equal to 0, I'm given with 0.1 moles of BaCl2. I'm given with 0.3 moles of Na3PO4. This is going to be 0, this is going to be 0 because the reaction has not started yet, right? Because the reaction has not started yet now. I'm given with the amounts of all the reactants, and whenever I'll be given with the amounts of all the reactants, at that time we use the concept of limiting reagent. And the first step in order to do the limiting reagent concept is to balance the reaction, and the reaction is already balanced, yeah? Now, let's identify the limiting reagent. Divide the respective moles of reactants by their respective stoichiometric coefficients. Stoichiometric coefficient is 3. Over here, stoichiometric coefficient is 2. 0.1 divided by 3 will come out to be 0.033. This will come out to be 0.15. Which value is lesser? This value is lesser. So BaCl2 is my limiting reagent. BaCl2 is my limiting reagent. I got to know which one is the limiting reagent, right? I got to know which one is the limiting reagent. Okay. Now people, if BaCl2 is the limiting reagent, it will get completely consumed in the reaction. Okay. And entire product is governed, is decided by the limiting reagent. Now it's simple. See guys, 3 moles of BaCl2 gives 1 mole of Ba3PO4 whole twice. So 1 mole of BaCl2 gives 1 by 3 moles. 0.1 moles will give 1 by 3 multiplied by 0.1 moles of Ba3PO4, which will come out to be 0.033. So these many moles of Ba3PO4 whole twice will be produced at the end of the reaction. Yes? Okay? Right people? So 0.033 moles of Ba3PO4 whole twice will be produced at the end of the reaction. I'm sure it's clear to everyone, right? Yes? Simple. Let's move on to one more. Let's move on to one more. Okay, so you got the moles of Ba3PO4 whole twice. You can calculate its mass as well. Just multiply the moles of Ba3PO4 whole twice by its respective molar mass. You'll be getting the mass of it which got formed, right? Yes, people? Let's move on to one more. 1.12 grams. Tanushri, there is an option on YouTube. What is that option? You can drag the video back. It'll be a replay. It'll be a repetition, right? Yeah? Okay, so people, how do we solve this question? We are supposed to calculate the percentage yield of the reaction. I hope you guys remember the formula to calculate percentage yield of the reaction. Yeah? I hope you remember the formula to calculate percentage yield of the reaction. Do you guys remember that? Can you let me know in the chat box what is the formula exactly to calculate percentage yield of the reaction? Exactly. Exactly, guys. By the way, this is our 900th slide. Yeah? This is our 900th slide. Yeah? Okay, how do we calculate the percentage yield of the reaction? There is a simple formula to calculate percentage yield. Let me write the formula first of all. Percentage yield is equal to experimental amount divided by expected amount multiplied by 100. This is the formula by means of which you can calculate percentage yield, right? Now see, this is the reaction given to me, and as per the equation itself, it is mentioned that 1.12 grams of calcium oxide is reacted with the excess of HCl and 1.776 grams of CaCl2 are obtained, right? So that's something which is done in laboratory, right? It is actually seen that on making 1.12 grams of calcium oxide to react with HCl, we get 1.776 grams of CaCl2. So this is something which I call as experimental amount of CaCl2 which have got formed. This is something which has been observed experimentally, right? So in order to calculate percentage yield, I need the experimental amount which I already have as per the equation. Now I need the expected amount which I'll be getting by using the stoichiometry, right? Right, people? Correct? That's all. That's what I'll be doing. That's all what I'll be doing. Right? See guys, it's simple now. It's simple. First of all, what is the molar mass of calcium oxide? Calcium 40, oxygen 16. That means 56 grams. Yeah? What is the molar mass of CaCl2? Cl2 means 71 plus 40. That's 111 grams. Can I say 56 grams of calcium oxide should produce 111 grams of CaCl2? I'm using the term should produce, right? It should give 111 grams of CaCl2. So 1 gram of calcium oxide should produce 111 divided by 56 grams of CaCl2. Yes? So can I say 1.12 grams of calcium oxide should produce 111 divided by 56 multiplied by 1.12 grams of CaCl2. So these many grams of CaCl2 should have got produced, right? These many grams of calcium chloride should have got produced, correct? And this value, as far as I remember, it comes out to be something as 2.2 grams. So 2.2 grams of CaCl2 should have got produced. So this is something which I was expecting. I was expecting some 1.12 grams of calcium oxide to produce 2.2 grams of calcium chloride, right? So this is something which I'll be calling as the expected amount. Well, people, you got the experimental amount, you got the expected amount, divide the two, multiplied by 100, that's it. That's it. Yes. So percentage yield will be equal to experimental amount, which is equal to 1.776 for CaCl2 divided by expected amount of CaCl2, which is 2.2, multiplied by 100, solve it, that's going to give you the percentage yield of the reaction, right? Yes, people? Clear to everyone? You can let me know in the chat box if it is clear fast. Yeah? Perfecto. The reaction will be given to you. Reaction will be given to you. So exactly the answer will be approximately something as 80%. So 80% is going to be percentage yield of this reaction. Yes? Perfect, guys. Let's move on to one more then. Let's move on to one more. This is one more question. Okay, so 20 grams of magnesium carbonate sample decomposes on heating to give carbon dioxide, all right? And 8 grams of magnesium oxide is produced, fine. What will be the percentage purity of magnesium carbonate in the sample? So basically, I'm given with an impure sample which contains magnesium carbonate, right? I'm given with an impure sample which contains magnesium carbonate, okay? And if I'll heat up that sample, whatever magnesium carbonate would be present in that sample, it will decompose into magnesium oxide. With this, you'll be getting carbon dioxide gas as well, right? Yes. So basically, what do we have? Basically, we have got an impure sample in which there is magnesium carbonate. I'm burning that impure sample. I'm decomposing that impure sample. So whatever magnesium carbonate will be there in the impure sample, that will be getting converted into magnesium oxide and carbon dioxide, correct? The reaction is balanced. The reaction is balanced. First of all, this 20 grams of magnesium carbonate sample. So this 20 grams is the mass of impure sample which contains magnesium carbonate as well, right? This is the mass of whole impure sample. This is the mass of whole impure sample, right? Yeah? Right? This is the mass of impure sample. How do we calculate percentage purity? Let me give you the formula first. Percentage purity is nothing. It is mass of pure compound. Mass of pure compound divided by mass of impure sample multiplied by 100. So mass of impure sample is something which I'm given with. That is how much? That is 20 grams. So I need to calculate the mass of pure magnesium carbonate in the sample. How do I calculate mass of pure magnesium carbonate in the sample? I'll be using stoichiometry for that. See how come? See, guys, understand? See, first of all, what is the molar mass of magnesium carbonate? Magnesium is 24. 24 plus 12 is 36. 36 plus 48. 36 plus 40 is 84, right? So 84 grams is the molar mass of magnesium carbonate, or you can say 84 grams is the mass of 1 mole of magnesium carbonate, right? Okay, so what is the, just a second. Okay, what is the molar mass of magnesium oxide? 24 plus 16. 24 plus 16 comes out to be 40, right? So 40 grams is the mass of 1 mole of magnesium oxide, correct? Can I say 40 grams of magnesium oxide are produced from 84 grams of magnesium carbonate? So 1 gram of magnesium oxide would have got produced from 84 divided by 40 grams of magnesium carbonate, right? So 8 grams of magnesium oxide should have got produced from 84 divided by 40 multiplied by 8 grams of magnesium carbonate, right? So 8 grams of magnesium oxide will be actually produced from these many grams of magnesium carbonate. And in the reaction, only pure mass of magnesium carbonate participates. So you got to know, if we are getting 8 grams of magnesium oxide from this reaction, that means these many grams of magnesium carbonate would have got consumed in the reaction. And only pure mass of magnesium carbonate would have got consumed. So this is the mass of pure magnesium carbonate which has got consumed in the reaction. So this is the mass of pure magnesium carbonate. I got the mass of pure magnesium carbonate. We have got the mass of impure sample. Just the percentage purity of magnesium carbonate is something which you can calculate now. So percentage purity is going to be equal. Mass of pure magnesium carbonate. It's going to be 8.1. This is going to be 8.5, right? So it will come out to be 5 1s are 5, 5 7s are around 16 point something, right? 16.8. So mass of pure magnesium carbonate which participate in the reaction is 16.8 grams. Mass of impure sample is 20 grams. Multiplied by 100, solid, you'll be getting the percentage purity of magnesium carbonate in the sample, right? I'm sure it's clear to everyone. Right, people? I'm sure it's clear. So people are saying 84%, all right? If 84% or 80%, whatever you're getting, that is going to be the percentage purity of magnesium carbonate in the impure sample, right? Okay, moving on to one more. 6.02 into 10 raised power 20 molecules of urea are present in 100 ml of its solution. The concentration of solution is, concentration means molarity. How do we calculate molarity of the solution? Number of moles of solute divided by volume of solution in liters, right? So these many molecules of solute we have, let me convert these molecules into moles. I'll say number of moles of urea, number of moles of solute will be equal given number of molecules of urea divided by Avogadro's number. The value comes out to be how much? It comes out to be 10 raised power minus 3, right? So these many moles of solute we have basically, right? These many moles of solute we have basically. So I have the moles of solute divided by volume of solution in liters. I'm given with 100 ml of solution. Just divide it with 1000, right? It's going to be 1 by 10. So we have got 1 by 10 liters of solution, correct? 1 by 10 liters of solution, right? That 10 goes up. So 10 raised power minus 3 multiplied by 10, the value comes out to be 10 raised power minus 2. So this is basically the molarity of the solution. That means 10 raised power minus 2 moles of urea are present in 1 liter of solution. The question is done and dusted, right? Yeah? Right, people? Exactly. Let's move on to one more then. Okay, dissolving 120 grams of urea in 1000 grams of water gave a solution of density this much. The molarity of the solution is, okay, before solving this question, let me have some water. Kaushik, is that? Yes, we are starting on the actual Vedantu platform. Me, Shimon sir and Hrs sir, we are starting a crash course. Not a crash course, sorry. It is basically the micro course, right? Chapter-wise micro courses for class 11th and class 12th people. You can join in, right? We'll be letting you know about that in detail. Yeah? Okay? Let's move on. Amir knows why I'm laughing, yeah? Okay. Yeah, it's going to be a micro course. Okay, let's try to solve this question, guys. It's a very simple one. I need to calculate molarity of the solution. Molarity of the solution. What is the formula to calculate molarity of the solution? Mass of solute in grams multiplied by 1000 divided by molar mass of solute multiplied by volume of solution in milliliters, right? This is a formula. This is a general formula by means of which we can calculate molarity. Yes? Okay. Now see what all parameters am I given with. I'm given with the mass of urea. I'm given with the mass of solute, 120 grams. So W2 value is given to me. W2 value is given to me. Mass of solute, mass of urea is given to me as 120. What is the formula for urea? NH2CONH2. That is the formula for urea, right? So what is going to be molar mass of urea? Molar mass of urea is going to be 60 grams per mole. Right? Molar mass of urea. Well, I'm given with the mass of solvent as well. W1 I'm given with mass of solvent. It is given to me as 1000 grams. Okay, density of the solution is given to me as density of solution is given to me as well, which is 1.15 grams per ml. What do we need to calculate? We need to calculate molarity. In order to calculate molarity, we should have the value of W2. Do we have it? Absolutely. We should have the molar mass of solute. Do we have it? Absolutely, we have it, right? We need the volume of solution, which is not given. So how do I calculate the volume of solution? There is a parameter, density parameter, which is given to me, right? There is a density parameter given to me. So I'll write something like this. Density of solution is nothing. That is mass of solution in grams divided by volume of solution in milliliters, right? This value is given to us as 1.15, correct? Right? What is the mass of solution? Mass of solution means mass of solute plus mass of solvent. So 1000 plus 120 will be 1120. It will be 1120 grams divided by 1.15. This is going to give you the volume of solution in milliliters. This is going to give you volume of solution in milliliters, right? And as far as I remember, this value will approximately come out to be 973 ml. Something like this, right? This is the volume of solution. This is the volume of solution, right? Now everything I have, I can write the molarity of the solution is equal to W2. W2 is the mass of solute, which is 120 grams, multiplied by 1000, divided by molar mass of solute, that's 60 grams, volume of solution in milliliters, that's 973, and when you solve it, you will get the approximate value as 2.05. So 2.05 is basically the molarity of the solution. That means 2.05 moles of solute of urea are present in 1 liter of solution, right? Yes? Perfect? Okay. Moving on to one more question. This is one more question, guys. A simple question. Calculate weight by weight percent of solute of 1.5 mole CH3COH solution where density is 0.8. People, I hope you remember I had given you one formula. General formula, molarity is equal to 10 multiplied by density of solution multiplied by weight percent of solute divided by molar mass of solute. I hope you remember this. I hope you remember this result. Right, people? I hope you remember this result. Correct? Now, what do I need to calculate? I need to calculate the weight by weight percent of solute. This term I need to calculate. Molarity is given to me as 1.5 is equal to 10 multiplied by density of solution is given to me as 0.8. Weight by weight percent of solute I need to calculate divided by molar mass of solute. Molar mass of CH3COH, you can calculate it. This is 12, this is 12, 24. 24 plus 4 is 28. 28 plus 32 comes out to be 60, right? This is 60. By solving this equation, you will be getting the weight by weight percent of solute. That's something which I was supposed to calculate, and the value will approximately come out to be 11 point something, right? 11.2% is going to be something as the weight by weight percent of solute, which I was supposed to calculate, right, people? Clear to everyone? Clear to everyone? Let me know fast. Is it clear? Yeah? Okay? Let's move on. Let's try to solve a few more questions. Okay, calculate the molality of KCl solution which is prepared by dissolving 7.45 grams of KCl in 500 ml of solution. Given density of the solution is this much. I need to calculate molality of the solution, right? I need to calculate the molality of the solution. Well, people, there is a simple formula by means of which you can calculate molality. It is going to be equal to mass of solute in grams multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent in grams. This is something which you all must be knowing, correct? Yes? Right, people? See, calculate the molality of KCl solution prepared by dissolving 7.45 grams of KCl. So mass of solute, which I'm representing by W2, it is given to me as 7.45 grams. This is the mass of solute. Volume of solution is also given to me. Volume of solution is given to me as well, which is 500 ml. Correct? Do I know the molar mass of KCl, molar mass of solute? Yes, which is going to be 74.5 grams per mole. Yeah. Do I know the density of solution? Yes, we know it. Density of solution is given to me as 1.2 grams per ml. 1.2 grams per ml. Density of solution is nothing, that is mass of solution divided by volume of solution. This value is given to me as 1.2 grams per ml, right? So from here, I can calculate mass of solution, which is going to be equal to 1.2 multiplied by volume of solution is given to me as 500, right? So 1.2 multiplied by 500 ml, the value comes out to be 600 grams. So this is the mass of solution. But do I need mass of solution here? No, we need mass of solvent, right? We need mass of solvent. Mass of solution I have, mass of solute I have. So mass of solvent can be calculated. Mass of solvent is going to be equal to 600 minus 7.45, which comes out to be 592.55. So these many grams of solvent I have. Correct? Now you got everything. Calculate the molality. Mass of solute is 7.45 grams multiplied by 1000. Molar mass of solute is 74.5 grams per mole. W1 mass of solvent, which is 592.55, right? Solid, it's going to give you the molality of the solution. That's something I was supposed to calculate. I'm sure it's clear to everyone, right? Right, people? It must be clear to you. Simple, use the formula. Get all the parameters which are required in order to solve this one, right? And kill it. Yeah? Okay, let's move on. Let's move on. All right, how much water should be added to, see guys, it is simple, molarity of dilution, M1V1 is equal to M2V2, right? How much water means final volume minus initial volume you are supposed to calculate. This is something you can do, right? This is something you can do. This is something you can do on your own. Yeah? Okay, right? You will be calculating the final volume. After calculating the final volume, you'll be doing the final volume minus initial volume. You'll be getting the amount of water added. That's simple, correct? Okay. A compound contains this much percentage of oxygen, this much percentage of nitrogen, and its molecular weight is 92. The formula of the compound is, right? We are supposed to calculate the molecular formula of the compound, right? We are supposed to calculate the molecular formula of the compound. So first of all, I'll be calculating the empirical formula. After calculating the empirical formula, I'll be getting the empirical formula mass. Then I'll divide the molecular mass by the empirical formula mass. I'll be getting something as N. Once I get N, I'll be getting the molecular formula. See, I'll be directly showing the solution. See guys, the percentage of nitrogen is given to me and the percentage of oxygen is given to me. Let's first of all divide these percentages by their respective atomic masses, right? So you get atomic ratio over here, 2.18, 4.38. Which one is the least value among all? 2.18. Divide both the ones by the least value, 2.18. You got 1 over here. You got approximately 2 over here. You got the least atomic ratio, 1, 2, right? Least atomic ratio is something which is what we call as empirical formula. So you got N1O2. NO2 you got as the empirical formula, correct? You got the empirical formula as NO2. Once you get the empirical formula, calculate the empirical formula mass, which will be 14 plus 32. That means 46. So 46 grams is the empirical formula mass, right? So 46 AMU is the empirical formula mass. Once you get the empirical formula mass, get the value of N, which is the molecular mass, that is 92, divided by empirical formula mass, that is 46, value comes out to be N. The formula then is molecular formula is equal to empirical formula multiplied by N. So finally the molecular formula comes out to be N2O4. It's simple, correct? This is something which you love to solve, I believe, yeah? Correct? Because these are very simple questions. Yeah? Right? Okay, so which chapter you want me to start next? Is it atomic structure? Or you want me to start chemical bonding? Or you want me to start states of matter? Or you want me to start thermodynamics or equilibrium or whatever? Let me know first. Let me know first in the charts. Which chapter you want me to start next? I think atomic structure is something which you can do on your own, right? Yes? So people are coming over the chemical equilibrium and thermodynamics, right? or chemical bonding if you are saying. Just give me a second. All right, let's do the chemical bonding first, yeah? Let's do the chemical bonding. Because from chemical bonding, 3-4 questions, I mean minimum of 3 questions will come in your NEET, yeah? Let's do the chemical bonding first. That won't take a lot of time as well, because in chemical equilibrium and thermodynamics, we need to solve a lot, right? So that will take time. So let's get started with chemical bonding, but before that, let's take a rest for 2-3 minutes. Then we'll be starting, right? Correct, guys? No, Divya, I cannot do that. Okay, let's start with the chemical bonding then, right? Yes. I'm starting one course for NEET 2022 students as well, right? Yeah. So just a second, let me find the chemical bonding. So till now we have done some 930 slides, yeah? Wait guys, it might take some time, just a second. Yeah. So let's start with the chemical bonding then, right? Excited for it? Excited for it, right? Let's see, Ranjit, I have no idea. Okay, so the first question, it is a simpler one, right? Kill this one, guys. Let me know its answer. It's not even a question. This is something which we study in class 11th, right? The attractive force which holds atoms, ions together in the chemical species is something which we call as chemical bond. Leave it. Which of the following does not represent the correct Lewis symbol? Okay, which of the following does not correctly represent the Lewis symbol? Can you give it a try? Let me know its answer fast. What do you think? People are coming up with option B, 2, 3 and 4. Is that? 2, 3 and 4. Yeah? So people, it's going to be option D is going to be correct answer of this question. Option D. See, valence electrons in oxygens are 6. In oxygen, valence electrons are 6, but over here it's mentioned as 5. Correct? Similarly, in case of neon, valence electrons are 8. Over here it's mentioned at only 6, right? So this is incorrect, this is incorrect. Beryllium, absolutely 2 electrons. Boron, 3 electrons. Carbon, 4 electrons. Rest all the ones are same, correct? So option D is the one which is correct among all. The bond formed as a result of electrostatic force of attraction between positive and negative ions is something which we call as ionic bond, or you call it as electrovalent bond, right? Yes, so option B is the one. These are all theoretical questions. Cation and anion combines in a crystal to form which type of a compound? Ionic compound, right? Electrovalency of calcium is +2, chlorine -1. Yeah? Right? These are all theoretical questions. These are basic questions which we have studied in class 11th. Correct, people? So +2 and -1. Okay. When a metal atom combines with a non-metal atom, the non-metal atom will lose electrons and decrease in size. Lose electrons? No. See, metal loses electron, non-metal atom gains electron. Right? Non-metal atom gains electron and its size increases. Right? So option D is the one which is the correct answer among all. See, in case of sodium, in case of NaCl, sodium is the metal, it loses electron, gets converted into cation. Size of cation is always less than that of the size of its respective parent atom, and size of anion is always more than that of size of its respective parent atom. Correct? So option 4 is the one which is correct among all. In N2 molecule, the number of electrons shared by the nitrogen atoms is, what is going to be the answer of this question? N2, there's a triple bond in between. The answer is going to be 3. 3 electrons are equally shared, right? Right, people? By each nitrogen atom. Yeah? Okay, among the following, the electron deficient compound is, which of the following is electron deficient? What do you think? I think BCl3, because its octet is not complete. It has got only 6 electrons. The boron has got only 6 electrons in its outermost shell. It's not complete, so it's going to be electron deficient species. Rest, in all the cases, the octet is complete. So option A is the answer of this question. Yeah? Okay, which of the following is electron deficient? Which of the following is electron deficient? Can you let me know fast? Which of the following is electron deficient? It is going to be B2H6, right? This one BH3 twice. This one is something which is electron deficient. Yeah? Okay, if I'll ask you how many 3-centered 2-electron bonds are there? There are 2 3-centered 2-electron bonds, and there are 4 2-centered 2-electron bonds, right? Basic question again. The pair of compounds which have odd electrons, NO and ClO2, these are the common examples of the odd electron species, right? Yes, so NO and ClO2, these are the odd electron species. Which of the following compounds does not follow the octet rule? Check it out. PCl5, phosphorus has some 10 electrons in its outermost shell as per this, right? So it's not following octet rule because it's forming some 5 bonds. So 10 electrons in its outermost shell. So option A. Yeah? Okay, one more. The correct order of O single bond, O length in O2, H2O2 and O3. See guys, in case of O2 there's a double bond. In case of O2 there's a double bond, right? In case of H2O2, hydrogen peroxide structure, there is a single bond between 2 oxygen atoms. And in case of O3, there is a case of resonance, right? It gets partial double bond character. See, in this case, there is a pure double bond, right? In this case, between 2 oxygen atoms, there is pure single bond. In this case, due to resonance, there is the partial double bond character, right? Okay, now you can compare the bond lengths, right? You can compare O bond lengths. O bond length will be minimum in O2, followed by O3, followed by H2O2. This is going to be the order of the bond length OO. Yes? Yes, Kavi, this is live. This is a live session going on. Yeah? So this is the order. You can reverse it as well. H2O2, O3 and O2. This is going to be the order of the bond lengths. Okay, ionic bond will be formed more easily between elements with comparatively A and B. What is it? With comparatively A, an element with comparatively high electronegativity value of B. Okay, ionic bond will be formed more easily between element with comparatively low ionization energy, right? Low ionization energy and with comparatively high negative value of electron gain enthalpy, right? So option B is the one which is correct among all. Yeah? Right, people? See, metals should have low ionization energy, non-metals should have high electron gain enthalpy, then only ionic bond gets formed easily, right? Yes, that's something which you all must be knowing. Okay, the isoelectronic set of ions. set of ions containing same number of electrons. F negative contains 10 electrons, Li positive, no way, right? No way. This one, no. N tri-negative, 10 electrons, O di-negative, 10 electrons, F negative, 10 electrons, Na positive, 10 electrons. So this is basically the set of isoelectronic species. Yeah, they contain same number of electrons, right? Okay, among the following compound, which will show highest lattice energy? Which will show highest lattice energy? Lattice energy is directly proportional to charge on ions and inversely proportional to size, right? Charge on ions everywhere is same. Now you are going to decide on the basis of size, right? Lesser the size, more is going to be the lattice energy. Among K positive, Na positive, CS positive, Na positive. Na positive has got the minimum size. Minimum size means more lattice energy. So option B is going to be the correct answer of this question, right? Which of the following bond will have highest ionic character? Which of the following bond will have highest ionic character? Check the electronegativity difference, right? Electronegativity difference is going to be maximum in HF. So HF bond is going to be highly ionic among all. Understood, right? Okay, which of the following pairs will form the most stable ionic bond? Which of the following will form most stable ionic bond? Well, I think magnesium and fluorine, right? Because you will be getting MgF2 over here. So Mg di positive, F negative. So its lattice energy will be more, right? Its lattice energy will be more. I think so. What do you think? What do you think about this one? See, if we make the compound from MgF, I mean magnesium and fluorine, it's going to be MgF2, right? Wherein cation is going to be Mg di positive, right? Charge on cation is more is the lattice energy. So the compound which is getting formed when magnesium and fluorine reacts, okay, that compound is going to have maximum lattice energy among all. So absolutely, I think B is going to be the answer of the question, and absolutely it's B, right? Yes, people? Simple? Yeah? Okay. Complete the following statements. With A in bond order, B increases, C decreases. What it's going to be? It's like a puzzle, that riddle it is, right? With A in the bond order, okay, with the increase in the bond order, bond length increases. No way, incorrect. With the decrease in the bond order, okay, bond enthalpy increases. No way. With the increase in the bond order, bond enthalpy increases, correct. Bond length decreases. Yes, option C is the one which is correct, right? Option C is the one which is correct. Yeah? Option C is the one which is correct. Okay. The number of possible resonating structures of CO3 dinegative. You know, this question was asked in this year's JEE mains question. There are 3 resonating structures for CO3 dinegative, right? These are the 3 resonating structures for CO3 dinegative. This was the question asked in this year's JEE. Okay, which of the following structure represents the structure of O3 more accurately? See, this is the resonance hybrid, and resonance hybrid, its structure, it is more closer to the actual O3 molecule, right? It is the maximum stable configuration among all, right? It is the maximum resonance hybrid is basically maximum stable among all the forms. Yeah, that's something which you all must be knowing, correct? So it's going to be absolutely option C, right? Okay, one more. Give the order of dipole moments. See guys, NH3, NF3. It looks like NF3 should have more, but NH3 has more. This is something which we have discussed many a times, right? Because the direction of the individual dipole moments in case of NH3, they are pointed in one direction, right? Whereas the individual dipole moments in case of NF3, they get cancelled out somehow, right? So NH3's dipole moment is always greater than NF3 dipole moment. That's something which you need to remember from now onwards. And I've discussed the same thing many a times in the actual sessions, yeah? Okay. All right, CCl. Chlorine is more electronegative, so delta negative, this is delta positive. This chlorine more negative, delta positive. The direction of dipole moment from positive to negative, direction of this dipole moment positive to negative. So net dipole moment will be in this way. So net dipole moment of this molecule is in this way, right? So positive to negative in this way, positive to negative in this way. The net dipole moment of this molecule, I mean, they'll try to cancel out. So the first one is going to have more dipole moment. HF, HCl, HBr, HI. What is going to be the order of dipole moments? This is going to be the order because F fluorine has got more negative charge than that of chlorine, than that of bromine, than that of iodine, right? Yes, because dipole moment, that's simple. Dipole moment is the product of charge and distance between them, right? Yes? So over here, charge dominates over everything. If charge dominates, charge on fluorine is more compared to all the halogens. So dipole moment is maximum in case of HF, correct? CH3F, CH3Cl, CH3Br, CH3I. This is something which we have discussed in haloalkane chapter as well. This one is going to have maximum dipole moment. Second is this one is third, this one is fourth, right? This is something, this question we have discussed in haloalkane arenes as well few hours back, right? NH3, PH3, absolutely NH3, nitrogen has got more charge. H2O, NH3, absolutely H2O, oxygen has got more charge. CHF3, CHCl3, absolutely CHF3, right? Right, people? Correct? Okay, one more. Give the order of dipole moments. This CH3, it's electron donating. So this will get delta positive, this will get delta negative. So dipole moment direction this way due to this bond. Similarly, this gets delta positive, this gets delta negative. So direction of dipole moment is in this way. So they try to cancel out each other's effect. So net dipole moment of the first molecule is 0. Right? Electron donating, so positive to negative. So this is the order. Positive to negative, this is the order. So what is the angle between these two dipole moments? One dipole moment is pointing downwards, one dipole moment is pointing in this way. So the angle is greater than 90. Right? What about in this case? Positive to negative, right? What is the angle between these two dipole moments? This angle is less than 90. Right? Angle is less than 90. Lesser the angle between the two dipole moments, more is the resultant, right? More will be the resultant. So what do you think about this one? What do you think about this one? So I'll say maximum dipole moment will be shown by 3, followed by 2, followed by 1. This is going to be the order. Yes? This is going to be the order. What about the next one? CH3 electron donating. So this is positive to negative, right? Positive to negative. NO2 is electron withdrawing. So positive to negative in this way. Correct? What is the angle between the two? One is pointing downwards and one is pointing in this way. So the angle is greater than 90. Right? See. Electron donating, right? Positive to negative, positive to negative. Electron withdrawing, positive to negative. What is the angle between the two? One is pointing downwards, right? One is pointing in this way. So angle is less than 90. Okay. CH3, electron donating, positive to negative. NO2, electron withdrawing, positive to negative. So net dipole moment is downwards only. So maximum dipole moment will be shown by third, followed by second, followed by first. 3 to 1 is going to be the order of dipole moments. I'm sure it's clear. Right? Right, people? I'm sure it's again clear to everyone. 3 to 1 is going to be the order. Moving on to one more. The molecule which has 0 dipole moment, it's going to be BF3. Very common question. Planar structure, right? Net dipole moment is 0. Yes, people? Okay, which of the following has the dipole moment? It's saying. See, carbon dioxide, net dipole moment is 0. Right? Para-dichlorobenzene, net dipole moment 0, right? It's going to be 1,4-dichlorobenzene. Net dipole moment of the molecule is 0. In case of NH3, net dipole moment is not 0, is non-zero, right? NH3 is a polar molecule. Its net dipole moment is non-zero, right? Yes? Right? Okay, CH4, it is a symmetrical one. Its net dipole moment is again going to be 0, right? Perfect. All right, one more. Identify the polar molecules. The one which is going to have net dipole moment non-zero, that's going to be polar. H2, net dipole moment 0, it's going to be non-polar. Net dipole moment 0, it's going to be non-polar, right? Yes. HCl, net dipole moment non-zero, it's going to be polar. HF, HBr, non-polar. HBr, non-polar, only H2 is, sorry, I'm telling the reverse, I'm sorry. See, H2, its net dipole moment is 0, so it's going to be non-polar, right? HCl, its net dipole moment is non-zero, so it's going to be polar, right? HF, polar, HBr, polar, right? So only one species is there, H2, which is basically non-polar. Simple question. Which of the following bonds will be the most polar? Which of the following is most polar among all? Can you let me know its answer fast? Oh, it's 10 hours. That's great. That's wonderful. Which of the following is the most polar among all? It's a simpler one, guys, right? It's NF. It's NF. Electronegativity difference is more in case of nitrogen and fluorine, right? If the electronegativity difference is more, that means this bond is more polar. And this is the electronegativity difference that's given to us, right? Okay, a neutral molecule XF3 has zero dipole moment. The element X is most likely to be XF3. That means it's going to be BF3, right? BF3 has got net dipole moment 0, right? BF3 has got net dipole moment 0, right? Okay, the most polar bond. You can answer this one as well. Where the electronegativity difference is more, that's going to be more polar, right? And electronegativity difference in case of carbon and fluorine is going to be more among all the cases, right? So CF bond is going to be more polar among all. Option A is the right one. Yeah? Right, people? Okay, one more. Which of the following possesses the dipole moment? Which of the following possesses the dipole moment? What is going to be the answer of this one, people? The answer is already given here, right? The answer is already given here. The answer is already given, people. You are not supposed to solve it. Answer is already given to us, yeah? Correct? Correct, correct, correct. Someone is saying, where is the answer given? Here is the answer given, right? These structures are given to us. Dipole moment, direction, everything is given to us. See, this molecule will have net dipole moment 0, right? This one will have net dipole moment 0. This one is going to have dipole moment because both the dipole moments are at some angle, correct? Okay? Right? And similarly, the other ones are also given to us. So what is going to be the answer of this question? So it is going to be SO2, H2S and SF4. These three are going to possess the dipole moment, whereas in case of SF6, due to its perfect symmetry, it's not going to possess any dipole moment, right? Okay, one more. According to Fajan's rules, covalent bond is favored by. Covalent bond is favored by. Covalent bond is favored by. What about this question, people? Let me know fast. Smaller cation and large anion, right? Absolutely, you all are correct. Smaller cation, large anion, right? Okay, covalent character as per Fajan's rules in the ionic bond is governed by two factors. One is polarizing power of cation, one is polarizability of anion. And polarizing power of cation is directly proportional to charge present on cation and inversely proportional to size of cation. Whereas polarizability of anion depends on the size of anion. More the size of anion, more the polarizability of anion. That's all. Arrange the following increasing order of their covalent character. The similar sort of question, right? Similar sort of question. On the basis of increasing order of their covalent character. See guys, remember, covalent character in an ionic bond is directly proportional to polarizing power of cation, and polarizing power of cation is directly proportional to charge present on cation and inversely proportional to size of cation, right? Inversely proportional to size of cation, right? And let me tell you, covalent character, it is inversely proportional to ionic character. It's inversely proportional to ionic character as well. Now you can kill it. See guys, you have got Na positive over here, this is Rb positive, this is Mg di positive, this is AlCl3, Al tri positive, correct? Right? The charge on cation is maximum in case of AlCl3, so polarizing power of cation will be maximum in the fourth case, right? So maximum covalent character, AlCl3. Increasing order I need to write, okay? So fourth one is going to have maximum covalent character, followed by the third one, so either this or this, right? Now among second and first, which one is going to have more polarizing power? Size of Na positive is less, so it is going to have more polarizing power, more covalent character. So one is going to have more covalent character than that of second, right? So option C is the one which is correct among all. Yeah? Right, people? Option C is the one. Okay. The correct sequence of increasing covalent character is represented by, again, the similar set of question, right? So this is Li positive basically, this is Na positive, this is Be di positive. This is going to be maximum covalent because charge present on cation is more. Na positive and Li positive. Size of Li positive is less, more polarizing power, more covalent character. So I should say the order should be BeCl2 should have maximum covalent character, followed by LiCl, followed by NaCl. So option C must be the answer, right? Right, people? Okay, strongest bond is in between. Check the ionic character. Wherever ionic character is maximum, the bond is going to be strongest there. Where is the ionic character maximum? Ionic character will be maximum in the one which will be having least covalent character. Which is having least covalent character? Check it out. It's a simpler one, guys. What is going to be the answer of this one? Strongest bond is present in. It is simple, right? No need to involve any concepts. See, wherever ionic character is going to be more, there only strength of bond is going to be more, right? And absolutely, all of you are perfectly correct. It's going to be CSF, right? CSF. Okay. Which of the following salt shows maximum covalent character? Again, the similar set of question. You can do this on your own on the basis of Hajan's rules, right? Okay, I'm not going to solve all these. These are same set of questions. Polarizability of halide ions. More the size, more the polarizability, right? Increasing order. I negative, Br negative, Cl negative, F negative. Option D, right? Okay. According to VSCPR theory, the geometry of a covalent molecule depends on number of bond pairs of electrons, absolutely. Number of lone pairs of electrons, absolutely. The number of electron pairs present in the outermost shell of the central atom, absolutely. All the above. All the above is the answer of the question, right? All these statements are the ones which are responsible for the geometry. Yeah? Right, people? Okay. One more. Predict the correct order of electron repulsion. This is a very basic, right? Lone pair repulsion maximum, followed by lone pair, followed by bond pair, correct? And see what kind of questions are asked in your NEET, people. The shape of ClO3 negative according to VSCPR. Okay, if I have ClO3 negative, if I'll be having ClO3 negative, correct? First of all, how many sigma bonds do we have? We have got some 3 sigma bonds. Is there on any lone pair on chlorine? Right? Is there any lone pair on chlorine? Is there any lone pair on chlorine? There is one lone pair, right? The hybridization is going to be, see, steric number is 3 plus 1, 4. It's going to be sp3. The geometry is tetrahedral, but what about the shape? Shape is going to be pyramidal, right? Shape is going to be pyramidal. Yeah? Shape is going to be pyramidal, people. Okay. In which of the following the bond angle is maximum? In which of the following the bond angle is maximum? What do you think about this one, guys? Let me know first. Let me know first. In which of the following the bond angle is maximum? So majority of the people are saying option C, absolutely. NH4 positive, sp3 hybridization, 109 degree 28 minutes, right? Yes? Right? There is no lone pair basically on nitrogen, so it's going to be perfectly 109 degree 28 minutes. In all the other cases, hybridization again is sp3, but every species central atom contains one lone pair or something, right? Central atom contains basically the lone pair due to which the bond angle decreases. So NH4 positive is the only one which has got the maximum bond angle. BrF3 molecule, the lone pairs contains equatorial positions. To minimize what? This is the question which we have done many a times, right? To minimize lone pair repulsions as well as bond pair, lone pair repulsions, right? Yes? Okay, what about this one? Which of the following increasing order of the lone pair of electrons? Lone pair of electrons you need to calculate on the central atom. See, I have 7 on iodine, there is no lone pair. There is one lone pair on iodine right here. ClF3, right? 2 lone pairs on chlorine. XeF2, 3 lone pairs. Arrange it on the basis of increasing order. You can do it now, right? So I have 7, then comes I think this is the correct order only, correct? Option 1 only is the correct order. This is the increasing order. Yeah? Okay. The number of lone pairs and bond pairs of electrons on sulfur atom in sulfur dioxide molecule, SO2. SO2, right? SO2. How many sigma bonds? 2 sigma bonds. How many lone pairs on sulfur? 1 lone pair on sulfur, right? The number of lone pairs and bond pairs. So sigma bonds are 2, but how many bond pairs are there? So it's going to be S double bond O, right? Double bond O, and on sulfur there is a lone pair. So 4 bond pairs and 1 lone pair. 4 bond pairs and 1 lone pair in SO2, right? I was supposed to calculate lone pair and bond pair. So 1 lone pair and 4 bond pair, right? Yes, simpler one. Okay, a molecule which has 2 lone pairs and 2 bond pairs around the central atom. 2 lone pairs and 2 bond pairs. Right. What is going to be the shape of the molecule? 2 bond pairs and 2 lone pairs. Can you let me know fast? The molecular shape is going to be what? People, in case of water, there are 2 bond pairs and 2 lone pairs, right? 2 sigma bonds, 2 lone pairs. It's a V shape. 104 degree 5 minutes, yeah? Yes, so it's a V shape, absolutely. Correct? Okay, using VSCPR, predict the shapes which has square pyramidal shape. Okay, which of the following has got the square pyramidal shape? Tin comes in carbon family, right? So sigma bonds 2, lone pair 1, right? CCl4, 4 sigma bonds, 0 lone pair on carbon. SO3, 3 sigma bonds, 0 lone pair on sulfur, right? BRF5, 5 sigma bonds, 1 lone pair on bromine, correct? Which of the following has got the square pyramidal shape? Now, which of the following has got the square pyramidal shape? Check it out. BRF5, absolutely, right? BRF5, square pyramidal. Yeah? BRF5, people. This is BR, this is 1F, this is one more F, this is one more F right here, this is one more F, and these 4 Fs are present in one plane. There is one F perpendicular to the plane like this, and there is one lone pair perpendicular downwards like this. So it is square pyramidal basically, right? Okay, in the structure of ClF3, the number of lone pair of electron on the central atom of Cl. 3 sigma bonds, 2 lone pairs, right? So 2 lone pairs on chlorine, ClF3, 2 lone pairs on chlorine, yeah? Correct? That's something which is very simple. This is ClF3, right? It's a T-shaped molecule, 2 lone pairs at equatorial positions. Okay. Which of the following molecules, SO2, SO4, ClF3, BRF5, XCF4, which of the following shapes do not describe any one of the molecule mentioned? See, SO2, there are 2 sigma bonds. There are 2 sigma bonds and 1 lone pair. 2 sigma and 1 lone pair, right? 2 sigma and 1 lone pair. SF4, 4 sigma and 1 lone pair, so it is going to be seesaw shape. ClF3, it is going to be T shape. BRF5, it's going to be square pyramidal. XCF4, it's going to be square planar, right? Okay. So is there anyone as T shape? Yes, T shape is there. Seesaw is there, SF4, right? Trigonal bipyramidal. There is no one carrying trigonal bipyramidal shape, right? There is no one carrying trigonal bipyramidal shape. See, the first one is bent. Second one is seesaw. Third one is T-shaped. Next one is square pyramidal. Next one is square planar. Yeah? Absolutely. Moving on to one more. Which of the following compound is isoelectronic and isostructural? See their hybridization, that's all. See their hybridization, that's all. Right? See their hybridization, people. So if you look at the option B, we have got IBr2 negative. So 2 sigma bonds and how many lone pairs? 3 lone pairs on iodine. Similarly, XCF2, 2 sigma bonds and 3 lone pairs on xenon, right? So steric number is same, 3 plus 2, 5 in both the ones, yeah? So their hybridization is same, so they are going to be isostructural, yes, as well as isoelectronic, yeah? Wait, these are going to be isostructural, right? Yeah, option B is the one which is the correct answer among all. Okay, number of lone pairs, total number of lone pairs in I3 negative. In case of I3 negative, if you remember, this is iodine, this is 1 lone pair, this is 1 more lone pair, this is 1 more lone pair. These 3 lone pairs are present on the equatorial plane. There is 1 iodine at the top, there is 1 more iodine at the bottom, right? This iodine contains 3 lone pairs, this iodine contains 3 lone pairs. So how many lone pairs in total? 3 with the central atom, 3 with this one, 3 with this one, 3, 3, 6, 3, 9. So total there are 9 lone pairs, right? Total. He's asking about total number of lone pairs. He's asking about total number of lone pairs. He's not asking about the number of lone pairs on the central atom. No. If he asked about the number of lone pairs on the central atom, then the answer would have been 3. Yeah? Okay, which of the following structure is most stable? ClF3. ClF3 has got the shape of T shape, right? In case of T shape, 2 lone pairs, they occupy the equatorial positions. So, which of the following is the correct representation? Option 1. 1 is the most stable form. 1 is the most stable form, right? ClF3 is a T shape. In T shape, repulsions are minimum, stability is maximum for ClF3, right? So it's going to be only one. Okay. A sigma bonded molecule MX3 is T-shaped, right? Like ClF3. The number of non-bonding pair of electrons. That means he's talking about the lone pairs. In case of ClF3, how many lone pairs are there on chlorine? 2 lone pairs, right? That is T-shaped only. Yeah, 2 lone pairs. The species having pyramidal shape. Pyramidal shape. Which one of the following will be having pyramidal shape? What do you think? The first one will not have pyramidal shape, right? 3 sigma bonds, 0 lone pair. BRF3, 3 sigma bonds, 2 lone pairs on the central atom. No. For the pyramidal shape, for the molecule to have the pyramidal shape, it should have 3 sigma bonds and 1 lone pair, right? Like in case of NH3. SiO3 dinegative, no one. Only option left is OSF2. OSF2 is the one which is going to have the pyramidal shape among all. For the molecule to exhibit pyramidal shape, it should have 3 sigma bonds and 1 lone pair, right people? That is the thing you are going to look for. The species having the bond angle of 120. See which one is sp2 hybridized? BCl3 is sp2 hybridized, so 120 bond angle, right? 120 bond angle, option C. Shape of methane, everyone knows it, tetrahedral. Okay, look at the following potential energy curve. Which of the following correctly represents the most stable state of hydrogen molecule? Most stable state. See, at point B, the energy of the molecule is minimum, and when the energy of the molecule is minimum, stability is maximum. So when the molecules are at maximum when these atoms of hydrogen are at maximum closest distance, right, at that time, potential energy of this system is minimum and stability is maximum. So at B, which is actually option B, right? Absolutely, people. Okay, the number of sigma bonds and pi bonds present in 1357 octa, what is it? Octatetraene respectively. So octatetraene, this is the structure, right? This is the structure of octatetraene. You can count the number of sigma bonds, you can count the number of pi bonds, right? Yes, you can do it. Allyl cyanide molecule. Allyl cyanide, this is the structure. Allyl cyanide. Cyanide is linked at the allylic position, right? Okay. Right? So you need to count the sigma bonds, pi bonds. You can do it on your own, right? This is simple. The molecule not having pi bond, it is going to be Cl2. Cl2 does not have any pi bond, right? O2, there is 1 pi bond. N2, there are 2 pi bonds. Carbon dioxide, there are 2 pi bonds. So Cl2 is the only one which does not have the pi bond. Yeah? The angle between the overlapping of 1s and 1p. 1s and 1p. What is the angle of overlapping? It's 180, right? It's 180 degree. Correct? S orbital and p orbital. When they overlap at an angle of 120. Sorry, 180. Yeah? Okay, the enolic form of acetone. Enolic form of acetone. If you look at acetone, this is CH3, this is C double bond O, this is CH3, this is acetone. If I make its enolic form, what is going to be its enolic form? Its enolic form is going to be CH3, this is C, this is OH, this is double bond CH2. This is the enolic form of acetone. Now count the pi bonds, sigma bonds, do the equation. So there are 3 sigma bonds, 4 sigma bonds, 5, 6, 7, 8, 9. There are 9 sigma bonds. And how many pi bonds? 1 pi bond. 9 sigma bond, 1 pi bond, and 2 lone pairs on this oxygen. So option 1 is the one which is the correct answer. Right? Yes, people? Simple again. Okay, the angular shape of ozone consists of, every one of you know it, right? 2 sigma and 1 pi, 2 sigma and 1 pi. In case of O3 molecule, I mean the structure. Just make it structure, rest everything you know. Okay, linear combination of 2 hybrid orbitals belonging to 2 atoms and each having 1 electron leads to. Linear combination of 2 hybrid orbitals. Yes, linear combination of 2 hybrid orbitals. What it leads to the formation of? Yeah? What it leads to the formation of? Whenever the hybrid orbitals overlap, they lead to the formation of sigma bond, except in case of benzene. Benzene is the only exception where the pi bonds overlap parallelly and lead to the formation of pi bond, right? So the answer of this question is going to be absolutely sigma. Which of the following statement is correct? Double bond is shorter than sigma bond. Absolutely. Asha is incorrect, is not correct, he's saying. Sigma bond is weaker than a pi bond. Option B is incorrect, right? Option B is incorrect. Sigma bond cannot be weaker than the pi bond. Okay, which of the following represents a zero overlap. Option C represents a zero overlap. There is no overlap over here, right? It shows the zero overlap. Yeah? This shows constructive interference. Yeah? This shows destructive interference. This does not show any interference over here. Yeah? It's a zero overlap case. As the S character of hybrid orbital increases, the bond angle increases. Yes. See guys, as the S character increases, electronegativity increases. As the electronegativity increases, bond angle also increases. Do remember this, okay? Do remember this. Do remember this, okay? See, as you can see over here, in case of sp3, percentage S character is 25, sp2, S character is 33, S character is 50. Bond angle, in case of sp3 hybridization, it's 109 degree, 28 minutes. Over here is 120, over here is 180. As the S character keeps on increasing, bond angle keeps on increasing, right? Simple. The nature of hybridization in ammonia, NH3, 3 sigma bonds, 1 lone pair, 3 plus 1, 4, steric number 4, sp3, right? sp3. The shape of sulfate ion, SO4 dinegative. SO4 dinegative, tell me fast. It is simple guys, right? H2SO4 is talking about, it's tetrahedral, right? SO4 dinegative is saying. Yeah? It was a simpler one. Strength of bonds forming by SS. So first SS overlap, then comes SP, then comes PP. Overlap in the order, right? Overlap in the order. SS overlap is maximum, followed by SP, followed by PP. Which of the following molecule does not have the linear arrangement? Which of the following does not have the linear arrangement? It is going to be C. CO2, it is linear. BH2, it is linear. C2H2, it is ethine, linear. H2S is not linear. Option 1, right? Option 1. Okay, in case of D2sp3 hybridization, which all d orbitals are involved? It is going to be dz square and dx square minus y square. Dz square and dx square minus y square, these are the orbitals which are involved in the overlapping, sorry, not in the overlapping, in the intermixing when there is D2sp3 hybridization, right? I'm sure it's clear. Which of the following species is underlined? Okay, in which of the following species is the underlined carbon having sp3 hybridization? See, this is basically C double bond OH, C double bond OH, this cannot be sp3. Yeah, this is sp3, 2 hydrogen atoms. So this carbon is forming 4 sigma bonds. 4 sigma bonds means sp3. So option B is the one which is correct among all, right? This is C double bond, this is sp2, right? This is again sp2. When 2 atomic orbitals combine, they form 2 molecular orbitals, right? Yes, it is simple. Right, people? This is something which you all must be knowing. Yeah? When 2 atomic orbitals combine, they lead to the formation of 2 molecular orbitals. Correct? Which of the following corresponds unstable molecule? Unstable molecule. Okay. If the number of antibonding electrons is equal to number of bonding electrons, at that time it's unstable. Or if the number of antibonding electrons is greater than number of bonding electrons, that is also unstable, right? So number of antibonding electrons is greater than number of bonding is less than number of antibonding. So in this case molecule is going to be unstable. In this case molecule is going to be unstable. So both B and C, right? Both B and C. Correct? Yeah? Okay. In the molecular orbital diagram of O2 positive, the highest occupied molecular orbital is, which one is it? It is pi star 2px, right? It is pi star molecular orbital. Pi star molecular orbital. For this, in order to solve these questions, you need to know how to write the molecular orbital configurations. Once you write the molecular orbital configurations, you can easily let me know, right? See, this is O2, but he's talking about O2 positive. So take 1 electron out from here. Take 1 electron out from here. So the last electron is in pi star 2px orbital, right? So it's going to be pi star. The bond order in case of N2 positive. So there is one thing which I would want you guys to remember. See, if I'll be having any species containing 14 electrons, its bond order will be 3. 15 electrons, its bond order is 2.5. Yes. 16 electrons, its bond order is 2. 17 electrons, its bond order is 1.5. 18 electrons, its bond order is 2. 13 electrons, its bond order is 2.5. 12 electrons, its bond order is 2. 11 electrons, bond order 1.5. 10 electrons, bond order 1, right? Okay, these are the respective bond orders. Now, N2 positive. N2 positive contains total how many electrons? 7, 7, 14, 1 is 1, 13. 13 electrons means bond order 2.5, so 2.5 is the answer, right? 2.5 is the answer. Okay, the correct statement with regard to H2 positive and H2 negative. H2 positive and H2 negative. First of all, you need to know their bond orders, and at the same time, you need to know their molecular orbital configuration. See, bond order of H2 positive is 1 by 2. At the same time, bond order of H2 negative is also 1 by 2. Now, people, be careful. Bond order of H2 positive is 1 by 2 and bond order of H2 negative is also 1 by 2, right? Now, which one is more stable? Which one is more stable? See, in H2 positive, there is no antibonding electron. In H2 negative, there is one antibonding electron. More the antibonding electron, less is the stability. So, H2 positive is going to be more stable than that of H2 negative. Yeah? H2 positive is going to be more stable than that of H2 negative. Right, people? Done? Okay. According to molecular orbital theory, which of the following statement about the magnetic character of bond order is correct regarding O2 positive? See, in case of O2, as you know, bond order is 2 and there are 2 unpaired electrons. There are 2 unpaired electrons. Few minutes back I told you pi star 2px1, pi star 2py1, right? There are 2 unpaired electrons. But if I talk about O2 positive, take 1 electron out. If you take 1 electron out, there will be 1 unpaired electron. If there is 1 unpaired electron, that means O2 positive is also going to be paramagnetic, right? Yes, O2 positive, 8816 minus 115. So bond order is 2.5, right? Bond order is 2.5. Few minutes back we saw bond order of O2 is 2. So bond order of O2 positive is greater than that of O2. Is greater than that of O2, right? Is greater than that of O2 and paramagnetic at the same time, right? Right, people? Yeah? Okay, which of the following has the minimum bond length? Again, you are supposed to calculate the bond order. Bond order is inversely proportional to bond length, right? Few minutes back only I gave you the order. See, it contains 15 electrons, right? It's going to have 2.5 bond order. It's going to contain 17 electrons. It's going to have 1.5 bond order. O2 di-negative 18 electrons, bond order 1. O2, bond order 2. So this one is going to have maximum bond order of 2.5 and minimum bond length, right? So option A. Yeah, option A. Which of the following does not exist on the basis of molecular orbital theory? The one with the bond order 0 or negative does not exist. He2 does not exist. Its bond order comes out to be 0 when you calculate, right? Which of the following is paramagnetic? O2, it has got 2 unpaired electrons, one in pi star 2px, one in pi star 2py, so it's absolutely going to be paramagnetic. The pair of species that has same bond order in the following, same bond order. The ones which are going to be isoelectronic will have same bond order always. The ones which are going to be isoelectronic will have same bond order. If I talk about CO, in case of CO there are total 14 electrons. In case of NO positive, 8 plus 7 is 15, 15 minus 1 is 14, so 14 electrons. So these two species are isoelectronic, they are going to have same bond order, option 2. Yes, they are going to have same bond order. Isoelectronic species have got same bond order, yeah? Okay, intramolecular hydrogen bonding exists in intramolecular, in the molecule, orthonitrophenol, due to which its size decreases and its boiling point that also decreases. Its volatility that increases, right? Yeah, that's something which is given in the NCERT. Correct, people? Right? Due to this intramolecular hydrogen bonding, the size of it decreases. When the size of it decreases, what happens? What happens? Van der Waals forces between these kind of molecules, that decreases. So boiling point also decreases, right? Volatility rate that increases. Correct? Yes? So orthonitrophenol is the answer. Okay, which of the following is the correct order of interaction? This is something which you all must be knowing, right? Let me know its answer, people. What is going to be the answer of this one? It is going to be covalent interaction is maximum followed by dipole-dipole, followed by hydrogen bonding, followed by van der Waals, right? Okay, do remember this. Strongest hydrogen bond is shown in case of hydrogen fluoride, strongest hydrogen bond is shown, right? Yes, that's evident. Methanol and ethanol are miscible in water due to Due to hydrogen bonding character? Yeah? Due to hydrogen bonding character? The hydrogen bond is shortest in. The hydrogen bond is shortest in case of HF because of more stronger hydrogen bond. Because of stronger hydrogen bond, this bond length is less, right? I mean, you can say this hydrogen bond is shorter. So option D is the one. Hydrogen bonding is maximum in. In which of the following hydrogen bonding is maximum, people? It is simpler one. It is going to be option A. Hydrogen bonding is possible only in compounds having hydrogen attached with fluorine, oxygen, neon, right? Hydrogen bonding is possible in this one. In the second one, hydrogen bonding is not possible, neither in this one nor in this one, right? Yes? Only in the first case, that is ethanol, hydrogen bonding is possible, right? The vapor pressure of orthonitrophenol is higher than the vapor pressure of paranitrophenol. Is that correct? Is that correct? Absolutely it's correct, right? Absolutely it's correct. What is the reason he's asking? The reason is due to the intramolecular hydrogen bonding in case of orthonitrophenol. Due to hydrogen bonding. Yes? Due to hydrogen bonding. Acetic acid exists as dimer in benzene due to, again, the same thing, hydrogen bonding. Yes? So with this, your chemical bonding is done and dusted, right? Yeah, it is hydrogen bonding. Guys, I think this much is enough for today, right? I'm done. I'm done and dusted. For 2023 students, I'll be taking class from Monday because on Sunday, I'll be doing the paper discussion for NEET 2021. People do one thing, when the paper of your NEET 2021, when you are done with the NEET 2021 paper, once you leave the examination center, do send me the pictures of your paper so that after the session only, I'll come up with a live interaction on this channel, right? Yeah? Okay, and from Monday, we'll be doing the NEET 2023 course, yeah? Guys, there is no need to be scared about the NEET exam. The paper is going to be all chilled, trust me on that. It's going to be very simple. All NCERT based is going to be. Just read your NCERT carefully. Now, there is no point of reading things. Just do the mock test in these couple of days. Don't study anything new. Okay, whatever you have studied till now, that's enough. Okay, do revise the same things. Do make the formula sheets, right? Do the formula revisions. Yeah. Go through your biology textbook once again. Do go through your NCERT inorganic chemistry once again, right? Do remember all the formulas of physics, all the formulas of physical chemistry, and I'm sure you would have made the notes of the organic reactions, right? The short notes. Do go through them as well. Definitely you're going to kill it. Okay? Right? So today we have completed 1228 slides. That's huge, yeah? So people, with this, I'll take a leave, right? I wish you all the luck. Take care. God bless you all and love you all. Chalo, take care guys. Bye-bye. Bye-bye, bye-bye, bye-bye. Take care.